Welcome to this first course in the design and analysis of algorithms. I imagine many of you are already clear on your reasons for taking this course, but let me begin by justifying the course's existence and giving you several different motivations for learning about algorithms. So what is an algorithm? Well, we're not going to be needing a precise definition in this course, but essentially an algorithm is a well-defined set of rules, a recipe in effect, for solving some kind of computational problem. So for example, maybe you're given a bunch of numbers and you want to rearrange them into sorted order. Maybe you're given a road network with an origin and a destination and you want to compute the shortest path from point A to point B. Maybe you're given a bunch of tasks with deadlines and you want to know whether or not it's feasible to accomplish all of those tasks by their respective deadlines. So why study algorithms? Well, first of all, understanding the field of algorithms and also the related field of data structures is crucial for doing serious work in pretty much any other branch of computer science. That's the precise reason why, here at Stanford University, this is the course that's required for all of the degrees that the computer science department grants. Be it a bachelor's, a master's, or a PhD degree, we insist that you have mastery of the field of algorithms. So what are some examples of uses in the rest of computer science? Well, if you're doing routing in a communication network, that piggybacks on classical shortest path algorithms. The effectiveness of public key cryptography really rests on that of number theoretic algorithms. In, say, computer graphics, you need the computational primitives that are supplied by the study of geometric algorithms. Database indices rely on balanced search tree data structures, as covered in this course. And computational biology uses dynamic programming algorithms to measure the similarity among genomes. And the list goes on and on. A second reason to study algorithms is that they play a key role in modern technological innovation. Obviously, I could give any number of examples here. Let me just state one super obvious one, which is that search engines use a tapestry of algorithms to efficiently compute the relevance of various web pages. The most famous such algorithm, which you may have heard of, is the PageRank algorithm in use by Google. Indeed, in a December 2010 report to the United States White House, the President's Council of Advisors on Science and Technology argued that, in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speed, as you'd be familiar with in the form of Moore's Law. Third, although this is getting significantly outside the scope of this course, algorithms are increasingly being used to provide a novel lens on processes outside of computer science and technology. For example, the study of quantum computation has provided a new and computational viewpoint on quantum mechanics. Price fluctuations in economic markets can be fruitfully viewed as an algorithmic process, and even evolution can be usefully thought of as a surprisingly effective search algorithm. The last two reasons I'm going to give you might sound a little flippant, but I think there's more than a grain of truth to both of them. Now, I don't know about you, but back when I was a student, my favorite classes were always challenging classes, but after I struggled through them, I somehow felt like I had a few more IQ points than when I started. So I hope this course provides a similar experience for many of you, that on the one hand, it's a bit of a struggle, you find the concepts challenging, but perhaps you feel just a tinge smarter after we're done. Finally, I hope that by the end of the course, a constant fraction of you will agree with me that designing and analyzing algorithms is simply fun. It's an endeavor that requires a rare blend of creativity and precision, and it can certainly be frustrating at times, but even more than that, it is addictive. So let's now descend from these lofty generalities and get much more concrete. And also, let's remember that we've all been learning and using algorithms since we were little kids. So once upon a time, in roughly third grade or so, you learned how to multiply two numbers. Now, you probably weren't thinking in these terms at the time, but multiplying two numbers is certainly a well-defined computational problem, and that procedure you learned back in third grade or so is indeed an algorithm. So let's just make that a little bit more precise. In this computational problem, we're given as input two numbers, let's say with n digits. And to make things interesting, why don't you think about n as being really quite large, say in the thousands. Maybe we're implementing an algorithm that's going to be used in a cryptography application where you need to keep track of really quite large numbers. So if we call the two input numbers x and y, the problem is simply to compute their product, x times y. So a quick digression. I'll certainly be the first to admit that my handwriting is not the greatest. I got a C in penmanship back in elementary school, and I think the teacher was being a little generous. But it's an acquired taste, but trust me, you will get used to it. Okay, back to integer multiplication. Now, when we talk about procedures for multiplying two numbers, we're going to be interested in counting how many steps are required in order to execute the multiplication. So how do we count a step? We'll talk more about this later, but for multiplying two numbers, let's just call a step the addition or multiplication of two single-digit numbers. So let's review the integer multiplication algorithm that we learned back in grade school just by working through a concrete example. Specifically, let's think of n equal 4, so let's look at two 4-digit numbers. Let's say 5, 6, 7, 8, and 1, 2, 3, 4. Now, as you'll recall, the procedure we learned way back when was just to take each digit of the bottom number and multiply it by each of the top numbers, and then to take each of those n partial products and add them up. So for example, you start with the 4, you multiply it by 8, you get 32, carry the 3, 4 times 7 is 28, add the 3, you get 1, carry the 3, and so on. So that gives you this first partial product, 22, 7, 12. Then you do a shift, so you effectively put a 0 in this final digit, and you repeat that procedure using the next digit, the 3. So again, 3 times 8 is 4, carry the 2, and so on. And you compute the final two partial products using the 2 and the 1. And having computed all of the partial products, you just add them up to get the final product. Now the question I'm interested in is how much work, how many primitive operations did we do to multiply these two numbers, and more generally, how many does it require to multiply two n-digit numbers as a function of n? Well, just to get sort of a ballpark viewpoint for what's going on, we started with two n-digit numbers, and at the end of the day, we basically filled out a grid of size roughly n by n, give or take a little bit. So just in ballpark terms, it seems that multiplying two n-digit numbers required essentially a quadratic number of operations, a small number of operations to fill in each entry in this grid. The grid is n by n, roughly, so that's roughly n squared operations. In a little more detail, we could look at each of the partial products separately. So to compute, say, this first partial product, what did we do? We took the 4, we multiplied it by each of the n digits on top. We also did some carries, so that affects things a little bit. But in the end, we did somewhere between, say, n and 2n primitive operations to compute this first partial product. And that's true, of course, for each of the n partial products. So that's roughly n operations for each of the n partial products. So that's roughly n squared operations to compute all of the partial products. Then we have to add it all up at the end, but that takes just an extra number of constant times n primitive operations to do all of those additions. So summarizing, overall, the number of primitive operations required to multiply two n-digit numbers using this procedure grows quadratically with the length n. So for example, if you double the length of two numbers, you expect to do roughly 4 times as many primitive operations if you use this iterative algorithm for multiplying two numbers. Now, depending on what type of third grader you were, you might well have accepted this procedure as being the unique, or at least the optimal way of multiplying two n-digit numbers together. And if you want to be an expert algorithm designer, that kind of obedient attitude is something you're going to have to learn to discard. Here's a favorite quote of mine. It's from a quite early textbook in the field, The Design and Analysis of Computer Algorithms by A.O. Hopcroft and Ullman. And after highlighting a number of algorithmic design techniques, they conclude by saying, perhaps the most important principle for the good algorithm designer is to refuse to be content. So that's a beautifully accurate quote. I might rephrase it more succinctly by just saying, if you want to be a good algorithm designer, you should adopt the following mantra. You should always be asking, can we do better? This is a particularly appropriate question to ask when you're faced with some kind of naive or obvious algorithm for solving a problem like the third grade algorithm for integer multiplication. But this will come up over and over again. We'll see an algorithm, there'll be an obvious solution, but with some extra algorithmic ingenuity, by detecting subtle structure in the problem, we'll be able to do significantly, qualitatively better than the naive or the obvious solution to the problem. So let's apply this cocky attitude to the problem of multiplying two integers. Let's just suppose as a working hypothesis that there is some procedure which is better than what we learned back in elementary school. What could it possibly look like? So as someone with some programming experience, you know that there are not only iterative algorithms, iterative programs, like the one we just outlined for multiplying two integers, but there are also recursive programs. These are programs that call themselves, typically on an input of a similar form, but with smaller size. So as a working hypothesis, let's imagine that there's some interesting recursive approach to multiplying two integers. What must such an algorithm look like? Well, it must somehow fundamentally involve calling itself on smaller problems, that is, on smaller numbers, numbers with fewer digits. So what kind of decomposition on numbers could we use to enable this kind of recursive approach? Well, if you think about it, there's a pretty natural way to break a number with a bunch of digits into a couple numbers with fewer digits. Namely, just take the first half of the digits, the first n over 2 digits, regard that as a number in its own right, and the second half of the digits, regard that as a number in its own right. So perhaps this decomposition will have some use in enabling a recursive attack on how to multiply two integers. So we're going to investigate that in more detail on this next slide. Given x and y, each with n over 2 digits, we're going to represent x as terms of its first half of the digits a and its second half of the digits b. Similarly, we will write y, the second input, in terms of its first half and second half of digits c and d. And in this expansion, a, b, c, and d are all n over 2 digit numbers. I'm assuming for convenience here that n is even. This would extend to the case where n is odd in the natural way, where you break it into n over 2 rounded up and n over 2 rounded down. So in our previous example, where x was 5678 and y was 1234, we would have a being equal to 56, the first two digits of the 4 in x, and then b would be the other two digits, and then similarly for c and d, being a decomposition of y. So now in a just purely mechanical way, we can expand the product of x times y in terms of this representation in terms of these smaller numbers, a, b, c, and d. So x times y by a representation is just the same thing as 10n over 2 times a plus b times quantity 10 to the n over 2 c plus d. And now if we expand this in group-like terms, we get a 10 to the n times ac plus a 10 to the n over 2 times ad plus bc, so that's combining two terms from the expansion, plus bd. And I'm going to call this expression circled in green star. Now what I want you to think about and make sure you understand is that this expansion that I've circled and called star immediately suggests a recursive algorithm for multiplying two integers. Now it's not clear whether that algorithm is going to be fast or slow, whether this is a good idea or a crackpot idea, but certainly it's a legitimate recursive approach to multiplying two integers. Specifically, the relevant products in star, namely AC, AD, BC, and BD, all involve smaller numbers than what we started with. Those are all n over 2 digit numbers, whereas our original inputs had n digits. So we can legitimately solve those recursively. We can invoke our same algorithm to compute those in a recursive way. Now once we've invoked our multiplication algorithm recursively 4 times to compute these 4 relevant products, now we can just compute the expression in star in the obvious way. We take AD and BC, we add them together using the just standard first grade iterative addition algorithm. Then we pad both AC and the result of that addition by a bunch of zeros, n over 2 zeros or n zeros as appropriate. Now we have these 3 constituent terms and we just add them up, again using the grade school algorithm to compute the overall expression. So to keep this intro lecture brisk, I haven't discussed the base case of this recursive algorithm. As hopefully you all know, recursive algorithms do need base cases. At some point the recursion has got to stop, otherwise your algorithm is never going to terminate. So in multiplication, all you do is if you were passed as input 2 single-digit numbers, you'd multiply them in one primitive operation and return the result. If the numbers have 2 or more digits, you would recurse in the way we've described here. If there's 1 digit, you just compute them and you're done. So who knows whether this recursive algorithm is a good idea or not? It's totally not obvious. You should not even necessarily have any intuition about how this compares to the iterative algorithm you learned back in elementary school. So in lieu of answering that question, although we will answer it several lectures hence, I want to show you a second, still more clever recursive algorithm for integer multiplication. So this goes by the name of Karatsuba multiplication after the founder, although really sort of the key point is a trick pointed out by the mathematician Gauss in the early 19th century. So to explain this algorithm, let me write once again our expansion in terms of the n over 2 digit numbers. So we have the product x times y, which we wrote as
10 to the n AC plus 10 to the n over 2 AD plus BC plus BD. Now, the previous approach was, in recognition of the four products that we see in this expression, we made four recursive calls. So here's the trick, and this is really what Gauss figured out over 200 years ago, which is that it seems there are four products, but fundamentally in this expression, there's really only three quantities that we care about. There's the AC, the coefficient of this first term, there's AD plus BC, the coefficient of this middle term, and there's BD. So we care about AD and BC as quantities individually only in as much as we care about their sum. We really don't care about them individually. So that motivates the question, perhaps we can somehow uncover these three different quantities using only three recursive calls rather than four. In fact, we can, and that's Karatsuba multiplication. So to be more specific, our first two recursive calls are shared with the previous recursive algorithm. We go ahead and compute AC and BD recursively. The third step is the clever one, where we recursively compute the product of quantity A plus B with C plus D. Now, expanding, what are we going to get when we recursively compute this product? We're going to get AC plus BD plus AD plus BC. And here is Gauss's trick, or observation, which is that the result of the third recursive call minus each of the first two, what happens? Well, the AC is going to cancel the AC, the BD is going to cancel the BD, and we will be left with AD plus BC, which is exactly that middle coefficient that we cared about. So we can indeed compute the sum of AD and BC without separately computing each of them, and that's exactly what we wanted. So what is this bias? This gives us a second recursive algorithm for multiplying two integers that makes use of fewer recursive calls, only three recursive calls rather than four. And as before, there's a little bit of work to do beyond the recursive calls, but not much. You just have to do some padding by zeros and adding up the results. So there's 2 points I want you to appreciate about all these integer multiplication algorithms. The first point is that the algorithm design space is incredibly rich, much richer than you might have initially had intuition for. Multiplying two integers, what else could you do other than the elementary school algorithm? Well, what have we seen? You can do a lot of other things. In particular, the second recursive algorithm looks nothing like what we learned back in grade school. And we'll see this over and over again, that with sufficient ingenuity, sufficient cleverness, you can solve problems in ways much differently and sometimes much better than using the naive, straightforward algorithm. The second takeaway point from this discussion of integer multiplication algorithms is that sometimes you have interesting algorithmic ideas for which it's totally not obvious what kinds of properties or what kind of performance guarantees those algorithms enjoy. So in particular, confronted with these three different integer multiplication algorithms, how could we not wonder which of the three is the best? Which of these requires the fewest number of primitive operations to multiply two integers? In particular, does one of these novel recursive approaches do better than the algorithm we learned back in elementary school? The answer to that question is totally non-obvious, and it requires non-trivial mathematical analysis to answer. In the upcoming lectures, I'll provide you with the tools to not only precisely understand and answer this question, but more generally to predict the running times of an entire genre of divide and conquer algorithms like Karatsuba multiplication. So, stay tuned. In this video, I'll talk about various aspects of the course, the topics that we'll cover, the kinds of skills you can expect to acquire, the kind of background that I expect, the supporting materials, and the available tools for self-assessment. Let's start with the specific topics that this course is going to cover. The course material corresponds to the first half of a 10-week Stanford course that's taken by all computer science undergraduates, as well as many of our graduate students. There will be 5 high-level topics, and at times these will overlap. The 5 topics are, first of all, the vocabulary for reasoning about algorithm performance, the design and conquer algorithm design paradigm, randomization in algorithm design, primitives for reasoning about graphs, and the use and implementation of basic data structures. The goal is to provide an introduction to and basic literacy in each of these topics. Much more can be said about each of them than we'll have time for here. The first topic is the shortest and probably also the driest, but it's a prerequisite for thinking seriously about the design and analysis of algorithms. The key concept here is big O notation, which conceptually is a modeling choice about the granularity with which we measure a performance metric, like the running time of an algorithm.
It turns out that the sweet spot for clear, high-level thinking about algorithm design is to ignore constant factors and lower-order terms and to concentrate on how well algorithm performance scales with large input sizes. Big O notation is the way to mathematicize this sweet spot. Now, there's no one silver bullet in algorithm design, no single problem-solving method that's guaranteed to unlock all of the computational problems that you're likely to face. That said, there are a few general algorithm design techniques, high-level approaches to algorithm design that find successful application across a range of different domains. These relatively widely applicable techniques are the backbone of a general algorithms course like this one. In this course, we'll only have time to deeply explore one such algorithm design paradigm, namely that of divide and conquer algorithms. In the sequel course, as we'll discuss, there's two other major algorithm design paradigms that get covered. But for now, a divide and conquer algorithm, the idea is to first break the problem into smaller subproblems, which then get solved recursively, and then to somehow quickly combine the solutions to the subproblems into one for the original problem that you actually care about. So for example, in the last video, we saw two algorithms of this sort, two divide and conquer algorithms for multiplying two large integers. In later videos, we'll see a number of different applications. We'll see how to design fast divide and conquer algorithms for problems ranging from sorting to matrix multiplication to nearest neighbor type problems in computational geometry. In addition, we'll cover some powerful methods for reasoning about the running time of recursive algorithms like these. As for the third topic, a randomized algorithm is one that, in some sense, flips coins while it executes. That is, a randomized algorithm will actually have different executions if you run it over and over again on a fixed input. It turns out, and this is definitely not intuitive, that allowing randomization internal to an algorithm often leads to simple, elegant, and practical solutions to various computational problems. The canonical example is randomized quicksort, and that algorithm and analysis we will cover in detail in a few lectures. Randomized primality testing is another killer application that we'll touch on, and we'll also discuss a randomized approach to graph partitioning, and finally we'll discuss how randomization is used to reason about hash functions and hash maps. One of the themes of this course, and one of the concrete skills that I hope you take away from the course, is literacy with a number of computational primitives for operating on data that are so fast that they're in some sense essentially free. That is, the amount of time it takes to invoke one of these computational primitives is barely more than the amount of time you're already spending just examining or reading the input. When you have a primitive which is so fast that the running time is barely more than what it takes to read the input, you should be ready to apply it, for example, in a pre-processing step, whenever it seems like it might be helpful. It should just be there on the shelf waiting to be applied at will. Sorting is one canonical example of a very fast, almost for-free primitive of this form. But there are ones that operate on more complex data as well. So recall that a graph is a data structure that has, on the one hand, vertices, and on the other hand, edges, which connect pairs of vertices. Graphs model, among many other things, different types of networks. So even though graphs are much more complicated than mere arrays, there are still a number of blazingly fast primitives for reasoning about their structure. In this class, we'll focus on primitives for computing connectivity information and also shortest paths. We'll also touch on how such primitives have been used to investigate the structure of information in social networks. Finally, data structures are often a crucial ingredient in the design of fast algorithms. A data structure is responsible for organizing data in a way that supports fast queries. Different data structures support different types of queries. I'll assume that you're familiar with the structures that you typically encounter in a basic programming class, including arrays and vectors, lists, stacks, and queues. Hopefully, you've seen at some point both trees and heaps, or you're willing to read a bit about them outside of the course, but we'll also include a brief review of each of those data structures as we go along. There's two extremely useful data structures that we'll discuss in detail. The first is balanced binary search trees. These data structures dynamically maintain an ordering on a set of elements while supporting a large number of queries that run in time logarithmic in the size of the set. The second data structure we'll talk a fair bit about is hash tables or hash maps, which keep track of a dynamic set while supporting extremely fast insert and lookup queries. We'll talk about some canonical uses of such data structures, as well as what's going on under the hood in a typical implementation of such a data structure. There's a number of important concepts in the design and analysis of algorithms that we won't have time to cover in this 5-week course. Some of these will be covered in the sequel course, Design and Analysis of Algorithms 2, which corresponds to the second half of Stanford's 10-week course on this topic. The first part of this sequel course focuses on two more algorithm design paradigms. First of all, the design and analysis of greedy algorithms with applications to minimum spanning trees, scheduling, and information theoretic coding. And secondly, the design and analysis of dynamic programming algorithms, with example applications being in genome sequence alignment and shortest path protocols in communication networks. The second part of the sequel course concerns NP-complete problems and what to do about them. Now, NP-complete problems are problems that, assuming a famous mathematical conjecture you might have heard of, which is called the P not equal to NP conjecture, are problems that cannot be solved under this conjecture by any computationally efficient algorithm. We'll discuss the theory of NP-completeness, and with a focus on what it means for you as an algorithm designer. We'll also talk about several ways to approach NP-complete problems, including fast algorithms that correctly solve special cases, fast heuristics with provable performance guarantees, and exponential time algorithms that are qualitatively faster than brute force search. Of course, there are plenty of important topics that can't be fit into either of these 2 5-week courses. Depending on the demand, there might well be further courses on more advanced topics. Following this course is going to involve a fair amount of time and effort on your part. So, it's only reasonable to ask, what can you hope to get out of it? What skills will you learn? Well, primarily, even though this isn't a programming class per se, it should make you a better programmer. You'll get lots of practice describing and reasoning about algorithms. You'll learn algorithm design paradigms, so really high-level problem-solving strategies that are relevant for many different problems across different domains, and tools for predicting the performance of such algorithms. You'll learn several extremely fast subroutines for processing data, and several useful data structures for organizing data that can be deployed directly in your own programs. Second, while this is not a math class per se, we'll wind up doing a fair amount of mathematical analysis, and this in turn will sharpen your mathematical and analytical skills. You might ask, why is mathematics relevant for a class in the design and analysis of algorithms, seemingly more of a programming class? Well, let me be clear. I am totally uninterested in merely telling you facts or regurgitating code that you can already find on the web or in any number of good programming books. My goal here in this class, and the way I think I can best supplement the resources that you probably already have access to, is to explain why things are the way they are, why we analyze the algorithms in the way that we do, why various superfast algorithms are in fact superfast, and so on. And it turns out that good algorithmic ideas usually require non-trivial mathematical analysis to understand properly. You'll acquire fundamental insights into the specific algorithms and data structures that we discuss in the course, and hopefully many of these insights will prove useful more generally in your other work. Third, and perhaps most relevant for those of you who work in some other discipline, this course should help you learn how to think algorithmically. Indeed, after studying algorithms, it's hard not to see them pretty much everywhere. Whether you're riding an elevator, watching a flock of birds, buying and selling stocks out of your portfolio, or even watching an infant learn. As I said in the previous video, algorithmic thinking is becoming increasingly useful and prevalent in fields outside of computer science and technology, like in biology, statistics, and economics. Fourth, if you're interested in feeling like a card-carrying computer scientist in some sense, then you'll definitely want basic literacy in all of the topics that we'll be covering. Indeed, one of the things that makes studying algorithms so fun is it really feels like you're studying a lot of the greatest hits from the last 50 years of computer science. So after this class, no longer will you feel excluded at that computer science cocktail party when someone cracks a joke about Dijkstra's algorithm. Now you'll know exactly what they mean. Finally, there's no question that studying this material is helpful for technical interview questions. To be clear, my sole goal here is to teach you algorithms and not to prepare you for interviews per se. But over the years, countless students of mine have regaled me with stories about how mastering the concepts in this class enabled them to ace every technical question they were ever asked. I told you, this is fundamental stuff. So what do I expect from you? Well, honestly, the answer is nothing. After all, isn't the whole point of a free online class like this one that anyone can take it and devote as much effort to it as they like? So that said, as a teacher, it's still useful to have one or more canonical students in mind, and I thought I'd go ahead and be transparent with you about how I'm thinking about these lectures, who I have in mind that I'm teaching to. Though again, please don't feel discouraged if you don't conform to this canonical student template. I'm happy to have the opportunity to teach you about algorithms, no matter who you are. So first, I have in mind someone who knows at least some programming. For example, consider the previous lecture. We talked about a recursive approach to multiplying two numbers, and I mentioned how a certain mathematical expression, back then we labeled it star and circled it in green, how that expression naturally translated into a recursive algorithm. In particular, I was certainly assuming that you had some familiarity with recursive programs. If you feel comfortable with my statement in that lecture, if you feel like you could code up a recursive integer multiplication algorithm based on the high-level outline that I gave you, then you should be in good shape for this course. You should be good to go. If you weren't comfortable with that statement, well, you might not be comfortable with the relatively high and conceptual level at which we discuss programs in this course. But I encourage you to watch the next several videos anyways to see if you get enough out of them to make it worth your while. Now, while I'm aiming these lectures at people who know some programming, I'm not making any assumptions whatsoever about exactly which programming languages you know. Any standard imperative language, something like C, Java, or Python, is totally fine for this course. Now, to make these lectures accessible to as many programmers as possible, and to be honest, also to promote thinking about programming at a relatively abstract and conceptual level, I won't be describing algorithms in any particular programming language. Rather, when I discuss algorithms, I'll use only high-level pseudocode or often simply English. My inductive hypothesis is that you are capable of translating such a high-level description into a working program in your favorite programming language. In fact, I strongly encourage everyone watching these lectures to do such a translation of all of the algorithms that we discuss. This will ensure your comprehension and appreciation of them. Indeed, many professional computer scientists and programmers don't feel that they really understand an algorithm until they've coded it up. Many of the course's assignments will have a problem in which we ask you to do precisely this. Put another way, if you're looking for a sort of coding cookbook, code that you can copy and paste directly into your own programs without necessarily understanding how it works, then this is definitely not the course for you. There are several books out there that cater to programmers looking for such coding cookbooks. Second, for these lectures I have in mind someone who has at least a modest amount of mathematical experience, though perhaps with a fair bit of accumulated rust. Concretely, I expect you to be able to recognize a logical argument, that is, a proof. In addition, two methods of proof that I hope you've seen before are proofs by induction and proofs by contradiction. I also need you to be familiar with basic mathematical notation, like the standard quantifier and summation symbols. A few of the lectures on randomized algorithms and hashing will go down much easier for you if you've seen discrete probability at some point in your life. But beyond these basics, the lectures will be self-contained. You don't even need to know any calculus, save for a single simple integral that magically pops up in the analysis of the randomized quicksort algorithm. I imagine that many of you have studied math in the past, but you could use a refresher. You're a bit rusty. And there's plenty of free resources out there on the web, and I encourage you to explore and find some that you like. But one that I want to particularly recommend is a great set of free lecture notes. It's called Mathematics for Computer Science. It's authored by Eric Lehman and Tom Layton, and it's quite easy to find on the web if you just do a web search. And those notes cover all of the prerequisites that we'll need in addition to tons of other stuff. In the spirit of keeping this course as widely accessible as possible, we're keeping the required supporting materials to an absolute minimum. Lectures are meant to be self-contained, and we'll always provide you with the lecture notes in PowerPoint and PDF format. Once in a while, we'll also provide some additional lecture notes. No textbook is required for this class, but that said, most of the material that we'll study is well covered in a number of excellent algorithms books that are out there. So I'll single out 4 such books here. The first 3 I mentioned because they've all had a significant influence on the way that I both think about and teach algorithms. So it's natural to acknowledge that debt here. One very cool thing about the second book, the one by Dasgupta, Papadimitriou, and Vazirani, is that the authors have made a version of it available online for free. And again, if you search on the authors' names and the textbook title, you should have no trouble coming up with it with a web search. Similarly, that's the reason I've listed the 4th book. Those authors have likewise made essentially complete version of that book available online, and it's a good match with the material that we're going to cover here. If you're looking for more details about something covered in this class or simply a different explanation than the one that I give you, all of these books are going to be good resources for you. There are also a number of excellent algorithms textbooks that I haven't put on this list. I encourage you to explore and find your own favorite. In our assignments, we'll sometimes ask you to code up an algorithm and use it to solve a concrete problem that is too large to solve by hand. Now, we don't care what programming language or development environment you use to do this, as we're only going to be asking you for the final answer. Thus, we're not requiring anything specific, just that you are able to write and execute programs. If you need help or advice about how to get set up with a suitable coding environment, we suggest that you ask other students for help via the course discussion forum. Finally, let's talk a bit more about assessment. Now, this course doesn't have official grades per se, but we will be assigning weekly homeworks. Now, we're going to assign homeworks for 3 different reasons. The first is just for self-assessment. It's to give you the opportunity to test your understanding of the material so that you can figure out which topics you've mastered and which ones that you haven't. The second reason we do it is to impose some structure on the course, including deadlines, to provide you with some additional motivation to work through all of the topics. Deadlines also have a very important side effect that it synchronizes a lot of the students in the class, and this of course makes the course discussion forum a far more effective tool for students to seek and provide help in understanding the course material. The final reason that we give homeworks is to satisfy those of you who, on top of learning the course material, are looking to challenge yourself intellectually. Now, this class has tens of thousands of students, so it's obviously essential that the assignments can be graded automatically. Now, we're currently only in the 1.0 generation of free online courses such as this one, so the available tools for auto-graded assessment are currently rather primitive. So we'll do the best we can, but I have to be honest with you. It's difficult or maybe even impossible to test deep understanding of the design and analysis of algorithms using the current set of tools. Thus, while the lecture content in this online course is in no way watered down from the original Stanford version, the required assignments and exams we'll give you are not as demanding as those that are given in the on-campus version of the course. To make up for this fact, we'll occasionally propose optional algorithm design problems, either in a video or via a supplementary assignment. We don't have the ability to grade these, but we hope that you'll find them interesting and challenging, and that you'll discuss possible solutions with other students via the course discussion forum. So I hope this discussion answered most of the questions that you have about the course. Let's move on to the real reason that we're all here, to learn more about algorithms. Okay, so in this video we'll get our first sense of what it's actually like to analyze an algorithm, and we'll do that by first of all reviewing a famous sorting algorithm, namely the merge sort algorithm, and then giving a really fairly mathematically precise upper bound on exactly how many operations the merge sort algorithm requires to correctly sort an input array. So I feel like I should begin with a bit of an apology. Here we are in 2012, a very futuristic sounding date, and yet I'm beginning with a really quite ancient algorithm. So for example, merge sort was certainly known to John von Neumann all the way back in 1945. So what justification do I have for beginning a modern class in algorithms with such an old example? Well, there's a bunch of reasons. One I haven't even put down on the slide, which is like a number of the algorithms we'll see, merge sort is an oldie but a goodie. So it's over 60 or maybe even 70 years old, but it's still used all the time in practice. Okay, so this really is one of the methods of choice for sorting. It's the standard sorting algorithm in a number of programming libraries. So that's the first reason. But there's a number of others as well that I want to be explicit about. So first of all, throughout these online courses, we'll see a number of general algorithm design paradigms, ways of solving problems that cut across different application domains. And the first one we're going to focus on is called the divide and conquer algorithm design paradigm. So in divide and conquer, the idea is you take a problem, you break it down into smaller subproblems, which you then solve recursively, and then you somehow combine the results of the smaller subproblems to get a solution to the original problem that you actually cared about. And merge sort is still, to this day, perhaps the most transparent application of the divide and conquer paradigm. It'll just be very clear what the paradigm is, what analysis challenges it presents, and what kind of benefits you might derive. As far as the benefits, so for example, you're probably all familiar with the sorting problem. Probably you know some number of sorting algorithms, perhaps including merge sort itself. And merge sort is better than a lot of the sort of simpler and I would say more obvious sorting algorithms. So for example, three other sorting algorithms that you might well know about, but that I'm not going to discuss here. If you don't know them, I encourage you to look them up in a textbook or look them up on the web. But so three sorting algorithms which are perhaps simpler. First of all is selection sort. So this is where you do a number of passes through your array, repeatedly identifying the minimum of the elements that you haven't looked at yet. So you do basically a linear number of passes, each time doing a minimum computation. There's insertion sort, which is still useful in certain cases in practice, as we'll discuss. But again, it's generally not as good as merge sort, where you just maintain the invariant that the prefix of the array is a sorted version of those elements. So after 10 loops of insertion sort, you'll have the invariant that whatever the first 10 elements of the array are, they're going to be in sorted order. And then when insertion sort completes, you have an entire sorted array. Finally, some of you may know about bubble sort. This is where you identify adjacent pairs of elements which are out of order, and you do repeated swaps until in the end the array is completely sorted. Again, I just say this to jog your memory. These are simpler sorts than merge sort, but all of them are worse in the sense that they all have performance in general, which scales with n squared when the input array has n elements. So they all have, in some sense, quadratic running time. But if we use this non-trivial divide and conquer approach, or non-obvious approach, we'll get, as we'll see, a much better running time than this quadratic dependence on the input. Okay, so we'll get a win for sorting in divide and conquer, and merge sort is the algorithm that realizes that benefit. So a second reason that I want to start out by talking about the merge sort algorithm is to help you calibrate your preparation. I think the discussion we're about to have will give you a good signal for whether your background's at about the right level of the audience that I'm thinking about for this course. So in particular, when I describe the merge sort algorithm, you'll notice that I'm not going to describe it in a level of detail that you could just translate it line by line into a working program in some programming language. My assumption, again, is that you're a solid enough programmer that you can take the high-level idea of the algorithm, how it works, and you're perfectly capable of turning that into a working program in whatever language you see fit. So hopefully, I don't, it may not be easy, the analysis of merge sort or the discussion of merge sort, but I hope that you find it at least relatively straightforward, because as the course moves on, we're going to be discussing algorithms and analyses which are a bit more complicated than the one we're about to do with merge sort. So in other words, I think this will be a good warm-up for what's to come. Now, another reason I want to discuss merge sort is that our analysis of it will naturally segue into discussion of how we analyze algorithms in this course and in general. So we're going to expose a couple of assumptions in our analysis. We'll focus on worst case behavior. We'll look for guarantees on performance, on running time that hold for every possible input of a given size. And it will also expose our focus on so-called asymptotic analysis, meaning we'll be much more concerned with the rate of growth of an algorithm's performance than on things like lower order terms or on small changes in constant factors. Finally, we'll do the analysis of merge sort using what's called a recursion tree method. So this is a way of counting up the total number of operations that are executed by an algorithm. And as we'll see a little bit later, this recursion tree method generalizes greatly, and it will allow us to analyze lots of different recursive algorithms, lots of different divide and conquer algorithms, including the integer multiplication algorithm that we discussed in an earlier segment. So those are the reasons to start out with merge sort. So what is the computational problem that merge sort is meant to solve? Well, presumably you all know about the sorting problem, but let me tell you a little bit about it anyways, just so that we're all on the same page. So we're given as input an array of n numbers in arbitrary order. And the goal, of course, is to produce an output array where the numbers are in sorted order, let's say from smallest to largest. Okay, so for example, we could consider the following input array, and then the goal would be to produce the following output array. Now, one quick comment. You'll notice that here in the input array, it had 8 elements and all of them were distinct. It was the different integers between 1 and 8. Now, the sorting problem really isn't any harder if you have duplicates. In fact, it can even be easier. But to keep the discussion as simple as possible, let's just, among friends, go ahead and assume that they're distinct for the purpose of this lecture. And I'll leave it as an exercise, which I encourage you to do, which is to think about how the merge sort algorithm implementation and analysis would be different, if at all, if there were ties. Okay, but we'll go ahead and make the distinctness assumption for simplicity from here on out. Okay, so before I write down any pseudocode for merge sort, let me just show you how the algorithm works using a picture. And I think it'll be pretty clear what the code would be, even just given a single example. So let's go ahead and consider the same unsorted input array that we had on the previous slide. So the merge sort algorithm is a recursive algorithm, and again, that means that it's a program which calls itself, and it calls itself on smaller subproblems of the same form. Okay, so the merge sort is, its purpose in life is to sort the given input array. So it's going to spawn off calls of itself on smaller arrays. And this is going to be a canonical divide and conquer application where we simply take the input array, we split it in half, we solve the left half recursively, we solve the right half recursively, and then we combine the results. So let's look at that in the picture. So the first recursive call gets the first 4 elements, the left half of the array, namely 5, 4, 1, and 8, and of course the other recursive call is going to get the rest of the elements, 7, 2, 6, and 3. You can imagine these as being copied into new arrays before they're given to the recursive calls. Now, by the magic of recursion, or by induction if you like, the recursive calls will do their task. They will correctly sort each of these arrays of 4 elements, and we'll get back sorted versions of them. So from our first recursive call, we receive the output 1, 4, 5, 8, and from the second recursive call, we receive the sorted output 2, 3, 6, 7. So now all that remains to complete merge sort is to take the 2 results of our recursive calls, these 2 sorted elements of length 4, and combine them to produce the final output, namely the sorted array of all 8 of the input numbers. And this is the step which is called the merge. And hopefully you already are thinking about how you might actually implement this merge in a computationally efficient way, but I do owe you some more details, and I will tell you exactly how the merge is done. In effect, you just walk pointers down each of the two sorted subarrays, copying over, populating the output array in sorted order. But I will give you some more details in just a slide or two. So that's merge sort in a picture. Split it in half, solve recursively, and then have some slick merging procedure to combine the two results into a sorted output. Okay, so let's move on and actually discuss the pseudocode for the merge sort algorithm. First, let me just tell you the pseudocode, leaving aside exactly how the merging subroutine is implemented. And thus high level should be very simple and clear at this point. So there's going to be two recursive calls, and then there's going to be a merging step. Now, I owe you a few comments because I'm being a little sloppy. Again, as I promised, this isn't something you would directly translate into code, although it's pretty close. But so what are a couple of the ways that I'm being sloppy? Well, first of all, there's, in any recursive algorithm, you got to have some base cases. You got to have this idea that when the input's sufficiently small, you don't do any recursion, you just return some trivial answer. So in the sorting problem, the base case would be if you're handed an array that has either 0 or 1 elements, well, it's already sorted, there's nothing to do, so you just return it without any recursion. Okay, so to be clear, I haven't written down the base cases, although of course you would if you were actually implementing merge sort. So let me make a note of that. A couple other things I'm ignoring. I'm ignoring what to do if the array has odd length. So if it has, say, 9 elements, obviously you have to somehow break that into 5 and 4 or 4 and 5. So you would do that just in either way, and that would be fine. And then secondly, I'm ignoring the details of what it really means to sort of recursively sort. So for example, I'm not discussing exactly how you would pass these subarrays onto the recursive calls. That's something that really would depend somewhat on the programming language. So that's exactly what I want to avoid. I really want to talk about the concepts which transcend any particular programming language implementation. So that's why I'm going to describe algorithms at this level. Okay. All right, so the hard part, relatively speaking then, is how do you implement the merge step? The recursive calls have done their work. We have these two sorted subarrays of half the numbers, the left half and the right half. How do we combine them into one? And in English, I already told you on the last slide, the idea is you just populate the output array in sorted order by traversing pointers or just traversing through the two sorted subarrays in parallel. So let's look at that in some more detail. Okay, so here is the pseudocode for the merge step. So let me begin by introducing some names for the characters in what we're about to discuss. So let's use C to denote the output array. So this is what we're supposed to spit out with the numbers in sorted order. And then I'm going to use A and B to denote the results of the two recursive calls. Okay, so the first recursive call has given us array A, which contains the left half of the input array in sorted order. Similarly, B contains the right half of the input array, again, in sorted order. So as I said, we're going to need to traverse the two sorted subarrays A and B in parallel. So I'm going to introduce a counter, I, to traverse through A, J to traverse through B. I and J will both be initialized to 1 to be at the beginning of their respective arrays. And now we're going to do a single pass through the output array, populating it in increasing order, always taking the smallest from the union of the two sorted subarrays. And if there's one idea in this merge step, it's just the realization that the minimum element that you haven't yet looked at in A and B has to be at the front of one of the two lists. Right? So, for example, at the very beginning of the algorithm, where is the minimum element overall? Well, whichever of the two arrays it lands in, A or B, it has to be the smallest one there. Okay, so the smallest element overall is either the smallest element in A or it's the smallest element in B. So you just check both places. The smaller one's the smallest. You copy it over and you repeat, and that's it. So the purpose of K is just to traverse the output array from left to right. That's the order we're going to populate it. We're currently looking at position I in the first array and position J in the second array. So that's how far we've gotten, how deeply we've probed into both of those two arrays. We look at which one has the current smallest and we copy the smallest one over. Okay, so if the entry in the ith position of A is smaller, we copy that one over. Of course, we have to increment I. We probe one deeper into the list A, and symmetrically for the case where the current position in B has the smaller element. Now again, I'm being a little bit sloppy so that we can focus on the forest and not not get bogged down with the trees. I'm ignoring some end cases. So if you really wanted to implement this, you'd have to add a little bit to keep track of when you fall off either A or B. Okay, so you'd have additional checks for when I or J reaches the end of the array, at which point you'd copy over all the remaining elements into C. All right, so I'm going to give you a cleaned up version of that pseudocode so that you don't have to tolerate my questionable handwriting any longer than is absolutely necessary. This again is just the same thing that we wrote on the last slide, okay, the pseudocode for the merge step. Now, so that's the merge sort algorithm. Now let's get to the meaty part of this lecture, which is, okay, so merge sort produces a sorted array. What makes it, if anything, better than much simpler non-divide and conquer algorithms like, say, insertion sort? In other words, what is the running time of the merge sort algorithm? Now, I'm not going to give you a completely precise definition of what I mean by running time, and there's good reason for that, as we'll discuss shortly. But intuitively, you should think of the running time of an algorithm. You should imagine that you're just running the algorithm in a debugger. Okay? And every time you press enter, you advance one line in the program through the debugger, and then basically the running time is just the number of operations executed, the number of lines of code executed. So the question is, how many times do you have to hit enter on your debugger before the program finally terminates? So we're interested in how many such lines of code get executed for a merge sort when the input array has n numbers. Okay, so that's a fairly complicated question. So let's start with a more modest goal. Rather than thinking about the number of operations executed by merge sort, which is this crazy recursive algorithm which is calling itself over and over and over again, let's just think about how many operations are going to get executed when we do a single merge of two sorted subarrays. That seems like it should be an easier place to start. So let me remind you the pseudocode of the merge subroutine. Here it is. So let's just go and count up how many operations are going to get used. So there's the initialization step. So let's say that I'm going to charge us one operation for each of these two initializations. So let's call this two operations to set I equal 1 and j equal 1. Then we have this for loop. So clearly the for loop executes a total number of n times. So in each of these n iterations of this for loop, how many instructions get executed? Well, we have one here. We have a comparison. So we compare AI to bj. And either way the comparison comes up, we then do two more operations. We do an assignment here or here, and then we do an increment of the relevant variable, either here or here. So that's going to be 3 operations per iteration. And then maybe I'll also say that in order to increment k, we're going to call it a 4th iteration. Okay, so for each of these n iterations of the for loop, we're going to do 4 operations. All right? So putting it all together, what do we have as the running time for merge? So let's say the upshot. So the upshot is that the running time of the merge subroutine, given an array of m numbers, is at most 4m plus 2. So a couple of comments. First of all, I've changed a letter on you, so don't get confused. In the previous slide, we were thinking about an input size of n. Here I've just I've changed the name of the variable to m. That's going to be convenient once we think about merge sort, which is recursing on smaller subproblems. But it's exactly the same thing, mn whatever. So an array of m entries, it does at most 4m plus 2 lines of code. The second thing is there's some ambiguity in exactly how we counted lines of code on the previous slide. So maybe you might argue that really each loop iteration should count as 2 operations, not just 1, because you don't just have to increment k, but you also have to compare it to the upper bound of n. Maybe. Would have been 5m plus 2 instead of 4m plus 2. So it turns out these small differences in how you count up the number of lines of code executed are not going to matter, and we'll see why shortly. So amongst friends, let's just agree, let's call it 4m plus 2 operations for merge to execute on an array of exactly m entries. So let me abuse our friendship now a little bit further with an inequality which is true but extremely sloppy. But I promise it'll make our lives just easier in some future calculations. So rather than 4m plus 2, this 2 is sort of getting on my nerves, let's just call this at most 6m, because m is at least 1. Okay? You have to admit, it's true, 6m always is at least 4m plus 2. It's very sloppy. These numbers are not anything close to each other for m large, but let's just go ahead and be sloppy in the interests of future simplicity. Okay? Now, I don't expect anyone to be impressed with this rather crude upper bound and the number of lines of code that the merge subroutine needs to finish, to execute. The key question to recall was how many lines of code does merge sort require to correctly sort the input array, not just this subroutine. And in fact, analyzing merge sort seems a lot more intimidating because it keeps spawning off these recursive versions of itself. So the number of recursive calls, the number of things we have to analyze is blowing up exponentially as we think about various levels of the recursion. Now, if there's one thing that we have going for us, it's that every time we make a recursive call, it's on quite a bit smaller input than what we started with. It's on an array of only half the size
of the input array. So there's some kind of tension between, on the one hand, explosion of subproblems, or proliferation of subproblems, and the fact that successive subproblems only have to solve smaller and smaller subproblems. And resolving these two forces is what's going to drive our analysis of merge sort. So the good news is I'll be able to show you a complete analysis of exactly how many lines of code merge sort takes, and I'll be able to give you, in fact, a very precise upper bound. Okay, so here's going to be the claim that we're going to prove in the remainder of this lecture. So the claim is that merge sort never needs more than 6 times n times the logarithm of n, log base 2, if you're keeping track, plus an extra 6n operations to correctly sort an input array of n numbers. Okay, so let's discuss for a second, is this good? Is this a win, knowing that this is an upper bound on the number of lines of code that merge sort takes? Well, yes it is, and it shows the benefits of the divide and conquer paradigm. Recall, in the simpler sorting methods that we briefly discussed, like insertion sort, selection sort, and bubble sort, I claimed that their performance was governed by a quadratic function of the input size. That is, they need a constant times n squared number of operations to sort an input array of length n. Merge sort, by contrast, needs at most a constant times n times log n, not n squared, but n times log n lines of code to correctly sort an input array. So to get a feel for what kind of win this is, let me just remind you, for those of you that are rusty or for whatever reason have lived in fear of the logarithm, just exactly what the logarithm is. Okay? So the way to think about the logarithm is as follows. So you have the x-axis, or you have n, which is going from 1 up to infinity. And for comparison, let's think about just the identity function. Okay? So the function which is just f of n equals n. Okay, and let's contrast this with the logarithm. So what is the logarithm? Well, for our purposes, we can just think of the logarithm as follows. Okay, so the log of n, log base 2 of n, is you type the number n into your calculator. Okay, then you hit divide by 2, and then you keep repeating dividing by 2, and you count how many times you divide by 2 until you get a number that drops below 1. Okay, so if you plug in 32, you got to divide 5 times by 2 to get down to 1. Log base 2 of 32 is 5. If you put in 1,024, you have to divide by 2 10 times until you get down to 1. So log base 2 of 10,024 is 10, and so on. Okay, so the point is, you can already see this. If log of 1,000 roughly is something like 10, then the logarithm is much, much smaller than the input. Okay, so graphically, what the logarithm is going to look like is it's going to look like a curve which becomes very flat very quickly as n grows large. Okay, so f of n being log base 2 of n, and I encourage you to do this perhaps a little more precisely on a computer or a graphing calculator at home, but log is going much, much, much slower than the identity function. And as a result, sorting algorithm which runs in time proportional to n times log n is much, much faster, especially as n grows large, than a sorting algorithm with a running time that's a constant times n squared. In this video, we'll be giving a running time analysis of the merge sort algorithm. In particular, we'll be substantiating the claim that the recursive divide and conquer merge sort algorithm is better, has better performance than simpler sorting algorithms that you might know, like insertion sort, selection sort, and bubble sort. So in particular, the goal of this lecture will be to mathematically argue the following claim from an earlier video, that in order to sort an array of n numbers, the merge sort algorithm needs no more than a constant times n log n operations. That's the maximum number of lines of code it will ever execute. Specifically, 6 times n log n plus 6n operations. So, how are we going to prove this claim? We're going to use what is called a recursion tree method. The idea of the recursion tree method is to write out all of the work done by the recursive merge sort algorithm in a tree structure, with the children of a given node corresponding to the recursive calls made by that node. The point of this tree structure is it will facilitate an interesting way to count up the overall work done by the algorithm, and will greatly facilitate the analysis. So specifically, what is this tree? So at level 0, we have a root, and this corresponds to the outer call of merge sort. Okay, so I'm going to call this level 0. Now this tree is going to be binary in recognition of the fact that each invocation of merge sort makes 2 recursive calls. So the 2 children will correspond to the 2 recursive calls of merge sort. So at the root, we operate on the entire input array. So let me draw a big array indicating that. And at level 1, we have one subproblem for the left half and another subproblem for the right half of the input array. And I'll call these first two recursive calls level 1. Now, of course, each of these two level 1 recursive calls will themselves make two recursive calls, each operating on then a quarter of the original input array. So those are the level 2 recursive calls, of which there are 4, and this process will continue until eventually the recursion bottoms out in base cases when there's only an array of size 0 or 1. So now I have a question for you, which I'll give you in the form of a quiz, which is at the bottom of this recursion tree corresponding to the base cases, what is the level number at the bottom? So at what level do the leaves in this tree reside? Okay, so hopefully you correctly guess that the answer is the second one. So namely that the number of levels of the recursion tree is essentially logarithmic in the size of the input array. The reason is basically that the input size is being decreased by a factor 2 with each level of the recursion. If you have an input size of n at the outer level, then each of the first set of recursive calls operates on an array of size n over 2. At level 2, each array has size n over 4, and so on. Where does the recursion bottom out? Well, down at the base cases where there's no more recursion, which is where the input array has size 1 or less. So in other words, the number of levels of recursion is exactly the number of times you need to divide n by 2 until you get down to a number that's at most 1. And recall that's exactly the definition of the logarithm base 2 of n. So since the first level is level 0 and the last level is level log base 2 of n, the total number of levels is actually log base 2 of n plus 1. And when I write down this expression, I'm here assuming that n is a power of 2, which is not a big deal. I mean, the analysis is easily extended to the case where n is not a power of 2. But this way, we don't have to think about fractions. Log base 2 of n then is an integer. Okay, so let's return to the recursion tree. Let me just redraw it really quick. So again, down here at the bottom of the tree, we have the leaves, i.e. the base cases where there's no more recursion, which when n is a power of 2 correspond exactly to single element arrays. So that's the recursion tree corresponding to an invocation of merge sort, and the motivation for writing down, for organizing the work performed by merge sort in this way is it allows us to count up the work level by level, and we'll see that that's a particularly convenient way to account for all of the different lines of code that get executed. Now, to see that in more detail, I need to ask you to identify a particular pattern. So first of all, the first question is, at a given level j of this recursion, exactly how many distinct subproblems are there as a function of the level j? That's the first question. The second question is, for each of those distinct subproblems at level j, what is the input size? So what is the size of the array which is passed to a subproblem residing at level j of this recursion tree? So the correct answer is the third one. So first of all, at a given level j, there's precisely 2 to the j distinct subproblems. There's one outermost subproblem at level 0. It has 2 recursive calls. Those are the 2 subproblems at level 1, and so on. In general, since merge sort calls itself twice, the number of subproblems is doubling each level, so that gives us the expression 2 to the j for the number of subproblems at level j. On the other hand, by a similar argument, the input size is halving each time. With each recursive call, you pass it half of the input that you were given. So at each level of the recursion tree, we're seeing half of the input size of the previous level. So after j levels, since we started with an input size of n, after j levels, each subproblem will be operating on an array of length n over 2 to the j. Okay, so now let's put this pattern to use and actually count up all of the lines of code that merge sort executes. And as I said before, the key idea is to count up the work level by level. Now, to be clear, when I talk about the amount of work done at level j, what I'm talking about is the work done by those 2 to the j invocations of merge sort, not counting their respective recursive calls, not counting work which is going to get done in the recursion lower in the tree. Now, recall, merge sort is a very simple algorithm. It just has 3 lines of code. First, there's a recursive call, so we're not counting that. Second, there's another recursive call. Again, we're not counting that at level j. And then third, we just invoke the merge subroutine. So really, outside the recursive calls, all that merge sort does is a single invocation of merge. Further, recall we already have a good understanding of the number of lines of code that merge needs. On an input of size m, it's going to use at most 6m lines of code. That's an analysis that we did in the previous video. So let's fix a level j. We know how many subproblems there are, 2 to the j. We know the size of each subproblem, n over 2 to the j, and we know how much work merge needs on such an input. We just multiply by 6, and then we just multiply it out, and we get the amount of work done at a level j, okay, at all of the level j subproblems. So here it is in more detail. All right, so we start with just the number of different subproblems at level j, and we just noticed that that was at most 2 to the j. We also observed that each level j subproblem is passed an array as input, which has length n over 2 to the j. And we know that the merge subroutine, when given an input, given an array of size n over 2 to the j, will execute at most 6 times that many number of lines of code. So to compute the total amount of work done at level j, we just multiply the number of problems times the work done per subproblem, and then something sort of remarkable happens. We get this cancellation of the 2 to the j's, and we get an upper bound, 6n, which is independent of the level j. So we do at most 6n operations at the root, we do at most 6n operations at level 1, at level 2, and so on. Okay, it's independent of the level. Morally, the reason this is happening is because of a perfect equilibrium between two competing forces. First of all, the number of subproblems is doubling with each level of the recursion tree, but secondly, the amount of work that we do per subproblem is halving with each level of the recursion tree. Since those two cancel out, we get an upper bound 6n, which is independent of the level j. Now, here's why that's so cool, right? We don't really care about the amount of work just at a given level. We care about the amount of work that merge sort does ever at any level. But if we have a bound on the amount of work at a level which is independent of the level, then our overall bound is really easy. What do? We just take the number of levels, and we know what that is. It's exactly log base 2 of n plus 1. Remember, the levels are 0 through log base 2 of n inclusive. And then we have an upper bound 6n for each of those log n plus 1 levels. So if we expand out this quantity, we get exactly the upper bound that was claimed earlier, namely that the number of operations merge sort executes is at most 6n times log base 2 of n plus 6n. So that, my friends, is a running time analysis of the merge sort algorithm. That's why its running time is bounded by a constant times n log n, which, especially as n grows large, is far superior to the more simple iterative algorithms like insertion or selection sort. Having completed our first analysis of an algorithm, namely an upper bound on the running time of the merge sort algorithm, what I want to do next is take a step back and be explicit about 3 assumptions, 3 biases that we made when we did this analysis of merge sort and interpreted the results. These 3 assumptions we will adopt as guiding principles for how to reason about algorithms and how to define a so-called fast algorithm for the rest of the course. So the first guiding principle is that we used what's often called worst case analysis. By worst case analysis, I simply mean that our upper bound of 6n log n plus 6n applies to the number of lines of executed for every single input array of length n. We made absolutely no assumptions about the input, where it comes from, what it looks like, beyond what the input length n was. Put differently, if hypothetically we had some adversary whose sole purpose in life was to concoct some malevolent input designed to make our algorithm run as slow as possible, the worst this adversary could do is upper bounded by this same number, 6n log n plus 6n. Now, this sort of worst case guarantee popped out so naturally from our analysis of merge sort, you might well be wondering, what else could you do? Well, 2 other methods of analysis, which do have their place, although we won't really discuss them in this course, are quote-unquote average case analysis and also the use of a set of pre-specified benchmarks. By average case analysis, I mean you analyze the average running time of an algorithm under some assumption about the relative frequencies of different inputs. So for example, in the sorting problem, one thing you could do, although it's not what we did here, you could assume that every possible input array is equally likely and then analyze the average running time of an algorithm. By benchmarks, I just mean that one agrees up front about some set, say 10 or 20, benchmark inputs which are thought to represent practical or typical inputs for the algorithm. Now, both average case analysis and benchmarks are useful in certain settings, but for them to make sense, you really have to have domain knowledge about your problem. You need to have some understanding of what inputs are more common than others, what inputs better represent typical inputs than others. By contrast, in worst case analysis, by definition, you're making absolutely no assumptions about where the input comes from. So as a result, worst case analysis is particularly appropriate for general purpose subroutines. Subroutines that you design without having any knowledge of how they will be used or what kind of inputs they will be used on. And happily, another bonus of doing worst case analysis, as we will in this course, it's usually mathematically much more tractable than trying to analyze the average performance of an algorithm under some distribution over inputs, or to understand the detailed behavior of an algorithm on a particular set of benchmark inputs. This mathematical tractability was reflected in our merge sort analysis, where we had no a priori goal of analyzing the worst case per se, but it's naturally what popped out of our reasoning about the algorithm's running time. The second and third guiding principles are closely related. The second one is that in this course, when we analyze algorithms, we won't worry unduly about small constant factors or lower order terms. We saw this philosophy at work very early on in our analysis of merge sort. When we discussed the number of lines of code that the merge subroutine requires, we first upper bounded it by 4m plus 2 for an array of length m, but then we said, let's just think about it as 6m instead. Let's have a simpler, sloppy upper bound and work with that. So that was already an example of not worrying about small changes in the constant factors. Now, the question you should be wondering about is, why do we do this, and can we really get away with it? So let me tell you about the justifications for this guiding principle. So the first motivation is clear, and we used it already in our merge sort analysis, which is it's simply way easier mathematically if we don't have to precisely pin down what the leading constant factors and lower order terms are. The second justification is a little less obvious, but is extremely important. So I claim that given the level at which we're describing and analyzing algorithms in this course, it would be totally inappropriate to obsess unduly about exactly what the constant factors are. Recall our discussion of the merge subroutine. So we wrote that subroutine down in pseudocode, and we gave an analysis of 4m plus 2 on the number of lines of code executed, given an input of length m. We also noted that it was somewhat ambiguous exactly how many lines of code we should count it as, depending on how you count loop increments, and so on. So even there, small constant factors could creep in, given the underspecification of the pseudocode. Depending on how that pseudocode gets translated into an actual programming language, like C or Java, you'll see the number of lines of code deviate even further. Not by a lot, but again by small constant factors. When such a program is then compiled down into machine code, you'll see even greater variance depending on the exact processor, the compiler optimizations, the programming implementation, and so on. So to summarize, because we're going to describe algorithms at a level that transcends any particular programming language, it would be inappropriate to specify precise constants. The precise constants will ultimately be determined by more machine-dependent aspects, like who the programmer is, what the compiler is, what the processor is, and so on. And now the third justification is, frankly, we're just going to be able to get away with it. That is, one might be concerned that ignoring things like small constant factors leads us astray, that we wind up deriving results which suggest that an algorithm is fast when it's really slow in practice, or vice versa. But for the problems that we discuss in this course, we'll get extremely accurate predictive power, even though we won't be keeping track of lower order terms and constant factors. When the mathematical analysis we do suggests that an algorithm is fast, indeed it will be. When it suggests that it's not fast, indeed that will be the case. So we lose a little bit of granularity of information, but we don't lose in what we really care about, which is accurate guidance about what algorithms are going to be faster than others. So the first two justifications, I think, are pretty self-evident. This third justification is more of an assertion, but it's one we'll be backing up over and over again as we proceed through this course. Now, don't get me wrong. I'm not saying constant factors aren't important in practice. Obviously, for crucial programs, the constant factors are hugely important. If you're running the sort of crucial loop for, that your startup's survival depends on, by all means, optimize the constant like crazy. The point is just that understanding tiny constant factors in the analysis is an inappropriate level of granularity for the kind of algorithm analysis we're going to be doing in this course. Okay, let's move on to the third and final guiding principle. So the third principle is that we're going to use what's called asymptotic analysis, by which I mean we will focus on the case of large input sizes, the performance of an algorithm as the size n of the input grows large, that is, tends to infinity. Now, this focus on large input sizes was already evident when we interpreted our bound on merge sort. So how did we describe the bound on merge sort? We said, oh, well, it needs a number of operations proportional, a constant factor times, n log n. And we very cavalierly declared that this was better than any algorithm which has quadratic dependence of its running time on the number of operations.
So for example, we argued that merge sort is a better, a faster algorithm than something like insertion sort without actually discussing the constant factors at all. So mathematically, we were saying the running time of merge sort, which we know we can represent as the function 6n log base 2 of n plus 6n, is better than any function which has a quadratic dependence on n, even one with a small constant, like let's say 1/2 n squared, which might be roughly the running time of insertion sort. And this is a mathematical statement that is true if and only if n is sufficiently large. Once n grows large, it's certainly true that the expression on the left is smaller than the expression on the right, but for small n, the expression on the right is actually going to be smaller because of the smaller leading term. So in saying that merge sort is superior to insertion sort, the bias is that we're focusing on problems with large n. So the question you should have is that reasonable? Is that a justified assumption to focus on large input sizes? And the answer is certainly yes. So the reason we focus on large input sizes is because, frankly, those are the only problems which are at all interesting. If all you need to do is sort 100 numbers, use whatever method you want, and it's going to happen instantaneously on modern computers. You don't need to know, say, the divide and conquer paradigm if all you need to do is sort 100 numbers. So one thing you might be wondering is if, with computers getting faster all the time, according to Moore's law, if really it doesn't even matter to think about algorithmic analysis, if eventually all problem sizes will just be trivially solvable on super fast computers. But in fact, the opposite is true. Moore's law, with computers getting faster, actually says that our computational ambitions will naturally grow. We naturally focus on ever larger problem sizes, and the gulf between an n squared algorithm and an n log n algorithm will become ever wider. A different way to think about it is in terms of how much bigger a problem size you can solve as computers get faster. If you're using an algorithm with a running time which is proportional to the input size, then if computers get faster by a factor of 4, then you can solve problems which are a factor of 4 larger. Whereas if you're using an algorithm whose running time is proportional to the square of the input size, then if computers get faster by a factor of 4, you can only solve double the problem size. And we'll see even starker examples of this gulf between different algorithmic approaches as time goes on. So to drive this point home, let me show you a couple of graphs. So what we're looking at here is we're looking at a graph of two functions. So the solid function is the upper bound that we proved on merge sort. So this is going to be 6n log base 2 of n plus 6n. And the dotted line is an estimate, a rather generous estimate about the running time of insertion sort, namely 1/2 times n squared. And we see here in the graph exactly the behavior we discussed earlier, which is that for small n, down here, in fact, because 1/2 n squared has a smaller leading constant, it's actually a smaller function. And this is true up to this crossing point of maybe 90 or so. But then beyond n equal 90, the quadratic growth in the n squared term overwhelms the fact that it had a smaller constant, and it starts being bigger than this other function, 6n log n plus 6n. So in the regime below 90, it's predicting that insertion sort will be better, and in the regime above 90, it's predicting that merge sort will be faster. Now here's what's interesting. Let's scale the x-axis. Let's look well beyond this crossing point of 90. Let's just increase it in order of magnitude up to arrays of size 1500. And I want to emphasize these are still very small problem sizes. If all you need to do is sort arrays of size 1500, you really don't need to know divide and conquer or anything else I'll talk about. That's a pretty trivial problem on modern computers. So what we're seeing is that even for very modest problem sizes, here array of size say 1500, the quadratic dependence in the insertion sort bound is more than dwarfing the fact that it had a lower constant factor. So in this large regime, the gulf between the two algorithms is growing, and of course if I increased it another 10x or 100x or 1000x to get to genuinely interesting problem sizes, the gap between these two algorithms would be even bigger. It would be huge. That said, I'm not saying you should be completely ignorant of constant factors when you implement algorithms. It's still good to have a general sense of what these constant factors are. So for example, in highly tuned versions of merge sort, which you'll find in many programming libraries, in fact, because of the difference in constant factors, the algorithm will actually switch from merge sort over to insertion sort once the problem size drops below some particular threshold, say 7 elements or something like that. So for small problem sizes, you use the algorithm with smaller constant factors, namely insertion sort. For larger problem sizes, you use the algorithm with better rate of growth, namely merge sort. So to review, our first guiding principle is that we're going to pursue worst case analysis. We're going to look to bounds on the performance, on the running time of an algorithm, which make no domain assumptions, which make no assumptions about which input of a given length the algorithm is provided. The second guiding principle is we're not going to focus on constant factors or lower order terms. That would be inappropriate given the level of granularity at which we're describing algorithms. And third is we're going to focus on the rate of growth of algorithms for large problem sizes. Putting these three principles together, we get a mathematical definition of a fast algorithm. Namely, we're going to pursue algorithms whose worst case running time grows slowly as a function of the input size. So let me tell you how you should interpret what I just wrote down in this box. So on the left-hand side is clearly what we want. Okay, we want algorithms which run quickly if we implement them. And on the right-hand side is a proposed mathematical surrogate of a fast algorithm. Right? The left-hand side is not a mathematical definition. The right-hand side is, as will become clear in the next set of lectures. So we're identifying fast algorithms, which those that have good asymptotic runtime, running time which grows slowly with the input size. Now, what would we want from a mathematical definition? We'd want a sweet spot. Okay, on the one hand, we want something we can actually reason about. This is why we zoom out and squint and ignore things like constant factors and lower order terms. We can't keep track of everything, otherwise we'd never be able to analyze stuff. On the other hand, we don't want to throw out the baby with the bathwater. We want to retain predictive power. And this definition turns out for the problems we're going to talk about in this course to be the sweet spot for reasoning about algorithms. Okay, worst case analysis using the asymptotic running time. We'll be able to prove lots of theorems. We'll be able to establish a lot of performance guarantees for fundamental algorithms. But at the same time, we'll have good predictive power. What the theory advocates will in fact be algorithms that are well known to be fast in practice. So the final explanation I owe you is what do I mean by the running time grows slowly with respect to the input size? Well, the answer depends a little bit on the context, but for almost all of the problems we're going to discuss, the holy grail will be to have what's called a linear time algorithm, an algorithm whose number of instructions grows proportional to the input size. So we won't always be able to achieve linear time, but that's in some sense the best case scenario. Notice linear time is even better than what we achieved with our merge sort algorithm for sorting. Merge sort runs a little bit superlinear. It's n times log n, where n is the input size. If possible, we'd love to be linear time. It's not always going to be possible, but that is what we will aspire toward for most of the problems we'll discuss in this course. Looking ahead, the next series of videos is going to have two goals. First of all, on the analysis side, I'll describe formally what I mean by asymptotic running time. I'll introduce big O notation and its variants, explain its mathematical definitions, and give a number of examples. On the design side, we'll get more experience applying the divide and conquer paradigm to further problems. See you then. In the following series of videos, we'll give a formal treatment of asymptotic notation, in particular big O notation, as well as work through a number of examples. Big O notation concerns functions defined on the positive integers. We'll call it T of n. We'll pretty much always have the same semantics for T of n. We're going to be concerned about the worst case running time of an algorithm as a function of the input size n. So the question I want to answer for you in the rest of this video is, what does it mean when we say a function T of n is big O of f of n? Where here f of n is some basic function like, for example, n log n. So I'll give you a number of answers, a number of ways to think about what big O notation really means. But for starters, let's begin with an English definition. What does it mean for a function to be big O of f of n? It means eventually, for all sufficiently large values of n, it's bounded above by a constant multiple of f of n. Let's think about it in a couple other ways. So next I'm going to translate this English definition into a picture, and then I'll translate it into formal mathematics. So pictorially, you could imagine that perhaps we have T of n denoted by this blue function here, and perhaps f of n is denoted by this green function here, which lies below T of n. But when we double f of n, we get a function that eventually crosses T of n and forevermore is larger than it. So in this event, we would say that T of n indeed is big O of f of n. The reason being that for all sufficiently large n, once we go far enough outright on this graph, indeed a constant multiple times f of n, twice f of n, is an upper bound on T of n. So finally, let me give you an actual mathematical definition that you could use to do formal proofs. So how do we say in mathematics that eventually it should be bounded above by a constant multiple of f of n? We say that there exist two constants, which I'll call c and n naught, so that T of n is no more than c times f of n
for all n that exceed or equal n naught. So the role of these two constants is to quantify what we mean by a constant multiple and what we mean by sufficiently large in the English definition. C obviously quantifies the constant multiple of f of n, and n naught is quantifying sufficiently large. That's the threshold beyond which we insist that c times f of n is an upper bound on t of n. So going back to the picture, what are c and n naught? Well, c of course is just going to be 2. And n naught is the crossing point. So if you look at where 2f of n and t of n cross, and then we drop the asymptote, this would be the relevant value of n naught in this picture. So that's the formal definition. The way to prove that something's big O of f of n, you exhibit these two constants, c and n naught, and it better be the case that for all n at least n naught, c times f of n upper bounds t of n. One way to think about it, if you're trying to establish that something is big O of some function, it's like you're playing a game against an opponent. And you want to prove that this inequality here holds, and your opponent wants to show that it doesn't hold for sufficiently large n. You have to go first. Your job is to pick a strategy in the form of a constant c and a constant n naught, and your opponent is then allowed to pick any number n larger than n naughts. So the function is big O of f of n if and only if you have a winning strategy in this game. If you can upfront commit to constants c and n naught so that no matter how big an n your opponent picks, this inequality holds. If you have no winning strategy, then it's not big O of f of n. No matter what c and n naught you choose, your opponent can always flip this inequality by choosing a suitable large value of n. I want to emphasize one last thing, which is that these constants, what do I mean by a constant? I mean they are independent of n. So when you apply this definition and you choose your constant c and n naught, it better be that n does not appear anywhere. So c should just be something like 1,000 or 1,000,000, some constant independent of n. So those are a bunch of ways to think about big O notation. In English, you want to have a bound above for sufficiently large numbers n. I've shown you how to translate that into mathematics. I give you a pictorial representation and also a sort of game theoretic way to think about it. Now let's move on to a video that explores a number of examples. Having slogged through the formal definition of big O notation, I want to quickly turn to a couple of examples. Now, I want to warn you up front, these are pretty basic examples. They're not really going to provide us with any insight that we don't already have, but they serve as a sanity check that the big O notation is doing what its intended purpose is, namely to suppress constant factors and lower order terms. Obviously, these simple examples will also give us some facility with the definition. So the first example is going to be to prove, formally, the following claim. The claim states that if t of n is some polynomial of degree k, so namely ak n to the k plus all the way up to a1n plus a naught for any integer k, positive integer k, and any coefficients ai's, positive or negative, then t of n is big O of n to the k. So this claim is a mathematical statement. It's something we'll be able to prove. As far as what this claim is saying, it's just saying big O notation really does suppress constant factors and lower order terms. If you have a polynomial, then all you have to worry about is what is the highest power in that polynomial, and that dominates its growth as n goes to infinity. So recall how one goes about showing that one function is big O of another. The whole key is to find this pair of constants c and n naught, where c quantifies the constant multiple of the function you're trying to prove big O of, and n naught quantifies what you mean by for all sufficiently large n. Now, for this proof, to keep things very simple to follow, but admittedly a little mysterious, I'm just going to pull these constants c and n naught out of a hat. So I'm not going to tell you how I derived them, but it'll be easy to check that they work. So let's work with a constant n naught equal to 1. So that's a very simple choice of n naught. And then c we're going to pick to be the sum of the absolute values of the coefficients. So the absolute value of ak plus the absolute value of ak minus 1, and so on. Remember, I didn't assume that the original polynomial had non-negative coefficients. So I claim these constants work in the sense that we'll be able to prove establish the definition of big O notation. What does that mean? Well, we need to show that for all n at least 1, because remember we chose n naught equal to 1, t of n, this polynomial up here, is bounded above by c times n to the k, where c is the way we chose it here, underlined in red. So let's just check why this is true. So for every positive integer n at least 1, what do we need to prove? We need to prove t of n is upper bounded by something else. So we're going to start on the left-hand side with t of n, and now we need a sequence of upper bounds terminating with c times n to the k for our choice of c, underlined in red. So T of n is given is equal to this polynomial underlined in green. So what happens when we replace each of the coefficients with the absolute value of that coefficient? Well, you take the absolute value of a number, either it stays the same as it was before, or it flips from negative to positive. Now, n here we know is at least 1, so if any coefficient flips from negative to positive, then the overall number only goes up. So if we apply the absolute value to each of the coefficients, we get an only bigger number. So T of n is bounded above by the new polynomial, where the coefficients are the absolute values of those that we had before. So why was that a useful step? Well, now what we can do is we can play the same trick, but with n. So it's sort of annoying how right now we have these different powers of n. It would be much nicer if we just had a common power of n. So let's just replace all of these different n's by n to the k, the biggest power of n that shows up anywhere. So if we replace each of these lower powers of n with the higher power n to the k, that number only goes up. Now the coefficients are all non-negative, so the overall number only goes up. So this is bounded above by the absolute value of ak n to the k, up to absolute value of a1 n to the k plus a naught n to the k. I'm using here that n is at least 1, so higher powers of n are only bigger. And now you'll notice this, by our choice of c, underlined in red, this is exactly equal to c times n to the k. And that's what we had to prove. We had to prove that T of n is a most c times n to the k, given our choice of c for every n at least 1, and we just proved that. So, end of proof. Now there remains the question of how did I know what a workable value of c and n naught were. And if you yourself want to prove that something is big O of something else, usually what you do is you reverse engineer constants that work. So you would go through a proof like this with a generic value of c and n naught, and then you'd say, oh, well, if only I choose c in this way, I can push the proof through. And that tells you what c you should use. If you look at the optional video on further examples of asymptotic notation, you'll see some examples where we derive the constants via this reverse engineering method. But now let's turn to a second example, or really I should say a non-example. So what we're going to prove now is that something is not big O of something else. So I claim that for every k, at least 1, n to the k is not big O of n to the k minus 1. And again, this is something you would certainly hope would be true. If this was false, there'd be something wrong with our definition of big O notation. And so really this is just to get further comfort with the definition, how to prove something is not big O of something else, and to verify that indeed you don't have any collapse of distinct powers of polynomials, which would be a bad thing. So how would we prove that something is not big O of something else? The most frequently useful proof method is going to be by contradiction. So remember, proof by contradiction, you assume what you're trying to establish is actually false, and from that you do a sequence of logical steps culminating in something which is just patently false, which contradicts basic axioms of mathematics or of arithmetic. So suppose in fact n to the k was big O of n to the k minus 1. So that's assuming the opposite of what we're trying to prove. What would that mean? Well, we just refer to the definition of big O notation. If, in fact, n to the k hypothetically were big O of n to the k minus 1, then, by definition, there would be two constants, a winning strategy, if you like, c and n naught, such that for all sufficiently large n, we have a constant multiple c times n to the k minus 1, upper bounding n to the k. So from this, we need to derive something which is patently false. That will complete the proof. And the easiest way to do that is to cancel n to the k minus 1 from both sides of this inequality. And remember, since n is at least 1 and k is at least 1, it's legitimate to cancel this n to the k minus 1 from both sides. And when we do that, we get the assertion that n is at most some constant c for all n at least n naught. And this now is a patently false statement. It is not the case that all positive integers are bounded above by a constant c. In particular, c plus 1, or the integer right above that, is not bigger than c. So that provides the contradiction. That shows that our original assumption that n to the k is big O of n to the k minus 1 is false, and that proves the claim. N to the k is not big O of n to the k minus 1 for every value of k. So different powers of polynomials do not collapse. They really are distinct with respect to big O notation. In this lecture, we'll continue our formal treatment of asymptotic notation. We've already discussed big O notation, which is by far the most important and ubiquitous concept that's part of asymptotic notation. But for completeness, I do want to tell you about a couple of close relatives of big O, namely omega and theta. If big O is analogous to less than or equal to, then omega and theta are analogous to greater than or equal to and equal to, respectively. But let's treat them a little more precisely. The formal definition of omega notation closely mirrors that of big O notation. We say that one function t of n is big omega of another function f of n if eventually, that is, for sufficiently large n, it's lower bounded by a constant multiple of f of n. And we quantify the ideas of a constant multiple and eventually in exactly the same way as before, namely via explicitly giving two constants c and n naught, such that t of n is bounded below by c times f of n for all sufficiently large n, that is, for all n at least n naught. There's a picture, just like there was for big O notation. Perhaps we have a function t of n, which looks something like this green curve. And then we have another function, f of n, which is above t of n. But then when we multiply f of n by 1/2, we get something that eventually is always below t of n. So in this picture, this is an example where t of n is indeed big omega of f of n. As far as what the constants are, well, the multiple that we use, c, is obviously just 1/2. That's what we're multiplying f of n by. And as before, n naught is the crossing point between the two functions. So n naught is the point after which c times f of n always lies below t of n forevermore. So that's big omega. Theta notation is the equivalent of equals, and so it just means that the function is both big O of f of n and omega of f of n. An equivalent way to think about this is that eventually t of n is sandwiched between two different constant multiples of f of n. I'll write that down and I'll leave it to you to verify that the two notions are equivalent. That is, one implies the other and vice versa. So what do I mean by t of n is eventually sandwiched between two multiples of f of n? Well, I just mean we choose two constants, a small one c1 and a big constant c2, and for all n at least n naught, t of n lies between those two constant multiples. One way that algorithm designers can be quite sloppy is by using O notation instead of theta notation. So that's a common convention, and I will follow that convention often in this class. Let me give you an example. Suppose we have a subroutine which does a linear scan through an array of length n. It looks at each entry in the array and does a constant amount of work with each entry. So the merge subroutine would be more or less an example of a subroutine of that type. So even though the running time of such an algorithm, a subroutine, is patently theta of n, it does constant work for each of n entries, so it's exactly theta of n. We'll often just say that it has running time O of n. We won't bother to make the stronger statement that it's theta of n. The reason we do that is because, as algorithm designers, what we really care about is upper bounds. We want guarantees on how long our algorithms are going to run, so naturally we focus on the upper bounds and not so much on the lower bound side. So don't get confused. Once in a while, there'll be a quantity which is obviously theta of f of n, and I'll just make the weaker statement that it's O of f of n. The next quiz is meant to check your understanding of these three concepts: big O, big omega, and big theta notation. So the final three responses are all correct. And I hope the high-level intuition for y is fairly clear. T of n is definitely a quadratic function. We know that the linear term doesn't matter much as n grows large. So since it has quadratic growth, then the third response should be correct. It's theta of n squared. And it is omega of n. So omega of n is not a very good lower bound on the asymptotic rate of growth of t of n, but it is legitimate. Indeed, as a quadratic growing function, it grows at least as fast as a linear function. So it's omega of n. For the same reason, big O of n cubed, it's not a very good upper bound, but it is a legitimate one. It is correct. The rate of growth of t of n is at most cubic. In fact, it's at most quadratic, but it is indeed at most cubic. Now, if you wanted to prove these three statements formally, you would just exhibit the appropriate constants. So for proving that it's big omega of n, you could take n naught equal to 1 and c equal to 1/2. For the final statement, again, you could take n naught equal to 1 and c equal to, say, 4. And to prove that it's theta of n squared, you could do something similar, just using the two constants combined. So n naught would be 1. You could take c1 to be 1/2 and c2 to be 4. And I'll leave it to you to verify that the formal definitions of big omega, big theta, and big O would be satisfied with these choices of constants. One final piece of asymptotic notation, we're not really going to use this much, but you do see it from time to time, so I wanted to mention it briefly. This is called little o notation, in contrast to big O notation. So while big O notation informally is a less than or equal to type relation, little o is a strictly less than relation. So intuitively it means that one function is growing strictly less quickly than another. So formally we say that a function t of n is little o of f of n, if and only if for all constants c, there is a constant n naught beyond which t of n is upper bounded by this constant multiple c times f of n. So the difference between this definition and that of big O notation is that to prove that one function is big O of another, we only have to exhibit one measly constant c, such that c times f of n is a upper bound eventually for t of n. By contrast, to prove that something is little o of another function, we have to prove something quite a bit stronger. We have to prove that for every single constant c, no matter how small, for every c there exists some large enough n naught beyond which t of n is bounded above by c times f of n. So for those of you looking for a little more facility with little o notation, I'll leave it as an exercise to prove that, as you'd expect, for all polynomial powers k, in fact, n to the k minus 1 is little o of n to the k. There is an analogous notion of little omega notation expressing that one function grows strictly quicker than another, but that one you don't see very often, and I'm not going to say anything more about it. So let me conclude this video with a quote from an article back from 1976 by my colleague Don Knuth, widely regarded as the grandfather of the formal analysis of algorithms. And it's rare that you can pinpoint why and where some kind of notation became universally adopted in the field. But in the case of asymptotic notation, indeed, it's very clear where it came from. The notation was not invented by algorithm designers or computer scientists. It's been in use in number theory since the 19th century, but it was Don Knuth in '76 that proposed that this become the standard language for discussing rate of growth, and in particular for the running time of algorithms. So in particular, he says in this article, on the basis of the issues discussed here, I propose that members of SIGACT, this is the special interest group of the ACM, which is concerned with theoretical computer science, in particular the analysis of algorithms. So I propose that the members of SIGACT and editors in computer science and mathematics journals adopt the O, Omega, and Theta notations as defined above, unless a better alternative can be found reasonably soon. So clearly a better alternative was not found, and ever since that time this has been the standard way of discussing the rate of growth of running times of algorithms, and that's what we'll be using here. This video is for those of you who want some additional practice with asymptotic notation, and we're going to go through 3 additional optional examples. Let's start with the first one. So the point of this first example is to show how to formally prove that one function is big O of another. So the function that I want to work with is 2 raised to the n plus 10. Okay, so it's the 2 to the n function that you're all familiar with, but I'm going to shift it by 10. And the claim is that this function is big O of 2 to the n, so without the 10. So how would one prove such a claim? Well, let's go back to the definition of what it means for one function to be big O of another. What we have to prove is we need to show that there exist 2 constants such that for all sufficiently large n, meaning n bigger than n naught, our left-hand side, so the function 2 to the n plus 10, is bounded above by the constant multiple c times the function on the right-hand side, 2 to the n. Right? So for all sufficiently large n, the function is bounded above by a constant multiple of 2 to the n. So unlike the first basic example where I just pulled the 2 constants out of a hat, let's actually start the proof and see how you'd reverse engineer the suitable choice of these 2 constants. So what a proof would look like, it would start with 2 to the n plus 10 on the left-hand side, and then there'd be a chain of inequalities terminating in this c times 2 to the n. So let's just go ahead and start such a proof and see what we might do. So if we start with 2 to the n plus 10 on the left-hand side, what would our first step look like? Well, this 10 is really annoying, so it makes sense to separate it out. So you could write 2 to the n plus 10 as the product of 2 terms, 2 to the 10 and then the 2 to the n, also known as just 1024 times 2 to the n. And now we're looking in really good shape. So if you look at where we are so far and where we want to get to, it seems like we should be choosing our constant c to be 1024. So if we choose c to be 1024, and we don't have to be clever with n naught, we can just set that equal to 1, then indeed star holds, so the desired inequality. And remember, to prove that one function is big O of another, all you got to do is come up with one pair of constants that works. And we've just reverse engineered it, just choosing the constant c to be 1024 and not to be 1 works. So this proves that 2 to the n plus 10 is big O of 2 to the n. Next, let's turn to another non-example, of a function which is not big O of another. And so this will look superficially similar to the previous one. Instead of adding 10 in the exponent of the function 2 to the n, I'm going to multiply by 10 in the exponent. And the claim is if you multiply by 10 in the exponent, then this is not the same asymptotically as 2 to the n. So once again, usually the way you prove that one thing is not big O of another is by contradiction. So we're going to assume the contrary, that 2 to the 10n is in fact big O of 2 to the n. What would it mean if that were true? Well, by the definition of big O notation, that would mean there are constants c and n naught, so that for all large n, 2 to the 10n is bounded above by c times 2 to the n. So to complete the proof, what we have to do is go from this assumption and derive something which is obviously false, but that's easy to do just by canceling this 2 to the n term from both sides. So if we divide both sides by 2 to the n, which is a positive number since n is positive, what we find would be a logical consequence of our assumption would be that 2 raised to the 9n is bounded above by some fixed constant c for all n at least n naught. But this inequality, of course, is certainly false. The right-hand side is some fixed constant independent of n. The left-hand side is going to infinity as n grows large, so there's no way that this inequality holds for arbitrarily large n. So that concludes the proof by contradiction. This means our assumption was not the case, and indeed it is not the case that 2 to the 10n is big O of 2 to the n. So our third and final example is a little bit more complicated than the first two. It'll give us some practice using theta notation. Recall that while big O is analogous to saying one function is less than or equal to another, theta notation is in the spirit of saying one function is equal asymptotically to another. So here's going to be the formal claim we're going to prove. For every pair of functions, f and g, both of these functions are defined on the positive integers, the claim is that it doesn't matter, up to a constant factors, whether we take the pointwise maximum of the two functions or whether we take the pointwise sum of the two functions. So let me make sure it's clear that you know what I mean by the pointwise maximum, by max f and g. So if we look at the two functions, both functions of n, maybe we have f being this green function here, and we have g equal to this red function. Then by the pointwise maximum, max fg, I just mean the upper envelope of these two functions. So that's going to be this blue function. So let's now turn to the proof of this claim, that the pointwise maximum of two functions is theta of the sum of the two functions. So let's recall what theta means formally. What it means is that the function on the left can be sandwiched between constant multiples of the function on the right. So we need to exhibit both the usual and not, but also two constants, a small one c1 and a big one c2, so that the pointwise maximum of f and g, whatever they may be, is wedged in between c1 and c2 times f of n plus g of n, respectively. So to see where these constants c1 and cn are going to come from, let's observe the following inequalities. So no matter what n is, any positive integer n, we have the following. Suppose we take the larger of f of n and g of n. And remember, now we've fixed the value of n is just some integer, like 23. And now f of n and g of n are themselves just numbers, maybe they're 57 and 74 or whatever. And if you take the larger of f of n and g of n, that's certainly no more than the sum of f of n plus g of n. Now I'm using in this inequality that f and g are positive, and that's something I've been assuming throughout the course so far. Here I want to be explicit about it. We're assuming that f and g cannot output negative numbers. Whatever integer you feed in, you get out something positive. Now the functions we care about are things like the running time of algorithms, so there's really no reason for us to pollute our thinking with negative numbers. So we're just going to always be assuming in this class positive numbers, and I'm actually using it here. The right-hand side is the sum of two things is bigger than just either one of the constituent summands. Secondly, if we double the larger of f of n and g of n, well then that's going to exceed the sum of f of n plus g of n, right? Because on the right-hand side we have a big number plus a small number, and on the left-hand side we have two copies of the big number. So that's going to be something larger. Now it's going to be convenient, it's going to be more obvious what's going on if I divide both of these sides by 2, so that the maximum of f of n and g of n is at least half of f of n plus g of n. That is, it's at least half of the average. And now we're pretty much home free, right? So what does this say? This says that for every possible n, the maximum is wedged between suitable multiples of the sum. So 1/2 f of n plus g of n is a lower bound on the maximum. This is just the second inequality that we derived. And by the first inequality, that's bounded above by once times the sum. And this holds no matter what n is, any n at least 1. And this is exactly what it means to prove that one function is theta of another. We've shown that for all n, not just for n sufficiently large, but in fact for all n, the pointwise maximum of f and g is wedged between suitable constant multiples of their sum. And again, just to be explicit, the certifying choices of constants are n naught equals 1, the smaller constant is 1/2, and the bigger constant equals 1. And that completes the proof. In this next series of videos, we'll get some more practice applying the divide and conquer algorithm design paradigm to various problems. This will also give us a glimpse of the kinds of application domains to which it's been successfully applied. We're going to start by extending the merge sort algorithm to solve a problem involving counting the number of inversions of an array. Before we tackle the specific problem of counting the number of inversions in an array, let me say a few words about the divide and conquer paradigm in general. So again, you've already seen the totally canonical example of divide and conquer, namely merge sort, so the following 3 conceptual steps will be familiar to you. The first step, no prizes for guessing, is you divide the problem into smaller subproblems. Sometimes this division happens only in your mind. It's really more of a conceptual step than part of your code. Sometimes you really do copy over parts of the input into, say, new arrays to pass on to your recursive calls. The second step, again, no prizes here, is you conquer the subproblems just using recursion. So for example, in merge sort, you conceptually divide the array into 2 different pieces, and then you recursively conquer or sort the first half of the array, and you do the same thing with the second half of the array. Now, of course, it's not quite as easy as just doing these 2 steps, dividing the problem and then solving the subproblems recursively. Usually you have some extra cleanup work after the recursive calls end to stitch together the solutions to the subproblems into one for the big problem, the problem that you actually care about. Recall, for example, in merge sort, after our recursive calls, the left half of the array was sorted, the right half of the array was sorted, but we still had to stitch those together and merge into a sorted version of the entire array. So the third step is to combine the solutions to the subproblems into one of the original problem. Generally, the largest amount of ingenuity happens in the third step. How do you actually quickly combine solutions to subproblems into one to the original problem? Sometimes you also get some cleverness in the first step with division. Sometimes it's as simple as just splitting an array in 2, but there are cases where the division step also has some ingenuity. Now let's move on to the specific problem of counting inversions and see how to apply this divide and conquer paradigm. So let me begin by defining the problem formally. We're given as input an array A of length n, and you could define the problem so that the array A contains any old distinct numbers, but let's just keep things simple and assume that it contains the numbers 1 through n, the integers in that range in some order. That captures the essence of the problem. And the goal is to compute the number of inversions of this array. So what's an inversion, you may ask? Well, inversion is just a pair of array indices I and j, with I smaller than j, so that the earlier array entry, the ith entry, is bigger than the later one, than the jth one. So one thing that should be evident is that if the array contains these numbers in sorted order, if the array is simply 1, 2, 3, 4, all the way up to n, then the number of inversions is 0. The converse you might also want to think through. If the array has any other ordering of the numbers between 1 and n other than the sorted one, then it's going to have a non-zero number of inversions. Let's look at another example. So suppose we have an array of 6 entries, so the numbers 1 through 6 in the following order. 1, 3, 5, followed by 2, 4, 6. So how many inversions does this array have? So again, what we need to look for are pairs of array entries so that the earlier or left entry is bigger than the later or right entry. So one example which we see right here would be 5 and 2. Those are right next to each other and out of order. The earlier entry is bigger than the other one. But there's others. There's 3 and 2, for example. Those are out of order. And 5 and 4 are also out of order. And I'll leave it to you to check that those are the only 3 pairs that are out of order. So summarizing the inversions in this array of length 6 are 3, 2, 5, 2, and 5, 4, corresponding to the array entries 2, 4, 3, 4, and 3, 5. Pictorially, we can think of it thusly. We can first write down the numbers in order, 1 up to 6, and then we can write down the numbers again, but ordered in the way that they're given in the input array. So 1, 3, 5, 2, 4, 6. And then we can connect the dots, meaning we connect 1 to 1, we connect 2 to 2, and so on. It turns out, and I'll leave it for you to think this through, that the number of crossing pairs of line segments precisely correspond to the number of inversions. So we see that there are 1, 2, 3 crossing line segments, and these are exactly in correspondence with the 3 inversions we found earlier: 5 and 2, 3 and 2, and 5 and 4. Now, why might you want to solve this problem, you might ask? Well, there's a few reasons it comes up, but one would be to have a numerical similarity measure that quantifies how close 2 different ranked lists are to each other. So for example, suppose I took you and a friend and I identified 10 movies that both of you had seen, and I asked each of you to rank these movies from your most favorite to your least favorite. Now I can form an array and compute inversions, and it quantifies in some sense how dissimilar your 2 rankings are to each other. So in more detail, in the first entry of this array, I would put down the ranking that your friend gave to your favorite movie. So if you had your favorite movie, Star Wars or whatever, and your friend only thought it was the 5th best out of the 10, then I would write down a 5 in the first entry of this array. Similarly, I would take your second favorite movie, I would look at how your friend ranked that, I would put that in the second entry of the array, and so on, all the way up to the 10th entry of the array, where I would put your friend's ranking of your least favorite movie. Now, if you have exactly identical preferences, if you rank them exactly the same way, the number of inversions of this array would be 0. And in general, the more inversions this array has, it quantifies that your lists look more and more different from each other. Now, why might you want to do this? Why might you want to know whether 2 different people ranked things in a similar way, had similar preferences? Well, one reason would be in what's called collaborative filtering. So probably many of you have had the experience of going to a website, and if you've made a few purchases from this website, it starts recommending further purchases for you. So one way to solve that problem under the hood is to look at your purchases, look at what you seem to like, find other people who have similar preferences or similar history, look at things that they've bought that you haven't, and then recommend new products to you based on what similar customers seem to have bought. So this problem captures some of the essence of identifying which customers or which people are similar based on data about what they prefer. So just to make sure we're all on the same page, let me pause for a brief quiz. We've already noticed that a given array will have 0 inversions if and only if it's in sorted order, or if it only contains the numbers 1 through n in order. So on the other side, what is the largest number of inversions an array could possibly have? Let's say just for an array of size 6, like the one in this example here. So the answer to this question is the first one, 15, or in general, in an n-element array, the largest number of inversions is n choose 2, also known as n times n minus 1 over 2. Which again, in the case of a 6-element array, is going to evaluate to 15. The reason is the worst case is when the array is in backwards order, reverse sorted order, and then every single pair of array indices is inverted, and so the number of indices ij with I less than j is precisely n choose 2. Let's now turn our attention to the problem of computing the number of inversions of an array as quickly as possible. So one option which is certainly available to us is the brute force algorithm. And by brute force, I just mean we could set up a double for loop, one which goes through I, one which goes through j bigger than I, and we just check each pair ij individually with I less than j, whether that particular pair of array entries, ai and aj, is inverted. And if it is, then we add it to a running count. And then we return the final count at the end of the double for loop. That's certainly correct. The only problem is, as we just observed, there's n choose 2, or a quadratic number of potential inversions, so this algorithm is always going to run in time quadratic in the array length. Now remember the mantra of any good algorithm designer. Can we do better? And the answer is yes, and the method will be using divide and conquer. The way in which we divide will be motivated directly by merge sort, where we recur separately on the left and the right halves of the array. We're going to do the same thing here. To understand how much progress we can make purely using recursion, let's classify the inversions of array into one of 3 types. So suppose we have an inversion of an array I comma j. And remember, in an inversion you always have I less than j. We're going to call it a left inversion if both of the array indices are at most n over 2, where n is the array length. We're going to call it a right inversion if they're both strictly greater than n over 2. And we're going to call it a split inversion if the smaller index is at most n over 2 and the larger index is bigger than n over 2. We can discuss the progress made by recursion in these terms. When we recurse on the left half of an array, if we implement our algorithm correctly, we'll successfully be able to count all of the inversions located purely in that first half. Those are precisely the left inversions. Similarly, a second recursive call on just the right half of an array, the second half of an array, will successfully count all of the right inversions. There remains the question of how to count the split inversions, but we shouldn't be surprised there's some residual work left over even after the recursive calls do their job. That, of course, was the case in merge sort. Recursion magically took care of sorting the left half of the array, sorting the right half of the array, but there was still, after their return, the matter of merging those two sorted lists into one. And here again, after the recursion, there's going to be the matter of cleaning up and counting the number of split inversions. So for example, if you go back to the 6-element array we worked through before, 1, 3, 5, 2, 4, 6, you'll notice that there, in fact, all of the inversions are split. So the recursive calls will both come back counting 0 inversions, and all of the work for that example will be done by the count split inversions subroutine. So let's summarize where things stand and give an underspecified high-level description of the algorithm as we envision it. There is a base case. I'll go ahead and write it down for completeness, which is if we're given a 1-element array, then there's certainly no inversion, so we can just immediately return the answer 0. For any bigger array, we're going to divide and conquer, so we'll count the left inversions with a recursive call, the right inversions with a recursive call, and then we'll have some currently unimplemented subroutine that counts the split inversions. Since every inversion is either left or right or split and can't be any more than one of those three, then having done these three things, we can simply return their sum. So that's our high-level attack on how we're going to count up the number of inversions. And of course, we need to specify how we're going to count the number of split inversions. And moreover, we like that subroutine to run quickly. In analogy to merge sort, where outside the recursive calls we did merely linear work, in the merge subroutine, here we'd like to do only linear work in counting up the number of split inversions. If we succeed in this goal, if we produce a correct and linear time implementation to count up the number of split inversions, then this entire recursive algorithm will run in big O of n log n time. The reason the overall algorithm will run in O of n log n time is exactly the same reason that merge sort ran in n log n time. There's two recursive calls, each on a problem of half the size, and outside of the recursive calls we would be doing linear work. So you could copy down exactly the same recursion tree argument we used for merge sort. It would apply equally well here. Alternatively, very soon we will cover the master method, and as one very special case, it will prove that this algorithm, if we can implement it thusly, will run in O of n log n time. Now, one thing to realize is this is a fairly ambitious goal, to count up the number of split inversions in linear time. It's not that there can't be too many split inversions. There can actually be a lot of them. If you have an array where the first half of the array contains the numbers n over 2 plus 1 up to n, whereas the second part of the array contains the numbers 1 up to n over 2, that has a quadratic number of inversions, all of which are split. So what we're attempting to do here is count up a quadratic number of things using only linear time. Can it really be done? Yes, it can, as we'll see in the next video. So far, we've developed a divide and conquer approach to counting the number of inversions of an array. So we're going to split the array in two parts, recursively count inversions on the left, on the right. We've identified the key challenge as counting the number of split inversions quickly, where a split inversion means that the earlier index is on the left half of the array, the second index is on the right half of the array. These are precisely inversions that are going to be missed by both of our recursive calls. And the crux of the problem is that there might be as many as quadratic split inversions, yet somehow to get the runtime we want, we need to do it in linear time. So here's the really nice idea which is going to let us do that. The idea is to piggyback on merge sort. By which I mean we're actually going to demand a bit more of our recursive calls to make the job of counting the number of split recursions easier. This is analogous to when you're doing a proof by induction. Sometimes by making the inductive hypothesis stronger, that's what lets you push through the inductive proof. So we're going to ask our recursive calls to not only count inversions in the array that they're passed, but also along the way to sort the array. And hey, why not? We know sorting is fast. Merge sort will do it in n log n time, which is the runtime we're shooting for. So why not just throw that in? Maybe it'll help us in the combine step, and as we'll see, it will. So what is this bias? Why should we demand more of our recursive calls? Well, as we'll see in a couple slides, the merge subroutine almost seems designed just to count the number of split inversions. As we'll see, as you merge two sorted subarrays, you will naturally uncover all of the split inversions. So let me just be a little bit more clear about how our previous high-level algorithm is going to now be souped up so that the recursive calls sort as well. So here's the high-level algorithm we proposed before, where we just recursively count inversions on the left side, on the right side, and then we have some currently unimplemented subroutine count split if which is responsible for counting the number of split inversions. So we're just going to augment this as follows. So instead of being called count, now we're going to call it sort and count. So that's going to be the name of our algorithm. The recursive calls, again, just invoke sort and count. And so now we know each of those will not only count the number of inversions in the subarray, but also return a sorted version. So out from the first one, we're going to get array B back, which is the sorted version of the array that we passed it. And we'll get a sorted array C back from the second recursive call, the sorted version of the array that we passed it. And now the count split inversions, now in addition to counting split inversions, it's responsible for merging the two sorted subarrays B and C. So count split if will be responsible for outputting an array D, which is a sorted version of the original input array A. And so I should also rename our unimplemented subroutine to reflect its now more ambitious agenda. So we'll call this merge and count split inv. Now, we shouldn't be intimidated by asking our combining subroutine to merge the two sorted subarrays B and C, because we've already seen we know how to do that in linear time. So the question is just piggybacking on that work, can we also count the number of split inversions in an additional linear time? We'll see that we can, although that's certainly not obvious. So you should again at this point have the question, why on earth are we doing this? Why are we just making ourselves do more work? And again, the hope is that the payoff is somehow counting split inversions becomes easier by asking our recursive calls to do this additional work of sorting. So to develop some intuition for why that's true, why merging naturally uncovers the number of split inversions, let's recall what the definition of just the original merge subroutine for merge sort was. So here's the same pseudocode we went through several videos ago. I have renamed the letters of the arrays to be consistent with the current notation. So we're given two sorted subarrays. These come back from recursive calls. I'm calling them B and C. They both have length n over 2. And we're responsible for producing the sorted combination of B and C. So that's an output array D of length n. And again, the idea is simple. You just take the two sorted subarrays B and C, and then you take the output array D, which you're responsible for populating, and using index k, you're going to traverse the output array D from left to right. That's what this outer for loop here does. And you're going to maintain pointers I and j to the sorted subarrays B and C respectively. And the only observation is that whatever the minimum element that you haven't copied over to D yet is, it's got to be either the leftmost element of B that you haven't seen yet or the leftmost element of C that you haven't seen yet. B and C, by virtue of being sorted, the minimum element remaining has to be the next one available to either B or C. So you just proceed in the obvious way. You compare the two candidates for the next one to copy over. You look at B of I, you look at C of j. Whichever one is smaller, you copy over. So the first part of the if statement is for when B contains the smaller one. The second part of the else statement is for when C contains the smaller one. Okay, so that's how merge works. You go down B and C in parallel, populating D in sorted order from left to right. Now, to get some feel for what on earth any of this has to do with the split inversions of an array, I want you to think about an input array A that has the following property. That has the property that there are no split inversions whatsoever. So every inversion in this input array A is going to be either a left inversion, so both indices are at most n over 2, or a right inversion, so both indices are strictly greater than n over 2. Now the question is, given such an array A, once you're merging at this step, what do the sorted subarrays B and C look like for an input array A that has no split inversions? The correct answer is the second one, that if you have an array with no split inversions, then everything in the first half is less than everything in the second half. Why? Well, consider the contrapositive. Suppose you had even one element in the first half which was bigger than any element in the second half. That pair of elements alone would constitute a split inversion. Okay, so if you have no split inversions, then everything on the left is smaller than everything in the right half of the array. Now, more to the point, think about the execution of the merge subroutine on an array with this property, on an input array A, where everything in the left half is less than everything in the right half. What is merge going to do? Right, so remember, it's always looking for whichever is smaller, the first element of remaining in B or the first element remaining in C, and that's what it copies over. Well, if everything in B is less than everything in C, everything in B is going to get copied over into the output array D before C ever gets touched. Okay, so merge has an unusually trivial execution on input arrays with no split inversions, with zero split inversions. First, it just goes through B and copies it over. Then it just concatenates C. Okay, there's no interleaving between the two. So no split inversions means nothing gets copied from C until it absolutely has to, until B is exhausted. So this suggests that perhaps copying elements over from the second subarray C has something to do with the number of split inversions in the original array. And that is in fact the case. So we're going to see a general pattern about copies from the second element C, second array C into the output array, exposing split inversions in the original input array A. So let's look at a more detailed example to see what that pattern is. So let's return to the example in the previous video, which is an array with 6 elements ordered 1, 3, 5, 2, 4, 6. So we do our recursive call, and in fact the left half of the array is sorted and the right half of the array is already sorted. So no sorting work is going to be done, and we're actually going to get 0 inversions for both our recursive calls. Remember, in this example it turns out all of the inversions are split inversions. So now let's trace through the merge subroutine invoked on these two sorted subarrays and try to spot a connection with the number of split inversions in the original 6-element array. So we initialize indices I and j to point to the first element of each of these subarrays. So this left one is B and this right one is C, and the output is D. Now the first thing we do is we copy the 1 over from B into the output array. So 1 goes there, and we advance this index over to the 3. And here nothing really interesting happens. There's no reason to count any split inversions, and indeed the number 1 is not involved in any split inversions because 1 is smaller than all of the other elements, and it's also in the first index. Things are much more interesting when we copy over the element 2 from the second array C. And notice at this point we have diverged from the trivial execution that we would see with an array with no split inversions. Now we're copying something over from C before we've exhausted copying B. So we're hoping this will expose some split inversions. So we copy over the 2 and we advance the second pointer j into C. And the thing to notice is this exposes 2 split inversions, the 2 split inversions that involve the element 2. And those inversions are 3, 2 and 5, 2. So why did this happen? Well, the reason we copied 2 over is because it's smaller than all the elements we haven't yet looked at in both B and C. So in particular, 2 is smaller than the remaining elements in B, the 3 and the 5, but also because B is the left array, the indices of the 3 and 5 have to be less than the index of this 2. So these are inversions. 2 is further to the right in the original input array, and yet it's smaller than these remaining elements in B. So there are 2 elements remaining in B, and those are the 2 split inversions that involve the element 2. So now let's go back to the merging subroutine. So what happens next? Well, next we make a copy from the first array, and we sort of realize that nothing really interesting happens when we copy from the first array, at least with respect to split inversions. Then we copy the 4 over, and yet again we discover a split inversion, the remaining one, which is 5, 4. Again, the reason is, given that 4 was copied over before what's left in B, it's got to be smaller than it, but by virtue of being in the rightmost array, it's also got to have a bigger index, so it's got to be a split inversion. And now the rest of the merge subroutine executes without any real incident. The 5 gets copied over, and we know copies from the left array are boring, and then we copy the 6 over, and copies from the right array are generally interesting, but not if the left array is empty. That doesn't involve any split inversions. And you will recall from the earlier video that these were the inversions in the original array, 3, 2, 5, 2, and 5, 4. We discovered them all in an automated method by just keeping an eye out when we copy from the right array C. So this is indeed a general principle, so let me state the general claim. So the claim is not just in this specific example, in this specific execution, but no matter what the input array is, no matter how many split inversions there might be, the split inversions that involve an element of the second half of the array are precisely those elements remaining in the first array when that element gets copied over to the output array. So this is exactly the pattern that we saw in the example. So on the right array, C, we had the elements 2, 4, and 6. Remember, every split inversion has to, by definition, involve one element from the first half and one element from the second half. So to count the split inversions, we can just group them according to which element of the second array that they involve. So out of the 2, 4, and 6, the 2 is involved in the split inversions 3, 2, and 5, 2. The 3 and the 5 were exactly the elements remaining in B when we copied over 2. The split inversions involving 4 is exactly the inversion 5, 4, and 5 is exactly the element that was remaining in B when we copied over the 4. There's no split inversions involving 6, and indeed the element B was empty when we copied the 6 over into the output array D. So what's the general argument? Well, it's quite simple. Let's just zoom in and fixate on a particular element x that belongs to that first half of the array, that's amongst the first half of the elements. And let's just examine which y's, so which elements of the second array, the second half of the original input array, are involved in split inversions with x. So there are two cases, depending on whether x is copied over into the output array D before or after y. Now, if x is copied to the output before y, well then since the output's in sorted order, it means x has got to be less than y, so there's not going to be any split inversion. On the other hand, if y is copied to the output D before x, then again, because we populate D left to right in sorted order, that's got to mean that y is less than x. Now, x is still hanging out in the left array, so it has a less index than y. Y comes from the right array, so this is indeed a split inversion. So putting these two together, it says that the elements x of the array B that form split inversions with y are precisely those that are going to get copied to the output array after y. So those are exactly the number of elements remaining in B when y gets copied over. So that proves the general claim. So this slide was really the key insight. Now that we understand exactly why counting split inversions is easy as we're merging together two sorted subarrays, it's a simple matter to just translate this into code and get a linear time implementation of a subroutine that both merges and counts the number of split inversions, which then in the overall recursive algorithm will have n log n running time just as in merge sort. So let's just spend a quick minute filling in those details. So I'm not going to write out the pseudocode, I'm just going to write out what you need to augment the merge pseudocode discussed a few slides ago by in order to count split inversions as you're doing the merging. And this will follow immediately from the previous claim, which indicated how split inversions relate to the number of elements remaining in the left array as you're doing the merge. So the idea is the natural one, as you're doing the merging, according to the previous pseudocode of the two sorted subarrays, you just keep a running total of the number of split inversions that you've encountered. Right, so you've got your sorted subarray B, you've got your sorted subarray C, you're merging these into an output array D, and as you traverse through D and K goes from 1 to N, you just start the count at 0 and you increment it by something each time you do a copy over from either B or C. So what's the increment? Well, what did we just see? We saw that copies involving B don't count. We're not going to look at split inversions when we copy over from B, only when we look at them from C, right? Every split inversion involves exactly one element from each of B and C, so we may as well count them via the elements in C. And how many split inversions are involved with a given element of C? Well, it's exactly how many elements of B remain when it gets copied over. So that tells us how to increment this running count. And it follows immediately from the claim on the previous slide that this implementation of this running total counts precisely the number of split inversions that the original input array A possesses. And recall that the left inversions are counted by the first recursive call, the right inversions are counted by the second recursive call. Every inversion is either left or right or split. It's exactly one of those three types. So with our three different subroutines, the two recursive ones and this one here, we successfully count up all of the inversions of the original input array. So that's the correctness of the algorithm. What's the running time? Well, recall in merge sort, we began by just analyzing the running time of merge, and then we discussed the running time of the entire merge sort algorithm. Let's do the same thing here briefly. So what's the running time of this subroutine for this merging and simultaneously counting the number of split inversions? Well, there's the work that we do in the merging, and we already know that that's linear. And then the only additional work here is incrementing this running count, and that's constant time for each element of D, right? Each time we do a copy over, we do a single addition to our running count. So constant time per element of D, or linear time overall. So I'm being a little sloppy here. It's sloppy in a very conventional way, but it is a little sloppy by writing O of n plus O of n equals O of n. Be careful when you make statements like that, right? So if you added O of n to itself n times, it would not be O of n. But if you add O of n to itself a constant number of times, it is still O of n. So you might, as an exercise, want to write out a formal version of what this means. Basically, there's some constant C1 so that the merge step takes at most C1 n steps. There's a constant C2 so that the rest of the work is at most C2 times n steps. So when we add them, we get its most quantity C1 plus C2 times n steps, which is still big O of n because C1 plus C2 is a constant. Okay, so linear work for merge, linear work for the running count, so that's linear work in the subroutine overall. And now by exactly the same argument we used in merge sort, because we have two recursive calls on half the size, and we do linear work outside of the recursive calls, the overall running time is O of n log n. So we've really just piggybacked on merge sort up to the constant factor a little bit to do the counting along the way, but the running time remains big O of n log n.
In this video, we'll apply the divide and conquer algorithm design paradigm to the problem of multiplying matrices. This will culminate in the study of Strassens matrix multiplication algorithm. And this is a super cool algorithm for two reasons. First of all, Strassens' algorithm is completely non-trivial. It's totally non-obvious, very clever, not at all clear how Strassen ever came up with it. The second cool feature is it's for such a fundamental problem. So computers, as long as they've been in use, from the time they were invented up till today, a lot of their cycles is spent multiplying matrices, because it just comes up all the time in important applications. So let me first just make sure we're all clear on what the problem is of multiplying two matrices. So we're going to be interested in three matrices, x, y, and z. I'm going to assume they all have the same dimensions, n by n. The ideas we'll talk about are also relevant for multiplying non-square matrices, but we're not going to discuss it in this video. The entries in these matrices, you could think of it as whatever you want. Maybe they're integers, maybe they're rationals, maybe they're from some finite field. It depends on the application, but the point is they're just entries that we can add and multiply. So how is it that you take two n by n matrices, x and y, and multiply them, producing a new n by n matrix, z? Well, recall that the ij entry of z, that means the entry in the ith row and the jth column, is simply the dot product of the ith row of x with the jth column of y. So if ij was this red square, this red entry over in the z matrix, that would be derived from the corresponding row of the x matrix and the corresponding column of the y matrix. And recall what I mean by dot product. That just means you take the products of the individual components and then add up the results. So ultimately, the zij entry boils down to a sum over n things, where each of the constituent products is just the xik entry, the ik entry of the matrix x with the kj entry of the matrix y, or here k is ranging from 1 to n. So that's how zij is defined for a given pair of indices I and j. One thing to note is that where we often use n to denote the input size, here we're using n to denote the dimension of each of these matrices. The input size is not n. The input size is quite a bit bigger than n. Specifically, each of these are n by n matrices and contains n squared entries. So since presumably we have to read the input, which has size n squared, and we have to produce the output, which also has size n squared, the best we could really hope for a matrix multiplication algorithm would be a running time of n squared. So the question is, how close can we get to it? Before we talk about algorithms for matrix multiplication, let me just make sure we're all crystal clear on exactly what the problem is. So let's just actually spell out what would be the result of multiplying two different 2 by 2 matrices. So we can parameterize two generic 2 by 2 matrices by just giving the first one entries A, B, C, and D, where these four entries could all be anything. And then we're multiplying by a second 2 by 2 matrix. Let's call its entries E, F, G, and H. Now, what's the result of multiplying these? Where again, it's going to be a 2 by 2 matrix where each entry is just the corresponding dot product of the relevant row of the first matrix and column of the second matrix. So to get the upper left entry, we take the dot product of the upper row of the first matrix and the first column of the left column of the second matrix. So that results in AE plus BG. To get the upper right entry, we take the dot product of the top row of the left matrix with the right column of the second matrix. So that gives us AF plus BH. And then filling in the other entries in the same way, we get CE plus DG and CF plus DH. Okay, so that's multiplying two matrices, and we've already discussed the definition in general. Now, suppose you had to write a program to actually compute the results of multiplying two n by n matrices. One natural way to do that would just be to return to the definition, and which defines each of the n squared entries in the Z matrix as a suitable sum of products of entries of the x and y matrices. So in the next quiz, I'd like you to figure out exactly what would be the running time of that algorithm as a function of the matrix dimension n, where as usual we count the addition or multiplication of two individual entries as a constant time operation. So the correct response to this quiz is the third answer, that the running time of the straightforward iterative algorithm runs in cubic time relative to the matrix dimension n.
To see this, just recall what the definition of the matrix multiplication was. The definition tells us that each entry Zij of the output matrix Z is defined as the sum from k equal 1 to n of xik times ykj. That is the dot product of the ith row of the X matrix and the jth column of the Y matrix. I'm certainly assuming that we have the matrices represented in a way that we can access a given entry in constant time. And under that assumption, remember each of these products only takes constant time. And so then to compute Zij, we just have to add up these n products. So that's going to be theta of n time to compute a given Zij, and then there's an n squared entries that we have to compute. There's n choices for I, n choices for j, so that gives us n squared times n, or cubic running time overall for the natural algorithm, which is really just a triple for loop which computes each entry of the output array separately using the dot product. So the question, as always, for the keen algorithm designer is, can we do better? Can we beat n cubed time for multiplying two matrices? And we might be especially emboldened with the progress that we've already seen in terms of multiplying two integers. We apply the divide and conquer algorithm to the problem of multiplying two n-digit integers, and we had both a naive recursive algorithm and a seemingly better algorithm due to Gauss, which made only 3 recursive calls. Now, we haven't yet analyzed the running time of that algorithm, but as we'll see later, that does indeed beat the quadratic running time of the grade school algorithm. So it's very natural to ask, can we do exactly the same thing here? There's the obvious n-cubed algorithm, which follows straight from the definition. Perhaps analogous to Gauss, we can have some clever divide and conquer method which beats cubic time. So that's what we're going to explore next. Let's recall the divide and conquer paradigm. What does it mean to use it? Well, we first have to identify smaller subproblems. So if we want to multiply two n by n matrices, we have to identify multiplications of smaller matrices that we can solve recursively. Once we've figured out how we want to divide the given problem into smaller ones, then in the conquer step, we simply invoke our own algorithm recursively. That's going to recursively multiply the smaller matrices together. And then, in general, we'll have to combine the results of the recursive calls to get the solution for the original problem, in our case, to get the product of the original two matrices from the product of whatever submatrices we identify. So how would we apply the divide and conquer paradigm to matrices? So we're given two n by n matrices, and we have to somehow identify smaller pairs of square matrices that we can multiply recursively. So the idea, I think, is fairly natural. So we start with a big n by n matrix X, right? So there's n rows and n columns, and we have to somehow divide it into smaller pieces. Now, the first thing you might think about is you put it into its left half and its right half, analogous to what we've been doing with arrays. But then we're going to break X into two matrices which are no longer square, which are n over 2 in one dimension and have length n in the other dimension. And we want to recursively call a subroutine that multiplies square matrices. So what seems like the clear thing to do is to divide X into quadrants. Okay, so we have 4 pieces of X. Each is going to be n over 2 by n over 2, corresponding to the different quarters of this matrix. So let's call these different quadrants, or blocks, in matrix terminology, A, B, C, and D. All of these are n over 2 by n over 2 matrices. As usual, for simplicity, I'm assuming that n is even, and as usual, it doesn't really matter. And we can do the same trick with Y. So we'll divide Y into quadrants, n over 2 by n over 2 matrices, which we'll call E, F, G, and H. So one thing that's cool about matrices is when you split them into blocks and you multiply them, the blocks just behave as if they were atomic elements. So what I mean by that is that the product of X and Y can be expressed in terms of its quadrants. And each of its 4 quadrants, each of its 4 corners, can be written as a suitable arithmetic expression of the quadrants of X and Y. So here's exactly what those formulas are. They're exactly analogous to when we just multiplied a pair of 2 by 2 matrices. So I'm not going to formally prove this fact. I'm sure many of you have seen it before, or familiar with it. And if you haven't, it's actually quite easy to prove. It's not obvious. You can't see it off the top of your head necessarily. But if you go back to the definition, it's quite easy to verify that indeed, when you multiply X and Y, you can express its quadrants, its blocks, in terms of the blocks of X and Y. So what we just did is completely analogous to when talking about integer multiplication, and we wanted to multiply two integers, little x and little y, and we broke them into
pairs of n over 2 digits. And then we just took the expansion, and we observed how that expansion could be written in terms of products of n over 2 digit numbers. Same thing going on here, except with matrices. So now we're in business as far as a recursive approach. We want to multiply x and y, they're n by n matrices, but we recognize we can express that product x times y in terms of the products of n over 2 by n over 2 matrices, things we're able to multiply recursively, plus additions. And additions is clearly easy. To multiply two different matrices with, say, n squared entries each, it's going to be linear in the number of entries. So it's going to be n squared time to add two matrices that are n by n. So this immediately leads us to our first recursive algorithm. To describe it, let me quickly rewrite that expression we just saw on the previous slide. And now our first recursive algorithm is simply to evaluate all of these expressions in the obvious way. So specifically in step 1, we recursively compute all of the necessary products and observe that there are 8 products that we have to compute, 8 products of n over 2 by n over 2 matrices. There are 4 entries in this expansion of x times y. Each of the blocks is the sum of 2 products, and none of the products reoccur. They're all distinct. So naively, if we want to evaluate this, we have to do 8 different products of n over 2 by n over 2 matrices. Once those recursive calls complete, then all we do is do the necessary 4 additions. As we discussed, that takes time proportional to the number of entries in the matrix, so this is going to take a quadratic time overall, quadratic in n, linear in the number of entries. Now, the question you should be asking is this a good algorithm? Was this good for anything, this recursive approach, splitting x and y into these blocks, expanding the product in terms of these blocks, then recursively computing each of the blocks? And I want to say it's totally not obvious. It is not clear what the running time of this recursive algorithm is. I'm going to go ahead and give you a spoiler, which is going to follow from the master method that we'll talk about in the next lecture. But it turns out with this kind of recursive algorithm, where you do 8 recursive calls, each on a problem with dimension half as much as what you started with, and then do quadratic time outside, the running time is going to be cubic. So exactly the same as with the straightforward iterative algorithm that follows from the definition. That was cubic, it turns out, and that was clearly cubic. This one, although it's not obvious, is cubic as well. So no better, no worse than the straightforward iterative algorithm. So in case you're feeling disappointed that we went through all this work and this sort of seemingly clever divide and conquer approach for matrix multiplication and came out at the end no better than the iterative algorithm, well, there's really no reason to despair. Because remember, back in integer multiplication, we had a straightforward recursive algorithm where we had to do 4 recursive calls, products of n over 2-digit numbers. But then we had Gauss's trick, which said, oh, if we only did more clever products and more clever additions and subtractions, then we can get away with only 3 recursive calls. And we'll see later that that is indeed a significant savings in the time needed for integer multiplication. And we've done nothing analogously clever to Gauss's trick for this matrix multiplication problem. All we did is the naive expansion in terms of submatrices and the naive evaluation of the resulting expressions. So the $64,000 question is then, can we do something clever to reduce the number of recursive calls from 8 down to something lower? And that is where Strassens' algorithm comes in. So at a high level, Strassens' algorithm has 2 steps, just like the first recursive algorithm that we discussed. It recursively computes some products of smaller matrices, n over 2, or roughly n over 2 by n over 2 matrices. But there's only going to be 7 of them. They will be much less straightforward. They will be much more cleverly chosen than in the first recursive algorithm. And step 2 then is to actually produce the product of x and y, produce each of those 4 blocks that we saw with suitable additions and subtractions of these 7 products. And again, these are much less straightforward than in the first recursive algorithm. And so while the additions and subtractions involved will be a little bit more numerous than they were in the naive recursive algorithm, it's only going to change the work in that part of the algorithm by a constant factor. So we'll still spend only theta of n squared work adding and subtracting things, and we get a huge win in decreasing the number of recursive calls from 8 to 7. Now, just in case you have the intuition that shaving off 1 of 8 recursive calls should only decrease the running time of an algorithm by 1/8, by 12.5%, in fact, it has a tremendously more amplified effect because we do 1 less recursive recursive call over and over and over again as we keep recursing in the algorithm. So it makes a fundamental difference in the eventual running time of the algorithm, as we'll explore in detail in the next set of lectures when we discuss the master method. So again, a bit of a spoiler alert. What you're going to see in the next set of lectures is that indeed Strassens' algorithm does beat cubic time. It's better than n-cubed time. You'll have to watch the next set of lectures if you want to know just what the running time is, but I'm going to tell you now that savings of the 8th recursive call is what changes the algorithm from cubic to subcubic. Now, 1969 was obviously quite a bit before my time, but by all accounts, from people I've talked to who were around then and from what the books say, Strassens' algorithm totally blew people's minds at the time. Everybody was assuming that there's no way you could do better than the iterative algorithm, the cubic algorithm. It just seemed that matrix multiplication intuitively fundamentally required all of the calculations that are spelled out in the definition. So Strassens' algorithm is an early glimpse of the magic and of the power of clever algorithm design. That if you really have a serious ingenuity, even for super fundamental problems, you can come up with fundamental savings over the more straightforward solutions. So those are the main points I wanted to talk about Strassens' algorithm, how you can beat cubic time by saving a recursive call with suitably chosen clever products and clever additions and subtractions. Maybe a few of you are wondering, what are these cleverly chosen products? Can you really do this? And I don't blame you. There's no reason to believe me just because I sort of spelled out this high-level idea. It's not obvious this should work. You might want to actually see the products. So for those of you like that, this last slide is for you. So here is Strassens' algorithm in its somewhat gory detail. So let me tell you what the 7 products are that we're going to form. I'm going to label them P1 through P7, and they're all going to be defined in terms of the blocks of the input matrices X and Y. So let me just remind you that we think of X in terms of its blocks, A, B, C, D, and we think of Y in terms of its blocks, E, F, G, H. And remember, A through H are all n over 2 by n over 2 submatrices. So here are the 7 products, P1 through P7. P1 is A times quantity F minus H. P2 is quantity A plus B times H. P3 is C plus D times E. P4 is D times G minus E. P5 is quantity A plus D times quantity E plus H. P6 is quantity B minus D times quantity G plus H. And finally, P7 is quantity A minus C E plus F. So I hope you'll agree that these are indeed only 7 products, and we could compute these with 7 recursive calls. So we pre-process with a little bit of additions and subtractions. We have to compute F minus H, A plus B, C plus D, and so on. We compute all of these new matrices from the blocks, and we can then recursively, with 7 recursive calls, do these 7 products that operate on n over 2 by n over 2 matrices. Now, the question is, why is this useful? Why on earth would we want to know the values of these 7 products? So the amazing other part of the algorithm is that from just these 7 products, we can, using only addition and subtraction, recover all 4 of the blocks of a x times y. So x times y, you'll recall we expanded in terms of the blocks. So we previously computed this to be AE plus BG in the upper left corner, and then similarly expressions for the upper right, lower left, and lower right blocks. So this we already know. So the content of the claim is that these 4 blocks also arise from the 7 products in the following way. So the claim here is that these 2 different expressions for x times y are exactly the same, and they're the same block by block. So in other words, what the claim is that this crazy expression, P5 plus P4 minus P2 plus P6, where those are 4 of the products that we've listed above, that is precisely AE plus BG. Similarly, we're claiming that P1 plus P2 is exactly AF plus BH. That's actually easy to see. P3 plus P4 is CE plus DG. That's also easy to see. And then the other complicated one is that P1 plus P5 minus P3 minus P7 is exactly the same as CF plus DH. So all 4 of those hold. So let me, just so you believe me, because I don't know why you would believe me unless I actually showed you some of this derivation.
Let's just look at the proof of one of the cases of the upper left corner. So that is, let's just expand out this crazy expression, P5 plus P4 minus P2 plus P6. What do we get? Well, from P5, we get AE plus AH plus DE plus DH. Then we add P4, so that's going to give us plus DG minus DE. Then we subtract P2, so that gives us a minus AH minus BH. And then we add in P6. So that gives us a BG plus BH minus DG minus DH. Okay, so what happens next? Well, now we look for cancellations. So we cancel the AHs, we cancel the DEs, we cancel the DHs, we cancel the DGs, we cancel the BHs, and holy cow, what do we get? We get AE plus BG. That is, we get exactly what we were supposed to in the upper left block of x times y. So we just actually verified that this equation holds for the upper left block. It's quite easy to see that it holds for the upper right and lower left blocks, and a comparable calculation verifies it for the lower right blocks of the two. So summarizing, because this claim holds, because actually we can recover the 4 blocks of x times y from these 7 products, Strassens' algorithm works in the following way. You compute the 7 products P1 through P7 using 7 recursive calls. Then you just compute the 4 blocks using some extra additions and subtractions as shown in the claim. So 7 recursive calls on n over 2 by n over 2 matrices plus n squared work to do the necessary additions. And as you'll see in the master method lecture, that is actually sufficient for subcubic time. Now, I sympathize with you if you have the following question, which is, how on earth did Strassen come up with this? And indeed, this sort of illustrates the difference between checking somebody's proof and coming up with a proof. Given that I told you the magical 7 products and how you, from them, can recover the 4 desired blocks of x times y, it's really just mechanical to see that it works. It's a totally different story of how do you come up with P1 through P7 in the first place. So how did Strassen come up with them? Honestly, your guess is as good as mine. So in this video and the next, we're going to study a very cool divide and conquer algorithm for the closest pair problem. This is a problem where you're given endpoints in the plane and you want to figure out which pair of points are closest to each other. So this will be the first taste we get of an application in computational geometry, which is the part of algorithms which studies how to reason and manipulate geometric objects. So those algorithms are important in, among other areas, robotics, computer vision, and computer graphics. So this is relatively advanced material. It's a bit more difficult than the other applications of divide and conquer that we've seen. The algorithm's a little bit tricky, and it has a quite non-trivial proof of correctness. So just be ready for that, and also be warned that because it's more advanced, I'm going to talk about the material at a slightly faster pace than I do in most of the other videos. So let's begin now by defining the problem formally. So we're given as input endpoints in the plane, so each one just defined by its x-coordinate and its y-coordinate. And when we talk about the distance between 2 points in this problem, we're going to focus on Euclidean distance. So let me remind you what that is briefly, but we'll introduce some simple notation for that, which we'll use for the rest of the lecture. So we're just going to note the Euclidean distance between 2 points pi and pj by d of pi pj. So in terms of the x and y coordinates of these 2 points, we just look at the squared differences in each coordinate, sum them up, and take the square root. And now, as the name of the problem would suggest, the goal is to identify among all pairs of points that pair which has the smallest distance between them. Next, let's start getting a feel for the problem by making some preliminary observations. First, I want to make an assumption, purely for convenience, that there's no ties. So that is, I'm going to assume all endpoints have distinct x-coordinates, and also all endpoints have distinct y-coordinates. It's not difficult to extend the algorithm to accommodate ties. I'll leave it to you to think about how to do that. So next, let's draw some parallels with the problem of counting inversions, which was an earlier application of divide and conquer that we saw. The first parallel I want to point out is that if we're comfortable with a quadratic time algorithm, then this is not a hard problem. We can simply solve this by brute force search. And again, by brute force search, I just mean we set up a double for loop, which iterates over all distinct pairs of points. We compute the distance for each such pair, and we remember the smallest. That's clearly a correct algorithm. It has to iterate over a quadratic number of pairs, so its running time is going to be theta of n squared. And as always, the question is, can we apply some algorithmic ingenuity to do better? Can we have a better algorithm than this naive one which iterates over all pairs of points? You might have an initial instinct that because the problem asks about a quadratic number of different objects, perhaps we fundamentally need to do quadratic work. But again, recall back in counting inversions, using divide and conquer, we were able to get an n log n algorithm, despite the fact that there might be as many as a quadratic number of inversions in an array. So the question is, can we do something similar here for the closest pair problem? Now, one of the keys to getting an n log n time algorithm for counting inversions was to leverage a sorting subroutine. Recall that we piggybacked on merge sort to count the number of inversions in n log n time. So the question is, here, with the closest pair problem, perhaps sorting again can be useful in some way to beat the quadratic barrier. So to develop some evidence that sorting will indeed help us compute the closest pair of points and better than quadratic time, let's look at a special case of the problem, really an easier version of the problem, which is when the points are just in one dimension, so on the line, rather than in two dimensions in the plane. So in the 1D version, all of the points just lie on a line like this one, and we're given the points in some arbitrary order, not necessarily in sorted order. So a way to solve the closest pair problem in one dimension is to simply sort the points, and then of course the closest pair better be adjacent in this ordering, so you just iterate through the n-1 consecutive pairs and see which one is closest to each other. So more formally, here's how you solve the one-dimensional version of the problem. You sort the points according to their only coordinate, because again, remember this is one dimension. So as we've seen using merge sort, we can sort the points in n log n time. And then we just do a scan through the points, so this takes linear time, and for each consecutive pair we compute their distance and we remember the smallest of those consecutive pairs and we return that. That's got to be the closest pair. So in this picture on the right, I'm just going to circle here in green the closest pair of points. So this is something we discover by sorting and then doing a linear scan. Now, needless to say, this isn't directly useful. This is not the problem I started out with. We wanted to find the closest pair among points in the plane, not points in the line. But I want to point out that this, even in the line, there are a quadratic number of different pairs, so brute force search is still a quadratic time algorithm, even in the 1D case. So at least with one dimension, we can use sorting, piggyback on it, to beat the naive brute force search bound and solve the problem in n log n time. So our goal for this lecture is going to be to devise an equally good algorithm for the two-dimensional case. So we want to solve closest pair of points in the plane, again in n log n time. So we will succeed in this goal. I'm going to show you an n log n time algorithm for 2D closest pair. It's going to take us a couple steps. So let me begin with the high-level approach. All right, so the first idea to try is just to copy what worked for us in the one-dimensional case. So in the one-dimensional case, we first sorted the points by their coordinate, and that was really useful. Now in the 2D case, points have two coordinates, x coordinates and y coordinates, so there's two ways to sort them. So let's just sort them both ways. That is, the first step of our algorithm, which you should really think of as a pre-processing step. We're going to take the input points, we invoke merge sort once to sort them according to x coordinate, that's one copy of the points, and then we make a second copy of the points where they're sorted by y-coordinate. So we're going to call those copies of points px, that's an array of the points sorted by x-coordinate, and py for them sorted by y-coordinate. Now we know merge sort takes n log n time, so this pre-processing step only takes O of n log n time. And again, given that we're shooting for an algorithm with running time big O of n log n, why not sort the points? We don't even know how we're going to use this fact right now, but it's sort of harmless. It's not going to affect our goal of getting a big of O of n log n time algorithm. And indeed, this illustrates a broader point, which is one of the themes of this course. So recall, I hope one of the things you take away from this course is a sense for what are the four free primitives. What are manipulations or operations you can do on data, which basically are costless, meaning that if your data set fits in the main memory of your computer, you can basically invoke the primitive and it's just going to run blazingly fast. And you can just do it even if you don't know why. And again, sorting is the canonical for free primitive, although we'll see some more later in the course. And so here we're using exactly that principle. So we don't even understand why yet we might want the points to be sorted. It just seems like it's probably going to be useful, motivated by the 1D case. So let's go ahead and make sorted copies of the points by x and y coordinate up front. So reasoning by analogy with the 1D case suggests that sorting the points might be useful, but we can't carry this analogy too far. So in particular, we're not going to be able to get away with just a simple linear scan through these arrays to identify the closest pair of points. So to see that, consider the following example. So we're going to look at a point set which has 6 points. There's going to be 2 points, which I'll put in blue, which are very close in x-coordinate, but very far away in y-coordinate. And then there's going to be another pair of points, which I'll do in green, which are very close in y-coordinate, but very far away in x-coordinate. And then there's going to be a red pair of points, which are not too far away in either the x-coordinate or the y-coordinate. So in this set of 6 points, the closest pair is the pair of red points, but they're not even going to show up consecutively in either of the two arrays, right? So in the array that's sorted by x-coordinate, this blue point here is going to be wedged in between the two red points. They won't be consecutive. And similarly in py, which is sorted by y-coordinate, this green point is going to be wedged between the two red points. So you won't even notice these red points if you just do a linear scan through px and py and look at the consecutive pairs of points. So following our preprocessing step where we just invoke merge sort twice, we're going to do a quite non-trivial divide and conquer algorithm to compute the closest pair. So really in this algorithm, we're applying the divide and conquer algorithm twice. First, internal to the sorting subroutine, assuming that we use the merge sort algorithm to sort, divide and conquer is being used there to get an n log n running time in this preprocessing step, and then we're going to use it again on the sorted arrays in a new way, and that's what I'm going to tell you about next. So let's just briefly review the divide and conquer algorithm design paradigm before we apply it to the closest pair problem. So as usual, the first step is to figure out a way to divide your problem into smaller subproblems. Sometimes this has a reasonable amount of ingenuity, but it's not going to here in the closest pair problem. We're going to proceed exactly as we did in the merge sort and counting inversions problems, where we took the array and broke it into its left and right half. So here we're going to take the input point set, and again, just recurse on the left half of the points and recurse on the right half of the points. Where here by left and right, I mean with respect to the points x-coordinates. There's pretty much never any ingenuity in the conquer step. That just means you take the subproblems you identified in the first step and you solve them recursively. That's what we'll do here. We'll recursively compute the closest pair in the left half of the points and the closest pair in the right half of the points. So where all the creativity in divide and conquer algorithms lie is in the combined step. Given solutions to your subproblems, how do you somehow recover a solution to the original problem, the one that you actually care about? So for closest pair, the question is going to be, given that you've computed the closest pair on the left half of the points, the closest pair on the right half of the points, how do you then quickly recover the closest pair from the whole point set? That's a tricky problem. That's what we're going to spend most of our time on. So let's make this divide and conquer approach for closest pair a little bit more precise. So let's now actually start spelling out our closest pair algorithm. The input we're given, this follows the preprocessing step. So recall that we invoke merge sort twice. We get our two sorted copies of the point set px sorted by x coordinate and py sorted by y coordinate. So the first step then is the division step. So given that we have a copy of the points px sorted by x coordinate, it's easy to identify the leftmost half of the points, those with those n over 2 smallest x coordinates, and then the right half, those with the n over 2 largest x coordinates. We're going to call those q and r respectively. One thing I'm skipping over is the base case. I'm not going to bother writing that down. So base case omitted, but it's what you would think it would be. So basically, once you have a small number of points, say 2 points or 3 points, then you can just solve the problem in constant time by brute force search. You just look at all the pairs and you return the closest pair. So think of there being at least 4 points in the input. Now, in order to recurse, to call closest pair again on the left and right halves, we need sorted versions of q and r, both by x-coordinate and by y-coordinate. So we're just going to form those by doing suitable linear scans through px and py. And so one thing I encourage you to think through carefully, or maybe even code up after the video, is how would you form qx, qy, rx, and ry, given that you already have px and py. And if you think about it, because px and py are already sorted, just producing these sorted sublists takes linear time. It's in some sense the opposite of the merge subroutine we used in merge sort. Here we're sort of splitting rather than merging. But again, this can be done in linear time. That's something you should think through carefully later. So that's the division step. Now we just conquer, meaning we recursively call closest pair on each of the two subproblems. So when we invoke closest pair on the left half of the points on Q, we're going to get back what are indeed the closest pair of points amongst those in Q. So we're going to call those P1 and PQ. So among all pairs of points that both lie in Q, P1 and Q1 minimize the distance between them. Similarly, we're going to call P2, Q2 the results of the second recursive call. That is, P2 and Q2 are amongst all pairs of points that both lie in R, the pair that has the minimum Euclidean distance. Now conceptually there's two cases. There's a lucky case and there's an unlucky case. In the original point set P, if we're lucky, the closest pair of points in all of P, actually both of them lie in Q or both of them lie in R. In this lucky case, we'd already be done. If the closest pair in the entire point set, they happen to both lie in Q, then this first recursive call is going to recover them, and we just have them in our hands, P1, Q1. Similarly, if both of the closest pair of points in all of P lies on the right side, in R, then they get handed to us on a silver platter by the second recursive call that just operates on R. So in the unlucky case, the closest pair of points in P happens to be split. That is, one of the points lies in the left half in Q, and the other point lies in the right half in R. Notice, if the closest pair of points in all of P is split, is half in Q and half in R, neither recursive call is going to find it. Okay? The pair of points is not passed to either of the two recursive calls, so there's no way it's going to be returned to us. Okay? So we have not identified the closest pair after these two recursive calls if the closest pair happens to be split. This is exactly analogous to what happened when we were counting inversions. The recursive call in the left half of the array counted the left inversions. The recursive call in the right half of the array counted the right inversions, but we still had to count the split inversions. So in this closest pair algorithm, we still need a special purpose subroutine that computes the closest pair for the case in which it is split, in which there's one point in Q and one point in R. So just like in counting inversions, I'm going to write down that subroutine. I'm going to leave it unimplemented for now. We'll figure out how to implement it quickly in the rest of the lecture. Now, if we have a correct implementation of closest split pair, so that takes as input the original point set sorted by x and y coordinate and returns the smallest pair that's split, where one point's in Q and one point's in R, then we're done. So then the closest pair has to either be on the left or on the right, or it has to be split. Steps 2 through 4 compute the closest pair in each of those categories. So those are the only possible candidates for the closest pair, and we just return the best of them. So that's an argument for why, if we have a correct implementation of the closest split pair subroutine, then that implies a correct implementation of closest pair. Now, what about the running time? So the running time of the closest pair algorithm is going to be in part determined by the running time of closest split pair. So in the next quiz, I want you to think about what kind of running time we should be shooting for with the closest split pair subroutine. So the correct response to this quiz is the second one. And the reasoning is just by analogy with our previous algorithms for merge sort and for counting inversions. So what is all of the work that we would do in this algorithm? Well, we do have this pre-processing step we call merge sort twice. We know that's n log n, so we're not going to have a running time better than n log n because we sort at the beginning. And then we have a recursive algorithm with the following flavor. It makes 2 recursive calls. Each recursive call is on a problem of exactly half the size with half the points of the original one. And outside of the recursive calls, by assumption, in the problem, we do a linear amount of work in computing the closest split pair. So the exact same recursion tree, which proves an n log n bound for merge sort, proves an n log n bound for how much work we do after the pre-processing step. So that gives us an overall running time bound of n log n. And remember, that's what we were shooting for. We were working n log n already to solve the one-dimensional version of closest pair, and the goal of these lectures is to have an n log n algorithm for the 2D version. So this would be great. So in other words, the goal should be to have a correct linear time implementation of the closest split pair subroutine. If we can do that, we're home free. We get the desired n log n algorithm. Now, I'm going to proceed in a little bit to show you how to implement closest split pair, but before I do that, I want to point out one subtle but key idea, which is going to allow us to get this linear time correct implementation. So let me just put that on this slide. So the key idea is that we don't actually need a full-blown correct implementation of the closest split pair subroutine. So I'm not actually going to show you a linear time subroutine that always correctly computes the closest split pair of a point set. The reason I'm not going to do that is that's actually a strictly harder problem than what we need to have a correct recursive algorithm. We do not actually need a subroutine that, for every point set, always correctly computes the closest split pair of points. Remember, there's a lucky case and there's an unlucky case. The lucky case is where the closest pair in the whole point set P happens to lie entirely in the left half of the points Q or in the right half of the points R. In that lucky case, one of our recursive calls will identify this closest pair and hand it over to us on a silver platter. We could care less about the split pairs in that case. We get the right answer without even looking at the split pairs. Now there's this unlucky case where the split pair happens to be the closest pair of points. That is when we need this linear time subroutine, and only then, only in the unlucky case where the closest pair of points happens to be split. Now that's in some sense a fairly trivial observation, but there's a lot of ingenuity here in figuring out how to use that observation, the fact that we only need to solve a strictly easier problem, and that will enable the linear time implementation that I'm going to show you next. So now let's rewrite the high-level recursive algorithm slightly to make use of this observation that the closest split pair subroutine only has to operate correctly in the regime of the unlucky case, when in fact the closest split pair is closer than the result of either recursive call. So I've erased the previous steps 4 and 5, but we're going to rewrite them in a second. So before we invoke closest split pair, what we're going to do is we're going to see how well did our recursive calls do. That is, we're going to define a parameter little delta, which is going to be the closest pair that we found, or the distance of the closest pair we found by either recursive call. So the minimum of the distance between P1 and Q1, the closest pair that lies entirely on the left, and P2, Q2, the closest pair that lies entirely on the right. Now we're going to pass this delta information as a parameter into our closest split pair subroutine. We're going to have to see why on earth that would be useful. I still owe you that information, but for now we're just going to pass delta as a parameter for use in closest split pair. And then as before, we just do a comparison between the 3 candidate closest pairs and return the best of the trio. And so just so we're all clear on where things stand, so what remains is to describe the implementation of closest split pair. Before I describe it, let me just be crystal clear on what it is that we're going to demand of this subroutine. What do we need to have a correct and O of n log n time closest pair algorithm? Well, as you saw in the quiz, we want the running time to be O of n always. And for correctness, what do we need? Again, we don't need it to always compute the closest split pair, but we need it to compute the closest split pair in the event that there is a split pair of distance strictly less than delta, strictly better than the outcome of either recursive call. So now that we're clear on what we want, let's go ahead and go through the pseudocode for this closest split pair subroutine. And I'm going to tell you up front, it's going to be fairly straightforward to figure out that the subroutine runs in linear time, O of n time. The correctness requirement of closest split pair will be highly non-obvious. In fact, after I show you the pseudocode, you're not going to believe me. You're going to look at the pseudocode and you're going to be like, what are you talking about? But in the second video on the closest pair lecture, we will in fact show that this is a correct subroutine. So how does it work? Well, let's look at a point set. So the first thing we're going to do is a filtering step. We're going to prune a bunch of the points away and sort of zoom in on a subset of the points. And the subset of the points we're going to look at is those that lie in a vertical strip, which is roughly centered in the middle of the point set. So here's what I mean. By centered, we're going to look at the middle x-coordinate. So let x bar be the biggest x-coordinate in the left half. So that is, in the sorted version of the points by x-coordinate, we look at the n over 2th smallest x-coordinate. So in this example where we have 6 points, all this means is we imagine drawing a line between the third point. So that's going to be x bar, the x-coordinate of the third point from the left. Now, since we're passed as input a copy of the points sorted by x-coordinate, we can figure out what x bar is in constant time, just by accessing the relevant entry of the array px. Now, the way we're going to use this parameter delta that we're passed, so remember what delta is. So before we invoke the closest split pair subroutine in the recursive algorithm, we make our 2 recursive calls. We find the closest pair on the left, the closest pair on the right, and delta is whatever the smaller of those 2 distances are. So delta is the parameter that controls whether or not we actually care about the closest split pair or not. We care if and only if there is a split pair at distance less than delta. So how do we use delta? Well, that's going to determine the width of our strip. So the strip's going to have width 2 delta, and it's going to be centered around x. And the first thing we're going to do is we're going to ignore forevermore points which do not lie in this vertical strip. So the rest of the algorithm will operate only on the subset of P, the subset of the points that lie in this strip. And we're going to keep track of them sorted by y-coordinate. So the formal way to say that they lie in this strip is that they have x-coordinate in the interval with lower endpoint x bar minus delta and upper endpoint x bar plus delta. Now, how long does it take to construct this set SY sorted by y-coordinate? Well, fortunately, we've been passed as input a sorted version of the points PY. So to extract SY from PY, all we need to do is a simple linear scan through PY, checking for each point where its x-coordinate is. So this can be done in linear time. Now, I haven't yet shown you why it's useful to have this sorted set SY, but if you take it on faith that it's useful to have the points in this vertical strip sorted by y-coordinate, you now see why it was useful that we did this merge sort all the way at the beginning of the algorithm, before we even underwent any recursion. Remember, what is our running time goal for closest split pair? We want this to run in linear time. That means we cannot sort inside the closest split pair subroutine. That would take too long. We want this to be linear time. Fortunately, since we sorted once and for all at the beginning of the closest pair algorithm, extracting sorted sublists from those sorted lists of points can be done in linear time, which is within our goals here. Now it's the rest of the subroutine where you're never going to believe me that it does anything useful. So I claim that essentially with a linear scan through SY, we're going to be able to identify the closest split pair of points in the interesting, unlucky case where there is such a split pair with distance less than delta. So here's what I mean by that linear scan through SY. So as we do the scan, we're going to keep track of the closest pair of points of a particular type that we've seen so far. So let me introduce some variables to keep track of the best candidate we've seen so far. So there's going to be a variable best, which will initialize to be delta. Remember, we're uninterested in split pairs unless they have distance strictly less than delta. And then we're going to keep track of the points themselves, so we'll initialize the best pair to be null. Now here's the linear scan. So we go through the points of SY in order of y coordinate. Okay, well, not quite all the points of SY. We stop at the 8th to last point, and you'll see why in a second. And then for each position I of the array SY, we investigate the 7 subsequent points of this same array SY. So for j going from 1 to 7, we look at the ith and I plus jth entry of SY. So if SY looks something like this array here, at any given point in this double for loop, we're generally looking at an index I, a point in this ith entry of the array, and then some really quite nearby point in the array I plus j, because j here is going to be at most 7. Okay, so we're constantly looking at pairs in this array, but we're not looking at all pairs at all. We're only looking at pairs that are very close to each other within 7 positions of each other. And what do we do for each choice of I and j? Well, we just look at those points, we compute the distance, we see if it's better than all of the pairs of points of this form that we've looked at in the past, and if it is better, then we remember it. So we just remember the best, i.e. closest pair of points of this particular type for choices of I and j of this form. So in more detail, if the distance between the current pair of points p and q is better than the best we've seen so far, we reset the best pair of points to be equal to p and q, and we reset the best distance, the closest distance seen so far, to be the distance between p and q. And that's it. Then once this double for loop terminates, we just return the best pair. So one possible execution of closest split pair is that it never finds a pair of points p and q with distance less than delta. In that case, this is going to return null, and then in the outer call, in the closest pair, obviously you interpret a null pair of points to having infinite distance. So if you call closest split pair and it doesn't return any points, then the interpretation is that there's no interesting split pair of points, and you just return the better of the results of the 2 recursive calls, p1 q1 or p2 q2. Now, as far as the running time of this subroutine, what happens here? Well, we do constant work, just initializing the variables. Then notice that the number of points in SY, well, in the worst case, you have all of the points of P, so there's going to be at most n points. And so you do a linear number of iterations in the outer for loop. But here's the key point. In the inner for loop, right, normally double for loops give rise to quadratic running time, but in this inner for loop, we only look at a constant number of other positions. We only look at 7 other positions. And for each of those 7 positions, we only do a constant number of work. Right? We just compare a distance and make a couple other comparisons and reset some variables. So for each of the linear number of outer iterations, we do a constant amount of work. So that gives us a running time of O of n for this part of the algorithm. So as I promised, analyzing the running time of this closest split pair subroutine was not challenging. We just, in a straightforward way, looked at all the operations. And again, because in the key linear scan we only do constant work per index, the overall running time is big O of n, just as we wanted. So this does mean that our overall recursive algorithm will have running time O of n log n. What is totally non-obvious, and perhaps even unbelievable, is that this subroutine satisfies the correctness requirements that we wanted. And remember what we needed that whenever we're in the unlucky case, whenever in fact the closest pair of points in the whole point set is split, this subroutine better find it. So, but it does, and that's made precise in the following correctness claim. So let me phrase the claim in terms of an arbitrary split pair which has distance less than delta, not necessarily the closest such pair. So suppose there exists a point on the left side and a point on the right side, so that is a split pair. And suppose the distance of this pair is less than q. Now there may or may not be such a pair of points pq. Don't forget what this parameter delta means. What delta is, by definition, is the minimum of d of p1 q1, where p1 q1 is the closest pair of points that lie entirely in the left half of the point set q, and d of p2 q2, where similarly p2 q2 is the closest pair of points that lies entirely on the right inside of R. So If there's a split pair with distance less than delta, this is exactly the unlucky case of the algorithm. This is exactly where neither recursive call successfully identifies the closest pair of points. Instead, that closest pair is a split pair. On the other hand, if we are in the lucky case, then there will not be any split pairs with distance less than delta, because the closest pair lies either all on the left or all on the right, and it's not split. But remember, so we're interested in the case where there is a split pair that has distance less than delta, where there is a split pair that is the closest pair. So the claim has two parts. The first part, part A, says the following. It says that if there's a split pair P and Q of this type, then P and Q are members of SY. Now let me just sort of redraw the cartoon. So remember what SY is. SY is that vertical strip. And again, the way we got that is we drew a line through a median x coordinate, and then we fattened it by delta on either side, and then we focused only on points that lie in the vertical strip. Now notice our counts split pair subroutine, if it ever returns a pair of points, it's going to return a pair of points PQ that belong to SY. First it filters down to SY, then it does a linear search through SY. So if we want to believe that our subroutine identifies best split pairs of points, then in particular such split pairs of points better show up in SY. They better survive the filtering step. So that's precisely what part A of the claim is. Here's part B of the claim, and this is the more remarkable part of the claim, which is that P and Q are almost next to each other in this sorted array SY. So they're not necessarily adjacent, but they're very close. They're within 7 positions away from each other. So this is really the remarkable part of the algorithm. This is really what's surprising and what makes the whole algorithm work. So just to make sure that we're all clear on everything, let's show that if we prove this claim, then we're done. Then we have a correct, fast implementation of a closest pair algorithm. I certainly owe you the proof of the claim. That's what the next video is going to be all about. But let's show that if the claim is true, then we're home free. So if this claim is true, then so is the following corollary, which I'll call corollary 1. So corollary 1 says, if we're in the unlucky case that we discussed earlier, if we're in the case where the closest point in the whole point set P does not lie both on the left, does not lie both on the right, but rather has one point on the left and one on the right, that is, it's a split pair, then in fact the count split pair subroutine will correctly identify the closest split pair, and therefore the closest pair overall. Why is this true? Well, what does count split pair do? Okay, so it has this double for loop, and it thereby explicitly examines a bunch of pairs of points, and it remembers the closest pair of all of the pairs of points that it examines. What does this, so what are the criteria that are necessary for a count split pair to examine a pair of points? Well, first of all, the points P and Q both have to survive the filtering step and make it into the array SY, right? So count split pair only searches over the array SY. Secondly, it only searches over pairs of points that are almost adjacent in SY, that are only 7 positions apart. But amongst pairs of points that satisfy those two criteria, count split pair will certainly compute the closest such pair, right? It just explicitly remembers the best of them. Now, what's the content of the claim? Well, the claim is guaranteeing that every potentially interesting split pair of points, namely every split pair of points with distance less than delta, meets both of the criteria which are necessary to be examined by the count split pair subroutine. So first of all, and this is the content of part A, if you have an interesting split pair of points with distance less than delta, then they'll both survive the filtering step. They'll both make it into the array SY. Part A says that. Part B says they're almost adjacent in SY. So if you have an interesting split pair of points, meaning it has distance less than delta, then they will in fact be at most 7 positions apart. Therefore, count split pair will examine all such split pairs, all split pairs with distance less than delta, and just by construction it will compute the closest pair of all of them. So again, in the unlucky case where the best pair of points is a split pair, then this claim guarantees that the count split pair will compute the closest pair of points. Therefore, having handled correctness, we can just combine that with our earlier observations about running time, and corollary 2 just says, if we can prove the claim, then we have everything we wanted. We have a correct O of n log n implementation for the closest pair of points. So with further work and a lot more ingenuity, we've replicated the guarantee that we got just by sorting for the one-dimensional case. Now again, these corollaries hold only if the claim is in fact true. And I've given you no justification for this claim, and indeed even the statement of the claim I think is a little bit shocking. So if I were you, I would demand an explanation for why this claim is true, and that's what I'm going to give you in the next video. All right, so the plan for this video is to prove the correctness of the divide and conquer closest pair algorithm that we discussed in the previous video. So just to refresh your memory, how does the outer algorithm work? Well, we're given endpoints in the plane. We begin by sorting them, first by x-coordinate and then by y-coordinate. That takes n log n time. Then we enter the main recursive divide and conquer part of the algorithm. So what do? We divide the point set into the left half and into the right half, capital Q and capital R. Then we conquer. We recursively compute the closest pair in the left half of the point set Q. We recursively compute the closest pair in the right half of the point set R. There's a lucky case where the closest pair in the entire point set lies either all on the left or all on the right. In that case, the closest pair is handed to us on a silver platter by one of the two recursive calls. But there remains the unlucky case where the closest pair is actually split with 1 point on the left and 1 point on the right. So to get our n log n running time bound, analogous to merge sort and our inversion counting, we need to have a linear time implementation of a subroutine which computes the closest pair of points, which is split, one on the left or one on the right. Well, actually, we don't need to do quite that. We need to do something only a little bit weaker. We need a linear time algorithm which, whenever the closest pair in the whole point set is in fact split, then computes that split pair in linear time. So let me now remind you how that subroutine works. So it has two basic steps. So first there's a filtering step. So it looks at, first of all, a vertical strip roughly down the middle of the point set, and it looks at only at points which fall into that vertical strip. That was a subset of the points that we called S sub y, because we keep track of them sorted by y-coordinate. And then we do essentially a linear scan through sy. So we go through the points one at a time, and then for each point, we look at only the almost adjacent points. So for each index I, we look only at j's that are between 1 and 7 positions further to the right than I. So among all such points, we compare them, we look at their distances, we remember the best such pair of points, and then that's what we return from the count split pair subroutine. So we've already argued in the previous video that the overall running time of the algorithm is n log n, and what remains is to prove correctness. And we also argued in the previous video that correctness boils down to the following correctness claim, in the sense that if we can prove this claim, then the entire algorithm is correct. So this is what remains. Our residual work is to provide a proof of the correctness claim. What does it say? It says consider any split pair, that is one point P from the left side Q, capital Q, and another point little q drawn from the right side of the point set, capital R, and further suppose that it's an interesting split pair, meaning that the distance between them is at most delta. Here delta is, recall, the parameter passed to the count split pair subroutine, which is the smallest distance between a pair of points which is all on the left or all on the right, and this is the only case we're interested in. There's two claims. First of all, for P and Q, both members of the split pair, survive the filtering step. They make it into the sorted list S sub y. And second of all, they will be considered by that double for loop, in the sense that the positions of P and Q in this array S sub y differ by at most 7. So that's the story so far. Let's move on to the proof. So let's start with part A, which is the easy part, relatively, of the claim. So remember what we start with. Our assumptions, we have a point P. Let's write it out in terms of the x-coordinates, x1 and y1, which is from the left half of the point set. And we have a point Q, which we'll call x2, y2, which comes from the right half of the point set. And furthermore, we're assuming that these points are close to each other. And we're going to use that hypothesis over and over again. So the Euclidean distance between P and Q is no more than this parameter delta. So first, something very simple, which is that if you have 2 points which are close in Euclidean distance, then both of their coordinates have to be close to each other. Right? If you have 2 points and they differ by a lot in one coordinate, then the Euclidean distance is going to be pretty big as well. So specifically, by our hypothesis that P and Q have Euclidean distance less than delta, it must be that the difference between their coordinates in absolute value is no more than delta, and as well, the difference between their y-coordinates is at most delta. Okay, and this is easy to see if you just return to the definition of Euclidean distance that we reviewed at the beginning of the discussion of closest point. Okay, so if your distance is at most delta, then in each coordinate you differ by at most delta as well. Now, what does A say? So proof of A. So what does part A of the claim assert? It asserts that P and Q are both members of SY, are both members of that vertical strip. So another way of saying that is that the x-coordinates of P and Q, that is the numbers x1 and x2, both are within delta of x bar. Remember, x bar was in some sense the median x-coordinate, so the x-coordinate of the n/2th leftmost point. So we're going to do a proof by picture. So forget about y-coordinates, that's sort of irrelevant right now, and just focus on the x-coordinates of all of these points. So on the one hand we have x bar, This is the x-coordinate of the n over 2th point from the left, and then there are the x-coordinates which define the left and the right borders of that vertical strip, namely x bar minus delta and x bar plus delta. And then somewhere in here are x1 and y1, the x-coordinates of the points we care about, p and q. So a simple observation, so because p comes from the left half of the point set and x bar is the rightmost x-coordinate of the left half of the point set, the x-coordinate of p is at most x bar. Right? So all points of Q have x-coordinate at most x bar, in particular P does. Similarly, since x bar is the rightmost edge of the left half of the point set, everything in the right half of the point set has x-coordinate at least x bar. So in particular, little q does as well. So what does this mean? So this means x1, wherever it is, has to be to the left of x bar. x2, wherever it is, has to be to the right of x bar. And what we're trying to prove is that they're wedged in between x bar minus delta and x bar plus delta. And the reason why that's true is because their x-coordinates also differ by at most delta. Okay, so what you should imagine is you can imagine x1 and x2 are sort of people tied by a rope at the waist, and this rope has length delta. So wherever x1 and x2 move, they're at most delta apart. Furthermore, x1, we just observed, can't move any farther to the right than x bar. So even if x1 moves as far to the right as it can, all the way to x bar, x2, since it's at most delta away, tied by the waist, can't extend beyond x bar plus delta. By the same reasoning, x2 can't move any further to the left than x bar. x1 being tied to the waist to x2 can never drift further to the left than x bar minus delta. So that's the proof that x1 and x2 both lie within this region that defines the vertical strip. So that's part A. You have any split pair whose distance between them is less than delta, they both have to wind up in this vertical strip, and therefore wind up in the filtered set, the pruned set, S sub y. So that's part A of the claim. Let's now move to part B. Recall what part B asserts. It says that the points P and Q, the split pair that are distance only delta apart, not only do they wind up in this sort of filtered set SY, but in fact they're almost adjacent in SY, in the sense that the indices in the array differ by at most 7 positions. And this is the part of the claim that's a little bit shocking. Really what this says is that we're getting away with more or less a variant of our one-dimensional algorithm. Remember when we wanted to find the closest pair of points on the line, all we had to do was sort them by their single coordinate and then look at consecutive pairs and return the best of those consecutive pairs. Here what we're saying is really once we do a suitable filtering and focus on points in this vertical strip, then we just go through the points according to their y coordinate. And okay, we don't just look at adjacent pairs, we look at pairs within 7 positions, but still we basically do a linear sweep through the points in SY according to their y coordinate, and that's sufficient to identify the closest split pair. So why on earth would this be true? So our workhorse in this argument will be a picture which I'm going to draw next. So I'm going to draw 8 boxes which have height and width delta over 2. So here delta is the same parameter that's passed to the closest split pair subroutine, and it's also the same delta which we're assuming P and Q are closer to each other than. Right? So remember that's one of our hypotheses in this claim. The distance between P and Q is strictly less than delta. So we're going to draw 8 delta over 2 boxes, and they're going to be centered at x bar, so this same center of the vertical strip that defines SY, and the bottom is going to be the smaller of the y coordinates of the points P and Q. So it might be P, it might be Q, it doesn't really matter. But so just the bottom is going to be the smaller of the two. So the picture then looks as follows. So the center of these collections of 8 boxes is x bar, the bottom is the minimum of y1, y2. We're going to have 2 rows and 4 columns. And needless to say, we're drawing this picture just for the sake of this correctness proof. Right? This picture is just a thought experiment in our head. We're just trying to understand why the algorithm works. The algorithm, of course, does not draw these boxes. The subroutine, the closest split pair subroutine, is just that pseudocode we saw in the previous video. This is just to reason about the behavior of that subroutine. Now, looking ahead, I'll make this precise in 2 lemmas that are about to come up. What's going to be true is the following. So either P or Q is on this bottom line, right? So we define the bottom to be the lower y coordinate of the 2. So maybe, for example, Q is the one that has the smaller y coordinate, in which case it's going to be somewhere, say, down here. P, remember, is from the left half of the point set, so P is maybe going to be here or something. And we're going to argue that both P and Q have to be in these boxes. Moreover, we're going to argue that these boxes are sparsely populated. Every one contains either 0 or 1 point of the array S sub y. So what we're going to see is that there's at most 8 points in this picture, 2 of which are P and Q, and therefore if you look at these points sorted by y-coordinate, it has to be that they're within 7 of each other. The difference of indices is no more than 7. So we're going to make those two statements precise one at a time via the following two lemmas. Let's start with lemma 1. Lemma 1 is the easy one, and it states that all of the points of S sub y, which show up in between the y-coordinates of the points we care about, P and Q, have to appear in this picture. They have to lie in one of these 8 boxes. So we're going to argue this in 2 steps. First, we're going to argue that all such points have to have y-coordinates within the relevant range of this picture between the minimum of y1 and y2 and delta more than that. And secondly, that they have to have x-coordinates in the range of this picture, namely between x bar minus delta and x bar plus delta. So let's start with y-coordinates. So again, remember this key hypothesis we have. Okay, we're dealing with a split pair PQ that are close to each other. The distance between x and y is strictly less than delta. So the very first thing we did at the beginning of this proof is we said, well, if their Euclidean distance is less than delta, then they have to differ by at most delta in both of their coordinates, and in particular in their y-coordinate. Now remember, whichever is the lower of P and Q, whichever one has a smaller y-coordinate, is precisely at the bottom of this diagram. So for example, if Q is the one with a smaller y-coordinate, it might be on the black line right here. So that means in particular, x has y-coordinate no more than the top part of this diagram, no more than delta bigger than q, and of course all points with y-coordinates in between them are equally well wedged into this picture. So that's why all points of sy with y-coordinate between those of p and q have to be in the range of this picture, between the minimum of the 2 y-coordinates and delta more than that. Now what about horizontally? What about the x-coordinates? Well, this just follows from the definition of S sub y. So remember, S sub y are the points that fall into this vertical strip. How did we define the vertical strip? Well, it had center x bar, and then we fattened it by delta on both sides. So just by definition, if you're in sy, you got to have x coordinates in the range of this picture. X delta plus minus, x bar plus minus delta. So that completes the proof of the lemma. So this is just a lemma, so I'll use a lowercase QED. Remember, this is just a step toward proving the overall correctness claim. But this is a good step. And again, the way to think about this is it says we draw these boxes. We know either P or Q is at the bottom. The other one is going to be on the other side of the black line x bar, but will be in some other box. So perhaps maybe P is here. And the lemma is saying that all the relevant points of sy have to be somewhere in this picture. Now remember, in our double for loop, we only search 7 positions away. So the concern is that this is a sort of super highly populated collection of 8 boxes. That's the concern, but that's not going to be the case. And that's exactly what lemma 2 is going to say. Not only do the points between P and Q and y coordinates show up in this diagram, but there have to be very few. In particular, every box has to be sparse with population either 0 or 1. So let's move on to lemma 2. So formally the claim is we have at most 1 point of the point set in each of these 8 boxes. And this is finally where we use, in a real way, the definition of delta. This is where we finally get the payoff from our realization long ago that when defining the closest split pair subroutine, we only really need to be correct in the unlucky case, in the case we're not handed the right answer by one of our recursive calls. We're finally going to use that fact in a fundamental way. So we're going to proceed by contradiction. So we're going to think about what happens if there are 2 points in a single box, and from that we'll be able to derive a contradiction. So call the points that wind up in the same box A and B. So to the contrary, suppose A and B lie in the same box. So maybe this is A here and this is B here, at antipical corners of this particular box. So from this supposition, we have 2 consequences. First of all, I claim that A and B lie on the same side of the point set. They're either both in the left side Q or they're both in the right side R. So why is this true? Well, it's because every box lies either entirely in the left half of the point set or in the right half of the point set. Recall how we define x bar. X bar is the x-coordinate of the rightmost point amongst the left half of the point set, capital Q. So therefore, points with x-coordinate at most x bar have to lie inside the left half Q. points with x coordinates at least x bar have to lie inside the right half of the point set, capital R. So that would be like in this example, A and B both lie in a box which is to the right of x bar, so they both have to come from the right half of the point set, capital R. This is one place we're using that there's no ties in x coordinate, so if there's a point with x coordinate x bar, we can count it as part of the left half. So every box, by virtue of being either to the left of x bar or to the right of x bar, can only contain points from a common half of the point set. So that's the first consequence of assuming that you have 2 points in the same box. The second consequence is, because the boxes are small, the points got to be close. So if A and B cohabitate a box, how far could they be from each other? Well, the farthest they could be is like I've drawn in the picture with the points A and B, where they're at opposite corners of a common box, and then you bust out Pythagorean's theorem, and what do you get? You get that the distance between them is delta over 2, the side of the box, times root 2. And what's relevant for us is this is strictly less than delta. Okay? But now, here's where we use, finally, the definition of delta. Consequences 1 and 2 in tandem contradict how we define delta. Remember what delta is? It's as close as a pair of points can get if they both lie on the left side of the point set or if they both lie on the right side of the point set. That is how we defined it. As small as a pair of points on a common half can get to each other. But what have we just done? We've exhibited a pair A and B that lie on the same half of the point set and are strictly closer than delta. So that contradicts the definition of delta. So that completes the proof of lemma 2. Let me just make sure we're all clear on why, having proved lemma 1 and lemma 2, we're done with the proof of part B of the claim, and therefore the entire claim, because we already proved part 1 now a long time ago. So let's interpret the two lemmas in the context of our picture that we've had all throughout in terms of the 8 boxes of side length delta over 2 by delta over 2. So again, whichever is the lower of P and Q, and again, let's just for the sake of concreteness, say it's Q, is at the bottom of the picture. The other point is on the other half of the line x bar and is in one of the other boxes. So for example, maybe P is right here. So lemma 1 says that every relevant point, every point that survives the filtering and makes it into SY by virtue of being in the vertical strip, has to be in one of these boxes, okay, if it has Y coordinate in between P and Q. Lemma 2 says that you can only have 1 point in each of these boxes from the point set. So that's going to be at most 8 total. So combining them, lemmas 1 and 2 imply that there are at most 8 points in this picture. And that includes P and Q, because they also occupy 2 of the 8 boxes. So in the worst case, if this is as densely populated as could possibly be, given lemmas 1 and 2, every other box might have a point, and perhaps every one of those points has Y coordinate between P and Q. But this is as bad as it gets. Any point of the strip with Y coordinate between P and Q occupies a box, so at most there are these 6 wedged in between them. What does this mean? This means if from Q you look 7 positions ahead in the array, you are guaranteed to find this point P. So a split pair with distance less than delta is guaranteed to be identified by our double for loop. Looking 7 positions ahead in the sorted array SY is sufficient to identify, to look at every conceivably interesting split pair. So that completes the assertion B of the correctness claim, and we're done. That establishes that this supremely clever divide and conquer algorithm is indeed a correct O of n log n algorithm that computes the closest pair of a set of n points in the plane. In this series of videos, we'll study the master method, which is a general mathematical tool for analyzing the running time of divide and conquer algorithms. We'll begin in this video motivating the method, then we'll give its formal description. That'll be followed by a video working through 6 examples. Finally, we'll conclude with 3 videos that discuss a proof of the master method, with a particular emphasis on the conceptual interpretation of the master method's 3 cases. So let me say at the outset that this lecture is a little bit more mathematical than the previous 2, but it's certainly not just math for math's sake. We'll be rewarded for our work with this powerful tool, the master method, which has a lot of predictive power. It'll give us good advice about which divide and conquer algorithms are likely to run quickly and which ones are likely to run less quickly. Indeed, it's sort of a general truism that novel algorithmic ideas often require mathematical analysis to properly evaluate. This lecture will be one example of that truism. As a motivating example, consider the computational problem of multiplying 2 n-digit numbers.
Recall from our first set of lectures that we all learned the iterative grade school multiplication algorithm, and that requires a number of basic operations, additions and multiplications between single digits, which grows quadratically with the number of digits n. On the other hand, we also discussed an interesting recursive approach using the divide and conquer paradigm. So recall divide and conquer necessitates identifying smaller subproblems. So for integer multiplication, we need to identify smaller numbers that we want to multiply. So we proceeded in the obvious way, breaking each of the two numbers into its left half of the digits and its right half of the digits. For convenience, I'm assuming that the number of digits n is even, but it really doesn't matter. Having decomposed x and y in this way, we can now expand the product and see what we get. So let's put a box around this expression and call it star. So we began with the sort of obvious recursive algorithm where we just evaluate the expression star in the straightforward way. That is, star contains four products involving n over two-digit numbers, AC, AD, BC, and BD. So we make four recursive calls to compute them, and then we complete the evaluation in the natural way. Namely, we append zeros as necessary and add up these three terms to get the final result. The way we reason about the running time of recursive algorithms like this one is using what's called a recurrence. So to introduce a recurrence, let me first make some notation, T of n. This is going to be the quantity that we really care about, the quantity that we want to upper bound. Namely, this will be the worst case number of operations that this recursive algorithm requires to multiply two n-digit numbers. This is exactly what we want to upper bound. A recurrence, then, is simply a way to express T of n in terms of T of smaller numbers. That is, the running time of an algorithm in terms of the work done by its recursive calls. So every recurrence has two ingredients. First of all, it has a base case describing the running time when there's no further recursion. And in this integer multiplication algorithm, like in most divide and conquer algorithms, the base case is easy. Once you get down to a small input, in this case two one-digit numbers, then the running time is just constant. All you do is multiply the two digits and return the result. So I'm going to express that by just declaring that T of 1, the time needed to multiply one-digit numbers, is bounded above by a constant. I'm not going to bother to specify what this constant is. You can think of it as 1 or 2 if you like. It's not going to matter for what's to follow. The second ingredient in a recurrence is the important one, and it's what happens in the general case when you're not in the base case and you make recursive calls. And all you do is write down the running time in terms of two pieces. First of all, the work done by the recursive calls, and second of all, the work that's done right here now, work done outside of the recursive calls. So on the left-hand side of this general case, we just write T of n, and then we want an upper bound on T of n in terms of the work done by recursive calls and the work done outside of recursive calls. And I hope it's self-evident what the recurrence should be in this recursive algorithm for integer multiplication. As we discussed, there's exactly 4 recursive calls, and each is invoked on a pair of n over two-digit numbers. So that gives us 4 times the time needed to multiply n over two-digit numbers. So what do we do outside of the recursive call? Well, we pad the results of the recursive calls with a bunch of zeros, and we add them up. And I'll leave it to you to verify that grade school addition, in fact, runs in time linear in the number of digits. So putting it all together, the amount of work we do outside of the recursive calls is linear. That is, it's big O of n. Let's move on to the second, more clever recursive algorithm for integer multiplication, which dates back to Gauss. Gauss's insight was to realize that in the expression star that we're trying to evaluate, there's really only 3 fundamental quantities that we care about, the coefficients for each of the 3 terms in the expression. So this leads us to hope that perhaps we can compute these 3 quantities using only 3 recursive calls rather than 4. And indeed, we can. So what we do is we recursively compute A times C, like before, and B times D, like before. But then we compute the product of A plus B with C plus D. And the very cute fact is, if we number these 3 products, 1, 2, and 3, that the final quantity that we care about, the coefficient of the 10 to the n over 2 term, namely AD plus BC, is nothing more than the third product minus each of the first 2. So that's the new algorithm. What's the new recurrence? The base case obviously is exactly the same as before. So the question then is, how does the general case change? And I'll let you answer this in the following quiz. So the correct response for this quiz is the second one, namely the only thing that changes with respect to the first recurrence is that the number of recursive calls drops from 4 down to 3. A couple of quick comments. So first of all, I'm being a little bit sloppy when I say there's 3 recursive calls, each on digits, each on numbers with n over 2 digits. When you take the sums a plus b and c plus d, those might well have n over 2 plus 1 digits. Amongst friends, let's ignore that. Let's just call it n over 2 digits in each of the recursive calls. As usual, the extra plus 1 is not going to matter in the final analysis. Secondly, I'm ignoring exactly what the constant factor is in the linear work done outside of the recursive calls. Indeed, it's a little bit bigger in Gauss's algorithm than it is in the naive algorithm with 4 recursive calls, but it's only by a constant factor, and that's going to be suppressed in the big O notation. So let's look at this recurrence and compare it to 2 other recurrences, one bigger, one smaller. So first of all, as we noted, it differs from the previous recurrence of the naive recursive algorithm in having 1 fewer recursive call. So we have no idea what the running time is of either of these 2 recursive algorithms, but we should be confident that this one certainly can only be better. That's for sure. Another point of contrast is merge sort. So think about what the recurrence would look like for the merge sort algorithm. It would be almost identical to this one, except instead of a 3, we'd have a 2. Right? Merge sort makes 2 recursive calls, each on an array of half the size, and outside of the recursive calls it does linear work, namely for the merge subroutine. We know the running time of merge sort, it's n log n. So this algorithm, Gauss's algorithm, is going to be worse, but we don't know by how much. So while we have a couple clues about what the running time of this algorithm might be more or less than, honestly, we have no idea what the running time of Gauss's recursive algorithm for integer multiplication really is. It is not obvious. We currently have no intuition for it. We don't know what the solution to this recurrence is, but it will be one super special case of the general master method, which we'll tackle next. So having motivated and hyped up the generality of the master method and its use for analyzing recursive algorithms, let's move on to its precise mathematical statement. Now, the master method is in some sense exactly what you want. It's what I'm going to call a black box for solving recurrences. Basically, it takes as input a recurrence in a particular format, and it spits out as output a solution to that recurrence, an upper bound on the running time of your recursive algorithm. That is, you just plug in a few parameters of your recursive algorithm, and boom, out pops its running time. Now, the master method does require a few assumptions, and let me be explicit about one of them right now. Namely, the master method, at least the one I'm going to give you, is only going to be relevant for problems in which all of the subproblems have exactly the same size. So for example, in merge sort, there are 2 recursive calls, and each is on exactly 1/2 of the array. So merge sort satisfies this assumption, both subproblems have equal size. Similarly, in both of our integer multiplication algorithms, all subproblems are on integers with n over 2 digits, with half as many digits. So those will all also obey this assumption. If for some reason you had a recursive algorithm that recursed on 1/3 of the array, and then on the other 2/3 of the array, the master method that I'm going to give you will not apply to it. There are generalizations of the master method that I'm going to show you which can accommodate unbalanced subproblem sizes, but those are outside the scope of this course. This will be sufficient for almost all of the examples we're going to see. One notable exception for those of you that watch the optional video on a deterministic algorithm for linear time selection, that will be one algorithm which has 2 recursive calls on different subproblem sizes. So to analyze that recurrence, we'll have to use a different method, not the master method. Next, I'm going to describe the format of the recurrences to which the master method applies. As I said, there are more general versions of the master method which apply to even more recurrences, but the one I'm going to give you is going to be reasonably simple, and it will cover pretty much all the cases you're likely to ever encounter. So recurrences have 2 ingredients. There's the relatively unimportant but still necessary base case step, and we're going to make the obvious assumption, which is just satisfied by every example we're ever going to see in this course, which is that at some point in which the input size drops to a sufficiently small amount, then the recursion stops and the problem is solved. The subproblem is solved in constant time. Since this assumption is pretty much always satisfied in every problem we're going to see, I'm not going to discuss it much further. Let's move on to the general case where there are recursive calls. So we assume the recurrence is given in the following format. The running time on an input of length n is bounded above by some number of recursive calls. Let's call it a different recursive calls. And then each of these subproblems has exactly the same size, and it's 1/b fraction of the original input size. So there's a recursive calls, each on an input of size n/b. Now, as usual, there's the case where n/b is a fraction and not an integer, and as usual, I'm going to be sloppy and ignore it, and as usual, that sloppiness has no implications for the final conclusion. Everything that we're going to discuss is true for the same reasons in the general case where n/b is not an integer.
Now outside the recursive calls we do some extra work, and let's say that it's O of n to the d for some parameter d. So in addition to the input size n, there are three letters here which we need to be very clear on what their meaning is. So first of all there's A, which is the number of subproblems, the number of recursive calls. So A could be as small as 1, or it might be some larger integer. Then there's B. B is the factor by which the input size shrinks before a recursive call is applied. B is some constant strictly greater than 1. So for example, if you recurse on half of the original problem, then B would be equal to 2. It better be strictly bigger than 1 so that eventually you stop recursion, so that eventually that you terminate. Finally, there's D, which is simply the exponent in the running time of the quote-unquote combined step. That is the amount of work which is done outside of the recursive calls. And D could be as small as 0, which would indicate constant amount of work outside of the recursive calls. One point to emphasize is that A, B, and D are all constants. That's all. They're all numbers that are independent of n. So A, B, and D are going to be numbers like 1, 2, 3, or 4. They do not depend on the input size n. And in fact, let me just redraw the D so that you don't confuse it with the A. So again, A is the number of recursive calls, and D is the exponent in the running time governing the work done outside of the recursive calls. Now, one comment about that final term, that big O of n to the d. On the one hand, I'm being sort of sloppy. I'm not keeping track of the constant that's hidden inside the big O notation. I'll be explicit with that constant when we actually prove the master method, but it's really not going to matter. It's just going to carry through the analysis without affecting anything. So you can go ahead and ignore that constant inside the big O. Obviously, the constant in the exponent, namely d, is very important. Right? So depending on what d is, depends on whether that amount of time is constant, linear, quadratic, or so on. So certainly we care about the constant d. So that's the input to the master method. It is a recurrence of this form. So you can think of it as a recursive algorithm which makes a recursive calls, each on subproblems of equal size, each of size n over b, plus it does n to the d work outside of the recursive calls. So having set up the notation, I can now precisely state the master method for you. So given such a recurrence, we're going to get an upper bound on the running time. So the running time on inputs of size n is going to be upper bounded by one of three things. So somewhat famously, the master method has three cases. So let me tell you about each of them. The trigger, which determines which case you're in, is a comparison between two numbers. First of all, a, recall a is the number of recursive calls made, and b raised to the d power. Recall b is the factor by which the input size shrinks before you recurse. D is the exponent in the amount of work done outside of the recursive call. So we're going to have one case for when they're equal. We're going to have one case for when a is strictly smaller than b to the d. And the third case is when a is strictly bigger than b to the d. And in the first case, we get a running time of big O of n to the d times log n. And again, this is d, the same d that was in the final term of the recurrence, okay, the work done outside of the recursive calls. So the first case, the running time is the same as the running time in the recurrence outside of the recursive calls, but we pick up an extra log n factor. In the second case, where a is smaller than b to the d, the running time is merely big O of n to the d. And this case might be somewhat stunning that this could ever occur because, of course, in the recurrence, what do? You do some recursion, plus you do n to the d work outside of the recursion. So in the second case, it actually says that the work is dominated by just what's done outside the recursion in the outermost call. The third case will initially seem the most mysterious. When a is strictly bigger than b to the d, we're going to get a running time of big O of n to the log base b of a. Where again, recall a is the number of recursive calls and b is the factor by which the input size shrinks before you recurse. So that's the master method with its three cases. Let me give this to you in a cleaner slide to make sure there's no ambiguity in my handwriting. So here's the exact same statement, the master method, once again with its three cases, depending on how a compares to b to the d. So one thing you'll notice about this version of the master method is that it only gives upper bound. So we only say that the solution to the recurrence is big O of some function. And that's because if you go back to our recurrence, we used big O rather than theta in the recurrence. And this is in the spirit of the course where, as algorithm designers, our natural focus is on upper bounds, on guarantees for the worst case running time of an algorithm. And we're not going to focus too much most of the time on proving stronger bounds in terms of theta notation. Now, a good exercise for you to check if you really understand the proof of the master method after we go through it would be to show that if you strengthen the hypothesis and you assume the recurrence has the form T of n equals A times T of n over B plus theta of n to the d, then in fact all three of these big O's in the statement of the master method become thetas and the solution becomes asymptotically exact. So one final comment, you'll notice that I'm being asymmetrically sloppy with the two logarithms that appear in these formulas, so let me just explain why. In particular, you'll notice that in case 1 with the logarithm, I'm not specifying the base. Why is that true? Well, it's because the logarithm, with respect to any two different bases, differs by a constant factor. So the logarithm base e, that is the natural logarithm, and the logarithm base 2, for example, differ by only a constant factor independent of the argument n. So you can switch this logarithm to whatever constant base you like. It only changes the leading constant factor, which of course is being suppressed in the big O notation anyways. On the other hand, in case 3, where we have a logarithm in the exponents, once it's in the exponent, we definitely care about that constant. Constants is the difference between, say, linear time and quadratic time. So we need to keep careful track of the logarithm base in the exponent in case 3, and that base is precisely b, the factor by which the input shrinks with each recursive call. So that's the precise statement of the master method, and the rest of this lecture will work toward understanding the master method. So first, in the next video, we'll look at a number of examples, including resolving the running time of Gauss's recursive algorithm for integer multiplication. Following those several examples, we'll prove the master method. And I know now these three cases probably look super mysterious, but if I do my job, by the end of the analysis, these three cases will seem. In this video, we'll put the master method to use by instantiating it for 6 different examples. But first, let's recall what the master method says. So the master method takes as input recurrences of a particular format, in particular recurrences that are parameterized by 3 different constants, a, b, and d. A refers to the number of recursive calls, or the number of subproblems that get solved. B is the factor by which the subproblem size is smaller than the original problem size. And d is the exponent in the running time of the work done outside of the recursive calls. So the recurrence has the form T of n, the running time on an input of size n, is no more than a, the number of subproblems, times the time required to solve each subproblem, which is T of n over b, because the input size of a subproblem is n over b, plus O of n to the d, the work outside of the recursive calls. There's also a base case, which I haven't written down, so once the problem size drops below a particular constant, then there should be no more recursion, and you can just solve the problem immediately, that is, in constant time. Now, given a recurrence in this permitted format, the running time is given by one of 3 formulas, depending on the relationship between a, the number of recursive calls, and b raised to the d power. Case 1 of the master method is when these two quantities are the same, a equals b to the d, then the running time is n to the d log n, no more than that. In case 2, the number of recursive calls, a, is strictly smaller than b to the d. Then we get a better running time upper bound of O of n to the d. And when a is bigger than b to the d, we get this somewhat funky looking running time of O of n raised to the log base b of a power. We'll understand where that formula comes from a little later. So that's the master method. It's a little hard to interpret the first time you see it, so let's look at some concrete examples. Let's begin with an algorithm that we already know the answer to, we already know the running time, namely, let's look at merge sort. So again, what's so great about the master method is all we have to do is identify the values of the 3 relevant parameters a, b, and d, and we're done. We just plug them in and we get the answer. So a, remember, is the number of recursive calls. So in merge sort, recall, we get 2 recursive calls. B is the factor by which the subproblem size is smaller than that in the original. Well, we recurse on half the array. So the subproblem size is half that of the original. So b is equal to 2. And recall that outside of the recursive calls, all merge sort does is merge, and that's a linear time subroutine. So the exponent d is 1 in reflection of the fact that it's linear time. So remember, the key trigger which determines which of the 3 cases is the relationship between a and b to the d. So a obviously is 2, and b to the d is also equal to 2. So this puts us in case 1. And remember, in case 1, we have that the running time is bounded above by O of n to the d log n. In our case, d equals 1, so this is just O of n log n, which of course we already knew. Okay? But at least this is a sanity check. The master method is at least reconfirming facts which we've already proven by direct means. So let's look at a second example. The second example is going to be for the binary search algorithm in a sorted array. Now, we haven't talked explicitly about binary search, and I'm not planning to. So if you don't know what binary search is, please read about it in a textbook or just look it up on the web, and it'll be easy to find descriptions. But the upshot is this is basically how you'd look up a phone number in a phone book. Now, I realize probably the youngest viewers of this video haven't actually had the experience of using a physical telephone book. But for the rest of you, as you know, you don't actually start with the A's and then go to the B's and then go to the C's if you're looking for a given name. You more sensibly split the telephone book roughly in the middle, and then depending on what if you're looking for is earlier or later in the alphabet, you effectively recurse on the relevant half of the telephone book. So binary search is just exactly the same algorithm when you're looking for a given element in a particular sorted array. You start in the middle of the array, and then you recurse on the left or the right half as appropriate, depending on if the element you're looking for is bigger or less than the middle element. Now, the master method applies equally well to binary search, and it tells us what its running time is. So in the next quiz, you'll go through that exercise. So the correct answer is the first one. To see why, let's recall what A, B, and D mean. A is the number of recursive calls. Now, in binary search, you only make one recursive call. This is unlike merge sort. Remember, you just compare the element you're looking for to the middle element. If it's less than the middle element, you recurse on the left half. If it's bigger than the middle element, you recurse on the right half. So in any case, there's only one recursive call. So A is merely 1 in binary search. Now, in any case, you recurse on half the array. So like in merge sort, the value of B equals 2. You recurse on a problem of half the size. And outside of the recursive call, the only thing you do is one comparison. You just determine whether the element you're looking for is bigger than or less than the middle element of the array that you recursed on. So that's constant time outside of the recursive call, giving us a value for D of 0. Just like merge sort, this is again case 1 of the master method, because we have A equal B to the D. Both in this case are equal to 1. So this gives us a recurrence, a solution to our recurrence of big O of n to the d log n. Since d equals 0, this is simply log n. And again, many of you probably already know that the running time of binary search is log n, or you can figure that out easily. Again, this is just using the master method as a sanity check to reconfirm that it's giving us the answers that we expect. Let's now move on to some harder examples, beginning with the first recursive algorithm for integer multiplication. Remember, this is where we recurse on 4 different products of n over 2 digit numbers, and then recombine them in the obvious way using padding by 0 and some linear time additions. So in the first integer multiplication algorithm, which does not make use of Gauss's trick, where we do the 4 different recursive calls in the naive way, we have A, the number of recursive calls is equal to 4. Now, in each case, whenever we take a product of 2 smaller numbers, the numbers have n over 2 digits, so that's half as many digits as we started with. So just like in the previous 2 examples, B is going to be equal to 2. The input size drops by a factor 2 when we recurse. Now, how much work do we do outside the recursive calls? Well, again, all it is doing is additions and padding by zeros, and that can be done in linear time. Linear time corresponds to a parameter value of D equal to 1. So next we determine which case of the master method we're in. A equals 4, B to the D equals 2, which in this case is less than A. So this corresponds to case 3 of the master method. And this is where we get the somewhat strange formula for the running time of the recurrence. T of n is big O of n to the log base B of A, which with our parameter values is n to the log base 2 of 4, also known as O of n squared. So let's compare this to the simple algorithm that we all learned back in grade school. Recall that the iterative algorithm for multiplying 2 integers also takes an n squared number of operations. So this was a clever idea to attack the problem recursively, but at least in the absence of Gauss's trick, where you just naively compute each of the 4 necessary products separately, you do not get any improvement over the iterative algorithm that you learned in grade school. Either way, it's an n squared number of operations. But what if we do make use of Gauss's trick, where we do only 3 recursive calls instead of 4?
Surely the running time won't be any worse than n squared, and hopefully it's going to be better. So I'll let you work out the details on this next quiz. So the correct answer to this quiz is the fourth option. It's not hard to see what the relevant values of A, B, and D are. Remember, the whole point of Gauss's trick is to reduce the number of recursive calls from 4 down to 3, so the value of A is going to be 3. As usual, we're recursing on a problem size which is half of that of the original, in this case n over 2-digit numbers, so B remains 2, and just like in the more naive recursive algorithm, we only do linear work outside of the recursive calls. All that's needed to do some additions and paddings by 0. So that puts us parameter values A, B, and D. Then we have to figure out which case of the master method that is. So we have A equal 3, B raised to the D equal to 2. So A has dropped by 1 relative to the more naive algorithm, but we're still in case 3 of the master method. A is still bigger than B to the D, so the running time is still governed by that rather exotic looking formula. Namely, T of n is big O of n to the log base B, which in our case is 2, of A, which is now 3 instead of 4. Okay? So the master method just tells us the solution to this recurrence. The running time of this algorithm is big O of n to the log base 2 of 3. So what is log base 2 of 3? Well, plug it in your computer or your calculator, and you'll find that it's roughly 1.59. So we get a running time of n to the 1.59, which is certainly better than n squared. It's not as fast as n log n, not as fast as the merge sort recurrence, which makes only 2 recursive calls, but it's quite a bit better than quadratic. So, summarizing, you did in fact learn a suboptimal algorithm for integer multiplication way back in grade school. You can beat the iterative algorithm using a combination of recursion plus Gauss's trick to save on the number of recursive calls. Let's quickly move on to our final 2 examples. Example number 5 is for those of you that watched the video on Strassens' matrix multiplication algorithm. So recall the salient properties of Strassens' algorithm. The key idea is similar to in Gauss's trick for integer multiplication. First, you set up the problem recursively. One observes that the naive way to solve the problem recursively would lead to 8 subproblems. But if you're clever about saving some computations, you can get it down to just 7 recursive calls, 7 subproblems. So A in Strassens' algorithm is equal to 7. As usual, each subproblem size is half that of the original one. So B is going to be equal to 2. And the amount of work done outside of the recursive calls is linear in the matrix size. So quadratic in n, quadratic in the dimension, because there's a quadratic number of entries in terms of the dimension. So n squared work outside of the recursive calls, leading to a value of D equal to 2. So as far as which case of the master method we're in, well, it's the same as in the last couple examples. A equals 7, B to the D equals 4, which is less than A. So once again, we're in case 3. And now the running time of Strassens' algorithm, T of n is big O of n to the log base 2 of 7, which is more or less n to the 2.81. And again, this is a win once we use the savings to get down to just 7 recursive calls. This beats the naive iterative algorithm, which recall would require cubic time. So that's another win for a clever divide and conquer in matrix multiplication via Strassens' algorithm. And once again, the master's method, just by plugging in parameters, tells us exactly what the right answer to this recurrence is. So for the final example, I feel a little guilty because I've shown you 5 examples and none of them have triggered case 2. We've had 2 in case 1 of the master method and 3 now in case 3. So this will be sort of a fictitious recurrence just to illustrate case 2, but there are examples of recurrences that come up where case 2 is the relevant one. So let's just look at the following recurrence. So this recurrence is just like merge sort. We recurse twice. There's 2 recursive calls, each on half the problem size. The only difference is in this recurrence we're working a little bit harder in the combined step. Instead of linear time outside of the recursive calls, we're doing a quadratic amount of work. Okay? So A equals 2, B equals 2, and D equals 2. So B to the D was equal to 4, strictly bigger than A, and that's exactly the trigger for case 2. Now recall what the running time is in case 2. It's simply n to the D, where D is the exponent in the combined step. In our case, D is 2, so we get a running time of n squared. And you might find this a little counterintuitive, right? Given the merge sort, all we did with merge sort is change the combined step from linear to quadratic, and merge sort has a running time of n log n, you might have expected the running time here to be n squared log n, but that would be an overestimate. So the master method gives us a tighter upper bound, shows that it's only quadratic work. So put differently, the running time of the entire algorithm is governed by the work outside of the recursive calls just in the outermost call to the algorithm, just at the root of the recursion tree. In this video, we'll begin the proof of the master method. The master method, you'll recall, is a generic solution to recurrences of a given form, recurrences in which there's a recursive calls, each on a subproblem of the same size n over b, assuming that the original problem had size n, and plus there is big O of n to the d work done by the algorithm outside of these a recursive calls. The solution that the master method provides has three cases, depending on how a compares to b to the d. Now, this proof will be the longest one that we've seen so far by a significant margin. It'll span this video as well as the next two, so let me say a few words up front about what you might want to focus on. Overall, I think the proof is quite conceptual. There's a couple of spots where we're going to have to do some computations, and the computations I think are worth seeing once in your life. I don't know that they're worth really committing to long-term memory. What I do think is worth remembering in the long term, however, is the conceptual meaning of the three cases of the master method. In particular, the proof will follow a recursion tree approach, just like we used in the running time analysis of the merge sort algorithm. And it's worth remembering what three different types of recursion trees the three cases of the master method corresponds to. If you can remember that, there will be absolutely no need to memorize any of these three running times, including the third rather exotic looking one. Rather, you'll be able to reverse engineer those running times just from your conceptual understanding of what the three cases mean and how they correspond to recursion trees of different types. So one final comment before we embark on the proof. So as usual, I'm uninterested in formality in its own sake. The reason we use mathematical analysis in this course is because it provides an explanation of fundamentally why things are the way they are. For example, why the master method has three cases and what those three cases mean. So I'll be giving you an essentially complete proof of the master method in the sense that it has all of the key ingredients. I will cut corners on occasion where I don't think it hinders understanding and where it's easy to fill in the details. So it won't be 100% rigorous, I won't dot every I and cross every T, but it will be a complete proof on the conceptual level. That being said, let me begin with a couple of minor assumptions I'm going to make our lives a little easier. So first, we're going to assume that the recurrence has the following form. So here, essentially all I've done is I've taken our previous assumption about the format of a recurrence and I've written out all of the constants. So I'm assuming that the base case kicks in when the input size is 1, and I'm assuming that the number of operations in the base case is at most c, and that constant c is the same one that was hidden in the big O notation of the general case of the recurrence. The constant c here isn't going to matter in the analysis, it's just all going to be a wash, but to keep everything clear, I'm going to write out all of the constants that were previously hidden in the big O notation. Another assumption I'm going to make, analogous to our merge sort analysis, is that n is a power of b. The general case would be basically the same, just a little more tedious. At the highest level, the proof of the master method should strike you as very natural. Really, all we're going to do is revisit the way that we analyze merge sort. Recall, our recursion tree method worked great and gave us this n log n bound on the running time of merge sort. So we're just going to mimic that recursion tree and see how far we get. So let me remind you what a recursion tree is. At the roots, at level 0, we have the outermost, the initial invocation of the recursive algorithm. At level 1, we have the first batch of recursive calls. At level 2, we have the recursive calls made by that first batch of recursive calls, and so on, all the way down to the leaves of the tree, which correspond to the base cases where there's no further recursion. Now, you might recall from the merge sort analysis that we identified a pattern that was crucial in analyzing the running time. And that pattern that we had to understand was, at a given depth j, at a given level j of this recursion tree, first of all, how many distinct subproblems are there at level j? How many different level j recursive calls are there? And secondly, what is the input size that each of those level j subproblems has to operate on? So think about that a little bit and give your answer in the following quiz. So the correct answer is the second one. At level j of this recursion tree, there are a to the j subproblems, and each has an input of size n over b to the j. So first of all, why are there a to the j subproblems? Well, when j equals 0 at the root, there's just the one problem, the original invocation of the recursive algorithm, and then each call to the algorithm makes a further calls. For that reason, the number of subproblems goes up by a factor of a with each level, leading to a to the j subproblems at level j. Similarly, b is exactly the factor by which the input size shrinks once you make a recursive call. So j levels into the recursion, the input size has been shrunk j times by a factor of b each time. So the input size at level j is n over b to the j. That's also the reason why, if you look at the question statement, we've identified the number of levels as being log base b of n. Back in merge sort, b was 2. We recursed on half the array, so the leaves all resided at level log base 2 of n. In general, if we're dividing by a factor b each time, then it takes log base b of n times before we get down to the base cases of size 1. So the number of levels overall is 0 through log base b of n, for a total of log base b of n plus 1 levels. Here then is what the recursion tree looks like. At level 0, we have the root corresponding to the outermost call, and the input size here is n, the original problem. Children of a node correspond to the recursive calls. Because there are a recursive calls, by assumption, there are a children, or a branches. Level 1 is the first batch of recursive calls, each of which operates on an input of size n over b. At level log base b of n, we've cut the input size by a factor b this many times, so we're down to 1, so that triggers the base case. So now the plan is to simply mimic our previous analysis of merge sort. So let's recall how that worked. What we did is we zoomed in a given level. And for a given level j, we counted the total amount of work that was done at level j subproblems, not counting work that was going to be done later by recursive calls. Then, given a bound on the amount of work at a given level j, we just summed up over all the levels to capture all of the work done by all of the recursive indications of the algorithm. So inspired by our previous success, let's zoom in on a given level j and see how much work gets done with level j subproblems. We're going to compute this in exactly the way we did in merge sort, namely we're just going to look at the number of problems that are at level j, and we're going to multiply that by a bound on the work done per subproblem. We just identified the number of level j subproblems as a to the j. To understand the amount of work done for each level j subproblem, let's do it in 2 parts. So first of all, let's focus on the size of the input for each level j subproblem. That's what we just identified in the previous quiz question. Since the input size is being decreased by a factor b each time, the size of each level j subproblem is n over b to the j. Now, we only care about the size of a level j subproblem in as much as it determines the amount of work, the number of operations that we perform per level j subproblem. And to understand the relationship between those two quantities, we just return to the recurrence. The recurrence says how much work gets done in a given subproblem. Well, there's a bunch of work done by recursive calls, the a recursive calls, and we're not counting that. We're just counting up the work done here at level j. And the recurrence also tells us how much work is done outside of the recursive calls. Namely, it's no more than the constant c times the input size raised to the d power. So here the input size is n over b to the j. So that gets multiplied by the constant c, and it gets raised to the d power. Okay? So c times quantity n over b to the j, that's the input size, raised to the d power. Next, I want to simplify this expression a little bit, and I want to separate out the terms which depend on the level number j and the terms which are independent of the level number j. So if you look at it, a and b are both functions of j, where the c and n to the d terms are independent of j. So let's just separate those out. And you will notice that we have now our grand entrance of the ratio between a and b to the d. And foreshadowing a little, recall that the 3 cases of the master method are governed by the relationship between a and b to the d. And this is the first time in the analysis where we get a clue that the relative magnitude of those 2 quantities might be important. So now that we've zoomed in on a particular level j and done the necessary computation to figure out how much work is done just at that level, let's sum over all of the levels so that we capture all of the work done by the algorithm. So this is just going to be the sum of the expression we saw on the previous slide. Now, since c n to the d doesn't depend on j, I can yank that out in front of the sum, and I'll sum the expression over all j. That results in the following. So believe it or not, we've now reached an important milestone in the proof of the master method. Specifically, this somewhat messy looking formula here, which I'll put a green box around, is going to be crucial. And the rest of the proof will be devoted to interpreting and understanding this expression and understanding how it leads to the 3 different running time bounds in the 3 different cases. Now I realize that at the moment this expression star probably just looks like alphabet soup. It probably just looks like a bunch of mathematical gibberish, but actually interpreted correctly, this has a very natural interpretation. So we'll discuss that in the next video. This video is the second of 3 that describes the proof of the master method. In the first of these 3 videos, we mimicked the analysis of merge sort. We used a recursion tree approach, which gave us an upper bound on the running time of an algorithm, which is governed by a recurrence of the specified form. Unfortunately, that video left us with a bit of an alphabet soup, this complicated expression. And so in the second video, we're not going to do any computations. We're just going to look at that expression, attach some semantics to it, and look at how that interpretation naturally leads to 3 cases, and also give intuition for some of the running times that we see in the master method. So recall from the previous video that the way we bounded the work done by the algorithm is we zoomed in on a particular level j of the recursion tree. We did a computation, which was the number of subproblems at that level, a to the j, times the work done per subproblem, that was the constant c, times quantity n over b to the j raised to the d, and that gave us this expression, c n to the d times the ratio of a over b to the d raised to the j at a given level j. The expression star that we concluded the previous video with was just the sum of these expressions over all of the logarithmic number of levels j. Now, as messy as this expression might seem, perhaps we're on the right track in the following sense. The master method has 3 different cases, and which case you're in is governed by how a compares to b to the d. And here in this expression, we are seeing precisely that ratio, a divided by b to the d. So let's drill down and understand why this ratio is fundamental to the performance of a divide and conquer recursive algorithm. So really, what's going on in the master method is a tug of war between 2 opposing forces, one which is forces of good and one which is forces of evil. And those correspond to the quantities b to the d and a, respectively. So let me be more precise. Let's start with the parameter a. So a, you'll recall, is defined as the number of recursive calls made by the algorithm. So it's the number of children that a node in the recursion tree has. So fundamentally, what a is, it's the rate at which subproblems proliferate as you pass deeper in the recursion tree. It's the factor by which there are more subproblems at the next level than the previous one. So let's think of a in this way, as the rate of subproblem proliferation, or RSP. And when I say rate, I mean as a function of the recursion level j. So these are the forces of evil. This is why our algorithm might run slowly, is because as we go down the tree, there are more and more subproblems, and that's a little scary. The forces of good, what we have going for us, is that with each recursion level j, we do less work per subproblem. And the extent to which we do less work is precisely b to the d. So I'll abbreviate this rate of work shrinkage, or this quantity b to the d, by RWS. Now perhaps you're wondering, why is it b to the d? Why is it not b? So remember what b denotes. That's the factor by which the input size shrinks with the recursion level j. So for example, if b equals 2, then each subproblem at the next level is only half as big as that at the previous level. But we don't really care about the input size of a subproblem, except in as much as it determines the amount of work that we do solving that subproblem. So that's where this parameter d comes into play. Think, for example, about the cases where you have a linear amount of work outside the recursive calls versus a quadratic amount of work. That is, consider the cases where d equals 1 or 2. If b equals 2 and d equals 1, that is, if you recurse on half the input and do linear work, then not only is the input size dropping by a factor 2, but so is the amount of work that you do per subproblem. And that's exactly the situation we had in merge sort, where we had linear work outside the recursive calls. But think about d equals 2. Suppose you did quadratic work per subproblem as a function of the input size. Then, again, if b equals 2, if you cut the input in half, the recursive call is only going to do 25% as much work as what you did at the current level. The input size goes down by a factor 2, and that gets squared because you do quadratic work as a function of the input size. So that would be b to the d, 2 raised to the 2, or 4. So in general, the input size goes down by a factor b, but what we really care about, how much less work we do per subproblem, goes down by b to the d. That's why b to the d is the fundamental quantity that governs the forces of good, the extent to which we work less hard with each recursion level j. So the question then is just what happens in this tug of war between these two opposing forces. So fundamentally, what the three cases of the master method correspond to is the three possible outcomes in this tug of war between the forces of good, namely the rate of work shrinkage, and the forces of evil, namely the rate of subproblem proliferation. There are three cases, one for the case of a tie, one for the case in which the forces of evil win, that is in which A is bigger than B to the D, and a case in which good wins, that is B to the D is bigger than A. To understand this a little bit better, what I want you to think about is the following. Think about the recursion tree that we drew in the previous slide, and as a function of A versus B to the D, think about the amount of work done per level. When is that going up per level? When is it going down per level? And when is it exactly the same at each level? So the answer is all of these statements are true except for the third one. So let's take them one at a time. So first of all, let's consider the first one. Suppose that the rate of subproblem proliferation, A, is strictly less than the rate of work shrinkage, B to the D. This is where the forces of good, the rate at which we're doing less work per subproblem, is outpacing the rate at which subproblems are proliferating. Okay, so the number of subproblems goes up, but the savings per subproblem goes up by even more. So in this case, it means we're going to be doing less work with each recursion tree level. The forces of good outweigh the forces of evil. The second one is true for exactly the same reason. If subproblems are proliferating so rapidly that it outpaces the savings that we get per subproblem, then we're going to see an increasing amount of work as we go down the recursion tree. It will increase with the level j. Given that these two are true, the third one is false. We can draw conclusions depending on whether the rate of subproblem proliferation is strictly bigger or strictly less than the rate of work shrinkage. And finally, the fourth statement is also true. This is the perfect equilibrium between the forces of good and the forces of evil. Subproblems are proliferating, but our savings per subproblem is increasing at exactly the same rate. The two forces will then cancel out, and we'll get exactly the same amount of work done at each level of the recursion tree. This is precisely what happened when we analyzed the merge sort algorithm. So let's summarize and conclude with the interpretation, and even understand how this interpretation lends us to forecast some of the running time bounds that we see in the master method. Summarizing, the three cases of the master method correspond to the three possible outcomes in the battle between subproblems proliferating and the work per subproblem shrinking. One for a tie, one for when subproblems is proliferating faster, and one for when the work shrinkage is happening faster. In the case where the rates are exactly the same and they cancel out, then the amount of work should be the same at every level of the recursion tree. And in this case, we can easily predict what the running time should work out to be. In particular, we know there's a logarithmic number of levels. The amount of work is the same at every level. And we certainly know how much work is getting done at the root, right? Because that's just the original recurrence, which tells us that there's asymptotically n to the d work done at the root. So with n to the d work for each of the log levels, we expect a running time of n to the d times log n. As we just discussed, when the rate of work done per subproblem is shrinking even faster than subproblems proliferate, then we do less and less work with each level of the recursion tree. So in particular, the biggest amount of work, the worst level, is at the root level. Now, the simplest possible thing that might be true would be that actually the root level just dominates the overall running time of the algorithm, and the other levels really don't matter up to a constant factor. So it's not obvious that's true, but if we keep our fingers crossed and hope for the simplest possible outcome, if the root has the most work, we might expect a running time that's just proportional to the running time at the root. As we just discussed, we already know that that's n to the d, because that's just the outermost call to the algorithm. By the same reasoning, when this inequality is flipped and subproblems proliferate so rapidly that it's outpacing the savings we get per subproblem, the amount of work is increasing the recursion level, and here the worst case is going to be at the leaves. That's where that level is going to have the most work compared to any other level. And again, if you keep your fingers crossed and hope that the simplest possible outcome is actually true, perhaps the leaves just dominate, and up to a constant factor, they govern the running time of the algorithm. In this third case, given that we do a constant amount of work for each of the leaves, since those correspond to base cases, here we'd expect a running time in the simplest scenario proportional to the number of leaves in the recursion tree. So let's summarize what we've learned in this video. we now understand that fundamentally there are three different types of recursion trees. Those in which the work done per level is the same at every level, those in which the work is decreasing with the level, in which case the root is the worst level, and those in which the amount of work is increasing in the level, where the leaves are the worst level. Furthermore, it's exactly the ratio between A, the rate of subproblem proliferation, and B to the D, the rate of work shrinkage per subproblem, that governs which of these three recursion trees we're dealing with. Furthermore, intuitively, we've now have predictions about what kind of running time we expect to see in each of the three cases. They're n to the d log n, that we're pretty confident about. There's a hope that in the second case, where the root is the worst level, that maybe the running time is n to the d, and there's a hope in the third case, where the leaves are the worst level, and we do constant time per leaf per base case, that it's going to be proportional to the number of leaves. Let's now sanity check this intuition against the formal statement of the master method, which we'll prove more formally in the next video. So in the three cases, we see they match up at least 2 out of 3 with exactly what our intuition lies. So in the first case, we see the expected n to the d times log n. In the second case, where the root is the worst level, indeed, the simplest possible outcome of big O of n to the d is the assertion. Now, the third case, there remains a mystery to be explained. Our intuition said this should hopefully be proportional to the number of leaves, and instead we've got this funny formula, big O of n to the log base b of a. So in the next video, we'll demystify that connection, as well as supply a formal proof for these assertions. Let's complete the proof of the master method. Let me remind you about the story so far. The first thing we did is we analyzed the work done by a recursive algorithm using a recursion tree. So we zoomed in at a given level j, we identified the total amount of work done at level j, and then we summed up over all of the levels, resulting in this rather intimidating expression star. C n to the d times a sum over the levels j from 0 to log base b of n of quantity a over b to the d raised to the j. Having derived this expression star, we then spent some time interpreting it, attaching to it some semantics, and we realized that the role of this ratio a over b to the d is to distinguish between three fundamentally different types of recursion trees. Those in which a equals b to the d, and therefore the amount of work is the same at every level. Those in which a is less than b to the d, and therefore the amount of work is going down with the level. And those in which a is bigger than b to the d, in which case the amount of work is growing with the level. This gave us intuition about the three cases of the master method, and even gave us predictions for the kind of running times that we might see. So what remains to do is really turn this hopeful intuition into a rigorous proof. So we need to verify that in fact the simplest possible scenarios outlined in the previous video actually occur. In addition, we need to demystify the third case and understand what the expression has to do with the number of leaves of the recursion tree. Let's begin with the simplest case, which is case 1. Recall in case 1, we're assuming that A equals B to the D. This is the case where we have a perfect equilibrium between the forces of good and evil, where the rate of subproblem proliferation exactly cancels out with the rate at which we do less work per subproblem. And now examining the expression star, we can see how easy our lives get when A equals B to the D. In that case, this ratio is equal to 1. So naturally, this ratio raised to the j is also equal to 1 for all j. And then, of course, this sum evaluates to something very simple, namely 1 summed with itself log base b of n plus 1 times. So the sum simply equals log base b of n plus 1. And that's going to get multiplied by this c n to the d term, which is independent of the sum. So summarizing, when a equals b to the d, we find that star equals c n to the d times log base b of n plus 1. Writing this in big O notation, we would write big O of n to the d log n. And again, I'm going to suppress the base of the logarithm. Since all logarithms differ only by a constant factor, we don't have to specify the base. That's just suppressed by the constant hidden in the big O notation. So that's it for case 1. Like I said, this is the easy case. So what do we do when a is not equal to b to the d? And remember, a could be either less than or bigger than b to the d. To answer that question, let's take a short detour into geometric series. For this single slide detour, we're going to think about a single constant number, r. Now, what you want to think about is r representing that ratio a over b to the d from the previous slide. But for this slide only, let's just call it r. This is a constant, it's bigger than 0, and it's not equal to 1. Now, suppose we sum up powers of r, stopping, let's say, at the kth power of r. I claim that this sum has a nice closed form formula. Specifically, it is exactly r to the k plus 1 minus 1 divided by r minus 1. Now, whenever you see a general formula like this, it's useful to keep in mind a couple of canonical values of the parameters that you can plug in to develop intuition. And for this expression, you might want to think canonically about the cases r equal 2 and r equals 1/2. So when r equals 2, we're summing up powers of 2, 1 plus 2 plus 4 plus 8 plus 16, and so on. When r is 1/2, we're summing up 1 plus 1/2 plus 1/4 plus 1/8, and so on. Now, I'm not going to prove this for you. I'd like you to prove this yourself, if you don't already know this fact. So the way to prove this is simply by induction, and I will leave this as an exercise. What I want to focus on instead is what this fact can do for us. The way we'll use this fact is to formalize the idea that in recursion trees where the amount of work is increasing in the levels, the leaves dominate the overall running time, and where recursion trees where the amount of work is decreasing in the level, the root dominates the running time, in the sense that we can ignore all of the other levels of the recursion tree. So in the notation in this slide, we have two upshots. First of all, for the case when r is less than 1. And in this case, this expression on the right-hand side, r to the k plus 1 minus 1 over r minus 1, can be upper bounded by 1 over 1 minus r. So again, remember, you might want to have a canonical value of r in mind here, namely 1/2. So what we're claiming here is that the right-hand side is no more than 2 for the case of r equal 1/2. And that's easy to see if you think about 1 plus 1/2 plus 1/4 plus 1/8 and so on. That sum is converging to 2 as k grows large. So in general, for r less than 1 and constant, the sum is bounded by 1 minus 1 over r. Now, we're not actually going to care about this formula, 1 minus 1 over r. The point for us is just that this is a constant. And by constant, I mean independent of k, independent of how many terms we sum up. Obviously, it depends on r, the ratio, but it does not depend on how many things we sum up on k. So the way to think about this is when we sum up a bunch of terms where r is less than 1, then the very first term dominates. The first term is equal to 1, and no matter how many terms we sum up, we never grow bigger than some constant. A similar situation holds for the case where r is a constant bigger than 1. When r is bigger than 1, a tiny bit of algebra shows that we can upper bound the right-hand side by r to the k times something which is constant, independent of k. So again, let's interpret the second upshot in terms of a canonical value of r, namely r equals 2. Then our sum is 1 plus 2 plus 4 plus 8 plus 16, and so on. And what this is saying is that no matter how many terms we sum up, the overall sum is never going to be more than twice the largest and final term. So if we sum up to, say, 128, the sum, you'll notice, will be 255, which is at most twice that largest term, 128. And that same is true for any k. The entire sum is no more than twice that of the largest term. In this sense, the largest term of the series dominates the whole thing. So to summarize this slide in just one sentence, when we sum up powers of a constant r, when r is bigger than 1, the largest power of that constant dominates the sum. When r is smaller than 1, then the sum is just a constant. Let's now apply this to prove case 2 of the master method. In case 2 of the master method, we assume that a is less than b to the d. That is, the rate at which subproblems are proliferating is drowned out by the rate at which we do less work per subproblem. So this is the case where the amount of work is decreasing with each level of the recursion tree, and our intuition said that, well, in the simplest possible scenario, we might hope that all of the work up to a constant factor is being done at the root. So let's make that intuition precise by using the basic sums fact on the previous slide. So since a is less than b to the d, this ratio is less than 1. So let's call this ratio equal to r. So r, you'll notice, does depend on the three parameters a, b, and d, but r is a constant. It does not depend on n. So what is this sum? This sum is we're just summing up powers of this constant r, where r is less than 1. What did we just learn? We just learned that any such sum is bounded above by a constant, independent of the number of terms that you sum up. So therefore, what does this expression star evaluates to? It evaluates to c, which is a constant, times n to the d times another constant. So suppressing the product of these two constants in big O notation, we can say that the expression star is upper bounded by big O of n to the d. And this makes precise our intuition that indeed the overall running time of the algorithm in this type of recursion tree with decreasing work per level is dominated by the root. The overall amount of work is only a constant factor larger than the work done merely at level 0 of the tree. Let's move on to the final and most challenging part of the proof, the final case. In case 3, we assume that A is bigger than b to the d. So in conceptual terms, we're assuming the rate at which subproblems proliferate is exceeding the rate at which we do less work per subproblem. So these are recursion trees where the amount of work is increasing with each level, with the most work being done at the leaves. And once again, using the basic sums fact, we can make precise the hope that in fact we only have to worry about the leaves. We can throw away the rest of the work, losing only a constant factor. So to see that, we will again denote this ratio between a and b to the d as r. And in this case, r is bigger than 1. So this sum is a sum of a bunch of powers of r where r is bigger than 1. What did we just learn about that 2 slides ago in the basic sums fact? We learned that such sums are dominated by the largest and last term of the sum. Okay? So they're bounded by a constant factor times the largest term. Therefore, we can simplify the expression star to the following. I'm going to write it in terms of big O notation, and like on the last slide, I'll use it to suppress 2 different constants. On the one hand, I'm going to be suppressing the constant c, which we inherited way back when from the original recurrence. And on the other hand, I'm going to use it to also suppress this constant that comes from the basic sums fact. So ignoring those 2 constants, what do we have left? We have n to the d times the largest term of the sum. So what is the largest term of the sum? Well, it's the last one. So we plug in the biggest value of j that we're ever going to see. So what's the biggest value of j we're ever going to see? Well, it's just this, log base b of n. So we get the ratio a over b to the d raised to the log base b of n power. Now don't despair how messy this looks. We can do some remarkable simplifications. So what I want to do next is I want to focus just on this 1 over b to the d raised to the log base b of n term. So that's going to be, we can write that as b to the minus d log base b of n, which if I factor this exponent into 2 successive parts, I can write this as b raised to the log base b of n power, and only then raised to the minus d. And now, of course, what happens is that taking the logarithm of n base b, followed by taking raising it to the b power, those are inverse operations that cancel, so that leaves us just with the n. So this results in a n to the minus d, and now, remarkably, this n to the minus d is just going to cancel out with this n to the d, leaving us with merely a raised to the log base b of n. And thus, out of this crazy sea of letters, rises a formula we can actually understand. So a to the log base b of n, if we step back and think for a minute, is actually a supernatural quantity. It describes something about the recursion trees that we already knew was supposed to pop up in the analysis. I'll let you think through exactly what that is in the following quiz. So the correct answer to this quiz is the 4th response. A raised to the log base b of n is precisely the number of leaves of the recursion tree. And remember, in our intuition for case 3, recursion trees where the amount of work is increasing per level, we thought that perhaps the work would be dominated by the work done at the leaves, which is just proportional to the number of leaves. So why is this the answer? We'll just remember what recursion trees look like. At level 0, we have a single node, and then with each level, we have a times as many nodes as before. That is, with each level of the recursion tree, the number of nodes goes up by a factor of a. How long does this process go on? Well, it goes on until we reach down to the leaves. Recall that the input size starts at n up at the root. It gets divided by a factor b each time, and it terminates once we get down to 1. So the leaves reside at precisely level log base b of n. So therefore, the number of leaves is just the branching factor, which is a, raised to the number of times that we actually multiply by a, which is just the number of levels, which is log base b of n. So each time we go down a level, we increase the number of nodes by a factor of a, and we go down a level log base b of n times, leaving us with a number of leaves equal to a raised to the log base b of n. So what we've done is we've mathematically confirmed in a very cool way our intuition about what case 3 should look like in the master method. We've proven that in case 3, when a is bigger than b to the d, the running time is O of the number of leaves in the recursion tree, just as the intuition predicted. But this leaves us with one final mystery. If you go back to the statement of the master method, we didn't say a to the log base b of n. In case 3, it says the running time is n to the log base b of a. And not only that, we've used this case 3 formula over and over again to evaluate Gauss's recursive algorithm for integer multiplication, to evaluate Strassens' matrix multiplication algorithm, and so on. So what's the story? How come we're not getting the same thing as in the statement of the master method? Well, there's a very simple explanation, which is simply that, believe it or not, a log base b of n and n to the log base b of a are exactly the same thing. This looks like the kind of mistake you'd make in freshman algebra, but actually if you think about it, these are simply the same quantity. If you don't believe me, just take the logarithm base b of both sides and you'll get the same thing on both sides. Now you might well be wondering why I didn't just state in the master method that the running time of case 3 is this very sensible and meaningful expression a raised to the log base b of n, i.e. the number of leaves in the recursion tree. Well, it turns out that while this expression on the left-hand side is the more meaningful conceptually, the right-hand side, n to the log base b of a, is the easiest one to apply. So recall when we worked through a bunch of examples of the master method, this right-hand side was super convenient when we evaluated the running times of algorithms, when we plugged in the numbers of a and b. In any case, whether or not you want to think about the running time in case 3 as proportional to the number of leaves in the tree or as proportional to n to the log base b of a, we're done. We've proved it. That's case 3. That was the last one. So we're done with the master method. QED. So that was a lot of hard work proving the master method, and I would never expect someone to be able to regurgitate all of the details of this proof. You know, it's something like a cocktail party. Well, maybe except at the nerdiest of all cocktail parties. But I do think there's a few high-level conceptual points of this proof that are worth remembering in the long term. So we started by just writing down a recursion tree for the recursive algorithm, and in a generic way, and going level by level, we counted up the work done by the algorithm. And this part of the proof had nothing to do with how a and b to the d related to each other. Then we recognized that there are 3 fundamentally different types of recursion trees. Those with the same amount of work per level, those where it increases with a level, and those where it decreases with a level. If you can remember that, you can even remember what the running times of the 3 cases should be. In the case where you do the same amount at every work at each level, we know there's a logarithmic number of levels. We know we do n to the d work at the root, so that gives us the running time in case 1 of n to the d log n. When the amount of work is decreasing with the levels, we now know that the root dominates. Up to a constant factor, we can throw out the rest of the levels, and we know n to the d work gets done at the root, so that's the overall running time. And in the third case, where it's increasing in the levels, the leaves dominate. The number of leaves is a raised to the log base to b of n, and that's the same as n to the log base b of a. And that's the proportion of the running time in case 3 of the master method. So now we come to one of my favorite sequence of lectures where we get to discuss the famous Quicksort algorithm. If you ask professional computer scientists and professional programmers to draw up a list of their top 5, top 10 favorite algorithms, I'll bet you'd see Quicksort on many of those people's lists. So why is that? After all, we've already discussed sorting. We already have a quite good and practical sorting algorithm, namely the merge sort algorithm. Well, Quicksort, in addition to being very practical, it's competitive with and often superior to merge sort. So in addition to being very practical and used all the time in the real world and in programming libraries, it's just an extremely elegant algorithm. When you see the code, it's just so succinct, it's so elegant, you just sort of wish you had come up with it yourself. Moreover, the mathematical analysis, which explains why Quicksort runs so fast, and that mathematical analysis we'll cover in detail, it's very slick. So it's something I can cover in just about half an hour or so. So more precisely, what we'll prove about the Quicksort algorithm is that a suitable randomized implementation runs in time n log n on average. And I'll tell you exactly what I mean by on average later on in this sequence of lectures. And moreover, the constants hidden in the big O notation are extremely small, and that'll be evident from the analysis that we do. Finally, and this is one thing that differentiates Quicksort from the merge sort algorithm, is it operates in place. That is, it needs very little additional storage beyond what's given in the input array in order to accomplish the goal of sorting. Essentially, what Quicksort does is just repeated swaps within the space of the input array until it finally concludes with a sorted version of the given array. The final thing I want to mention on this first slide is that, unlike most of the videos, this set of videos will actually have an accompanying set of lecture notes, which I've posted in PDF from the course website. Those are largely redundant, they're optional, but if you want another treatment of what I'm going to discuss, a written treatment, I encourage you to look at the lecture notes on the course website. So for the rest of this video, I'm going to give you an overview of the ingredients of Quicksort and what we have to discuss in more detail, and the rest of the lectures will give details of the implementation as well as the mathematical analysis.
So let's begin by recalling the sorting problem. This is exactly the same problem we discussed back when we covered merge sort. So we're given as input an array of n numbers in arbitrary order. So for example, perhaps the input looks like this array here. And then what do we got to do? We just got to output a version of these same numbers, but in increasing order. Like when we discussed merge sort, I'm going to make a simplifying assumption just to keep the lectures as simple as possible. Namely, I'm going to assume the input array has no duplicates. That is, all of the entries are distinct. And like with merge sort, I encourage you to think about how you would alter the implementation of quicksort so that it deals correctly with ties, with duplicate entries. To discuss how quicksort works at a high level, I need to introduce you to the key subroutine. And this is really the key great idea in quicksort, which is to use a subroutine which partitions an array around a pivot element. So what does this mean? Well, the first thing you got to do is you got to pick one element in your array to act as a pivot element. Now, eventually we'll worry quite a bit about exactly how we choose this magical pivot element, but for now you can just think of it that we pluck out the very first element in the array to act as the pivot. So for example, in the input array that I mentioned on the previous slide, we could just use 3 as the pivot element. After you've chosen a pivot element, you then rearrange the array. And you rearrange it so that all the elements which come to the left of the pivot element are less than the pivot, and all the elements which come after the pivot element are greater than the pivot. So for example, given this input array, one legitimate way to rearrange it so that this holds is the following. Perhaps in the first two entries we have the 2 and the 1, then comes the pivot element, and then comes the elements 4 through 8 in some perhaps jumbled order. So notice that the elements to the left of the pivot, the 2 and the 1, are indeed less than the pivot, which is 3. And the 5 elements to the right of the pivot, to the right of the 3, are indeed all greater than 3. Notice in the partitioning subroutine we do not insist that we get the relative order correct amongst those elements less than the pivot or amongst those elements bigger than the pivot. So in some sense we're doing some kind of partial sorting. We're just bucketing the elements of the array into one bucket, those less than the pivot, and then a second bucket, those bigger than the pivot. And we don't care about getting right the order amongst within each of those two buckets. So partitioning is certainly a more modest goal than sorting, but it does make progress towards sorting. In particular, the pivot element itself winds up in its rightful position. That is, the pivot element winds up where it should be in the final sorted version of the array. You'll notice in the example we chose as the pivot the third largest element, and it does indeed wind up in the third position of the array. So more generally, where should the pivot be in the final sorted version? Well, it should be to the right of everything less than it. It should be to the left of everything bigger than it, and that's exactly what partitioning does by definition. So why is it such a good idea to have a partitioning subroutine? After all, we don't really care about partitioning. What we want to do is sort. Well, the point is that partitioning can be done quickly, it can be done in linear time, and it's a way of making progress toward having a sorted version of an array, and it's going to enable a divide and conquer approach toward sorting the input array. So in a little bit more detail, let me tell you about 2 cool facts about a partition subroutine. I'm not going to give you the code for partitioning here, I'm going to give it to you on the next video. But here are the 2 salient properties of the partition subroutine discussed in detail in the next video. So the first cool fact is that it can be implemented in linear, that is big O of n time, where n is the size of the input array, and moreover not just linear time, but linear time with essentially no extra overhead. So we're going to give a linear time implementation where all you do is repeated swaps. You do not allocate any additional memory, and that's key to the practical performance of the quicksort algorithm. Secondly, it cuts down the problem size. So it enables a divide and conquer approach. Namely, after we've partitioned an array around some pivot element, all we have to do is recursively sort the elements that lie on the left of the pivot and recursively sort the elements that lie on the right of the pivot, and then we'll be done. So that leads us to the high-level description of the Quicksort algorithm. Before I give the high-level description, I should mention that this algorithm was discovered by Tony Hoare, roughly 1961 or so. This was at the very beginning of Hoare's career. He was just about 26, 27 years old. He went on to do a lot of other contributions and eventually wound up winning the highest honor in computer science, the ACM Turing Award, in 1980. And when you see this code, I'll bet you feel like you wish you had come up with this yourself. It's hard not to be envious of the inventor of this very elegant quicksort algorithm. So just like in merge sort, this is going to be a divide and conquer algorithm. So it takes an array of some length n, and if it's an array of length n, it's already sorted, and that's the base case, and we can return. Otherwise, we're going to have two recursive calls. The big difference from merge sort is that whereas in merge sort we first split the array in two pieces, recurse, and then combine the results, here the recursive calls come last. So the first thing we're going to do is choose a pivot element, then partition the array around that pivot element, and then do two recursive calls. And then we'll be done. There will be no combine step, no merge step. So in the general case, the first thing you do is choose a pivot element. For the moment, I'm going to leave the choose pivot subroutine unimplemented. There's going to be an interesting discussion about exactly how you should do this. For now, you just do it in some way, that for somehow you come up with one pivot element. For example, a naive way would be to just choose the first element. Then you invoke the partition subroutine that we discussed in the last couple slides. So recall that results in a version of the array in which the pivot element p is in its rightful position. Everything to the left of p is less than p. Everything to the right of the pivot is bigger than the pivot. And now all I have to do to finish up is recurse on both sides. So let's call the elements less than p the first part of the partitioned array, and the elements greater than p the second part of the recursive array. And now we just call quicksort again to recursively sort the first part and then to recursively sort the second part. And that is it. That is the entire quicksort algorithm at a high level. This is one of the relatively rare recursive or divide and conquer algorithms that you're going to see where you literally do no work after solving the subproblems. There is no combine step, no merge step. Once you've partitioned, you just sort the two sides and you're done. So that's the high-level description of the quicksort algorithm. Let me give you a quick tour of what the rest of the videos are going to be about. So first of all, I owe you details on this partition subroutine. I promised you it could be implemented in linear time with no additional memory, so I'll show you an implementation of that on the next video. We'll have a short video that formally proves correctness of the quicksort algorithm. I think most of you will kind of see intuitively why it's correct, so that's a video you can skip if you want. But if you do want to see what a formal proof of correctness for a divide and conquer algorithm looks like, you might want to check out that video. Then we'll be discussing exactly how the pivot is chosen. It turns out the running time of quicksort depends on what pivot you choose. So we're going to have to think carefully about that. Then we'll introduce randomized quicksort, which is where you choose a pivot element uniformly at random from the given array, hoping that a random pivot is going to be pretty good sufficiently often. And then we'll give the mathematical analysis in three parts. We'll prove that the quicksort algorithm runs in n log n time with small constants on average for a randomly chosen pivot. In the first analysis video, I'll introduce a general decomposition principle of how you take a complicated random variable, break it into indicator random variables, and use linearity of expectation to get a relatively simple analysis. That's something we'll use a couple more times in the course, for example, when we study hashing. Then we'll discuss sort of the key insight behind the quicksort analysis, which is about understanding the probability that a given pair of elements gets compared at some point in the algorithm. That'll be the second part. Then there's going to be some mathematical computations just to sort of tie everything together, and that'll give us the bound on the quicksort running time. Another video that's available is a review of some basic probability concepts for those of you that are rusty that we'll be using in the analysis of quicksort. Okay, so that's it for the overview. Let's move on to the details. The goal of this video is to provide more details about the implementation of the quicksort algorithm, and in particular here we're going to drill down on the key partition subroutine. So let me remind you what the job of the partition subroutine is in the context of sorting an array. So recall the key idea in quicksort is to partition the input array around a pivot element. So this has two steps. First, you somehow choose a pivot element. And in this video, we're not going to worry about how you choose the pivot element. For concreteness, you might just want to think about you pick the first element of the array to serve as your pivot. So in this example array, the first element happens to be 3, so we could choose 3 as the pivot element. Now, there's a key rearrangement step. So you rearrange the array so that it has the following property. Any entries that are to the left of the pivot element should be less than the pivot element, whereas any entries which are to the right of the pivot element should be greater than the pivot element. So for example, in this version of the second version of the array, we see to the left of the 3 is the 2 and the 1. They're in reverse order, but that's okay. Both the 2 and the 1 are to the left of the 3, and they're both less than 3. And the 5 elements to the right of 3 they're jumbled up, but they're all bigger than the pivot element. So this is a legitimate rearrangement that satisfies the partitioning property. And again, recall this definitely makes partial progress toward having a sorted array. The pivot element winds up in its rightful position. It winds up where it's supposed to be in the final sorted array, to the right of everything less than it, to the left of everything bigger than it. Moreover, we've correctly bucketed the other n-1 elements to the left or to the right of the pivot according to where they should wind up in the final sorted array. So that's the job that the partitioning subroutine is responsible for. Now what's cool is we'll be able to implement this partition subroutine in linear time. Even better, we'll be able to implement it so that all it does really is swaps in the array. That is, it works in place. It needs no additional, essentially constant additional memory to rearrange the array according to those properties. And then, as we saw in the high-level description of the quicksort algorithm, what partitioning does is it enables a divide and conquer approach. It reduces the problem size. After you've partitioned an array around the pivot, all you got to do is recurse on the left side, recurse on the right side, and you're done. So what I owe you is this implementation. How do we actually satisfy the partitioning property, stuff to the left of the pivot smaller than it, stuff to the right of the pivot bigger than it, in linear time and in place? Well, first let's observe that if we didn't care about the in-place requirement, if we were happy to just allocate a second array and copy stuff over, it would actually be pretty easy to implement a partitioning subroutine in linear time. That is, using O of n extra memory, it's easy to partition around a pivot element in O of n time. And as usual, probably I should be more precise and write theta of n in these two cases. That would be the more accurate, stronger statement. But I'm going to be sloppy, and I'm just going to write the weaker but still correct statement using big O. Okay, so big O of n time using linear extra memory. So how would you do this? Well, let me just sort of illustrate by example. I think you'll get the idea. So let's go back to our running example of an input array. Well, if we're allowed to use linear extra space, we can just pre-allocate another array of length n. And then we can just do a single scan through the input array, bucketing elements according to whether they're bigger than or less than the pivot. And so, for example, we could fill in the additional array both from the left and the right using elements that are less than or bigger than the pivot, respectively. So, for example, we start with the 8. We note that the 8 is bigger than the pivot, so we put that at the end of the output array. Then we get to the 2. The 2 is less than the pivot, so that should go on the left-hand side of the output array. We get to the 5. It should go on the right-hand side, and the 1 should go on the left-hand side, and so on. When we complete our scan through the input array, there'll be one hole left, and that's exactly where the pivot belongs, to the right of everything less than it, to the left of everything bigger than it. So what's really interesting then is to have an implementation of partition which is not merely linear time, but also uses essentially no additional space, that doesn't resort to this cop-out of pre-allocating an extra array of length n. So let's turn to how that works, first starting at a high level, then filling in the details. So I'm going to describe the partitioning subroutine only for the case where the pivot is in fact the first element. But really this is without loss of generality. If instead you want to use some pivot from the middle of the array, you can just have a pre-processing step that swaps the first element of the array with the given pivot and then run the subroutine that I'm about to describe. Okay, so with constant time pre-processing, the case of a general pivot reduces to the case of where the pivot is the first element. So here's the high-level idea, and it's very cool. The idea is we're going to be able to get away with just a single linear scan of the input array. So at any given moment in this scan, which is just going to be a single for loop, we'll be keeping track of both the part of the array we've looked at so far and the part that we haven't looked at so far. So there's going to be two groups, what we've seen, what we haven't seen. Then within the group we've seen, we're going to have that be split further according to the elements that are less than the pivot and those that are bigger than the pivot. So we're going to leave the pivot element just hanging out in the first element of the array until the very end of the algorithm when we correct its position with a swap. And at any given snapshot of this algorithm, we will have some stuff that we've already looked at and some stuff that we haven't yet looked at in our linear scan. Of course, we have no idea what's up with the elements that we haven't looked at yet. Who knows what they are and whether they're bigger or less than the pivot. But we're going to implement the algorithm, so among the stuff that we've already seen, it will be partitioned in the sense that all elements less than the pivot come first, all elements bigger than the pivot come last. And as usual, we don't care about the relative order amongst elements less than the pivot or amongst elements bigger than the pivot. So summarizing, we do a single scan through the input array. And the trick will be to maintain the following invariant throughout the linear scan. That basically everything we've looked at in the input array is partitioned. Everything less than the pivot comes before everything bigger than the pivot. And we want to maintain that invariant, doing only constant work and no additional storage with each step of our key for loop, each step of our linear scan. So here's what I'm going to do next. I'm going to go through an example and execute the partition subroutine on a concrete array, the same input array we've been using as an example thus far. Now maybe it seems weird to give an example before I've actually given you the algorithm, before I've given you the code, but doing it this way, I think you'll see the gist of what's going on in the example, and then when I present the code, it'll be very clear what's going on. Whereas if I presented the code first, it might seem a little opaque when I first show you the algorithm. So let's start with an example. Throughout the example, we want to keep in mind the high-level picture that we discussed in the previous slide. The goal is that at any time in the partition subroutine, we've got the pivot hanging out in the first entry. Then we've got stuff that we haven't looked at. So of course, who knows whether those elements are bigger than or less than the pivot. And then for the stuff we've looked at so far, everything less than the pivot comes before everything bigger than the pivot. This is the picture we want to retain as we go through the linear scan. As this high-level picture would suggest, there's two boundaries that we're going to need to keep track of throughout the algorithm. We're going to need to keep track of the boundary between what we've looked at so far and what we haven't looked at yet. So that's going to be, we're going to use the index j to keep track of that boundary. And then we also need a second boundary for amongst the stuff that we've seen, where is the split between those less than the pivot and those bigger than the pivot. So that's going to be I. So let's use our running example array. So stuff is pretty simple when we're starting out. We haven't looked at anything. So all of this stuff is unpartitioned. And I and j both point to the boundary between the pivot and all the stuff that we haven't seen yet. Now to get a running time which is linear, we want to make sure that at each step we advance j. We look at one new element. That way in a linear number of steps we'll have looked at everything and hopefully we'll be done and we'll have a partitioned array. So in the next step we're going to advance j. So the region of the array which we haven't looked at, which is unpartitioned, is one smaller than before. We've now looked at the 8, the first element, after the pivot. Now the 8 itself is indeed a partitioned array. Everything less than the pivot comes before everything after the pivot. Turns out there's nothing less than the pivot. So vacuously this is indeed partitioned. So j, recall, delineates the boundary between what we looked at and what we haven't looked at. I delineates amongst the stuff we've looked at, where is the boundary between what's bigger than and what's less than the pivot. So the 8 is bigger than the pivot, so I should be right here. Okay, because we want I to be just to the left of all the stuff bigger than the pivot. Now, what's going to happen in the next iteration? This is where things get interesting. Suppose we advance j one further. Now the part of the array that we've seen is an 8 followed by a 2. Now, an 8 and a 2 is not a partitioned subarray. Remember what it means to be a partitioned subarray. All the stuff less than the pivot, all the stuff less than 3 should come before everything bigger than 3. So A2 obviously fails that property. 2 is less than the pivot, but it comes after the 8, which is bigger than the pivot. So to correct this, we're going to need to do a swap. We're going to swap the 2 and the 8. That gives us the following version of the original array. So now the stuff that we have not yet looked at is 1 smaller than before. We've advanced j. So all this stuff is unpartitioned. Who knows what's going on with that stuff? J is 1 further entry to the right than it was before. And at least after we've done this swap, we do indeed have a partitioned array. So post-swap, the 2 and the 8 are indeed partitioned. Now remember, I delineates the boundary between amongst what we've seen so far, the stuff less than the pivot, less than 3 in this case, and that bigger than 3. So I is going to be wedged in between the 2 and the 8. In the next iteration, our life is pretty easy. So in this case, in advancing j, we uncover an element which is bigger than the pivot. So this is what happened in the first iteration when we uncovered the 8. It's different than what happened in the last iteration when we uncovered the 2. Okay, so this case, this third iteration is going to be more similar to the first iteration than the second iteration. In particular, we won't need to swap, we won't need to advance I, we just advance j and we're done. So let's see why that's true. So we've advanced j, we've done one more iteration, so now the stuff that we haven't seen yet is only the last 4 elements. So who knows what's up with the stuff we haven't seen yet. But if you look at the stuff we have seen, the 2, the 8, and the 5, this is in fact partitioned, right? All the numbers that are bigger than 3 succeed, come after all the numbers bigger than, smaller than 3. So the j, the boundary between what we've seen and what we haven't, is between the 5 and the 1. And the I, the boundary between the stuff less than the pivot and bigger than the pivot, is between the 2 and the 8, just like it was before. Adding a 5 to the end didn't change anything. So let's wrap up this example on the next slide. So first, let's just remember where we left off on the previous slide. So I'm just going to redraw that same step after 3 iterations of the algorithm. And now notice in the next iteration we're going to again have to make some modifications to the array if we want to preserve our invariant. The reason is that when we advance j, when we scan this 1, now again we're scanning in a new element which is less than the pivot. And what that means is that the partitioned region, or the region that we've looked at so far, will not be partitioned. We'll have 2, 8, 5, 1. Remember, we need everything less than 3 to precede everything bigger than 3, and this 1 at the end is not going to cut it. So we're going to have to make a swap. Now, what are we going to swap? We're going to swap the 1 and the 8. So why do we swap the 1 and the 8? Well, clearly we have to swap the 1 with something. And what makes sense? What makes sense is the leftmost array entry, which is currently bigger than the pivot, and that's exactly the 8. Okay, that's the first leftmost entry bigger than 3, so if we swap the 1 with it, then the 1 will become the rightmost entry smaller than 3. So after the swap, we're going to have the following array. The stuff we haven't seen is the 4, the 7, and the 6. So the j will be between the 8 and the 4. The stuff we have seen is the 2, 1, 5, and 8. And notice that this is indeed partitioned. All the elements which are less than 3, the 2 and the 1, precede all of the entries which are bigger than 3, the 5 and the 8. I, remember, is supposed to split, be the boundary between those less than 3 and those bigger than 3, so that's going to lie between the 1 and the 5. That is 1 further to the right than it was in the previous iteration. Okay, so because the rest of the unseen elements, the 4, the 7, and the 6, are all bigger than the pivot, the last 3 iterations are easy. No further swaps are necessary. No increments to I are necessary. J is just going to get incremented until we fall off the array, and then fast forwarding, the partition subroutine, or this main linear scan, will terminate with the following situation. So at this point, all of the elements have been seen, and all the elements are partitioned. J, in effect, has fallen off the end of the array, and I, the boundary between those less than and bigger than the pivot, still lies between the 1 and the 5. Now, we're not quite done because the pivot element 3 is not in the correct place. Remember, what we're aiming for is an array where everything less than the pivot is to the left of it, and everything bigger than the pivot is to the right, but right now the pivot still is hanging out in the first element. So we just have to swap that into the correct place. Where's the correct place? Well, it's going to be the rightmost element, which is smaller than the pivot. So in this case, the 1. So the subroutine will terminate with the following array: 1, 2, 3, 5, 8, 4, 7, 6. And indeed, as desired, everything to the left of the pivot is less than the pivot, and everything to the right of the pivot is bigger than the pivot. The 1 and 2 happen to be in sorted order, but that was just sort of an accident. And the 4, 5, 6, and 7, and 8, you'll notice, are jumbled up. They're not in sorted order. So hopefully from this example you have a gist of how the partition subroutine is going to work in general. But just to make sure the details are clear, let me now describe the pseudocode for the partition subroutine. So the way I'm going to denote it is there's going to be an input array A, but rather than being told some explicit link, what's going to be passed to the subroutine are 2 array indices. The leftmost index, which delineates this part of the subarray you're supposed to work on, and the rightmost index. The reason I'm writing it this way is because partition is going to be called recursively from within a quicksort algorithm. So at any point in quicksort, we're going to be recursing on some subset, contiguous subset of the original input array. L and R are meant to denote what the left boundary and the right boundary of that subarray are. So let's not lose sight of the high-level picture of the invariant that the algorithm is meant to maintain. So as we discussed, we're assuming the pivot element is the first element, although that's really without loss of generality. And in a given time, there's going to be stuff we haven't seen yet. Who knows what's up with that? And amongst the stuff we've seen, we're going to maintain the invariant that all the stuff less than the pivot comes before all the stuff bigger than the pivot. And J and I denote the boundaries between the seen and the unseen, and between the small elements and the large elements, respectively. So back to the pseudocode, we initialize the pivot to be the first entry in the array. And again, remember, L denotes the leftmost index that we're responsible for looking at. The initial value of I should be just to the right of the pivot, so that's going to be L plus 1. That's also the initial value of J, which we'll assign in the main for loop. So this for loop with J taking on all values from L plus 1 to the rightmost index R denotes the linear scan through the input array. And what we saw in the example is that there were 2 cases, depending on, for the newly seen element, whether it's bigger than the pivot or less than the pivot. The easy case is when it's bigger than the pivot. Then we essentially don't have to do anything. Remember, we didn't do any swaps, we didn't change I, the boundary didn't change. It was when the new element was less than the pivot that we had to do some work. So we're going to check that. Is the newly seen element, a J, less than P? And if it's not, we actually don't have to do anything. So let me just put as a comment, if the new element is bigger than the pivot, we do nothing. Of course, at the end of the for loop, the value of J will get incremented. So that's the only thing that changes from iteration to iteration when we're sucking up new elements that happen to be bigger than P. So what did we do in the example when we suck up a new element less than P? Well, we have to do 2 things. So in the event that the newly seen element is less than P, I'll circle that here in pink, we need to do a rearrangement, so we again have a partitioned subarray amongst those elements we've seen so far. And the best way to do that is to swap this new element with the leftmost element that's bigger than the pivot. And because we have an index I, which is keeping track of the boundary between the elements less than the pivot and bigger than the pivot, we can immediately access the leftmost element bigger than the pivot. That's just the ith array index of that's just the ith entry in the array. Now I am doing something a little sneaky here, I should be honest about, which is there is the case where you haven't yet seen any elements bigger than the pivot. and then you don't actually have a leftmost element bigger than the pivot to swap with. Turns out this code still works. I'll let you verify that, but it does do some redundant swaps. Really, you don't need to do any swaps until you first see some elements bigger than the pivot and then see some elements less than the pivot. So you can imagine a different implementation of this where you actually keep track of whether or not that's happened to avoid the redundant swaps. I'm just going to give you the simple pseudocode. And again, for intuition, you want to think about the case just like in the picture here in blue, where we've already seen some elements that are bigger than the pivot, and the next newly seen element is less than the pivot. That's really sort of the key case here. Now, the other thing we have to do after one of these swaps is now the boundary between where the pivot elements, where the array elements less than the pivot and those bigger than the pivot has moved. It's moved one to the right, so we have to increment I. So that's the main linear scan. Once this concludes, J will have fallen off the end of the array, and everything that we've seen, the final elements except for the pivot, will be arranged so that those less than P are first, those bigger than P will be last. The final thing we have to do is just swap the pivot into its rightful position, and recall for that we just swap it with the rightmost element less than it. So that is it. That is the partition subroutine. There's a number of variants of partition. This is certainly not the unique implementation. If you look on the web or if you look in certain textbooks, you'll find some other implementations as well as discussion of the various merits. But I hope this gives you, this is a canonical implementation, and I hope it gives you a clear picture of how you rearrange the array using in-place swaps to get the desired property, that all the stuff before the pivot comes first, all the stuff after the pivot comes last. Let me just add a few details about why this pseudocode I just gave you does indeed have the properties required. The running time is O of n, really theta of n, but again I'll be sloppy and write big O of n, where n is the number of array elements that we have to look at. So n is r minus l plus 1, which is the length of the subarray that this partition subroutine is invoked upon. And why is this true? Well, if you just go inspect the pseudocode, you can just count it up naively, and you'll find that this is true. We just do a linear scan through the array, and all we do is basically a comparison and possibly a swap and an increment for each array entry that we see. Also, if you inspect the code, it is evident that it works in place. We do not allocate some second copy of an array to populate like we did in the naive partitioning subroutine. All we do is repeated swaps. Correctness of the subroutine follows by induction. So in particular, the best way to argue it is via an invariant. So I'll state the invariant here, but mostly leave it for you to check that indeed every iteration of the for loop maintains this invariant. So first of all of the stuff to the right of the pivot element, to the right of the leftmost entry, and up to the index I is indeed less than the pivot element, as suggested by the picture. And also suggested by the picture, everything beginning with the ith entry leading just up before the jth entry is bigger than the pivot. And I'll leave it as a good exercise for you to check that this holds by induction. The invariant holds initially when both I and j are equal to L plus 1 because both of these sets are vacuous. Okay, so there are no such elements, so they're trivially satisfy these properties. And then every time we advance j, well, in one case it's very easy, where the new element is bigger than the pivot. It's clear that if the invariant held before, it also holds it at the next iteration. And then if you think about it carefully, this swap and this increment of I that we do in the case where the new element is less than the pivot, after the swap, once the for loop completes, again, if this invariant was true at the beginning of it, it's also true at the end. So what good is that? Well, if by this claim, at the conclusion of the linear scan, at which point j has fallen off the end of the array must look like this. At the end of the for loop, the question mark part of the array has vanished, so everything other than the pivot has been organized so that all of the stuff less than the pivot comes before everything after the pivot. And that means once you do the final swap, once you swap the pivot element from the leftmost entry with the rightmost entry less than the pivot, you're done. Okay, you've got the desired property that everything to the left of the pivot is less than it, everything to the right of the pivot is bigger than it. So now that given a pivot element, we understand how to very quickly rearrange the array so that it's partitioned around that pivot element. Let's move on to understanding how that pivot element should be chosen and how, given suitable choices of that pivot element, we can implement the quicksort algorithm to run very quickly, in particular on average in n log n time. We've discussed a number of divide and conquer algorithms, and so far I've been giving short shrift to proofs of correctness. This has been a conscious decision on my part. Coming up with the right divide and conquer algorithm for a problem can definitely be difficult, but once you have that eureka moment and you figure out the right algorithm, you tend to also have a good understanding of why it's correct, why it actually solves the problem at every possible input. Similarly, when I present to you a divide and conquer algorithm, like say merge sort or quicksort, I expect that many of you have a good and accurate intuition about why the algorithm is correct. In contrast, the running time of these divide and conquer algorithms is often highly non-obvious. So correctness proofs for divide and conquer algorithms tend to simply formalize the intuition that you have via a proof by induction. That's why I haven't been spending much time on them. But nevertheless, I do feel like I owe you at least one rigorous correctness proof for a divide and conquer algorithm, and we may as well do it for quicksort. So in this optional video, we'll briefly review proofs by induction, and then we'll show how such a proof can be used to rigorously establish the correctness of quicksort. The correctness proofs for most of the other divide and conquer algorithms that we discuss can be formalized in a similar way. So let's begin by reviewing the format for proofs by induction. So the canonical type of proof by induction, and the kind that we'll be using here, is when you want to establish an assertion for all of the positive integers n. So note some assertion which is parameterized by n, where n is a positive integer. I know this is a little abstract, so let me just be concrete about the assertion we actually care about for quicksort. So for us, the assertion P of n is the statement that quicksort is always correct on inputs of length n, arrays that have n elements. So an induction proof has two parts. The first part is a base case, and the second part is an inductive step. For the base case, you have to get started, so you show that at the very least, your assertion is true when n equals 1. This is often a trivial matter, and that'll be the case when we establish the correctness of quicksort, just on arrays with only one element. So the non-trivial part of a proof by induction is usually the inductive step. And in the inductive step, you look at a value of n not covered by the base case, so a value of n bigger than 1, and you show that if the assertion holds for all smaller values, small integers, then it also holds for the integer n. That is, you show that for every positive integer n that's 2 or greater, you assume that p of k holds for all k strictly less than n, and under that assumption, which is called the inductive hypothesis, under the assumption that p of k holds for all k strictly less than n, you then establish that p of n holds as well. So if you manage to complete both of these steps, if you prove both the base case that p of 1 holds, you argue that directly, and then also you argue that assuming the inductive hypothesis that the assertion holds for all smaller integers, it also holds for an arbitrary integer n, then you're done. Then in fact, you have proven that the assertion p of n holds for every single positive integer n. Right? So for any given n that you care about, the way you can derive that from 1 and 2 is you just start from the base case, p of 1 holds, then you apply the inductive step n minus 1 times, and boom, you've got it. So you know that p holds for the integer n that you care about as well. And that's true for arbitrarily large values of n. So those are proofs by induction in general. Now let's instantiate this proof format, this type of proof, for establishing the correctness of quicksort. So let me write again what is the assertion we care about. Our definition of p of n is going to be that quicksort is always correct on arrays of length n. And of course, what we want to prove is that Quicksort is correct no matter what size array that you give it. That is, we want to prove that P of n holds for every single n at least 1. So this is right in the wheelhouse of proofs by induction. Okay? So that's how we're going to establish it. Now, depending on the order in which you're watching the videos, you may or may not have seen our discussion about how you actually choose the pivot. Recall that the first thing Quicksort does is choose a pivot, then it partitions the array around a pivot. So we're going to establish the correctness of Quicksort no matter how the choose pivot subroutine gets implemented. Okay, so no matter how you choose pivots, you'll always have correctness. As we'll see in a different video, the choice of pivots definitely has an influence on the running time of Quicksort, but the correctness of Quicksort is no matter how you choose the pivot. So let's proceed by a proof by induction. So for the base case, when n equals 1, this is a fairly trivial statement. Right? So then we're just talking about inputs that have only one element. Every such array is already sorted. Quicksort when n equals 1 just returns the input array. It doesn't do anything, and that is indeed a sorted array that it returns. So by this rather trivial argument, we have directly proven that P of 1 holds. We've proven the rather unimpressive statement that Quicksort always correctly sorts one element arrays. Okay, no big deal. So let's move on to the inductive step. So in the inductive step, we have to fix an arbitrary value of n that's at least 2, a value of n not covered by the base case. So let's fix some value of n, at least 2. Now, what are we trying to prove? We're trying to prove that Quicksort always correctly sorts every input array of length n, so we also have to fix an arbitrary such input. So let's make sure we're all clear on what it is we need to show. What are you showing in an inductive step? Assuming that P of k holds for all smaller values, all smaller integers, then P of n holds as well. And remember, this is the inductive hypothesis. So in the context of Quicksort, we're assuming that Quicksort never makes a mistake on any input array that has length strictly smaller than n. And now we just have to show it never makes a mistake on input arrays that have size exactly n. So this is the point in the proof where we actually delve into how Quicksort is implemented to argue correctness. So recall what the first step of Quicksort is. It picks some pivot arbitrarily. We don't know how. We don't care how. And then it partitions the array around this pivot element P. Now, as we argued in the video where we discussed the partition subroutine, at the conclusion of that subroutine, the array has been rearranged into the following format. The pivot is wherever it is. Everything to the left of the pivot is less than the pivot, and everything bigger than the pivot is greater than the pivot. Right? This is how things stand at the conclusion of the partitioning subroutine. So let's call the stuff less than the pivot the first part of the partitioned array, and the stuff bigger than the pivot the second part of the partitioned array. And recall our observation from the overview video that the pivot winds up in its correct position. Right? Where would the pivot be? Where is any element supposed to be in the final sorted array? Well, it's supposed to be to the right of everything less than it and to the left of everything bigger than it. And that's exactly where this partitioning subroutine deposits the pivot element P. So now to imply the inductive hypothesis, which you'll recall is a hypothesis about how Quicksort operates on smaller subarrays, let's call the length of the first part and the second part of the partitioned array K1 and K2, respectively. Now, crucially, both K1 and K2 are strictly less than n. Both of these two parts have length strictly less than that of the given input array A. That's because the pivot, in particular, is excluded from both of those two parts, so they can have at most n-1 elements. That means we can apply the inductive hypothesis, which says that the Quicksort never makes a mistake on an array that has size strictly less than n. That implies that our two recursive calls to Quicksort, the one to the first part and the one to the second part, don't make mistakes. They're guaranteed to sort those subarrays correctly by the inductive hypothesis. And to be very precise, what we're using to argue that the recursive calls are correct are P of K1 and P of K2, where P is the assertion that Quicksort is always correct on arrays of length K1 and K2. And we know that both of these statements are true because K1 and K2 are both less than n, and because of the inductive hypothesis. So what's the upshot? The upshot is Quicksort's going to be correct. All right, so the first recursive call puts all of the elements that are less than the pivot in the correct relative order. Next comes the pivot, which is bigger than all of that stuff in the first part and less than all of the stuff in the second part. And then the second recursive call correctly orders all of the elements in the second part. So with those three things pasted together, we have a sorted version of the input array. And since this array was an arbitrary one of length n, that establishes the assertion P of n. And since n was arbitrary, that establishes the inductive step and completes the proof of correctness of Quicksort for an arbitrary method of choosing the pivot element. So let's review the story so far. We've been discussing the Quicksort algorithm. Here again is its high-level description. So Quicksort, you call two subroutines first, and then you make two recursive calls. So the first subroutine, choose pivot, we haven't discussed yet at all. That'll be one of the main topics of this video. But the job of the choose pivot subroutine is to somehow select one of the n elements in the input array to act as a pivot element. Now, what does it mean to be a pivot? Well, that comes into play in the second subroutine, the partition subroutine, which we did discuss quite a bit in a previous video. So what partition does is it rearranges the elements in the input array so that it has the following property, so that the pivot P winds up in its rightful position. That is, it's to the right of all of the elements less than it, and it's to the left of all of the elements bigger than it. The stuff less than it's to the left in some jumbled order. The stuff bigger than it's to the right in some jumbled order. That's what's listed here as the first part and the second part of the partitioned array. Now, once you've done this partitioning, you're good to go. You just recursively solve, you recursively sort the first part to get them in the right order. You call Quicksort again to recursively sort the right part, and bingo, the entire array is sorted. You don't need a combined step. You don't need a merge step. Moreover, recall in a previous video, we saw that the partition array can be implemented in linear time, and moreover, it works in place with essentially no additional storage. We also, in an optional video, formally proved the correctness of Quicksort, and remember, Quicksort is independent of how you implement the choose pivot subroutine. So what we're going to do now is discuss the running time of the Quicksort algorithm, and this is where the choice of the pivot is very important. So what everybody should be wondering about at this point is Quicksort a good algorithm? Does it run fast? The bar is pretty high. We already have merge sort, which is a very excellent practical n log n algorithm. The key point to realize at this juncture is that we are not currently in a position to discuss the running time of the Quicksort algorithm. The reason is we do not have enough information. The running time of Quicksort depends crucially on how you choose the pivot. It depends crucially on the quality of the pivot chosen. You'd be right to wonder what I mean by a pivot's quality, and basically what I mean is a pivot is good if it splits the partitioned array into roughly two equal sized subproblems, and it's bad, it's of low quality if we get very unbalanced subproblems. So to understand both what I mean and the ramifications of having good quality and bad quality pivots, let's walk through a couple of quiz questions. This first quiz question is meant to explore a sort of worst-case execution of the Quicksort algorithm. What happens when you choose pivots that are very poorly suited for the particular input array? Let me be more specific. Suppose we use the most naive choose pivot implementation, like we were discussing in the partition video. So remember here we just pluck out the first element of the array and we use that as the pivot. So suppose that's how we implement the choose pivot subroutine, and moreover, suppose that the input array to Quicksort is an array that's already in sorted order. So for example, if it just had the numbers 1 through 8, it would be 1, 2, 3, 4, 5, 6, 7, 8 in order. My question for you is, what is the running time of this recursive Quicksort algorithm on an already sorted array if we always use the first element of a subarray as the pivot? Okay, so this is a slightly tricky, but actually a very important question. So the answer is the fourth one. So it turns out that Quicksort, if you pass it an already sorted array and you're using the first element as pivot elements, it runs in quadratic time. And remember, for a sorting algorithm, quadratic is bad. It's bad in the sense that we can do better. Merge sort runs in time n log n, which is much better than n squared. And if we were happy with an n squared running time, we wouldn't have to resort to these sort of relatively exotic sorting algorithms. We could just use insertion sort, and we'd be fine. We'd get that same quadratic running time. Okay, so now I owe you an explanation. Why is it that Quicksort can actually run in quadratic time in this unlucky case of being passed a already sorted input array? Well, to understand, let's think about what pivot gets chosen and what are the ramifications of that pivot choice for how the array gets partitioned, and then what the recursion looks like. So let's just think of the array as being the numbers 1 through n in sorted order. What is going to be our pivot? Well, by definition, we're choosing the first element of the pivot, so the pivot is just going to be 1. Now we're going to invoke the partition subroutine, and if you go back to the pseudocode of the partition subroutine, you'll notice that if we pass it an already sorted array, it's going to do essentially nothing. Okay, so it's just going to advance the index j until it falls off the end of the array, and it's just going to return back to us the same array that it was passed as input. So partition subroutine, if given an already sorted array, returns an already sorted array. Okay, so we have just the pivot 1 in the first position, and then the numbers 2 through n in order in the remainder of the positions. So if we draw our usual picture of what a partitioned array looks like, with everything less than the pivot to the left, everything bigger than the pivot to the right, well, since nothing is less than the pivot, this stuff is going to be empty. This will not exist. And to the right of the pivot, this will have length n minus 1, and moreover, it will still be sorted. So once partition completes, we go back to the outer call of Quicksort, which then calls itself recursively twice. Now, in this case, one of the recursive calls is just vacuous. There's just an empty array. There's nothing to do. So really, there's only one recursive call, and that happens on a problem of size only 1 less. So this is about the most unbalanced split we could possibly see, right? Where one side has 0 elements, one side has n minus 1. Splits don't really get any worse than that. And this is going to keep happening over and over and over again. We're going to recurse on the numbers 2 through n. We're going to choose the first element, the 2, as the pivot. Again, we'll feed it to partition. We'll get back the exact same subarray that we handed it in. We get through the numbers 2 through n in sorted order. We exclude the pivot 2. We recurse on the numbers 3 through n, a subarray of length n minus 2. The next recursion level, we recurse on an array of size of length n minus 3, then n minus 4, then n minus 5, and so on, until finally, after at a recursion depth of n, roughly, we get down to just the last element, n. The base case kicks in, and we return that, and Quicksort completes. So that's how Quicksort is going to execute on this particular input with these particular pivot choices. So what running time does that give to us? Well, the first observation is that, in each recursive call, we do have to invoke the partition subroutine. And the partition subroutine does look at every element in the array it is passed as input. So if we pass partition an array of length k, it's going to do at least k operations, because it looks at each element at least once. So the runtime is going to be bounded below by the work we do in the outermost call, which is on an array of length n, plus the amount we do in the second level of recursion, which is on a subarray of length n minus 1, plus n minus 2, plus blah, 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 all the way down to plus 1 for the very last level of recursion. So this is a lower bound on our running time, and this is already theta of n squared. So one easy way to see why this sum n plus n minus 1 plus etc. leads to a bound of n squared is to just focus on the first half of the terms. So the first n over 2 terms in the sum are all of magnitude at least n over 2. So the sum is at least n squared over 4. It's also evident that this sum is at most n squared. So overall, the running time of Quicksort on this bad input is going to be quadratic. Now, having understood what the worst case performance of the Quicksort algorithm is, let's move on to discuss its best case running time. Now, we don't generally care about the best case performance of algorithms for its own sake. The reason that we want to think about Quicksort in the best case, first of all, it'll give us better intuition for how the algorithm works. Second of all, it'll draw a line in the sand. Its average case running time certainly can't be better than the best case, so this will give us a target for what we're shooting for in our subsequent mathematical analysis. So what was the best case? What is the highest quality pivot we could hope for? Well, again, we think of the quality of a pivot as the amount of balance that it provides between the two subproblems. So ideally, we'd choose a pivot which gave us two subproblems, both of size n over 2 or less. And there's a name for the element that would give us that perfectly balanced split. It's the median element of the array. Okay, the element where exactly half of the elements are less than it and half of the elements are bigger than it. That would give us a essentially perfect 50-50 split of the input array. So here's the question. Suppose we had some input and we ran Quicksort and everything just worked out in our favor magically in the best possible way. That is, in every single recursive invocation of Quicksort on any subarray of the original input array, suppose we happen to get as our pivot the median element. That is, suppose in every single recursive call we wind up getting a perfect 50-50 split of the input array before we recurse. This question asks you to analyze the running time of this algorithm in this magical best case scenario. So the answer to this question is the third option. The answer is it runs in n log n time. Why is that? Well, the reason is that then the recurrence which governs the running time of Quicksort exactly matches the recurrence that governs the merge sort running time, which we already know is n log n. That is, the running time Quicksort requires in this magical special case on an array of length n. Well, as usual, you have a recurrence in two parts. There's the work that gets done by the recursive calls, and there's the work that gets done now. Now, by assumption, we wind up picking the median as the pivot. So there's going to be two recursive calls, each of which will be on an input of size at most n over 2. And we can write this. This is because the pivot equals the median. So this is not true for Quicksort in general. It's only true in this magical case where the pivot is the median. So that's what gets done by the two recursive calls. And then how much work do we do outside of the recursive calls? Well, we have to do the choose pivot subroutine. And I guess strictly speaking, I haven't said how that was implemented. But let's assume that choose pivot does only a linear amount of work. And then as we've seen, the partition subroutine only does a linear amount of work as well. So let's say O of n for work outside of the recursive calls. And what do we know? We know this implies, say by using the master method or just by using the exact same argument as for merge sort, this gives us a running time bound of n log n. And then again, something I haven't really been emphasizing, but which is true, is that actually we can write theta of n log n. And that's because in the recurrence, in fact, we know that the work done outside of the recursive calls is exactly theta of n. Okay, partition needs really linear time, not just big O of n time. In fact, the work done outside of the recursive calls is theta of n. That's because the partition subroutine does indeed look at every entry in the array that it passed. And as a result, we didn't really discuss this so much in the master method, but as I mentioned in passing, if you have recurrences which are tight in this sense, then the result of the master method can also be strengthened to be theta instead of just big O. But those are just some extra details. The upshot of this quiz is that even in the best case, even if we magically get perfect pivots throughout the entire trajectory of Quicksort, the best we can hope for is an n log n upper bound. It's not going to get any better than that. So the question is, how do we have a principled way of choosing pivots so that we get this best case, or something like it, this best case n log n running time? So that's what the problem that we have to solve next. So the last couple of quizzes have identified a super important question as far as the implementation of Quicksort, which is how are we going to choose these pivots? Right? We now know that they have a big influence on the running time of our algorithm. It could be as bad as n squared or as good as n log n, and we really want to be on the n log n side. So the key question, how to choose pivots. And Quicksort is the first killer application we're going to see of the idea of randomized algorithms. That is, allowing your algorithms to flip coins in the code so that you get some kind of good performance on average. So the big idea is random pivots. By which I mean, for every time we recursively call Quicksort and we are passed some subarray of length k, among the k candidate pivot elements in the subarray, we're going to choose each one with equally likely, with probability 1 over k. And we're going to make a new random choice every time we have a recursive call, and then we're just going to see how the algorithm does. So this is our first example of a randomized algorithm. This is an algorithm where if you feed it exactly the same input, it will actually run differently on different executions. And that's because there's randomness internal to the code of the algorithm. Now, it's not necessarily intuitive that randomization should have any purpose in computation, in software design and algorithm design. But in fact, and this has been sort of one of the real breakthroughs in algorithm design, mostly in the 70s, realizing how important this is, that the use of randomization can make algorithms more elegant, simpler, easier to code, more faster, or just simply you can solve problems that you could not solve, or at least not solve as easily without the use of randomization. So it's really one thing that should be in your toolbox as an algorithm designer, randomization. Quicksort will be the first killer application, but we'll see a couple more later in the course. Now, by the end of this sequence of videos, I'll have given you a complete, rigorous argument about why this works. Why with random pivots, Quicksort always runs very quickly on average. But before moving into anything too formal, let's develop a little bit of intuition, or at least kind of a daydream about why on earth could this possibly work? Why on earth could this possibly be a good idea to have randomness internal to our Quicksort implementation? Well, so first, just very high level, what would be sort of the hope or the dream? The hope would be, random pivots are not going to be perfect. I mean, you're not going to just sort of guess the median, or you only have a 1 in n chance of figuring out which one the median is. But the hope is that most choices of a pivot will be good enough. So that's pretty fuzzy. Let's drill down a little bit and develop this intuition further. Let me describe it in 2 steps. The first claim is that, in our last quiz, we said, suppose we get lucky and we always pick the median in every single recursive call. And we observed we'd do great. We get n log n running time. So now let's observe that actually, to get the n log n running time, it's not important that we magically get the median every single recursive call. If we get any kind of reasonable pivot, by which a pivot that gives us some kind of approximately balanced split of the problems, again, we're going to be good. Okay, so the last quiz really wasn't particular to getting the exact median. Near medians are also fine. To be concrete, suppose we always pick a pivot which guarantees us a split of 25, 75, or better. That is, both recursive calls should be called on arrays of size at most 75% of the one that we started with. So precisely, if we always get a 25, 75 split or better in every recursive call, I claim that the running time of Quicksort in that event will be big O of n log n, just like it was in the last quiz where we were actually assuming something much stronger, that we were getting the median. Now, this is not so obvious, the fact that 25-75 splits guarantee n log n running time. For those of you that are feeling keen, you might want to try to prove this. You can prove this using a recursion tree argument, but because you don't have balanced subproblems, you have to work a little bit harder than you do in the cases covered by the master method. So that's the first part of the intuition, and this is what we mean by a pivot being good enough. If we get a 25-75 split or better, we're good to go. We get our target n log n running time. So the second part of the intuition is to realize that actually we don't have to get all that lucky to just be getting a 25-75 split. That's actually a pretty modest goal, and even this modest goal is enough to get the n log n running time. Right, so suppose our array contains the numbers, the integers between 1 and 100, so it's an array of length 100. Think for a second, which of those elements is going to give us a split that's 25-75 or better? So if we pick any element between 26 and 75, inclusive, will be totally good, right? If we pick something that's at least 26, that means the left subproblem is going to have at least the elements 1 through 25. That'll have at least 25% of the elements. And if we pick something less than 75, then the right subproblem will have all of the elements 76 through 100 after we partition. So that'll also have at least 25% of the elements. So anything between 26 and 75 gives us a 75-25 split or better. But that's a full half of the elements. So it's as good as just flipping a fair coin and hoping we get heads. So with 50% probability, we get a split good enough to get this n log n bound. And so again, the high-level hope is that often enough, half of the time, we get these, good enough splits, 25-75 splits or better. So that would seem to suggest an n log n running time on average is a legitimate hope. So that's the high-level intuition, but if I were you, I would certainly not be content with this somewhat hand-wavy explanation that I've given you so far. What I've told you is sort of the hope, the dream, why there is at least a chance this might work. But the question remains, and I would encourage such skepticism, which is, does this really work? And to answer that, we're going to have to do some actual mathematical analysis, and that's what I'm going to show you. I'm going to show you a complete, rigorous analysis of the Quicksort algorithm with random pivots, and we'll show that yes, in fact, it does really work. And this highlights what's going to be a recurring theme in this course, and a recurring theme just in the study and understanding of algorithms, which is it's quite often there's some fundamental problem when you're trying to code up a solution, and you come up with a novel idea. It might be brilliant, and it might suck, and you have no idea. Now, obviously, you can code up the idea, run it on some concrete instances, and get a feel for whether it seems like a good idea or not. But if you really want to know fundamentally what makes the idea good or what makes the idea bad, really you need to turn to mathematical analysis to give you a complete explanation. And that's exactly what we're going to do with Quicksort, and it will explain in a very deep way why it works so well. Specifically, in the next sequence of 3 videos, I'm going to show you an analysis, a proof of the following theorem about Quicksort. So under no assumptions about the data, that is, for every input array of a given length, say n, the average running time of Quicksort implemented with random pivots is big O of n log n. And again, in fact, it's theta of n log n, but we'll just focus on the big O of n log n part. So this is a very, very cool theorem about this randomized quicksort algorithm. One thing I want to be clear so that you don't undersell this guarantee in your own mind, this is a worst case guarantee with respect to the input. Okay, so notice at the beginning of this theorem, what do we say? For every input array of length n. All right, so we have absolutely no assumptions about the data. This is a totally general purpose sorting subroutine, which you can use whenever you want, even if you have no idea where the data is coming from. And these guarantees are still going to be true. This, of course, is something I held forth about at some length back in our guiding principles video. When I argued that, if you can get away with it, what you really want is general purpose algorithms which make no data assumptions so they can be used over and over again in all kinds of different contexts, and that still have great guarantees. And Quicksort is one of those. So basically, if you have a data set and it fits in the main memory of your machine, again, sorting is a for-free subroutine. In particular, Quicksort, the Quicksort implementation is for free. So this just runs so blazingly fast. Doesn't matter what the array is. Maybe you don't even know why you want to sort it. But go ahead. Why not? Maybe it'll make your life easier, like it did, for example, in the closest pair algorithm, for those of you that watch those 2 optional videos. Now, the word average does appear in this theorem, and as I've been harping on, this average is not over any assumptions on the data. We're certainly not assuming that the input array is random in any sense. The input array can be anything. So where is the averaging coming from? The averaging is coming only from randomness, which is internal to our algorithm. Randomness that we put in the code ourselves, that we're responsible for. So remember, randomized algorithms have the interesting property that even if you run it on the same input over and over again, you're going to get different executions. So the running time of a randomized algorithm can vary as you run it on the same input over and over again. The quizzes have taught us that the running time of Quicksort on a given input fluctuates from anywhere between the best case of n log n to the worst case of n squared. So what this theorem is telling us is that for every possible input array, while the running time does indeed fluctuate between an upper bound of n squared and a lower bound of n log n, the best case is dominating. On average, it's n log n. On average, it's almost as good as the best case. That's what's so amazing about Quicksort. The n squared that can pop up once in a while doesn't matter. You're never going to see it. You're always going to see this n log n-like behavior in randomized Quicksort. So for some of you, I'll see you next in a video on probability review. That's optional. For the rest of you, I'll see you in the analysis of this theorem. So this is the first video of 3 in which we'll mathematically analyze the running time of the randomized implementation of Quicksort. So in particular, we're going to prove that the average running time of Quicksort is big O of n log n. Now, this is the first randomized algorithm that we've seen in the course, and therefore, in its analysis, will be the first time that we're going to need any kind of probability theory. So let me just explain up front what I might expect you to know in the following analysis. Basically, I need you to know the first few ingredients of discrete probability theory. So I need you to know about sample spaces, that is how to model all of the different things that could happen, all of the ways that random choices could resolve themselves. I need you to know about random variables, functions on sample spaces which take on real values. I need you to know about expectations, that is average values of random variables. And very simple but very key property we're going to need in the analysis of Quicksort is linearity of expectation. So if you haven't seen this before, or if you're too rusty, definitely you should review this stuff before you watch this video. Some places you can go to get that necessary review. You can look at the probability review part 1 video that's up on the course's website. If you prefer to read something, like I said at the beginning of the course, I recommend the free online lecture notes by Eric Lehman and Tom Layton, Mathematics for Computer Science. That covers everything we'll need to know, plus much, much more. There's also a wiki book on discrete probability, which is a perfectly fine, obviously free source in which you can learn the necessary material. Okay, so after you've got that sort of fresh in your mind, then you're ready to watch the rest of this video, and in particular, we're ready to prove the following theorem stated in the previous video. So the quicksort algorithm with a randomized implementation, that is where in every single recursive subcall you pick a pivot uniformly at random, we stated the following assertion, that for every single input, so for a worst case input array of length n, the average running time of quicksort with random pivots is O of n log n. And again, to be clear where the randomness is not in the data. We make no assumptions about the data as per our guiding principles. No matter what the input array is, averaging only over the randomness in our own code, the randomness internal to the algorithm, we get a running time of n log n. We saw in the past that the best case behavior of quicksort is n log n. Its worst case behavior is n squared. So this theorem is asserting that no matter what the input array is, the typical behavior of quicksort is far closer to the best case behavior than it is to the worst case behavior. Okay, so that's what we're going to prove in the next few videos. So let's go ahead and get started. So first I'm going to set up the necessary notation and be clear about exactly what is the sample space, what is the random variable that we care about, and so on. So we're going to fix an arbitrary array of length n. That's going to be the input to the quicksort algorithm. And we'll be working with this fixed but arbitrary input array for the remainder of the analysis. Okay, so just fix a single input in your mind. Now, what's the relevant sample space? Well, recall what a sample space is. It's just all the possible outcomes of the randomness in the world. So it's all the distinct things that could happen. Now, here, the randomness is of our own devising. It's just the random pivot sequences, the random pivots chosen by Quicksort. So omega is just the set of all possible random pivots that Quicksort could choose. Now, the whole point of this theorem, proving that the average running time of Quicksort is small, boils down to computing the expectation of a single random variable. So here's the random variable we're going to care about. For a given pivot sequence, remember that random variables are real-valued functions defined on the sample space. So for a given point in the sample space, or pivot sequence sigma, we're going to define capital C of sigma as the number of comparisons that Quicksort makes. Where by a comparison, I don't mean something like with an array index in a for loop. That's not what I mean by a comparison. I mean a comparison between two different entries of the input array, like comparing the third entry in the array against the seventh entry in the array to see whether the third entry or the seventh entry is smaller. Notice that this is indeed a random variable that is given knowledge of the pivot sequence sigma, the choices of all pivots. You can think of Quicksort at that point as just a deterministic algorithm with all of the pivot choices predetermined. And so a deterministic version of Quicksort makes some deterministic number of comparisons. So for a given pivot sequence sigma, we're just calling C of sigma to be however many comparisons it makes, given those choices of pivots. Now, what the theorem I stated is not about the number of comparisons of Quicksort, but rather about the running time of Quicksort. But really, if you think about it, kind of the only real work that the Quicksort algorithm does is make comparisons between pairs of elements in the input array. Yes, there's a little bit of other bookkeeping, but that's all noise. That's all second-order stuff. All Quicksort really does is comparisons between the pairs of elements in the input array. And if you want to know what I mean by that a little more formally, dominated by comparisons, I mean that there exists a constant C so that the total number of operations of any type that Quicksort executes is at most a constant factor larger than the number of comparisons. So let's say that by RT, I mean the number of primitive operations of any form that Quicksort uses, and for every pivot sequence sigma, the total number of operations is no more than a constant times the total number of comparisons. And if you want a proof of this, it's not that interesting, so I'm not going to talk about it here, but in the notes posted on the website, there is a sketch of why this is true, how you can formally argue that there isn't much work beyond just the comparisons. But I hope most of you find that to be pretty intuitive. So, given that the running time of Quicksort boils down just to the number of comparisons, we want to prove the average running time is n log n, all we got to do, quote unquote, all we have to do is prove that the average number of comparisons the Quicksort makes is O of n log n. And that's what we're going to do. So that's what the rest of these lectures are about. So that's what we got to prove. We got to prove that the expectation of this random variable c, which counts up the number of comparisons Quicksort makes, is for this arbitrary input array A of length n, bounded by big O of n log n. So the high order bit of this lecture is a decomposition principle. We've identified this random variable c, the number of comparisons, and it's exactly what we care about. It governs the average running time of Quicksort. The problem is it's quite complicated. It's very hard to understand what this capital C is. It's fluctuating between n log n and n squared, and it's hard to know how to get a handle on it. So how are we going to go about proving this assertion that the expected number of comparisons that Quicksort makes is on average just O of n log n? At this point, we actually have a fair amount of experience with divide and conquer algorithms. We've seen a number of examples. And whenever we had to do a running time analysis of such an algorithm, we wrote out a recurrence, we applied the master method, or in the worst case, we wrote out a recursion tree to figure out the solution to that recurrence. So you'd be very right to expect something similar to happen here. But as we probe deeper and we think about Quicksort, we quickly realize that the master method just doesn't apply, or at least not in the form that we're used to. The problem is twofold. So first of all, the size of the two subproblems is random, right? As we discussed in the last video, the quality of the pivot is what determines how balanced a split we get into the two subproblems. It could be as bad as a subproblem of size 0 and one of size n-1, or it could be as good as a perfectly balanced split into two subproblems of equal sizes. But we don't know. It's going to depend on our random choice of the pivot. Moreover, the master method, at least as we discussed it, required solve subproblems to have the same size. And unless you're extremely lucky, that's not going to happen in the Quicksort algorithm. It is possible to develop a theory of recurrence relations for randomized algorithms and to apply that to Quicksort in particular, but I'm not going to go that route for two reasons. The first one is it's really quite messy. It gets pretty technical to talk about solutions to recurrences for randomized algorithms or to think about random recursion trees. Both of those get pretty complicated. The second reason is I really want to introduce you to what I call a decomposition principle, by which you take a random variable that's complicated but that you care about a lot, you decompose it into simple random variables, which you don't really care about in their own right, but which are easy to analyze, and then you stitch those two things together using linearity of expectation. So that's going to be the workhorse for our analysis of the Quicksort algorithm, and it's going to come up again a couple times in the rest of the course, for example, when we study hashing. So to explain how this decomposition principle applies to Quicksort in particular, I'm going to need to introduce you to the building blocks, simple random variables which will make up the complicated random variable that we care about, the number of comparisons. So here's some notation. Recall that we fixed in the background an arbitrary array of length n, and that's denoted by capital A. And some notation, which is simple but also quite important, by z sub I, what I mean is the ith smallest element in the input array capital A, also known as the ith order statistic. So let me tell you what zi is not. Okay, what zi is not in general is the element in the ith position of the input unsorted array. What zi is it's the element which is going to wind up in the ith element of the array once we sort it. Okay, so if you fast forward to the end of a sorting algorithm, in position I, you're going to find zi. So let me give you an example. So suppose we had just a simple array here, unsorted, with the numbers 6, 8, 10, and 2. Then z1, well, that's the first smallest, the one smallest, or just the minimum. So z1 would be the 2, z2 would be the 6, z3 would be the 8, and z4 would be the 10 for this particular input array. Okay, so zi is just the ith smallest number. Wherever it may lie in the original unsorted array, that's what zi refers to. So we already defined the sample space. That's just all possible choices of pivots that Quicksort might make. I already described one random variable, the number of comparisons that Quicksort makes on a particular choice of pivots. Now I'm going to introduce a family of much simpler random variables, which count merely the comparisons involving a given pair of elements in the input array. Not all elements, just a given pair. So for a given choice of pivots, a given sigma, and for given choices of I and j, both of which are between 1 and n, and so we only count things once. I'm going to insist that I is less than j always. And now here's a definition. By xij, and this is a random variable, so it's a function of the pivots chosen, this is going to be the number of times that zi and zj are compared in the execution of Quicksort. Okay, so this is going to be an important definition in our analysis. It's important you understand it. So for something like the third smallest element and the seventh smallest element, xij is asking, that's when I equals 3 and j equals 7. x37 is asking how many times those two elements get compared as Quicksort proceeds. And this is a random variable in the sense that if the pivot choices are all predetermined, if we think of those being chosen in advance, then there's just some fixed deterministic number of times that zi and zj get compared. So it's important you understand these random variables xij, so the next quiz is going to ask a basic question about the range of values that a given xij can take on. So for this quiz, we're considering, as usual, some fixed input array, and now furthermore fixed two specific elements of the input array. For example, the third smallest element, wherever it may lie, and the seventh smallest element, wherever it may lie. Think about just these pair of two elements. What is the range of values that the corresponding random variable xij can take on? That is, what are the different numbers of times that a given pair of elements might conceivably get compared in the execution of the Quicksort algorithm? All right, so the correct answer to this quiz is the second option. This is not a trivial quiz. This is a little tricky to see. So the assertion is that a given pair of elements, they might not be compared at all. They might be compared once, and they're not going to get compared more than once. Okay, so here what I'm going to discuss is why it's not possible for a given pair of elements to be compared twice during the execution of Quicksort. It'll be clear later on, if it's not already clear now, that both 0 and 1 are legitimate possibilities. A pair of elements might never get compared, and they might get compared once. And we'll go into more detail on that in the next video. So, but why is it impossible to be compared twice? Well, think about two elements, say the third element and the seventh element, and let's recall how the partition subroutine works. Observe that in Quicksort, the only place in the code where comparisons between pairs of input array elements happens, it only happens in the partition subroutine. So that's where we have to drill down. So what are the comparisons that get made in the partition subroutine? Well, go back and look at that code. The pivot element is compared to each other element in the input array exactly once. Okay, so the pivot just hangs out in the first entry of the array. We have this for loop, this index j, which marches over the rest of the array, and for each value of j, the jth element of the input array gets compared to the pivot. Okay, so summarizing, in an invocation of partition, every single comparison involves the pivot element. Okay, so two elements get compared if and only if one is the pivot. All right, so let's go back to the question. Why can't a given pair of elements in the input array get compared two or more times? Well, think about the first time they ever get compared in Quicksort. It must be the case that at that moment we're in a recursive call where either one of those two is the pivot element. So if it's the third smallest element or the seventh smallest element, the first time those two elements get compared to each other, either the third smallest or the seventh smallest is currently the pivot, because all comparisons involve a pivot element. Therefore, what's going to happen in the recursion? Well, the pivot is excluded from both recursive calls. So for example, if the seventh smallest element is currently the pivot, that's not going to be passed on to the recursive call which contains the third smallest element. Therefore, if you're compared once, one of the elements is the pivot, and they'll never be compared again, because the pivot will not even show up in any future recursive calls. So let me just remind you of some terminology. So a random variable which can only take on the value 0 or 1 is often called an indicator random variable, because it's just indicating whether or not a certain thing happens. So in that terminology, each xij is indicating whether or not the ith smallest element in the array and the jth smallest element in the array ever get compared. It can't happen more than once. It may or may not happen, and xij is 1 precisely when it happens. So that's the event that it's indicating. Having defined the building blocks I need, these indicator random variables, these xij's, now I can introduce you to the decomposition principle as applied to Quicksort. So there's a random variable that we really care about, which is denoted capital C, the number of comparisons that Quicksort makes. That's really hard to get a handle on in and of itself. But we can express C as a sum of indicator random variables of these xij's. And those we don't care about in their own right, but they're going to be much easier to understand. So let me just rewrite the definitions of C and the xij's so we're all clear on them. So C, recall, counts all of the comparisons between pairs of input elements that Quicksort ever makes, whereas an xij only counts the number, and it's going to be 0 or 1, comparisons that involve the ith smallest and the jth smallest elements in particular. Now, since every comparison involves precisely one pair of elements, some I and some j with I less than j, we can write C as the sum of the xij's. So don't get intimidated by this fancy double sum. All this is doing is it's iterating over all of the ordered pairs. So all of the pairs ij, where I and j are both between 1 and n, and where I is strictly less than n. This double sum is just a convenient way to do that iteration. And of course, no matter what the pivots chosen are, we have this equality. Okay, the comparisons are somehow split up amongst the various pairs of elements, the various i's and j's. Why is it useful to express a complicated random variable as a sum of simple random variables? Well, because an equation like this is now right in the wheelhouse of linearity of expectation. So let's just go ahead and apply that. Remember, and this is super, super important, linearity of expectation says that the expectation of a sum equals the sum of the expectations. And moreover, this is true whether or not the random variables are independent. Okay, and I'm not going to prove it here, but you might want to think about the fact that the xij's are not, in fact, independent. So we're using the fact that linearity of expectation works even for non-independent random variables. Again, why is this interesting? Well, the left-hand side, this is complicated. Right? This is some crazy number of comparisons by some algorithm on some arbitrarily long array, and it fluctuates between two pretty far apart numbers, n log n and n squared. On the other hand, this does not seem as intimidating. A given xij, it's just 0 or 1, whether or not these two guys get compared or not. So that is the power of this decomposition approach. Okay, so it reduces understanding a complicated random variable to understanding simple random variables. In fact, because these are indicator random variables, we can even clean up this expression some more. So for any given xij being a 0, 1 random variable, if we expand the definition of expectation, just as an average over the various values, what is it? It's just, well, there's some probability it takes on the value 0. That's possible. And there's some possibility it takes on the value 1. And of course, this 0 part we can very satisfyingly delete, cancel. And so the expected value of a given xij is just the probability that xij equals 1. And remember, it's an indicator random variable. It's 1 precisely when the ith smallest and the jth smallest elements get compared. So putting it all together, we find that what we care about, the average value of the number of comparisons made by Quicksort on this input array, is this double sum, which iterates over all ordered pairs, where each summand is the probability that the corresponding xij equals 1. That is the probability that zi and zj get compared. And this is essentially the stopping point for this video for the first part of the analysis. So let's call this star and put a nice circle around it. So what's going to happen next is that in the second video for the analysis, we're going to drill down on this probability that a given pair of elements gets compared, and we're going to nail it. We're going to get an exact expression as a function of I and j for exactly what this probability is. Then in the third video, we're going to take that exact expression, plug it into the sum, and then evaluate this sum. And it turns out the sum will evaluate to big O of n log n. So that's the plan. That's how you apply decomposition in terms of 0, 1 or indicator random variables, apply linearity of expectation. In the next video, we'll understand these simple random variables, and then we'll wrap up in the third video. Before we move on to the next part of the analysis, I do just want to emphasize that this decomposition principle is relevant not only for Quicksort, but it's relevant for the analysis of lots of randomized algorithms. And we will see more applications, at least one more application later in the course. So just to kind of really hammer the point home, let me spell out the key steps for the general decomposition principle. So first you need to figure out what is it you care about. So in Quicksort we cared about the number of comparisons. We had this lemma that said the running time is dominated by comparisons, so we understood what we wanted to know, the average value for the number of comparisons. The second step is to express this random variable y as a sum of simpler random variables, ideally indicator or 0, 1 random variables. Now you're in the wheelhouse of linearity of expectation. You just apply it. And you find that what it is you care about, the average value of the random variable y, is just the sum of the probabilities of various events. That a given xl random variable is equal to 1. And so the upshot is, to understand the seemingly very complicated left-hand side, all you have to do is understand something which in many cases is much simpler, which is understand the probability of these various events. In the next video, I'll show you exactly how that's done in the case of Quicksort, where we care about the xij's, the probability that two elements gets compared. So let's move on and get an exact expression for that probability. This is the second video of 3 in which we prove that the average running time of randomized Quicksort is big O of n log n. So to remind you of the formal statement, so again we're thinking about Quicksort, where we implement the choose pivot subroutine to always choose a pivot uniformly at random from the subarray that it gets passed. And we're proving that for a worst case input array, for an arbitrary input array of length n, the average running time of Quicksort, where the average is over the random pivot choices, is big O of n log n. So let me remind you of the story so far. This is where we left things at the previous video. We defined a few random variables. The sample space, recall, is just the all of the different things that could happen. That is, all of the random coin flip outcomes that Quicksort could produce, which is equivalent to all of the pivot choices made by Quicksort. Now, the random variables we care about, so first of all, there's capital C, which is the number of comparisons between pairs of elements in the input array that Quicksort makes for a given pivot sequence sigma. And then there are the xij's, and so that's just meant to count the number of comparisons involving the ith smallest and the jth smallest elements in the input array. Where you'll recall zi and zj denote the ith smallest and jth smallest entries in the array. Now, because every comparison involves some zi and some zj, we can express capital C as a sum over the xij's. So we did that in the last video. We applied linearity of expectation. We used the fact that xij are 0, 1, that is indicator random variables, to denote that, to write the expectation of an xij just as the probability that it's equal to 1, and that gave us the following expression. So the key insight, and really the heart of the Quicksort analysis, is to derive an exact expression for this probability as a function of I and j. So for example, if the third smallest element in the array, the seventh smallest element in the array, wherever they may be scattered in the input array, we want to know exactly what's the probability that they get compared at some point in the execution of Quicksort. And we're going to get an extremely precise understanding of this probability in the form of this key claim. So for all pairs of elements, and again, ordered pairs, so we're thinking of I being less than j, the probability that zi and zj get compared at some point in the execution of Quicksort is exactly 2 divided by j minus I plus 1. So for example, in this example, the third smallest element and the seventh smallest element, it would be exactly 40% of the time. 2 over 5 is how often those two elements would get compared if you ran Quicksort with a random choice of pivots. And that's going to be true for every j and I. The proof of this key claim is the purpose of this video. So how do we prove this key claim? How do we prove that the probability that zi and zj get compared is exactly 2 over quantity j minus I plus 1? Well, fix your favorite ordered pair. So fix elements zi, zj with I less than j, for example, the third smallest and the seventh smallest element in the array. Now, what we want to reason about is the set of all elements in the input array between zi and zj inclusive. And I don't mean between in terms of positions in the array, I mean between in terms of their values. So consider the set between zi and zj plus 1 inclusive. So zi plus 1, dot, 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 zj minus 1, zj. So for example, the third, fourth, fifth, sixth, and seventh smallest elements in the input array, wherever they may be. Okay? And of course, the initial array is not sorted, so there's no reason to believe that these j minus I plus 1 elements are contiguous. Okay? They're scattered throughout the input array, but we're going to think about them. Okay? zi through zj inclusive. Now, throughout the execution of Quicksort, these j minus I plus 1 elements lead parallel lives, at least for a while, in the following sense. Begin with the outermost call to Quicksort, and suppose that none of these j minus I plus 1 elements is chosen as a pivot. Where then could the pivot lie? Well, it could only be a pivot that's greater than all of these, or it could be less than all of these. For example, if this is the third, fourth, fifth, sixth, and seventh smallest elements in the array, well, the pivot is either the minimum or the second minimum, in which case it's smaller than all 5 elements, or it's the eighth or largest or larger elements in the array, in which case it's bigger than all of them. There's no way you can have a pivot that somehow is wedged in between this set, because this is a contiguous set of order statistics. Okay? Now, what do I mean by these elements leading parallel lives? Well, in the case where the pivot is chosen to be smaller than all of these elements, then all of these elements will wind up to the right of the pivot, and they will all be passed to a common recursive call, the second recursive call. If the pivot is chosen to be bigger than all of these elements, then they'll all show up on the left side of the partitioned array, and they'll all be passed to the first recursive call. Iterating this, or proceeding inductively, we see that as long as the pivot is not drawn from the set of j minus I plus 1 elements, this entire set will get passed on to the same recursive call. So these j minus I plus 1 elements are living blissfully together in harmony until the point at which one of them gets chosen as a pivot. And that, of course, has to happen at some point. The recursion only stops when the array length is equal to 0 or 1. So if for no other reason, at some point there will be no other elements in a recursive call other than these j minus I plus 1. Okay, so at some point the reverie is interrupted and one of them is chosen as a pivot. So let's pause the Quicksort algorithm and think about what things look like at the time that one of these j minus I plus 1 elements is first chosen as a pivot element. There are 2 cases worth distinguishing between. In the first case, the pivot happens to be either zi or zj. Now remember what it is we're trying to analyze. We're trying to analyze the frequency, the probability with which zi and zj gets compared. Well, if zi and zj are in the same recursive call, and one of them gets chosen as the pivot, then they're definitely going to get compared. Remember, when you partition an array around its pivot element, the pivot gets compared to everything else. So if zi is chosen as a pivot, it certainly gets compared to zj. If zj gets chosen as a pivot, it gets compared to zi. So either way, if one of these two is chosen, they're definitely compared. If, on the other hand, the first of these j minus I plus 1 elements to be chosen as a pivot is not zi or zj, if instead it comes from the set zi plus 1 so on up to zj minus 1, then the opposite is true. Then zi and zj are not compared now, nor will they ever be compared in the future. So why is that? Well, that requires 2 observations. First, recall that when you choose a pivot and you partition an array, all of the comparisons involve the pivot. So 2 elements which are neither of which is the pivot do not get compared in a partition subroutine. So they don't get compared right now. Moreover, since zi is the smallest of these and zj is the biggest of these, and the pivot comes from somewhere between them, this choice of pivot will split zi and zj into different recursive calls. Zi gets passed to the first recursive call, zj gets passed to the second recursive call, and they will never meet again. So there's no comparisons in the future either. So these 2 observations right here, I would say, is the key insight in the Quicksort analysis. The fact that for a given pair of elements we can very simply characterize exactly when they get compared and when they do not get compared in the quicksort algorithm. That is, they get compared exactly when one of them is chosen as the pivot before any of the other elements with value in between those two has had the opportunity to be a pivot. That's exactly when they get compared. So this will allow us to prove this key claim, this exact expression on the comparison probability. That will plug into the formula we had earlier and will give us the desired bound on the average number of comparisons. So let's fill in those details. So first let me just rewrite the high order bit from the previous slide. So now at last we will use the fact that our quicksort implementation always chooses a pivot uniformly at random, that each element of a subarray is equally likely to serve as the pivot element in the corresponding partition call. So what does this buy us? This just says all of the elements are symmetric, so each of the elements zi, zi plus 1 all the way up to zj is equally likely to be the first one asked to serve as a pivot element. Now the probability that Zi and Zj get compared is simply the probability that we're in case 1 as opposed to in case 2. And since each element is equally likely to be the pivot, that just means there's sort of two bad cases, two cases in which one can occur out of the j minus I plus 1 possible different choices of pivot. Now we're talking about a set of j minus I plus 1 elements, each of whom is equally likely to be asked to be served first as a pivot element. And the bad case, the case that leads to a comparison, there's two different possibilities for that, if Zi or Zj is first, and the other j minus I minus 1 outcomes lead to the good case where Zi and Zj never get compared. So overall, because everybody's equally likely to be the first pivot, we have that the probability that Zi and Zj get compared is exactly the number of pivot choices that lead to a comparison divided by the number of pivot choices overall. And that is exactly the key claim. That is exactly what we asserted was the probability that a given Zi and Zj get compared for no matter what I and j are. So wrapping up this video, where does that leave us? We can now plug in this expression for this probability of comparison probabilities into the double sum that we had before. So putting it all together, what we have is that what we really care about, the average number of comparisons that Quicksort makes on this particular input of array n, of length n, is just this double sum, which iterates over all possible ordered pairs, ij. And what we had here before was the probability of comparing Zi and Zj. We now know exactly what that is, so we just substitute. And this is where we're going to stop for this video. So this is going to be our key expression star, which we still need to evaluate, but that's going to be the third video. So essentially we've done all of the conceptual difficulty in understanding where comparisons come from in the quicksort algorithm. All that remains is a little bit of an algebraic manipulation to show that this starred expression really is big O of n log n. And that's coming up next. So we're almost at the finish line of our analysis of Quicksort. Let me remind you what we're proving. We're proving that for the randomized implementation of Quicksort, where we always choose a pivot element to partition around uniformly at random, we're showing that for every array, every input of length n, the average running time of Quicksort over the random choices of pivots is big O of n log n. So we've done a lot of work in the last couple videos. Let me just remind you about the story so far. In the first video, what we did is we identified the relevant random variable that we cared about, capital C, the number of comparisons that Quicksort makes among pairs of elements in the input array. Then we applied a decomposition approach. We expressed capital C, the overall number of comparisons, as a sum of indicator or 0, 1 random variables, where each of those variables xij just counted the number of comparisons involving the ith smallest and jth smallest entries in the array, and that's going to be either 0 or 1. Then we applied linearity of expectation to realize all we really needed to understand was the comparison probabilities for different pairs of elements. In the second video, we nailed what that comparison probability is. Specifically, for the ith smallest and the j smallest elements in the array, the probability that Quicksort compares them when you always make random pivot choices is exactly 2 divided by the quantity j minus I plus 1. So putting that all together yields the following expression. governing the average number of comparisons made by Quicksort. And one thing I want you to appreciate is in the last couple of videos we've been sort of amazingly exact as algorithmic analysis goes. Specifically, we've done nothing sloppy whatsoever. We've done no estimates. The number of comparisons the Quicksort makes on average is exactly this double sum. Now, shortly we'll do some inequalities to make our lives a little bit easier, but up to this point everything has been completely exact. And this lets you see why there's small constants also in Quicksort. It's basically going to be this factor 2. Now the next question to ask is, what are we shooting for? Remember, the theorem we want to prove is that the expected number of comparisons, really the expected runtime, is O of n log n. So are we already done? Well, not quite. We're going to have to be a little bit clever. So if we look at this double sum, and we ask, how big are the summands and how many terms are there? Well, the biggest summands we're ever going to see are when I and j are right next to each other, where j is 1 bigger than I. In that case, this fraction is going to be 1/2. So the terms can be as big as 1/2. How many terms are there? Well, there's a quadratic number of terms. So it'd be very easy to derive an upper bound that's quadratic in n, but that's not what we want. We want one that's n log n. So to derive that, we're going to have to be a little bit more clever about how we evaluate this sum. So the idea is what we're going to do is we're going to think about a fixed value of I in this outermost sum, and then we're going to ask, how big could the inner sum be? So let's fix some value of I, the value of the index in the outer sum. And then let's look at the inner sum, where j ranges from I plus 1 up to n, and the value of the summand is 1 over the quantity j minus I plus 1. So how big can this be? Well, let's first understand what the terms actually are. So j starts at I plus 1, and then it ascends to n. And as j gets bigger, the denominator gets bigger, so the summands get smaller. So the biggest summand is going to be the very first one when j is as small as possible, namely I plus 1. When j is I plus 1, the summand is 1/2. Then j gets incremented in the sum, and so we're going to pick up a 1/3 term, followed by a 1/4 term, and so on. So there's going to be, for every inner sum is going to have of this form, 1/2 plus 1/3 plus 1/4, and then it's going to sort of run out at some point when j equals n, and the biggest term we're ever going to see is going to be a 1 over n, in the case where I equals 1. So let's make our lives easier by taking this expression we started with, star, and instead of having a double sum, let's just upper bound this with a single sum. So what are the ingredients of the single sum? Well, there's this 2. Can't forget the 2. Then there's n choices for I. Actually, there's n minus 1 choices for I, but let's just be sloppy and say n choices. So that gives us a factor n. And then how big can an inner sum be? Well, an inner sum is just a bunch of these terms, 1/2 plus 1/3, and so on. The biggest of those inner sums is the one occurring when I equals 1, at which point the last term is 1 over n. So we're going to just do a change of variable and express the inner sum, an upper bound on each inner sum, as the sum from k equal 2 to n of 1 over k. So that's looking more manageable, just having this single sum involving this index k. And life's going to get really good when we prove the next claim, which is that this sum cannot be very big. It's only logarithmic in n. Even though there's a linear number of summands, the overall value of the sum is only logarithmic. That, of course, is going to complete the proof, because that'll give us an overall bound of 2 times n times the natural log of n. So that's an n log n bound with really quite reasonable constants. So why is this true? Why is this sum only logarithmically large? Well, let's do a proof by a picture. I'm going to write this sum in a geometric fashion. So on the x-axis, let me mark off points corresponding to the positive integers. And on the y-axis, let me mark off points corresponding to fractions of the form 1 over k. And what I'm going to do is I'm going to draw a bunch of rectangles of decreasing area. Specifically, they all have width 1, and the heights are going to be like 1 over k. So the area of this guy is 1, the area of this guy is 1/2, the area of this guy is 1/3, and so on. And now I'm going to overlay on this picture the graph of the function, the continuous function f of x equals 1 over x. So notice that is going to go through these 3 points. It's going to kiss all of these rectangles on their upper right corners. Now what is it we're trying to prove? The claim we're trying to prove is that this sum of 1/2 plus 1/3 and so on is upper bounded by something. So this sum can be just thought of as the areas in these rectangles, the 1/2, the 1/3, and so on. And we're going to upper bound it by the area under the blue curve. So you notice the area under the blue curve is at least as big as the sum of the areas of the rectangles because the curve hits each of these rectangles in its northeast corner. So putting that into mathematics, the sum from k equal 2 to n of 1 over k is bounded above by the integral, and we'll start the area under the curve at 1, and then we need it to go all the way up to n of the function 1 over x dx. So that's the area under the curve. And if you remember a little bit of calculus, the integral of 1 over x is the natural log of x. So this equals the natural log of x evaluated at n1, also known as log n minus log 1. And of course, log 1 would be 0. So that gives us our log n. So that completes the proof of the claim that indeed the sum of these 1 over k's is bounded above by the natural log of n, and that in fact completes the proof of the theorem. We've got that the expected number of comparisons is at most 2n times this sum, which is at most log n. Putting it all together, we find that the expected number of comparisons that Quicksort makes on an arbitrary input of length n is 2 times n times the natural log of n. So that would be big O of n log n with quite reasonable constants. Now this is just the number of comparisons, but as we observed earlier, the running time of Quicksort on average is not much more than that. The running time is dominated by the number of comparisons that it makes. Moreover, as we discussed when we were talking about the details of the implementation, it works in place. Essentially no extra storage is necessary. So that is a complete and mathematically rigorous explanation of just why Quicksort is so quick. Welcome to part 1 of our probability review. The first time that we need these concepts in the course is for those of you that want to understand the analysis of Quicksort, why it runs in big O of n log n time on average. And these topics will also come up a couple other times in the course, for example, when we study a randomized algorithm for the minimum cut problem in graphs, and also when we try to understand the performance of hashing. Here are the topics we're going to cover. We'll start at the beginning with sample spaces, and then we'll discuss events and their probabilities. We'll talk about random variables, which are real valued functions on a sample space. We'll talk about expectation, which is basically the average value of a random variable. We'll identify and prove a very important property called the linearity of expectation, which will come up over and over again in our analyses of randomized processes. So that's going to be the topics for part 1. That will conclude the video with one example tying these concepts together in load balancing. And this video is by no means the only source you can turn to learn about these concepts. A couple other sources I recommend are the online lecture notes by Eric Lehman and Tom Layton. Also, there's a wiki book on discrete probability which you could check out. And I want to be clear, this is really not meant to be a course or a tutorial on probability concepts. It's really only meant to be a refresher. So I'm going to go at a reasonably fast pace, and it's going to be a pretty cursory presentation. And if you want a more thorough review, I would check out one of these other sources or your favorite book on discrete probability. And along those same lines, I'm thinking that many of you have seen some of this material before. Don't feel compelled to watch this video straight from the beginning to the end. Feel free to just sort of dip in and review the concepts that you need a refresher on. So let's start at the beginning with sample spaces. So what is a sample space? Well, we're analyzing random processes, so any number of things could happen, and the sample space is just a collection of all of the things that could happen. So this is basically the universe in which we're going to discuss probabilities and average values. So I'll often use the notation big omega to describe the sample space. So one thing we've got going for us in the design of algorithms is typically we can take omega to be a finite set. So that's why we're dealing only with discrete probability, which is a very happy thing, because that's much more elementary than more general probability. In addition to defining the outcomes, everything that could possibly happen, we need to define what is the probability of each individual outcome. So of course the probability of each outcome should be at least 0, should be non-negative, and there's also the obvious constraint that the sum of the probabilities should be 1. So exactly one thing is going to happen. Now I realize this is a super abstract concept, and the next few definitions are also a little abstract. So throughout them I'm going to use two really simple, really concrete examples to illustrate what these concepts mean. So the first example is just going to be you take two 6-sided dice and you roll them. And then of course the sample space is just the 36 different outcomes you could have of these two dice. And assuming that each of these two dice is well crafted, then we expect each of these 36 outcomes to be equally likely to occur with probability 1 over 36. The second running example I'm going to use is more directly related to algorithms, and it's motivated by the Quicksort algorithm. Recall that we're studying the implementation of Quicksort that chooses a pivot uniformly at random in every recursive call. So let's just focus on the very first outermost call of Quicksort and think about the random choice of the pivot just in that call. So then the sample space, all of the different things that could happen, is just all of the n different choices for a pivot, assuming the array has length n. So we can represent the sample space just as the integers 1, 2, all the way up to n, corresponding to the array index of the randomly chosen pivot. And again, by definition, by the construction of our code, each of these things is equally likely, probability 1 over n. Now let's talk about events. An event is nothing more than a subset of all of the things that could happen. That is a subset of the sample space omega. The probability of an event is exactly what you'd think it would be. It's just the sum of the probabilities of all of the outcomes contained in that event, right? So an event is just a bunch of stuff that might happen. We know the probability of each individual thing that could happen. We add them up to get the probability of an event. So the next two quizzes are meant to give you some practice with these concepts, and in particular, they'll ask you to compute the probability of events in our two running examples. So in the first quiz, this is our first running example where we think about two dice and we have our 36 possible outcomes. Consider the subset of outcomes in which the sum of the two dice equals 7. What is the probability of that event? All right, so the correct answer is the third one. The probability is 1 over 6. Why is that? Well, first let's be more precise about what this event is. What are the outcomes in which the sum of the dice is equal to 7? Well, there's exactly 6 such outcomes. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Each of the 36 outcomes is equally likely, has probability 1 over 36. So we have 6 members of the set, each with probability 1 over 36. So the probability is 1/6. Let's move on to the next quiz, which considers our second running example, namely the randomly chosen pivot in the outermost call to Quicksort on an input array of length n. So recall that in Quicksort, when you choose a pivot, you then partition the array around the pivot, and this splits the input array into two subarrays, a left one, elements less than the pivot, and a right one, those bigger than the pivot. And the more balanced the split into these two subproblems, the better. So ideally, we'd like a 50-50 split. So what this quiz asks you is what fraction of pivots, that is, what's the probability that a randomly chosen pivot will give you a reasonably good split, meaning both of the subproblems have size at least 25%. That is, you get a split of 25, 75, or better. So that's what this quiz asks about. What's the probability that your randomly chosen pivot satisfies that property? So the correct answer to this quiz is, again, the third option. It's a 50% probability. You get a 25-75 split or better. So to see why, let's again be precise about what is the event that we're talking about, then we'll compute its probability. So when does a pivot give you a 25-75 split or better? Well, for concreteness, suppose the array contained just the integers between 1 and 100. Now what's the property we want? We want that both of the two subarrays have at least 25% of the elements. Neither one has more than 75% of the elements. Well, if we choose an element that's 26 or bigger in value, then the left subproblem will have at least 25 elements, the numbers 1 through 25. And if we choose an index if we choose an element that's at most 75, then the right subarray is going to have at least 25 elements, namely the numbers 76 to 100. So anything between 26 and 75 inclusive is going to give us a 25-75 split. More generally, any pivot from the middle 50%, of the quantiles is going to give us the desired split. So we do badly if we get something within the first quarter. We do badly if we get something within the last quarter. Anything in the middle works. So more formally, we can say that the event S that we're analyzing is, among the possible pivot choices, we're interested in the ones that is not in the first quarter and not in the last quarter. Now the cardinality of S, the number of pivots in this set, is essentially half of the overall number of pivot choices. I'm ignoring fractions here for simplicity. So the probability of this event is the cardinality of this divided by, or times the probability of each of the individual outcomes. And since we choose the pivot uniformly at random, each one has probability 1 over n, so we get n over 2 divided by n, or 1/2. Okay, now that we've explored the concept of events in our running 2 examples, we see that the probability that the sum of 2 dice is equal to 1/6, a useful fact to know if you're ever playing craps. And we know that a pivot gives us a 25-75 split or better in randomized quicksort with 50% probability. A useful fact if you want to develop intuition for why quicksort is in fact quick. So that's events. Let's move on to random variables. So random variables are basically some statistic measuring what happens in the random outcome. So formally, if we want to define it, it's a real valued function defined on the sample space omega. So given an outcome, given a realization of the randomness, this gives you back a number. Now the random variable that we most often care about in algorithm design is the running time of a randomized algorithm. That's the case, for example, with the quicksort algorithm. So notice that is in fact a random variable. If we know the state of the world, if we know the outcome of all of the coin flips that our code's going to make, then there's just some running time of our algorithm. So in that sense, it's a random variable. Given the outcomes of the coin flips, out pops a number, the running time, say in milliseconds, of the algorithm. Here I'm going to give you a couple more modest examples of random variables in our 2 running examples. If we're rolling 2 dice, one very simple random variable takes as input the outcome, so the result of the 2 dice, and spits out the sum. So that's certainly a random variable. On any given outcome, it's going to take on some integer value between 2 at the minimum and 12 at the maximum. Our second running example is the randomly chosen pivot made by the outermost call to quicksort. So let's think about the random variable, which is the size, meaning the subarray length, passed to the first recursive call. Equivalently, this random variable is the number of elements of the input array smaller than the randomly chosen pivot. So this is a random variable that takes on some integral value between 0 at the smallest, that's if we happen to pick the pivot equal to the minimum of the array, and n-1 at the largest, that's if we happen to pick the maximum element as the pivot element. Next, let's talk about the expectation of a random variable. This is really nothing more than the average. And of course, when you take the average of some statistic, you want to do it weighted by the probability of its various values. So let's just make that precise real quick. So consider some random variable capital X. The expectation, this is also called the expected value. And the notation is capital E, square bracket, then of the random variable. And again, in English, the expectation is just the average value, naturally weighted by the probability of the various possible outcomes. Or more mathematically, we sum over everything that could happen, so let little I denote one possible outcome. We look at the value of this random variable when that outcome occurs, and then we weight it times the probability of that outcome occurring. So the next 2 quizzes ask you to compute the expectation of the 2 random variables that we identified on the previous slide. So the first quiz is about 2 dice and the random variable, which is the sum of the values of those 2 dice. What is the average value of that random variable? What is its expectation? Okay, so the answer to this question is the second option. The average value is 7. There's a bunch of different ways to see that. In my opinion, the best way to compute this is using linearity of expectation, which is the next concept we're going to cover. If you wanted to, you could just compute this by brute force, by which I mean you could iterate over all 36 possible outcomes, look at the value of the 2 dice in each, and just evaluate that sum we had in the definition on the last slide. A slightly sneakier way to do it, if you don't know linearity of expectation, would be to pair up the various outcomes. So it's equally likely that the sum of the two dice is 2 or 12. It's equally likely to be 3 or 11, 4 and 10, and so on. Each way of pairing up these values of the two dice results in 14, and when you average, you get 7. But again, the right way to do this is linearity of expectation, which we'll cover next. So the second quiz covers the second random variable we identified. So now we're back to quicksort and the random pivot chosen in the outermost call. And the question is, how big on average in expectation is the subarray in the first recursive call? Equivalently, on average, how many elements are going to be less than the randomly chosen pivot? So the correct answer to this quiz is the third option. In fact, it's actually quantity n minus 1 over 2, not n over 2, but basically half of the elements. Again, there's sort of a sneaky way to see this if you want, which is that clearly the two recursive calls are symmetric. The expected value of the left recursive call is going to be the same as the expected size of the right recursive call. The two recursive calls always comprise n minus 1 of the elements, so because they're symmetric, you expect half in each, so n minus 1 over 2 in each. So for this problem, I think it's perfectly fine just to compute this using the definition of expectation. So if we let x denote the random variable that we care about, the subarray size, then we can just compute directly by summing over all of the possible outcomes, all of the possible choices of the pivot. So with probability 1 over n, we choose the minimum of the pivot, resulting in 0 elements being passed to the first recursive call. With probability 1 over n, we pick the second smallest element, resulting in 1 element being passed to the first recursive call. With probability 1 over n, we pick the third smallest, giving us a subarray size of 2, and so on. And then with probability 1 over n, we pick the maximum element, giving us a subarray size of n minus 1. So if you just sort of compute this sum out, you will get, as expected, n minus 1 over 2. So expectation is the last definition that I'm going to give you in this part 1 of the probability review. Next is our fifth and final concept for this video, which is linearity of expectation. And that's not a definition, that's more of a theorem. So what is linearity of expectation? Well, this is a very simple property of random variables that's super, super important. This comes up all the time when we analyze randomized algorithms and random processes more generally. So what is linearity of expectation? Well, it's the following very simple claim, which I'll sometimes denote just by linx for short. Suppose you got a bunch of random variables defined on the same sample space. Then, if you want to think of the expected value of the sum of these random variables, it doesn't matter if you take the sum first and then take the expectation, or if you take expectations first and then sum. That is, the expected value of a sum of random variables is equal to the sum of the expectations of the individual random variables. And one of the reasons linearity of expectation is so ubiquitously useful is because it always works, no matter what these random variables are. In particular, even when the random variables are not independent. Now, I haven't defined independent random variables yet. That will come in part 2 of the probability review, but hopefully you have an intuitive sense of what independence means. So things are independent if knowing something about one of the random variables doesn't influence what you expect from the other random variable. Now, I realize the first time you see linearity of expectation, it's a little hard to appreciate. So first of all, as far as applications, we'll see plenty throughout this course. Pretty much every single application of probability that we'll see, the analysis will involve linearity of expectation. But it may be hard to appreciate why this is not a tautology. Just symbolically, it may look like it has to be true. But to point out that there is content here, if I replace the sums by products, then this equation would in general be false if the random variables are not independent. So the same thing is not true about products. It's really about sums. So let me just give you a trivial illustration of linearity of expectation, point out how it really easily allows us to evaluate the sum of two dice. So in our first running example, let's introduce the random variables x1 and x2 for the results of the first and second die respectively. Now, computing the expected value of a single die is easy. There's only 6 outcomes to enumerate over. Contrast that with the 36 outcomes to enumerate over when we evaluated the sum of the two dies. So the average value of a single die, you won't be surprised to hear, is 3.5. right? So it ranges integers between 1 and 6 uniformly, so 3.5 on average. And now, using linear of expectation, the sum of two dice is simply double the average value of a single one. So in the next slide, I'm going to prove this property, prove linearity of expectation. But frankly, the proof is pretty trivial. So if you don't care about the proof, that's fine. You can skip it without loss. I'm including it just for completeness. And I gotta say, I don't know of another mathematical statement which is simultaneously so trivial to prove and so unbelievably useful. It's really something remarkable about linearity of expectation. So how does the proof go? Well, honestly, we just write out the sum, the definition of an expectation, we reverse the sums, and we're done. So let me start with the right-hand side of the equation. So that was the sum of the expectations of the random variables. So now let's just apply the definition of expectation. So it's just a weighted average over the possible outcomes. And now instead of summing first over the random variable j and then over the realized outcome I, I'm going to do it in reverse order. I'm going to sum first over the outcome I and then over the random variable j. Now the probability of outcome I is independent of j, so we can yank the p of I outside of that inner sum. But now what have we got? So inside the parentheses, we simply have the value of the sum of the xj's on the outcome I, and then over here we're just averaging the sum of the xj's with respect to the probabilities, the pi's. So this is just the definition of the expectation of the sum of the random variables. So that's it. So linearity of expectation is really just a reversal of the double sums. Now, for those of you that are rusty on these kinds of manipulations, I just want to point out, this reversal of the double sum itself there's nothing complicated at all about what's going on. So if you want a really pedestrian way to think about what's happening, just imagine that we take these summands, these xji pi's, and we just write them out in a grid, where let's just say the columns are indexed by the random variable j, and the rows are indexed by the outcome I. And in a given cell of this grid, we just write the summand xji times pi. So if you get lost in the notation with these double sums, the point is you can just interpret each of them in terms of this grid. Both of these double sums are nothing more than the sum of the values in all of the cells of this grid. One order of summation just says you group first according to row sums and then sum those up. That's the first summation. The second summation, you first take column sums and then sum those up. But of course it doesn't matter. You just get the result of everything in the grid. Okay, so there's no tricks up my sleeve when I reverse these sums. It's a totally elementary, trivial thing. Okay, so again, linear of expectation, trivial to prove, incredibly useful. Don't forget it. So I want to conclude this video with one final example in order to tie together all of the concepts that we've just learned or just reviewed. And it's going to be an example about load balancing, assigning processes to servers. But this, in fact, is quite important for the analysis of hashing that we're going to see toward the end of the course as well. But for now, let's just think about the following simple problem. For some integer n, you have n computer processes that have to be assigned to n servers in some way. Now, you're feeling really lazy. Okay, so you're just going to take each of these processes and you're just going to assign it to a totally random server, okay, with each server equally likely to get a given process. And the question I want to study is, does this laziness cost you, at least on average? So if you look at a server, what's the expected load? So let's proceed to the solution, the answer to this question. So before you start talking about expectations, one has to be clear about the sample space and what are the probabilities of the various outcomes. So remember, the sample space omega just denotes every possible thing that could happen. So what are we doing? For each process, we're assigning it to a random server. So all of the things that could happen are all of the different assignments of these n processes to these n servers. And if you think about it, there are n raised to the n possible outcomes because you have n choices for each of the n processes. Moreover, because each process is assigned to one of the servers uniformly at random, each of these n to the n assignments is equally likely, probability 1 over n to the n. Now that we have a sample space, we're in a position to define a random variable. And we already know what random variable we care about. We care about the average load of a server. Now, all of the servers are exactly the same, so we just have to focus on one server, let's say the first server, and look at the number of processes assigned to it. And if you go back to the problem statement, what we're asked is to compute the expected value of y, the expected number of processes assigned to a server. Now, of course, in principle, we could go to the definition of expectation and just compute by brute force the sum over all possible outcomes of the value of y and take the average. Unfortunately, there are n to the n different outcomes, and that's a lot. So what could we do other than this brute force computation? Well, recall our example of linearity of expectation and the sum of two dice. We observed that instead of computing the sum by enumerating over all 36 outcomes, it was much better to just focus on a single die, compute its expectation, and then conclude with linearity of expectation. So we'll do the same thing here. Instead of focusing on the sum y, we'll focus on constituent parts of y. So whether or not a single process gets assigned to the first server, and then we'll get away with that by linearity of expectation. So more precisely, for a given process j, let's define xj to be to be 1 if and only if the jth process gets assigned to the first server, 0 otherwise. 0-1 random variables like xj are often called indicator random variables. That's because they in effect indicate whether or not a certain event occurs. In this case, whether or not the jth process gets assigned to the first server. Why did I make this definition? Well, observe that the total number of processes that gets assigned to the first server is simply the sum from j equal 1 to n of xj. Xj says whether or not a given process, the jth process, is on the first server. The total number is just the sum of these over all j. Now, the benefit from this maneuver is we only have to compute the expectation of an extremely simple indicator random variable xj. This is like the win that we got when we were summing up two dice. By instead of having to compute the sum, the expected value of the sum, we just had to focus on the expectation of a single die. That was really easy. Similarly here, the expectation of a single xj is really easy. Specifically, let's write it out just using the definition of the expectation. So the expected value of an xj is, well, let's group together all the outcomes in which it takes on the value 0. So the contribution to the expectation is 0 for all of those outcomes. And then there's the rest of the outcomes where xj takes on the value 1. And in those cases, it contributes 1 to the expectation. Now, obviously, we get some happy cancellation happening here with the 0 part. And all we have to worry about is the probability that xj takes on the value 1. Okay, what was xj again? How do we define it? Remember, it's the event that it's 1 exactly when the jth process gets assigned to the first server. How are processes assigned? Well, remember, the proposed solution assigns each process to each of the n servers equally likely with uniform probability. So the probability the jth process gets assigned to the first server is 1 over n. So this leaves us with just the sum from j equal 1 to n of 1 over n. That is, we just sum up 1 over n with itself n times. This, of course, is equal to 1. So at the end of the day, what we find is that the expected number of processes assigned to a given server, say the first server, is just 1. So at least if we only care about averages, we lose very little from this trivial process of randomly spraying the process to the server. On average, any given server has just one process on it. This is characteristic of the role that randomization plays in algorithm design and computer science more generally. Often we can get away with really simple heuristics just by making random choices. Of course, Quicksort is one example of that, where we get an extremely prevalently used practical sorting algorithm just by making randomly chosen pivots in every recursive call. So welcome to part 2 of our probability review. This video assumes that you've already watched part 1, or at least are familiar with the concepts covered in part 1, namely sample spaces, events, random variables, expectation, and linearity of expectation. In this part of the review, we're going to be covering just 2 topics, conditional probability and the closely related topic of independence, both between events and between random variables. I want to remind you that this is by no means the only source you can or should use to learn this material. A couple other sources free that I recommend are lecture notes that you can find online by Eric Lehman and Tom Layton, and also there's a wiki book on discrete probability. So conditional probability, I hope you're not surprised to hear, is fundamental to understanding randomized algorithms. That said, in the 5 weeks we have here, we'll probably only use it once, and that's in analyzing the correctness of the random contraction algorithm for computing the minimum cut of an undirected graph. So just to make sure we're all on the same page, here's some stuff you should have learned from part 1 of the probability review. You should know what a sample space is. This represents all of the different outcomes of the random coin flips, all of the different things that could happen. Often in randomized algorithm analysis, this is just all of the possible random choices that the algorithm might make. Each outcome has some known probability, P of I,
and of course the sum of the probabilities equal 1. And remember that event is nothing more than a subset of omega. Omega is everything that could possibly happen. S is some subset of things that might happen. And of course the probability of an event is just the probability of all of the outcomes that the event contains. So let's talk about conditional probability. So one discusses the conditional probability of one event given a second event. So let x and y denote two events, subsets of the same sample space. You might want to think about these two events x and y in terms of a Venn diagram. So we can draw a box representing everything that could conceivably happen. So that's omega. Then we can draw a blob corresponding to the event x. So that's some stuff. Might or might not happen, who knows. And then the other event y is some other stuff, which might or might not happen. And in general, these two events could be disjoint, that is, they could have no intersection, or they might have a non-trivial intersection, x intersect y. Similarly, they need not cover all of omega. It's possible that nothing in x nor y happens. So what we're looking to define is the probability of the event x given the event y. So we write probability of x bar y, phrased x given y. And the definition is, I think, pretty intuitive. So given y means we assume that something in y happened. Originally, anything in omega could have happened. We didn't know what. Now we're being told that whatever happened, it lies somewhere in y. So we zoom in on the part of the picture which contains y. So that's going to be our denominator. So our new world is the stuff in y. That's what we know happened. And now we're interested in the proportion of y that is filled up with x. So we're interested in what fraction of y's area is occupied also by stuff in x. So x intersect y divided by the probability of y. That is, by definition, the conditional probability of x given y. Let's turn to a quiz using our familiar example of rolling two dice to make sure that the definition of conditional probability makes sense to you. Okay, so the correct answer to this quiz is the third answer. So let's see why that is. So what are the two events that we care about? We want to know the probability of x given y, where x is the event that at least one die is a 1, and y is the event that the sum of the two dice is 7. Now, the easiest way to explain this is let's zoom in, let's drill down on y. Let's figure out exactly which outcomes y comprises. So the sum of the two dice being 7, we saw in the first part of the probability review that there's exactly 6 outcomes which give rise to the sum 7. Namely, the ordered pairs 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Now, remember that the probability of x given y is, by definition, the probability of x intersect y divided by the probability of y. Now, what you notice from this formula is we actually don't care about the probability of x per se, or even about the event x per se, just about x intersect y. So let's just figure, so now we know what y is, it's these 6 outcomes. Which of those also belong to x? Well, x is those where at least one die is 1. So x intersect y is just going to be the 1, 6 and the 6, 1. Now, the probability of each of the 36 possible outcomes is equally likely, so each one is 1 over 36. So since x intersect y has only 2 outcomes, that's going to give us a 2 over 36 in the numerator. Since y has 6 outcomes, that gives us a 6 over 36 in the denominator. When you cancel everything out, you're left with a 1/3. So just applying the definition of conditional probability to the correct definition of the two relevant events, we find that indeed a third of the time is when you have a 1 conditioned on the sum of the two dice being 7. Let's move on to the independence of two events. So, again, we consider two events, x and y. By definition, the events are independent if, and only if, the following equation holds. The probability that both of them happen, that is the probability of x intersect y, is exactly equal to the probability that x happens times the probability that y happens. So that's a simple, innocuous looking definition. Let me rephrase it in a way that it's even more intuitive. So I'll let you check this. It's just some trivial algebra.
This equation holds for the events x and y if and only if, this is just using the definition of conditional probability we had on the last slide, if and only if the probability of x given y is exactly the same thing as the probability of x. So intuitively, knowing that y happened gives you no information about the probability that x happens. That's the sense in which x and y are independent. And you should also check that this holds if and only if the probability of y given x equals the probability of y. So symmetrically, knowing that x has occurs gives you no new information about whether or not y has occurred. The probability of y is unaffected by conditioning on x. So at this juncture, I feel compelled to issue a warning, which is you may feel like you have a good grasp of independence, but in all likelihood, you do not. For example, I rarely feel confident that I have a keen grasp on independence. Of course, I use it all the time in my own research and my own work, but it's a very subtle concept. Your intuition about independence is very often wrong, even if you do this for a living. I know of no other source that's created so many bugs and proofs by professional mathematicians and professional computer science researchers as misunderstandings of independence and using intuition instead of the formal definition. So for those of you without much practice with independence, here's my rule of thumb for whether or not you treat random variables as independent. If things are independent by construction, like for example, you define it in your algorithm so the two different things are independent, then you can proceed with the analysis under the assumption that they're independent. If there's any doubt, if it's not obvious that two things are independent, you might want to, as a rule of thumb, assume that they're dependent until further notice. So the slide after next, I'll give you an example showing you things which are independent and things which are not independent. But before I do that, I want to talk about independence of random variables rather than just independence of events. So you'll recall what a random variable is from the first video on probability review. It's just a real valued function from the sample space to the real numbers. So once you know what happens, you have some number. The random variable evaluates to some real number. Now what does it mean for two random variables to be independent? It means the events of the two variables taking on any given pair of values are independent events. So informally, knowing the value taken on by one of the random variables tells you nothing about what value is taken on by the other random variable. Recalling the definition of what it means for two events to be independent, this just means that the probability that A takes on value little a, B takes on value little b, the probability that both of those happen is just the product of the probabilities that each happens individually. So what's useful about independence of events is that probabilities just multiply. What's useful about independence of random variables is that expectations just multiply. So we're going to get an analog of linearity of expectation where we can interchange an expectation and a product freely, but I want to emphasize this interchange of the expectation and the product is valid only for independent random variables and not in general, unlike linearity of expectations. And we'll see a non-example. We'll see how this fails on the next slide for non-independent random variables. So I'll just state it for two random variables, but the same thing holds by induction for any number of random variables. If two random variables are independent, then the expectation of their product equals the product of their expectations. And again, do not forget that we need a hypothesis. Remember, linearity of expectations did not have a hypothesis for this statement about products. We do have a hypothesis of them being independent. So why is this true? Well, it's just a straightforward derivation where you follow your nose. I'll write it out here for completeness, but I really don't think it's that important. So you start with the expectation of the product. This is just the average value of A times B, of course weighted by the probability of any particular value. So the way we're going to group that sum is we're going to sum over all possible combinations of values, A and B, that capital A and capital B might take on. So that's going to give us a value of A times B times the probability that big A takes on the value little a and capital B takes on the value little b. So that's just by definition where this is the value of the random variable, capital A times capital B, and this is the probability that it takes on that value with the constituent values A and B. Now because A and B are independent, this probability factors into the product of the two probabilities. This would not be true if they were not independent. It's true because they're independent. So same sum over all possible joint values of A and B. Still have A times B, but now we have times the probability that A takes on the value A times the probability that B takes on the value B. So now we just need to regroup these terms. So let's first sum over A. Let's yank out all the terms that depend on little a. Notice none of those depend on little b, so we can yank it out in front of the sum over little b. So we have an a times the probability that big A takes on the value little a. And then the stuff that we haven't yanked out is this sum over b of b times the probability that capital B takes on the value little b. Now what's here inside the quantity? This is just the definition of the expectation of b. And then what remains after we've factored out the expectation of b? Just this other sum, which is the definition of the expectation of a. So indeed, for independent random variables, the expected value of the product is equal to the product of the expectations. Let's now wrap up by tying these concepts together in an example. A simple example that nevertheless illustrates how it can be tricky to figure out what's independent and what's not. So here's the setup. We're going to consider three random variables, x1, x2, and x3. x1 and x2 we choose randomly, so they're equally likely to be 0 or 1. But x3 is completely determined by x1 and x2, so it's going to be the XOR of x1 and x2. So XOR stands for exclusive OR. So what that means is that both of the operands are 0, or if both of them are 1, then the output is 0. And if exactly one of them is 1, exactly one of them is 0, then the output is 1. So it's like the logical OR function, except if both of the inputs are true, then you output false. Okay? So that's exclusive OR. Now this is a little hand-wavy. When we start talking about probabilities, if we want to be honest about it, we should be explicit about the sample space. So what I mean by this is that x1 and x2 take on all values. They're equally likely. So we could have a 0, 0, or a 1, 0, or a 0, 1, or a 1, 1. And in each of these four cases, x3 is determined by the first two as the XOR. So we get a 0 here, a 1 here, a 1 here, and a 0 there. And each of these four outcomes is equally likely. So let me now give you an example of two random variables which are independent and a non-example. I'll give you two random variables which are not independent. So first I claim that if you look at x1 and x3, then they're independent random variables. I'll leave this for you to check. This may or may not seem counterintuitive to you. Remember, x3 is derived in part from x1. Nevertheless, x1 and x3 are indeed independent. And why is that true? Well, if you enumerate over the four possible outcomes, you'll notice that all four possible 2-bit strings occur as values for 1 and 3. So here they're both 0, here they're both 1, here you have a 0 and 1, and here you have a 1 and a 0. So you get all four of the combinations with probability 1 over 4, so it's just as if x1 and x3 were independent fair coin flips. So that's basically why the claim is true. Now, that's a perhaps counterintuitive example of independent random variables. Let me give you a perhaps counterintuitive example of dependent random variables. Needless to say, this example just scratches the surface, and you can find much more devious examples of both independence and non-independence if you look in, say, any good book on discrete probability. So now let's consider the random variables x1 product x3 and x2. And the claim is these are not independent. So this I'll give you a formal proof for. The way I'm going to prove this is going to be slightly sneaky. I'm not going to go back to the definition. I'm rather going to contradict the consequence of the definition. So to prove that they're not independent, all I need to do is show that the product of the expectations is not the same as the expectations of the products. Remember, if they were independent, then we would have that equality. Okay? The product of expectations would equal the expectation of the products. So if that's false, then there's no way these random variables are independent. So the expectation of the product of these two random variables is just the expected value of the product of all three. And then on the other side, we look at the product of the expected value of x1 and x3 and the expected value of x2. So let's start with the expected value of x2. That's pretty easy to see. That is 0 half the time, and that is 1 half the time. So the expected value of x2 is going to be 1 half. How about the expected value of x1 and x3? Well, from the first claim, we know that x1 and x3 are independent random variables. Therefore,
the expected value of their product is just the product of their expectations. This expectation is equal to the expected value of x1 times the expected value of x2, of x3. And again, x1 is equally likely to be 0 or 1, so its expected value is a half. x3 is equally likely to be 0 or 1, so its expected value is a half. So the product of their expectations is 1/4. So the right-hand side here is 1/8, 1/2 times a quarter, so that's an eighth. What about the left-hand side, the expected value of x1 times x3 times x2? Well, let's go back to the sample space. What is the value of the product in the first outcome? 0. What is the value of the product in the second outcome? 0. Third outcome? 0. Fourth outcome? 0. The product of all three random variables is always 0, with probability 1. Therefore, the expected value, of course, is going to be 0. So indeed, the expected value of the product of x1, x3, and x2, 0, is not equal to the product of the corresponding expectations. So this shows that x1, x3, and x2 are not independent. I've said pretty much everything I want to say about sorting at this point, but I do want to cover one more related topic, namely the selection problem. This is the problem of computing order statistics of an array, with computing the median of an array being a special case. Analogous to our coverage of Quicksort, the goal is going to be the design and analysis of a super practical randomized algorithm that solves the problem. And this time we'll even achieve an expected running time that is linear in the length of the input array. That is big O of n for input arrays of length n, as opposed to the O of n log n time that we had for the expected running time of Quicksort. Like Quicksort, the mathematical analysis is also going to be quite elegant. So in addition, these two required videos on this very practical algorithm will motivate two optional videos that are on very cool topics, but of a somewhat more theoretical nature. The first optional video is going to be on how you solve the selection problem in deterministic linear time, that is without using randomization. And the second optional video will be a sorting lower bound, that is why no comparison-based sort can be better than merge sort, can have better running time than big O of n log n. So a few words about what you should have fresh in your mind before you watch this video. I'm definitely assuming that you've watched the Quicksort videos, and not just watched them, but that you have that material pretty fresh in your mind. So in particular, the video of Quicksort about the partition subroutine. So this is where you take an input array, you choose a pivot, and you do, by repeated swaps, you rearrange the array so that everything less than the pivot is to the left of it, everything bigger than the pivot is to the right of it. You should remember that subroutine. You should also remember the previous discussion about pivot choices, the idea that the quality of a pivot depends on how balanced a split into two different subproblems it gives you. Those are both going to be important. For the analysis of this randomized linear time selection algorithm, I need you to remember the concepts from probability review part 1, in particular random variables, their expectation, and linearity of expectation. That said, let's move on and formally define what the selection problem is. The input is the same as for the sorting problem, just you're given an array of n distinct entries. But in addition, you're told what order statistic you're looking for. So that's going to be a number I, which is an integer between 1 and n. And the goal is to output just a single number, namely the ith order statistic. That is the ith smallest entry in this input array. So just to be clear, if you had an array entry of, let's just say, 4 elements containing the numbers 10, 8, 2, and 4, and you were looking for, say, the third order statistic, that would be this 8. The first order statistic is just the minimum element of the array. That's easy to find with a linear scan. The nth order statistic is just the maximum. Again, easy to find with a linear scan. The middle element is the median, and you should think of that as the canonical version of the selection problem. Now, when n is odd, it's obvious what the median is. That's just the middle element, so the n plus 1 over 2th order statistic. If the array has even length, there's two possible medians, so let's just take the smaller of them. That's the n over 2th order statistic. You might wonder why you'd ever want to compute the median of an array rather than the mean, that is the average. It's easy to see that you can compute the average just with a simple linear scan. And the median, one motivation is it's a more robust version of the mean. So if you just have a data entry problem and it corrupts one element of an input array, it can totally screw up the average value of the array, but it has generally very little impact on the median. Final comment about the problem is I am going to assume that the array entries are distinct, that is, there's no repeated elements, but just like in our discussions of sorting, this is not a big assumption. I can encourage you to think about how to adapt these algorithms to work even if the arrays do have duplicates. You can indeed still get the same very practical, very fast algorithms with duplicate elements. Now, if you think about it, we already have a pretty darn good algorithm that solves the selection problem. Here's the algorithm. It's 2 simple steps and it runs in O of n log n time. Step 1, sort the input array. We have various subroutines to do that. Let's say we pick merge sort. Now, what is it we're trying to do? We're trying to find the ith smallest element of the input array. Well, once we've sorted it, we certainly know where the ith smallest element is. It's in the ith position of the sorted array. So that's pretty cool. We've just done what a computer scientist would call a reduction, and that's a super useful and super fundamental concept. It's when you realize that you can solve one problem by reducing it to another problem that you already know how to solve. So what we just showed is that the selection problem reduces easily to the sorting problem. We already know how to solve the sorting problem in n log n time, so that gives us an n log n time solution to the selection problem. But again, remember the mantra of any algorithm designer worth their salt is, can we do better? We should avoid contentness. Just because we got n log n doesn't mean we should stop there. Maybe we can be even faster. Now, certainly we're going to have to look at all of the elements in the input array in the worst case. We shouldn't expect to do better than linear, but hey, why not linear time? Actually, if you think about it, we probably should have asked that question back when we were studying the sorting problem. Why were we so content with the n log n time bound for merge sort and the O of n log n time on average bound for quicksort? Well, it turns out we have a really good reason to be happy with our n log n upper bounds for the sorting problem. It turns out, and this is not obvious and will be the subject of an optional video, you actually can't sort an input array of length n better than n log n time, either in the worst case or on average. So in other words, if we insist on solving the selection problem via a reduction to the sorting problem, then we're stuck with this n log n time bound. Okay, strictly speaking, that's for something called comparison sorts. See the video for more details. But the upshot is, if we want a general purpose algorithm and we want to do better than n log n for selection, we have to do it using ingenuity beyond this reduction. We have to prove that selection is a strictly easier problem than sorting. That's the only way we're going to have an algorithm that beats n log n. It's the only way we can conceivably get a linear time algorithm. And that is exactly what is up next on our plate. We're going to show selection is indeed fundamentally easier than sorting. We can have a linear time algorithm for it, even though we can't get a linear time algorithm for sorting. You can think of the algorithm we're going to discuss as a modification of Quicksort, and in the same spirit of Quicksort, it will be a randomized algorithm, and the running time will be an expected running time that will hold for any input array. Now, for the sorting problem, we know that Quicksort that's n log n time on average, where the average is over the coin flips done by the code, but we also know that if we wanted to, we could get a sorting algorithm in n log n time that doesn't use randomization. The merge sort algorithm is one such solution. So here we're giving a linear time solution for selection, for finding order statistics, that uses randomization, and it would be natural to wonder, is there an analog to merge sort? Is there an algorithm which does not use randomization and gets this exact same linear time bound? In fact, there is. The algorithm's a little more complicated and therefore not quite as practical as this randomized algorithm, but it's still very cool. It's a really fun algorithm to learn and to teach. So I will have an optional video about linear time selection without randomization. So for those of you who aren't going to watch that video or want to know what's the key idea, the idea is to choose the pivot deterministically in a very careful way using a trick called the median of medians. That's all I'm going to say about it now. You should watch the optional video if you want more details. I do feel compelled to warn you that if you're going to actually implement a selection algorithm, you should do the one that we discuss in this video, not the linear time one, because the one we'll discuss in this video has both smaller constants and works in place. So what I want to do next is develop the idea that we can modify the quicksort paradigm in order to directly solve the selection problem. So to get an idea of how that works, let me review the partition subroutine. Like in Quicksort, this subroutine will be our workhorse for the selection algorithm. So what the partition subroutine does, it takes as input some jumbled up array, and it's going to solve a problem which is much more modest than sorting. So in partitioning, it's going to first choose a pivot element somehow. We'll have to discuss what's a good strategy for choosing a pivot element. But suppose, in this particular input array, it chooses the first element, this 3, as the pivot element. The responsibility of the partition subroutine then is to rearrange the elements in this array so that the following properties are satisfied. Anything less than the pivot is to the left of it. It can be in jumbled order, but if you're less than the pivot, you better be to the left, like this 2 and 1 is less than the 3. If you're bigger than the pivot, then again, you can be in jumbled order amongst those elements, but all of them have to be to the right of the pivot. And that's true for the numbers 4 through 8. They all are to the right of the pivot 3 in a jumbled order. So this in particular puts the pivot in its rightful position where it would belong in the final sorted array, and at least for quicksort, it enabled us to recursively sort to smaller subproblems. So this is where I want you to think a little bit about how we should adapt this paradigm. So suppose I told you the first step of our selection algorithm is going to be to choose a pivot and partition the array. Now the question is, how are we going to recurse? We need to understand how to find the ith order statistic of the original input array. It suffices to recurse on just one subproblem of smaller size and find a suitable order statistic in it. So how should we do that? Let me ask you that with some very concrete examples about what pivot we choose and what order statistic we're looking for, and see what you think. So the correct answer to this quiz is the second answer. So we can get away with recursing just once, and in this particular example we're going to recurse on the right side of the array. And instead of looking for the fifth order statistic like we were originally, we're going to recursively search for the second order statistic. So why is that? Well, first, why do we recurse on the right side of the array? So by assumption, we have this array with 10 elements. We choose the pivot. We do partitioning. Remember, the pivot winds up in its rightful position. That's what partitioning does. So if the pivot winds up in the third position, we know it's the third smallest element in the array. Now, that's not what we were looking for. We were looking for the fifth smallest element in the array. That, of course, is bigger than the third smallest element of the array. So by partitioning, where is the fifth element going to be? It's got to be to the right of this third smallest element, to the right of the pivot. So we know for sure that the fifth order statistic of the original array lies to the right of the pivot. That is guaranteed. So we know where to recurse on the right-hand side. Now, what are we looking for? We are no longer looking for the fifth order statistic, the fifth smallest element. Why? Well, we've thrown out both the pivot and everything smaller than it. Remember, we're only recursing on the right-hand side. So we've thrown out the pivot, the third element, and everything less than it, the minimum and the second minimum. Having deleted the three smallest elements and originally looking for the fifth smallest, of what remains of what we're recursing on, we're looking for the second smallest element. So the selection algorithm in general is just the generalization of this idea to arbitrary arrays and arbitrary situations of whether the pivot comes back equal to, less than, or bigger than the element you're looking for. So let me be more precise. I'm going to call this algorithm rselect for randomized selection. And according to the problem definition, it takes as input, as usual, an array A of some length n, but then also the order statistic that we're looking for. So we're going to call that I. And of course we assume that I is some integer between 1 and n inclusive. So for the base case, that's going to be if the array has size 1, then the only element we could be looking for is the 1th order statistic, and we just return the sole element of the array. Now we have to partition the array around the pivot element. And just like in Quicksort, we're going to be very lazy about choosing the pivot. We're going to choose it uniformly at random from the n possibilities and hope things work out. And that'll be the crux of the analysis, proving that random pivots are good enough sufficiently often. Having chosen the pivot, we now just invoke the standard partitioning subroutine. As usual, that's going to give us the partitioned array. You'll have the pivot element, you'll have everything less than the pivot to the left, everything bigger than the pivot to the right. As usual, I'll call everything to the left the first part of the partitioned array, and everything bigger the second part. Now we have a couple of cases depending on whether the pivot is bigger or less than the element we're looking for. So I need a little notation to talk about that. So let's let J be the order statistic that P is. So if P winds up being the third smallest element, like in the quiz, then J is going to be equal to 3. Equivalently, we can think of J as defined as the position of the pivot in the partitioned version of the array. Now there's one case which is very unlikely to occur, but we should include it just for completeness. If we're really lucky, then in fact our random pivot just happens to be the order statistic we were looking for. That's when I equals J. We're looking for the ith smallest element. If by dumb luck the pivot winds up being the ith smallest element, we're done. We can just return it. We don't have to recurse. Now in general, of course, we don't randomly choose the element we're looking for. We choose something that, well, it could be bigger or it could be smaller than it. In the quiz, we chose a pivot that was smaller than what we're looking for. Actually, that's the harder case. So let's first start with a case where the pivot winds up being bigger than the element we're looking for. So that means that j is bigger than I. We're looking for the ith smallest. We randomly chose the jth smallest for j bigger than I. So this is the opposite case of the quiz. This is where we know what we're looking for has to be to the left of the pivot. The pivot's the jth smallest, everything less than it's to the left. We're looking for the ith smallest, I is less than j, so that's got to be on the left. That's where we recurse. Moreover, it's clear we're looking for exactly the same order statistic. If we're looking for the third smallest element, we're only throwing out stuff which is bigger than something even bigger than the third smallest element. So we're still looking for the third smallest of what remains. And naturally, the new array size is j minus 1, because that's what is to the left of the pivot. And then finally, the final case is when the random element that we choose is less than what we're looking for, and then we're just like the quiz. So namely, what we're looking for is bigger than the pivot. It's got to be on the right-hand side. We know we got to recurse on the right-hand side. We know the right-hand side has n minus j elements. We threw out everything up to the pivot, so we threw out j things. There's n minus j left. And all of those j things we threw out are less than what we're looking for. So if we used to be looking for the ith smallest element, now we're looking for the I minus jth smallest element. So that is the whole algorithm. That is how we adopt the approach we took toward the sorting problem in Quicksort and adapt it to the problem of selection. So, is this algorithm any good? Let's start studying its properties and understand how well it works. So let's begin with correctness. So the claim is that no matter how the algorithm's coin flips come up, no matter what random pivots we choose, the algorithm is correct in the sense that it's guaranteed to output the ith order statistic. The proof is by induction. It proceeds very similarly to Quicksort, so I'm not going to give it here. If you're curious about how these proofs go, there's an optional video about the correctness of Quicksort. If you watch that and understand it, it should be clear how to adapt that inductive argument to apply to this selection algorithm as well. So as usual for divide and conquer algorithms, the interesting part is not so much understanding why the algorithm works, but rather understanding how fast it runs. So the big question is, what is the running time of this selection algorithm? Now, to understand this, we have to understand the ramifications of pivot choices on the running time. So you've seen the Quicksort videos, they're fresh in your mind. So what should be clear is that just like in Quicksort, how fast this algorithm runs is going to depend on how good the pivots are. And what good pivots means is pivots that guarantee a balanced split. So the next quiz will make sure that you understand this point and ask you to think about just how bad the running time of the selection algorithm could be if you get extremely unlucky in your pivot choices. So the correct answer to this question is exactly the same as the answer for Quicksort. The worst case running time, if the pivots are chosen just in a really unlucky way, is actually quadratic in the array length. Remember, we're shooting for linear time, so this quadratic is a total disaster. So how could this happen? Well, suppose you're looking for the median, and suppose you choose the minimum element as the pivot every single time. So if this is what happens, if every time you choose the pivot to be the minimum, just like in Quicksort, this means every time you recurse, all you succeed in doing is peeling off a single element from the input array. Now, you're not going to find the median element until you've done roughly n over 2 recursive calls, each on an array that has size at least a constant fraction of the original one. So there's a linear number of recursive calls, each on an array of size at least some constant times n, so that gives you a total running time of quadratic overall. Of course, this is an absurdly unlikely event. Frankly, your computer is more likely to be struck by a meteor than it is for the pivot to be chosen as the minimum element in every recursive call, but if you really had an absolutely worst case choice of pivots, it would give this quadratic runtime bound. So the upshot then is that the running time of this randomized selection algorithm depends on how good our pivots are. And for a worst case choice of pivots, the running time can be as large as n squared. Now hopefully most of the time we're going to have much better pivots. And so the analysis proceeds by making that idea precise. So the key to a fast running time is going to be the usual property that we want to see in divide and conquer algorithms, namely every time we recurse, the problem size better not just be smaller, but it better be smaller by a significant factor. How would that happen in this selection approach based on the partition subroutine? Well, if both of the subproblems are not too big, then we're guaranteed that when we recurse, we make a lot of progress. So let's think about what the best possible pivot would be in the sense of giving a balanced split. Right? So of course, in some sense, the best pivot is you just choose the order statistic you're looking for. and then you're done in constant time, but that's extremely unlikely and it's not worth worrying about. So ignore the fact that we might guess the pivot. What's the best pivot if we want to guarantee an aggressive decrease in the input size before the next iteration? Well, the best pivot's the one that gives us as most balanced split as possible. So what's the pivot that gives us the most balanced split, a 50-50 split? Well, if you think about it, it's exactly the median. Of course, this is not super helpful because the median might well be what we're looking for in the first place. So this is sort of a circular idea. But for intuition, it's still worth exploring what kind of running time we would get in the best case, right? If we're not going to get linear time even in this magical best case, we certainly wouldn't expect to get it on average over random choices of the pivots. So what would happen if we actually did luckily choose the median as the pivot every single time? Well, we get the recurrence that the running time that the algorithm requires on an array of length n. Well, there's only going to be one recursive call. So this is the big difference from Quicksort, where we had to recurse on both sides. And we had two recursive calls. So here we're going to have only one recursive call. In the magical case where our pivots are always equal to the median, both subproblem sizes are only half as large as the original one. So when we recurse, it's on a problem size guaranteed to be at most n over 2. And then outside of the recursive call, pretty much all we do is a partitioning invocation, and we know that that's linear time. So the recurrence we get is t of n is at most t of n over 2 plus big O of n. This is totally ready to get plugged into the master method. It winds up being case 2 of the master method, and indeed we get exactly what we wanted, linear time. To reiterate, this is not interesting in its own right. This is just for intuition. This was a sanity check that at least for a best case choice of pivots, we get what we want, a linear time algorithm, and we do. Now the question is, how well do we do with random pivots? Now the intuition, the hope, is exactly as it was for Quicksort, which is the random pivots are a perfectly good surrogate for the median, for the perfect pivot. So having the analysis of Quicksort under our belt, where indeed random pivots do approximate very closely the performance you'd get with best case pivots, maybe now we have reason to believe that this is hopefully true. That said, as a mathematical statement, this is totally not obvious, and it's going to take a proof. That's the subject for the next video. But let me just be clear exactly what we're claiming. Here is the running time guarantee that randomized selection provides. For an arbitrary input array of length n, the average running time of this randomized selection algorithm is linear, big O of n. Let me reiterate a couple points I made for the analogous guarantee for the Quicksort algorithm. The first is that we're making no assumptions about the data whatsoever. In particular, we're not assuming that the data is random. This guarantee holds no matter what input array you feed into this randomized algorithm. In that sense, this is a totally general purpose subroutine. So where then does this averaging come from? Where does the expectation come from? The randomness is not in the data. Rather, the randomness is in the code, and we put it there ourselves. Now let's proceed to the analysis. In this video, I'll explain the mathematical analysis of the randomized linear time selection algorithm that we studied in the previous video. Specifically, I'm going to prove to you the following guarantee for that algorithm. For every single input array of length n, the running time of this randomized selection algorithm, on average, will be linear. Pretty amazing if you think about it, because that's barely more than the time it takes just to read the input. And in particular, this linear time algorithm is even faster than sorting. So this shows that selection is a fundamentally easier problem than sorting. You don't need to reduce to sorting. You can solve it directly in big O of n time. I want to reiterate the same points I made about Quicksort. The guarantee is the same. It is a general purpose subroutine. We make no assumptions about data. This theorem holds no matter what the input array is. The expectation, the average that's in the theorem statement, is only over the coin flips made by the algorithm, made inside its code of our own devising. Before we plunge into the analysis, let me just make sure you remember what the algorithm is. So it's like Quicksort. We partition around a pivot, except we only recurse once, not twice. So we're given an array with some length n. We're looking for the ith order statistic, the ith smallest element. The base case is obvious. If you're not in the base case, you choose a pivot p uniformly at random from the input array, just like we did in Quicksort. We partition around the pivot, just like we did in Quicksort. That splits the array into a first part, those elements less than the pivot, and the second part, those elements which are bigger than the pivot. Now we have a couple cases. The case which is very unlikely, so we don't really worry about it, is if we're lucky enough to guess the pivot as the ith order statistic, what we're looking for. That's when the new position j of the pivot element happens to equal I, what we're looking for. Then, of course, we just return it. That was exactly what we wanted. In the general case, the pivot is going to be in a position J, which is either bigger than what we're looking for, I, that's when the pivot is too big, or J, its position will be less than the order statistic I that we're looking for. That's when the pivot is too small. So if the pivot's too big, if J is bigger than I, then we know that what we're looking for is on the left-hand side amongst the elements less than the pivot, so that's where we recurse. We've thrown out both the pivot and everything to the right of it. That leaves us with an array of J minus 1 elements, and we're still looking for the ith smallest among these J minus 1 smallest elements. And in the final case, this is what we went through in the quiz in the last video, is if we choose a pivot who's smaller than what we're looking for, that's when J is less than I. Then it means we're safe to throw out the pivot and everything less than it. We're safe recursing on the second part, those elements bigger than the pivot. Having thrown out the J smallest elements, we're recursing on an element of length n minus J, and we're looking for the I minus J smallest element in those that remain, having already thrown out the J smallest from the input array. So that's randomized selection. Let's discuss why it's linear time on average. The first thought that you might have, and this would be a good thought, would be that we should proceed exactly the same way that we did in Quicksort. You'll recall that when we analyzed Quicksort, we set up these indicator random variables xij, determining whether or not a given pair of elements got compared at any point in the algorithm. And then we just realized the sum of the comparisons is just the sum over all of these xij's. We applied linearity of expectation, and it boiled down to just figuring out the probability that a given pair of elements gets compared. You can analyze this randomized selection algorithm in exactly the same way, and it does give you a linear time bound on average, but it's a little messy. It winds up being not quite as clean as in the quicksort analysis. Moreover, because of the special structure of the selection problem, we can proceed in an even more slick way here than the way we did with Quicksort. So again, we'll have some constituent random variables. We'll again apply linearity of expectation, but the definition of those random variables is going to be a little bit different than it was in Quicksort. So first, a preliminary observation, which is that the workhorse for this randomized selection procedure is exactly the same as it was in Quicksort, namely it's the partition subroutine. Essentially, all of the work that gets done outside of the recursive calls just partitions the input array around some pivot element, as we discussed in detail in a separate video. That takes linear time. So usually when we say something's linear time, we just use big O notation. I'm going to go ahead and explicitly use a constant C here for the operations outside the recursive call. That'll make it clear that I'm not hiding anything up my sleeves when we do the rest of the analysis. Now what I want to do on this slide is introduce some vocabulary, some notation, which will allow us to cleanly track the progress of this recursive selection algorithm. And by progress, I mean the length of the array on which it's currently operating. Remember, we're hoping for a big win over Quicksort, because here we do only one recursive call, not two. We don't have to recurse on both sides of the pivot, just on one of them. So it stands to reason that we can think about the algorithm as making more and more progress as its single recursive call is operating on arrays of smaller and smaller length. So the notion that will be important for this proof is that of a phase. This quantifies how much progress we've made so far, with higher numbered phases corresponding to more and more progress. We'll say that the rselect algorithm, at some midpoint of its execution, is in the middle of phase J if the array size that the current recursive call is working on has length between 3/4 raised to the j times n and the smaller number 3/4 raised to the j plus 1 times n. For example, think about the case where j equals 0. That says phase 0 recursive calls operate on arrays with size between n, that's the length of the original input array, and 75% of n. So certainly the outermost recursive call is going to be in phase 0 because the input array has size n. And then, depending on the choice of the pivot, you may or may not get out of phase 0 in the next recursive call. If you choose a good pivot and you wind up recursing on something that has at most 75% of the original elements, you will no longer be in phase 0. If you recurse on something that has more than 75% of what you started with of the input array, then you're still going to be in phase 0 even in the second recursive call. So overall, the phase number j quantifies the number of times we've made 75% progress relative to the original input array. And the other piece of notation that's going to be important is I'm going to call xj. So for phase j, xj simply counts the number of recursive calls in which a randomized selection algorithm is in phase j. So this is going to be some integer. It could be as small as 0 if you think about it for some of the phases, or it could be larger. So why am I doing this? Why am I making these definitions of phases and of these xj's? What's the point? Well, again, remember the point was we want to be able to cleanly talk about the progress that the randomized selection algorithm makes through its recursion. And what I want to now show you is that in terms of these xj's, counting the number of iterations in each phase, we can derive a relatively simple upper bound on the number of operations that our algorithm requires. Specifically, the running time of our algorithm can be bounded above by the running time in a given phase and then summing those quantities over all of the possible phases. So we're going to start with a big sum over all the phases j. We're going to look at the number of recursive calls that we have to endure during phase j, so that's xj by definition. And then we're going to look at the work that we do outside of the recursive calls in each recursive call during phase j. Now, in a given recursive call, outside of its recursive call, we do c times m operations, where m is the length of the input array. And during phase j, we have an upper bound on the length of the input array. By definition, it's at most 3/4 raised to the j times n. So that is, we multiply the running time times this constant c. This we inherit from the partition subroutine. And then we can, for the input length, we can put an upper bound of 3/4 raised to the j times n. So just to review where all of these terms come from, this 3/4 j times n is an upper bound on the array size during phase j. This is by the definition of a phase. Then if we multiply that times c, that's the amount of work that we do on each phase j subproblem. How much work do we do in phase j overall? Well, we just take the work per subproblem, that's what's circled in yellow, and we multiply it times the number of such subproblems we have. And of course, we don't want to forget any of our subproblems, so we just make sure we sum over all of the phases j to ensure that at every point we count the work done in each of the subproblems. Okay, so that's the upshot of this slide. We can upper bound the running time of our randomized algorithm very simply in terms of phases and the xj's, the number of subproblems that we have to endure during phase j. So this upper bound on our running time is important enough to give some notation. We'll call this star. This will be the starting point of our final derivation when we complete the proof of this theorem. Now don't forget, we're analyzing a randomized algorithm. So therefore, the left-hand side of this inequality, the running time of r select, that's a random variable. So that's a different number depending on the outcome of the random coin flips of the algorithm. Depending on the random pivots chosen, you'll get different running times. Similarly, the right-hand side of this inequality is also a random variable. That's because the xj's are random variables. The number of subproblems in phase j depends on which pivots get chosen. So to analyze, what we care about is the expectations of these quantities, their average values. So we're going to start modestly, and as usual, this will extend our modest accomplishments to much more impressive ones using linearity of expectation. But our first modest goal is just to understand the average value of an xj, the expected value of xj. We're going to do that in 2 steps. On the next slide, I'm going to argue that to analyze the expectation of xj, it's sufficient to understand the expectation of a very simple coin flipping experiment. Then we'll analyze that coin flipping experiment. Then we'll have the dominoes all set up in a row. And on the final slide, we'll knock them down and finish the proof. So let's try to understand the average number of recursive calls we expect to see in a given phase. So again, just so we don't forget, xj is defined as the number of recursive calls during phase j, where a recursive call is in phase j if and only if the current subarray length lies between 3/4 raised to the j plus 1 times n, and then the larger number of 3/4 raised to the j times n. So again, for example, phase 0 is just the recursive calls in which the array length is between 75% of the original elements and 100% of the original elements. So what I want to do next is point out that a very simple sufficient condition guarantees that we'll proceed from a given phase on to the next phase. So it's a condition guaranteeing termination of the current phase. And it's an event that we've discussed in previous videos, namely that the pivot that we choose gives a reasonably balanced split, 25-75 or better. So recall how partitioning works. We choose a pivot P. It winds up wherever it winds up, and the stuff to the left of it's less than P. The stuff to the right of it's bigger than P. So 25-75 split or better, what I mean is that each of these, the first part and the second part has at most 75% of the elements in the input array. Both have at least 25% and at most 75%. And the key point is that if we wind up choosing a pivot that gives us a split that's at least this good, the current phase must end. Why must the current phase end? Well, if we get a 25-75 split or better, then no matter which case we wind up in the algorithm, we're guaranteed to recurse on a subproblem that has at most 75% of what we started with. That guarantees that whatever phase we're in now, we're going to be in an even bigger phase when we recurse. Now I want you to remember something that we talked about before, which is that you've got a decent chance when you pick a random pivot of getting something that gives you a 25-75 split or better. In fact, the probability is 50%. Right? If you have an array that has the integers from 1 to 100 inclusive, anything from 26 to 75 will do the trick. That'll ensure that at least the first 25 elements are excluded from the rightmost call, and at least the rightmost 25 elements are excluded from the left recursive call. So this is why we can reduce our analysis of the number of recursive calls during a given phase to a simple experiment involving flipping coins. Specifically, the expected number of recursive calls that we are going to see in a given phase j is no more than the expected number of coin flips in the following experiment. Okay, so you have a fair coin, 50% heads, 50% tails. You commit to flipping it until you see a head. And the question is, how many coin flips does it take up to and including the first head that you see? Okay, so at minimum, it's going to be one coin flip. If you get a head the first time, it's 1. If you get a tails, then a head, then it's 2. If it's tails, tails, heads, it's 3, and so on. And you always stop when you get that first head. So what's the correspondence? Well, think of heads as being you're in phase J, and if you get a good pivot that gives you a 25-75 split, call that heads, and it guarantees that you exit this phase J, just like it guarantees that you get to terminate the coin flipping experiment. Now, if you get a pivot which doesn't give you a 25-75 split, you may or may not pass to a higher phase J, but in the worst case, you don't. You stick in phase J if you get a bad split, and that's like getting a tails in the coin flipping experiment, and you have to try again. This correspondence gives us a very elementary way to think about the progress that our randomized selection algorithm is making. So there's one recursive call at every step in our algorithm, and each time we either choose a good pivot or a bad pivot. Both could happen, 50-50 probability. Good pivot means we get a 75-25 split or better. Bad pivot means, by definition, we get a split worse than 25-75. So what have we accomplished? We've reduced the task of upper bounding the expected number of recursive calls in a phase J to understanding the expected number of times you have to flip a fair coin before you get one heads. So on the next slide, we'll give you the classical and precise answer to this coin flipping experiment. So let me use capital N to denote the random variable, which we were just talking about, the number of coin flips you need to do before you see the first heads. And it's not very important, but you should know that these random variables have their own name. This would be a geometric random variable with parameter 1/2. So you can use a few different methods to compute the expected value of a geometric random variable such as this, and brute force using the definition of expectation works fine as long as you know how to manipulate infinite sums. But for the sake of variety, let me give you a very sneaky proof of what its expectation is. So the sneaky approach is to write the expected value of this random variable in terms of itself, and then solve for the unknown, solve for the expectation. So let's think about it. So how many coin flips do you need? Well, for sure, you're going to need 1. That's the best case scenario. And now two things could happen. Either you get heads, and that happens with 30% probability, you stop. Or you get tails, that happens with 50% probability. And now you start all over again. Again, you just flip coins until you get the first heads. On average, how many times does that take? Well, by the definition of capital N, you expect the expectation of n coin flips in the case where you get tails and you have to start all over. So this 1 represents the first coin flip. The 1/2 is the probability that you can't stop, that you have to start all over, probability of tails. And then, because it's a memoryless process, because when you start anew on the second coin flip having gotten the tails, it's as if you're back at time 1 all over again. So now we have a trivial equation in terms of the unknown expected value of n, and the unique solution, the unique value that the expected value of capital N could have in light of this equation is 2. So on average, if you flip a fair coin and stop when you get heads, you're going to see 2 coin flips on average. To make sure you haven't sort of lost the forest for the trees, let me remind you why we were talking about this coin flipping analysis in the first place. So recall on the previous slide, we showed that xj, and remember xj is the number of recursive calls you expect to see in a given phase j, and we argued that the number of recursive calls you're going to see is bounded above by the expected number of coin flips until it heads. So this exact calculation of 2 for the coin flips gives us an upper bound of 2 for the number of recursive calls on average in any given phase j. So now we got all our ducks lined up in a row. Let's wrap up the proof on this final slide. So inherited from part 1 of the proof, we have an upper bound on the expected running time of the R-select algorithm. This is what we were calling star on the first proof slide. In star, it looked a little messy, but we had the sum over the phases j, but we had two things that were independent of j, the constant c and the original input length n. So let me just yank the c and the n out front. And then we have this residual sum over the phases j of 3/4 raised to the j. Remember, that comes from our upper bound on the subproblem size during phase j. And then, of course, we have to keep track of how many phase j subproblems we got to solve. That, by definition, is xj. Now, star was written as a inequality in terms of the random variables. Now we're going to go ahead and take the expectations. And again, I've said this over and over, but don't forget, where does the expectation come from? This is over the random pivot choices that our code makes. So the expected running time of the algorithms is mostly the expectation of this starred quantity. So like I said earlier, pretty much every time we're going to do any analysis of a randomized process, we're going to wind up using linearity of expectation at some point. Here's where we do it. Linearity of expectation says the expectation of a sum is just the sum of the expectations. So we yank the c and the n outside of the expectation. We yank this sum over phases outside of the expectation. We yank this 3/4 raised to the j outside of the expectation, and then we just have the expected value of xj, the average number of recursive calls we expect to see in phase j. Now, in the previous two slides, we figured out an upper bound on how many recursive calls we expect to see in each phase. So first, by the coin flip analysis, by the reduction to the coin flip analysis, this is the most expected number of coin flips n, which on the previous slide we argued was exactly 2. So bringing that 2 out in front of the sum, that no longer depends on j. So we get a most 2cn times the sum over phases j of 3/4 raised to the j. Now, this kind of sum we have seen previously in the course. It came up when we were analyzing the master method, and we summed up our running time upper bounds over the levels of our recursion tree. And if we're not in case 1, if we were in case 2 or 3, we had geometric sums that were non-trivial, that required a certain formula to calculate. So let me remind you of that formula here, when 3/4 is the number being powered up to the j. So this has value at most 1 over 1 minus the number that's getting powered. So in this case, it's 3/4. So 1 minus 3/4 is a quarter. You take the reciprocal, you get 4. And the upshot is that the expected number of operations that this randomized selection algorithm uses to find the ith ordered statistic in a given input array is 8 times c times n, where c is the hidden constant in the linear running time of partition. And so that completes the proof. The input array was arbitrary. We showed the expected running time over the random choices of the algorithm is linear in n. That is only a constant factor larger than what is required to read the input. Pretty amazing. Previous videos covered an outstanding algorithm for the selection problem, the problem of computing the ith order statistic of a given array. That algorithm, which we called the R-select algorithm, was excellent in two senses. First, it's super practical, it runs blazingly fast in practice, but also it enjoys a satisfying theoretical guarantee. For every input array of length n, the expected running time of R-select is big O of n, where the expectation is over the random choices of the pivots that R-select makes during its execution. Now, in this optional video, I'm going to teach you yet another algorithm for the selection problem. Well, why bother, given that R-select is so good? Well, frankly, I just can't help myself. The ideas of this algorithm are just too cool not to tell you about, at least in an optional video like this one. The selection algorithm we'll cover here is deterministic. That is, it uses no randomization whatsoever, and it's still going to run in linear time, big O of n time, but now in the worst case for every single input array. Thus, the same way merge sort gets the same asymptotic running time, big O of n log n, as quicksort gets on average, this deterministic algorithm will get the same running time O of n as the rselect algorithm does on average. That said, the algorithm we're going to cover here, well, it's not slow. It's not as fast as rselect in practice, both because the hidden constants in it are larger, and also because it doesn't operate in place. For those of you who are feeling keen, you might want to try coding up both the randomized and the deterministic selection algorithms and make your own measurements about how much better the randomized one seems to be. But if you have an appreciation for brilliant algorithms, I think you'll enjoy these lectures nonetheless. So let me remind you the problem. This is the ith order statistic problem. So we're given an array. It has n distinct entries. Again, the distinctness is for simplicity. And you're given a number I between 1 and n. You're responsible for finding the ith smallest number, which we call the ith order statistic. For example, if I is something like n over 2, then we're looking for the median. So let's briefly review the randomized selection algorithm. We can think of the deterministic algorithm covered here as a modification of the randomized algorithm, the rselect algorithm. So when that algorithm is passed an array with length n, and when you're looking for the ith order statistic, as usual there's a trivial base case, but when you're not in the base case, just like in quicksort, what you do is you're going to partition the array around a pivot element p. Now, how are you going to choose p? Well, just like quicksort, in the randomized algorithm, you choose it uniformly at random. So each of the n elements of the input array are equally likely to be chosen as the pivot. So call that pivot p. Now do the partitioning. Remember, partitioning puts all of the elements less than the pivot to the left of the pivot. We call that the first part of the partitioned array. Anything bigger than the pivot gets moved to be right of the pivot. We call that the second part of the array. And let j denote the position of the pivot in this partitioned array. Equivalently, let j be what order statistic the pivot winds up happening to be, right? So if we happen to choose the minimum element, then j is going to be equal to 1. If we happen to choose the maximum element, j is going to be equal to n, and so on. So there's always the lucky case, chance 1 in n, that we happen to choose the ith order statistic as our pivot. So we're going to find that out when we just notice that j equals I. In that super lucky case, we just return the pivot and we're done. That's what we were looking for in the first place. Of course, that's so rare, it's not worth worrying about. So really the two main cases depend on whether the pivot that we randomly choose is bigger than what we're looking for, or if it's less than what we're looking for. So if it's bigger than what we're looking for, that means j is bigger than I. We're looking for the ith smallest. We randomly chose the jth smallest. Then remember, we know that the ith smallest element has to lie to the left of the pivot element in that first part of the partitioned array. So we recurse there. It's an array that has j minus 1 elements in it, everything less than the pivot, and we're still looking for the ith smallest among them. In the other case, this was the case covered in a quiz a couple videos back, if we guess a pivot element that is less than what we're looking for, well then we should discard everything less than the pivot and the pivot itself. So we should recurse on the second part of A, stuff bigger than the pivot. We know that's where what we're looking for lies. And having thrown away j elements, the smallest ones at that, we're recursing on an array of length n minus j. I'm looking for the I minus jth smallest element in that second part. So that was the randomized selection algorithm, and you'll recall the intuition for why this works is random pivots should usually give pretty good splits. So the way the analysis went is we showed that each iteration, each recursive call, with 50% probability we get a 25-75 split or better. Therefore, on average, every 2 recursive calls, we are pretty aggressively shrinking the size of the recursive call, and for that reason we should get something like a linear time bound. We do almost as well as if we pick the median in every single call, just because random pivots are a good enough proxy of best case pivots of the median. So now the big question is, suppose we weren't permitted to make use of randomization. Suppose this choose a random pivot trick was not in our toolbox. What could we do? How are we going to deterministically choose a good pivot? Okay, so let's just remember quickly what it means to be a good pivot. A good pivot is one that gives us a balanced split after we do the partitioning of the array. That is, we want as close to a 50-50 split between the first and the second parts of the partitioned array as possible. Now, what pivot would give us the perfect 50-50 split? Well, in fact, that would be the median. But that seems like a totally ridiculous observation because we canonically are trying to find the median. So previously we were able to be lazy and we just picked a random pivot and used that as a pretty good proxy for the best case pivot. But now we have to have some subroutine that deterministically finds us a pretty good approximation of the median. And the big idea in this linear time selection algorithm is to use what's called the median of medians as a proxy for the true median of the input array. So when I say median of medians, you're not supposed to know what I'm talking about, You're just supposed to be intrigued. Now let me explain a little bit further. Here's the plan. We're going to have our new implementation of ChoosePivot, and it's going to be deterministic. You will see no randomization on this slide, I promise. So the high-level strategy is going to be we're going to think about the elements of this array like sports teams, and we're going to run a tournament, a 2-round knockout tournament, and the winner of this tournament is going to be who we return as the proposed pivot element. Then we'll have to prove that this is a pretty good pivot element. So there's going to be 2 rounds in this tournament. Each element, each team is going to first participate in a world group, if you will. So there will be small groups of 5 teams each, 5 elements each. And to win your first round, you have to be the middle element out of those 5. So that'll give us n over 5 first round winners. And then the winner of that second round is going to be the median of those n over 5 winners from the first round. Here are the details. The first step isn't really something you actually do in the program, it's just conceptually. So logically, we're going to take this array capital A, which has n elements, and we're going to think of it as comprising n over 5 groups with 5 elements each. So if n is not a multiple of 5, obviously there'll be one extra group that has size between 1 and 4. Now for each of these groups of 5, we're going to compute the median, so the middle element of those 5. Now for 5 elements, we may as well just invoke our reduction to sorting. We're just going to sort each group separately and then use the middle element, which is the median. It doesn't really matter how you do the sorting because after all there's only 5 elements, but let's use merge sort. What the heck. Now what we're going to do is we're going to take our first round winners and we're going to copy them over into their own private array. Now this next step is the one that's going to seem dangerously like cheating, dangerously like I'm doing something circular and not actually defining a proper algorithm. So C, you'll notice, has length over n over 5. We started with an array of length n. This is a smaller input. So let's recursively compute the median of this array capital C. That is the second round of our tournament. Amongst the n over 5 first round winners, the n over 5 middle elements of the sorted groups, we recursively compute the median. That's our final winner, and that's what we return as the pivot element from this subroutine. Now I realize it's very hard to keep track of both what's happening internal to this ChoosePivot subroutine and what's happening in the calling function of our deterministic selection algorithm. So let me put them both together and show them to you cleaned up on a single slide. So here is the proposed deterministic selection algorithm. So this algorithm uses no randomization. Previously, the only randomization was in choosing the pivot. Now we have a deterministic subroutine for choosing the pivot, and so there's no randomization at all. I've taken the liberty of inlining a ChoosePivot subroutine. So that is exactly what lines 1, 2, and 3 are. I haven't written down the base case just to save space. I'm sure you can remember it. So if you're not in the base case, what did we do before? The first thing we did was choose a random pivot. What do we do now? Well, we have steps 1 through 3. We do something much more clever to choose a pivot. And this is exactly what we said on the last slide. We break the array into groups of 5. We sort each group, for example, using merge sort. We copy over the middle element of each of the n over 5 groups into their own array capital C. And then we recursively compute the median of C. So when we recurse on select, we pass it the input C. C has n over 5 elements, so that's the new link. That's a smaller link than what we start with, so it's a legitimate recursive call. We're finding the median of n over 5 elements, so that's going to be the n over 10th order statistic. As usual, to keep things clear, I'm ignoring stuff like fractions. In your real implementation, you would just round it up or down, as appropriate. So steps 1 through 3 are the new ChoosePivot subroutine that replaces the randomized selection that we had before. Steps 4 through 7 are exactly the same as before. We've changed nothing. All we have done is ripped out that one line where we chose the pivot randomly and pasted in these lines 1 through 3. That is the only change to the randomized selection algorithm. So the next quiz is a sanity check that you understand this algorithm, at least not necessarily why it's fast, but at least just how it actually works. And it only asks you to identify how many recursive calls there are each time. So for example, in merge sort, there's 2 recursive calls. In quicksort, there's 2 recursive calls. In rselect, there's 1 recursive call. How many recursive calls do you have each time outside of the base case in the deselect algorithm? All right, so the correct answer is 2. There are 2 recursive calls in deselect. And maybe the easiest way to answer this question is not to think too hard about it and literally just inspect the code and count, right? Namely, there's 1 recursive call in line 3, and there's 1 recursive call in either 6 or 7. So quite literally, there's 7 lines of code, and 2 of the ones that get executed have a recursive call. So the answer is 2. Now, what's confusing is that in the couple of things. First, in the randomized selection algorithm, we only had 1 recursive call. We had the recursive call in line 6 or 7. We didn't have this one in line 3. That one in line 3 is new compared to the randomized procedure. So we're kind of used to thinking of 1 recursive call using the divide and conquer approach to selection. Here we have 2. Moreover, conceptually, the role of these 2 recursive calls are different. So the one in line 6 or 7 is the one we're used to. That's after you've done the partitioning, so you have a smaller subproblem, and then you just recursively find the residual order statistic in the residual array. That's sort of the standard divide and conquer approach. What's sort of crazy is this second use of a recursive call, which is part of identifying a good pivot element for this outer recursive call. And this is so counterintuitive, many students in my experience don't even think that this algorithm will halt. They sort of expect it to go into an infinite loop. But again, that's sort of overthinking it. Okay, so let's just compare this to an algorithm like merge sort. What does merge sort do? Well, it does 2 recursive calls, and it does some other stuff. Okay? It does linear work. That's what it does to merge. And then there are 2 recursive calls on smaller subproblems, right? No issue. We definitely feel confident that merge sort is going to terminate because the subproblems keep getting smaller. What does deselect do if you squint? So don't think about the details. Just at a high level, what is the work done in deselect? Well, there are 2 recursive calls. There's the one's in line 3, one's in line 6 or 7. But there's 2 recursive calls on smaller subproblem sizes. And it does some other stuff. It does some stuff in steps 1 and 2 and 4. But whatever. Those aren't recursive calls. It does some work. 2 recursive calls and smaller subproblems. It's got to terminate. We don't know what the runtime is, but it's got to terminate. Okay? So if you're worried about this terminating, forget about the fact that the 2 recursive calls have different semantics, and just remember, if ever you only recurse on smaller subproblems, you're definitely going to terminate. Now, of course, who knows what the running time is? I owe you an argument about why it would be anything reasonable. That's going to come later. In fact, what I'm going to prove to you is not only does this selection algorithm terminate, run in finite time, it actually runs in linear time, no matter what the input array is. So whereas with rselect, we could only discuss its expected running time being linear, we showed that with disastrously bad choices for pivots, rselect can actually take quadratic time. Under no circumstances will deselect ever take quadratic time. So for every input array, it's big O of n time. There's no randomization because we don't randomly do anything and choose pivot. So there's no need to talk about average running time. Just the worst case running time over all inputs is O of n. That said, I want to reiterate the warning I gave you at the very beginning of this video, which is if you actually need to implement a selection algorithm, this one wouldn't be a disaster, but it is not the method of choice. So I don't want you to be misled. As I said, there were 2 reasons for this. The first is that the constants hidden in the big O notation are larger for deselect than for rselect. That will be somewhat evident from the analyses that we give for the 2 algorithms. The second reason is, recall we made a big deal about how partitioning works in place, and therefore Quicksort and rselect also both work in place, that is with no real additional memory storage. But in this deselect algorithm, we do need this extra array C to copy over the middle elements, the first round winners, and so that extra memory, as usual, slows down the practical performance. One final comment. So for many of the algorithms that we cover, I hope I explained them clearly enough that their elegance shines through, and that for many of them you feel like you could have come up with it yourself, but if only you'd been in the right place at the right time. I think that's a great way to feel and a great way to appreciate some of these very cool algorithms. That said, linear time selection, I don't blame you if you feel like you never might have come up with this algorithm. I think that's a totally reasonable way to feel after you see this code. If it makes you feel better, let me tell you about who came up with this algorithm. It's quite old at this point, about 40 years, from 1973. And the authors, there are 5 of them, and at the time this was very unusual. So Manuel Blum, Bob Floyd, Von Pratt, Ron Levesque, and Bob Tarjan. And this is a pretty heavyweight lineup. So as we've discussed in the past, the highest award in computer science is the ACM Turing Award, given once each year. And I like to ask my algorithms classes how many of these authors do they think have been awarded a Turing Award. I've asked it many times. The favorite answer anyone's ever given me has been 6, which I think is, in spirit, should be correct. Strictly speaking, the answer is 4. So the only one of these 5 authors that doesn't have a Turing Award is von Pratt, although he's done remarkable things spanning the gamut from co-founding Sun Systems to having very famous theorems about, for example, testing primality. But the other 4 have all been awarded the Turing Award at some point. So in chronological order, so the late Bob Floyd, who was a professor here at Stanford, was awarded the 1978 Turing Award, both for contributions to algorithms, but also to programming languages and compilers. So Bob Tarjan, who, as we speak, is here as a visitor at Stanford and has spent his PhD here and has been here as a faculty at other times, was awarded it for contributions to graph algorithms and data structures. We'll talk some more about some of his other contributions in future courses. Manuel Blum was awarded the Turing Award in '95, largely for contributions in cryptography. And many of you probably know Ron Rivest as the R in the RSA crypto system. So he won the Turing Award along with Shamir and Edelman back in '02. So in summary, if this algorithm seems like one that might have eluded you even on your most creative days, I wouldn't feel bad about it. This is a quite clever algorithm. So let's now turn to the analysis and explain why it runs in linear time in the worst case. Now let's turn to the analysis of the deterministic selection algorithm that we discussed in the last slide by Blum, Floyd, Pratt, Rivest, and Tarjan. In particular, let's prove that it runs in linear time on every possible input. Let's remind you what the algorithm is. So the idea is we just take the rselect algorithm, but instead of choosing a pivot at random, we do quite a bit more work to choose what we hope is going to be a guaranteed pretty good pivot. So again, lines 1 through 3 are the new choose pivot subroutine, and it's essentially implementing a 2-round knockout tournament. So first we do the first round matches. So what does that mean? That means we take A, we think of it as comprising these groups of 5 elements. So the first 5 elements, 1 through 5, then the elements 6 through 10, the elements 11 through 15 in the array, and so on. We sort each of those 5 using, let's say, merge sort, although it doesn't matter much. Then the winner of each of these n over 5 first round matches is the median of those 5. That is the third largest element out of the 5. So we take those n over 5 first round winners, the middle element of each of the 5 in the sorted groups. We copy those over into a new array, capital C, of length n over 5. And then we run the second round of our tournament, at which we elect the median of these n over 5 first round winners as our final pivot, as our final winner. So we do that by recursively calling deselect on C. It has length n over 5, we're looking for the median, so that's the n over 10th order statistic in that array. So we call the pivot P, and then we just proceed exactly like we did in the randomized case. That is, we partition A around the pivot, we get a first part, a second part, and we recurse on the left side or the right side as appropriate, depending on whether the pivot is less than or bigger than the element that we're looking for. So the claim is, believe it or not, that this algorithm runs in linear time. Now, you'd be right to be a little skeptical of that claim. Certainly you should be demanding from me some kind of mathematical argument about this linear time claim. It's not at all clear that that's true. One reason for skepticism is that this is an unusually extravagant algorithm in 2 senses for something that's going to run in linear time. First is its extravagant use of recursion. There are 2 different recursive calls, as discussed in the previous video, and we have not yet seen any algorithm that makes 2 recursive calls and runs in linear time. The best case scenario was always n log n time for our 2 recursive call algorithms like merge sort or quicksort. The second reason is that outside of the recursive calls, it seems like it does kind of a lot of work as well. So to drill down on that point and get a better understanding for how much work this algorithm is doing, the next quiz asks you to focus just on line 1. So when we sort groups of 5 in the input array, how long does that take? So the correct answer to this quiz is the third answer. Maybe you would have guessed that, given that I'm claiming that the whole algorithm takes linear time. You could have guessed that this subroutine wouldn't be worse than linear time. But you should also be wondering, isn't sorting always n log n? So aren't we doing sorting here? Why isn't the n log n thing kicking in? The reason is we're doing something much, much more modest than sorting the length n input array. All we're sorting are these puny little subarrays that have only 5 elements. And that's just not that hard. That can be done in constant time. So let me be a little more precise about it. The claim is that sorting an array with 5 elements takes only some constant number of operations. Let's say 120.
Where did this number 120 come from? Well, for example, suppose we use merge sort. If you go back to those very early lectures, we actually counted up the number of operations that merge sort needs to sort an array of length m for some generic m. Here m is 5, so we can just plug 5 into our previous formula that we computed for merge sort. Right? If we plug m equal 5 into this formula, what do we get? We get 6 times 5 times log base 2 of 5 plus 1. Who knows what log base 2 of 5 is? That's some weird number, but it's going to be at most 3, right? So if that's at most 3, 3 plus 1 is 4, multiply that by 5, then again times 6, and boom, you get your 120. So it's constant time to sort just one of these groups of 5. Now, of course, we have to do a bunch of groups of 5, but there's only a linear number of groups, constant per each, so that's going to be linear time overall. So to be really pedantic, we do 120 operations at most per group. There's n over 5 different groups. We multiply those, we get 24n operations to do all the sorting, and that's obviously a big O of n. So linear time for step 1. So having warmed up with step 1, let's look now at the whole 7-line algorithm and see what's going on. Now, I hope you haven't forgotten the paradigm that we discussed for analyzing the running time of deterministic divide and conquer algorithms, like this one. So, namely, we're going to develop a recurrence, and remember, a recurrence expresses the running time, the number of operations performed, in 2 parts. First of all, there's the work done by the recursive calls on smaller subproblems, and secondly, there's the work done locally, not in the recursive calls. So let's just go through these lines one at a time and just do a running tally of how much work is done by this algorithm, both locally and by the recursive calls. So the quiz was about step number 1. We just argued that since it's constant time to sort each group and there's a linear number of groups, we're going to do linear work, theta of n, for step 1. So copying these first round winners over into their special array C is obviously linear time. Now when we get to the third line, we have a recursive call, but it's a quite easy recursive call to understand. It's just recursing on an array that has size 20% as large as the one we started with, on n over 5 elements. So this, remember the notation we use for recurrences. Generally we denote by capital T the running time of an algorithm on arrays of a given length. So this is going to be the running time that our algorithm has in the worst case on inputs of length n over 5, because n over 5 is the length of the array that we're passing to this recursive call. Good. Step 4, partition. Well, we had videos about how to implement partition and why it's linear time. We knew that all the way back in Quicksort. So that's definitely theta of n. Step 5 is constant time. I'm not going to worry about it. And finally, we get to lines 6 and 7. So at most, one of these will execute. So in either case, there's one recursive call. So that's fine. We know in recurrences, when there's a recursive call, we just write capital T of whatever the input length is. So we just have to figure out what the input length here is. It was n over 5 in line 3. So we just have to figure out what it is in line 6 or 7. Oh yeah, now we're remembering why we didn't use recurrences when we discussed randomized quicksort and the randomized selection algorithm. It's because we don't actually know how big the recursive call is, how big the input passed to this recursive call in line 6 or 7 is. Line 3, no problem. It's guaranteed to be 20% of the input array because that's how we define it. But for line 6 or 7, the size of the input array that gets passed to the recursive call depends on how good the pivot is. It depends on the splitting of the array A into the 2 parts, which depends on the choice of the pivot P. So at the moment, all we can write is T of question mark. We don't know. We don't know how much work gets done in that recursion because we don't know what the input size is. Let me summarize the results of this discussion. So I'm going to write down a recurrence for the deselect algorithm. So let T of n denote the maximum number of operations that deselect ever requires to terminate on an array input of length n. This is just the usual definition of T of n we use in recurrences. What we established in our tally on the last slide is that deselect does linear stuff outside the recursive calls. It does the sorting of groups of 5, it does the copying, and it does the partitioning. Each of those is linear, so all of them together is also linear. And then it does 2 recursive calls. One whose size we understand, one whose size we don't understand. So for once, I'm not going to be sloppy, and I'm going to write out an explicit constant about the work done outside the recursive calls. I'm not going to write big O of n. I'm going to actually write C times n for some constant C. So So of course, no one ever cares about base cases, but for completeness, let me write it down anyways. When deselect gets an input of only one element, it returns it. Let's call that one operation for simplicity. And then in the general case, and this is what's interesting, when you're not in the base case, when you have to recurse, what happens? Well, you do linear work outside of the recursive calls, so that's c times n for some constant c. C is just the linear, the expressed constant in all of our big thetas on the previous slide. Plus the recursive call in line 3, and we know that happens on an array of size n over 5. As usual, I'm not going to worry about rounding up or rounding down, it doesn't matter. Plus our mystery recursive call on an array of unknown size. So that's where we stand, and we seem stuck because of this pesky question mark. So let's prove a lemma, which is going to replace this question mark with something we can reason with an actual number that we can then analyze. So the upshot of this key lemma is that all of our hard work in our choose pivot subroutine in lines 1 through 3 bears fruit in the sense that we're guaranteed to have a pretty good pivot. It may not be the median, it may not give us a 50-50 split. Then we could replace the question mark with 1/2 times n, but it's going to let us replace the question mark by a 7/10 times n. Now, I don't want to lie to you. I'm going to be honest, it's not quite 7/10 n. It's more like 7/10 n minus 5. There's a little bit of additive error. So taking care of the additive error adds nothing to your conceptual understanding of this algorithm or why it works. But for those of you who want a truly rigorous proof, there are some posted lecture notes which go through all the gory details. But in lecture, I'm just going to tell you what's sort of morally true and ignore the fact that we're going to be off by 3 here and 4 there. And it will be clear when I show you the proof of this lemma where I'm being a little bit sloppy and why it really shouldn't matter, and it doesn't. So to explain why this key lemma is true, why we get a 30-70 split or better guaranteed, let me set up a little notation. I'm getting sick of writing n over 5 over and over again, so let's just give that a synonym. Let's say k. So this is the number of different sort of first round matches that we have, the number of groups. I also want some notation to talk about the first round winners, that is the medians of these groups of 5, the k first round winners. So we're going to call xi the ith smallest of those who win their first round match, who make it to the second round. So just to make sure the notation is clear, we can express the pivot element in terms of these x's. Remember, the pivot is the final winner. It wins not only its first round tournament, but also the second round tournament. It's not only the middle element of the first group of 5, it's actually the median of the n over 5 middle elements. It's the median of the medians. That is, of the k middle elements, it's the k over 2th order statistic, k over 2th smallest. I'm saying this assuming that k is even. If k was odd, it would be some slightly different formula, as you know. So let's remember what we're trying to prove. We're trying to prove that for our proposed pivot, which is exactly this element x sub k over 2, it's exactly the winner of this 2-round knockout tournament, we're trying to argue that for this proposed pivot, we definitely get a 30-70 split or better. So what that means is there better be at least 30% of the elements that are bigger than the pivot. That way, if we recurse on the left side in the first part, we don't have to deal with more than 70% of the original elements. Similarly, there better be at least 30% of the elements that are smaller than the pivot. That way, if we recurse on the right-hand side, we know we don't have to deal with more than 70% of the original input elements. So if we achieve this goal, we prove that there's at least 30% on each side of xk over 2, then we're done. That proves the key lemma, that we get a 30-70 split or better. So I'm going to show you why this goal is true. I'm going to introduce a thought experiment, and I'm going to lay out it abstractly. Then we'll sort of do an example to make it more clear, and then we'll go back to the general discussion and finish the proof. So what we're going to do is a thought experiment for the purposes of counting how many elements of the input array are bigger than our pivot choice and how many are smaller. So in our minds, we're going to imagine that we take the n elements in A and we arrange them in a 2D grid. So here are the semantics of this grid. Each column will have exactly 5 elements, and it will correspond to one of the groups of 5. So we'll have n over 5 columns corresponding to our n over 5 groups in our first round of our tournament. If n is not a multiple of 5, then one of these groups has size between 1 and 4, but I'm just not going to worry about it. That's some of the additive loss, which I'm ignoring.
Moreover, we're going to arrange each column in a certain way so that going from bottom to top, the entries of that group go from smallest to largest. So this means that in this grid we have 5 rows, and the middle row, the third row, corresponds exactly to the middle elements, to the winners of the first round matches. So because these middle elements, these first round winners, are treated specially, I'm going to denote them with big squares. The other 4 elements of the group, 2 of which are smaller, 2 of which are bigger, are just going to be little circles. Furthermore, in this thought experiment, in our mind, we're going to arrange the columns from left to right in order of increasing value of the middle element. Now remember, I introduced this notation, x sub I is the ith smallest amongst the middle elements. So a different way of what I'm trying to say is that the leftmost column is the group that has x1 as its middle element. So among the n over 5 middle elements, one of the groups has the smallest middle element. We put that all the way on the left. So this is going to be x1 in the first column, the smallest of the first round winners. x2 is the second smallest of the first round winners. x3 is the third smallest, and so on. At some point we get to the median of the first round winners, xk over 2. And then way at the right is the largest of the first round winners. And I'm sure that you remember that the median of medians, which is xk over 2, is exactly our pivot. So this is our lucky winner. I know this is a lot to absorb, so I'm going to go ahead and go through an example. If what I've said so far makes perfect sense, you should feel free to skip the following example. But if there's still some details you're wondering about, I'm hoping this example will make everything crystal clear. So let's suppose we have an input array. I need a slightly big one to make the grid make sense. So let's say there's an input array of 20 elements. So there's going to be the input array, which is in a totally arbitrary order. There's going to be the version of the array after we sort each group of 5. And then I'm going to show you the grid. So here's the input array we're going to use. Let's now go ahead and delineate the various groups of 5. So after sorting each group, we get the following. From each group, there's a single winner, namely the middle element. So that would be the 12 and the 6 and the 9 and the 14. Those are the 4 survivors from the first round of the tournament. And the median of these 4 elements, which at the end of the day is going to be our pivot, is the second smallest of the 4. That's how we define the median for an even number of elements. So that's going to be the 9. So this first transformation from the input array to this vaguely mini-sorted version of this input array with the groups of 5 sorted, this we actually do in the code. This happens in the algorithm. Now this grid we're just doing in our minds. Okay? We're just in the middle of proving why the algorithm is fast, why the pivot's guaranteed to give us close to a 30-70 split or better. So let me show you an example of this grid in our mind, what it looks like for this particular input. So the grid always has 5 rows. The columns always have 5 elements because the columns correspond to the groups. Here, because n equals 20, n over 5 is 4. So there's going to be 4 columns and 5 rows. And moreover, we arrange the columns from left to right so that these middle elements go from smallest to largest. So our middle elements are 6, 9, 12, and 14, and we're going to draw the columns in that order from left to right. So first we'll write down the middle elements, the middle row, from decreasing to increasing, 6, 9, 12, 14. Again, the median of these is our pivot, which is the 9. And then each column is just the other 4 elements that goes along with this middle element from decreasing to increasing as we go from bottom to top. So this is the grid that we've been talking about on the other slide in this particular example. So I hope that makes what we're talking about clear, what these X's mean and what order we have amongst the rows, amongst the columns, and so on. So let's go back to the general argument. Here is the key point. Here is why we're doing this entire thought experiment. It's going to let us prove our key lemma that we get a 30-70 split or better. 30% of the stuff at least is less than the pivot. 30% of the stuff at least is bigger than the pivot. So why is there at least 30% of the stuff below the pivot? Why is the pivot bigger than at least 30%? Well, it's bigger than everything to the left and everything below the stuff to the left.
That is, we know that xk over 2 is bigger than the k over 2 minus 1 elements that are to the left of it, those other middle elements that it's bigger than. That's because it's the median of the medians. So if we just go straight west from the pivot, we only see stuff which is less. Furthermore, these columns are arranged from decreasing to increasing order as we go from south to north, from bottom to top. So if we travel south from any of these smaller x sub i's, we only see stuff which is still smaller. So all we're using here is transitivity of the less than relation. You go straight west, you see stuff which is only smaller. From any of those points, if you go southward, you'll see stuff which is even smaller than that. So this entire yellow region, everything southwest of the pivot element is smaller than it. And that's a good chunk of the grid, right? So for all of these columns, it's basically 3 out of the 5, or 60% of them, are smaller than the pivot, and half of the columns essentially are in this part of the grid. So if the pivot's bigger than 60% of the stuff in 50% of the groups, that means it's bigger than 30% of the elements overall. And if we reason in an exactly symmetric way, we find that the pivot is also smaller than at least 30% of the array. So to find things bigger than the pivot, what do? First, we travel eastward. That gives us middle elements that are only bigger than it. And then we stop wherever we want on our eastward journey and we head north. And we're going to see stuff which is still bigger. So this entire northeastern corner is bigger than the pivot element. And again, that's 50%. That's at 60% of roughly 50% of the groups. Returning to our example, the southwest region of the 9 is this stuff, 1, 3, 4, 5, 6. Certainly all of that is smaller than the 9. You'll notice there's other things smaller than the 9 as well. There's the 8, there's the 2, there's the 7, which we're not counting. But it depends on the exact array, whether or not in those positions you're going to have stuff smaller than the pivot or not. So it's this yellow region we're guaranteed to be smaller than the pivot. Similarly, everything northeast of the pivot is bigger than it. Those are all double-digit numbers, and our pivot is 9. Again, there's some other stuff in other regions bigger than the pivot, the 20, the 10, the 11. But again, those are positions where we can't be guaranteed that it will be bigger than the pivot. So it's the yellow regions which are guaranteed to be bigger and smaller than the pivot. And that gives us the guaranteed 30-70 split. Okay, so that proof was hard work, showing that this deterministic choose pivot subroutine guarantees a 30-70 split or better. And you probably feel a little exhausted and like we deserve a QED at this point. But we haven't earned it. We have not at all proved that this deterministic selection algorithm runs in linear time. Why doesn't a guaranteed 30-70 split guarantee us linear time automatically? Well, we had to work pretty hard to figure out this element guaranteeing this 30-70 split. In particular, we had to invoke another recursive call. So maybe this was a Pyrrhic victory. Maybe we had to work so hard to compute the pivot that it outweighs the benefit we get from this guaranteed 30-70 split. So we still have to prove that's not the case. Even in conjunction doing both of these things, we still have our linear time bound. We'll finish the analysis in the next video. So the time has arrived for us to finish the proof of the fact that this deterministic selection algorithm based on the median of median ideas does indeed run in linear time. We've done really all of the conceptually difficult work. We discussed the algorithmic ingenuity required to choose a pivot deterministically that's guaranteed to be pretty good. So remember, the idea was you take the input array, you logically break it into groups of 5, you sort each group. That's like the first round of a 2-round knockout tournament. The winners of the first round are the middle elements of each group of 5s. That's the initial set of medians. And then the second round, we take a median of these n over 5 first round winners. And that's what we return as the pivot. And we prove this key lemma, which is the 30-70 lemma, which says that if you choose the pivot by this 2-round knockout tournament, you're guaranteed to get a 30-70 split or better. So your recursive call in line 6 or 7 of deselect is guaranteed to be on an array that has at most 70% of the elements that you started with. In other words, you're guaranteed to prune at least 30% of the array before you recurse again. But what remains to understand is whether or not we've done a sensible trade-off. Have we kept the work required to compute this 30-70 split small enough that we get the desired linear running time? Or is the cost of finding a pretty good pivot outweighing the benefit of having guaranteed good splits? That's what we got to prove. That's the next subject. Here's the story so far.
You'll recall that, as usual, we define T of n to be the worst case running time of an algorithm, in this case deselect on inputs of input arrays of length n. And we discussed, okay, there's the base case as usual, but in the general case, we discussed how outside of the two recursive calls, the deselect algorithm does a linear number of operations. What does it have to do? It has to do the sorting, but each sorting is on a group of size constant, of size 5, so it takes constant time per group. There's a linear number of groups, so step 1 takes linear time, the copying takes linear time, and the partitioning takes linear time. So there's some constant c, which is going to be bigger than 1, but it's going to be constant, so that outside the recursive calls, deselect always does at most c times n operations. Now, what's up with the recursive calls? Well, remember, there's two of them. First, there's one on line 3. This is responsible for helping choose the pivot. This one we understand. It's always on 20% of the input array, namely the first round winners. So we can very safely write t of n over 5 for the work done in the worst case by that first recursive call. What we didn't understand until we proved the key lemma was what's up with the second recursive call, which happens on either line 6 or line 7. The size of the input array on which we recurse depends on the quality of the pivot, and it was only when we proved the key lemma that we had a guarantee on the quality of our pivot. 30-70 split or better, what does that mean? That means the largest subarray we could possibly recurse on has 7/10 n elements. So what remains is to find the solution for this recurrence and hopefully prove that it is indeed big O of n. So let me go ahead and rewrite the recurrence at the top of this slide. We're not really going to worry about the base case t of 1 equals 1, but what we're interested in is the fact that the running time on an input of length n is at most c times n, where again c is some constant, which is going to have to be at least 1, given all the work that we do outside the recursive calls, plus the recursive call on line 3 on an array of size n over 5, plus the second recursive call, which is on some array that has size, in the worst case, 7/10 n. So that's cool. This is exactly how we handled the other deterministic divide and conquer algorithms that we studied in earlier videos. We just wrote down a recurrence, and then we solved the recurrence. But now, here's the trick. In all of the other recurrences that came up, for example, merge sort, Strassens matrix multiplication algorithm, Karatsuba multiplication, you name it, we just plugged the parameters into the master's method, and because of the power of the master method, boom, out popped up an answer. It just told us what the recurrence evaluated to. Now, the master method, as powerful as it is, it did have an assumption, you might recall. The assumption was that every subproblem solved had the same size. And that assumption is violated by this linear time selection algorithm. There are two recursive calls. One of them's on 20% of the original array. The other one is probably on much more than 20% of the original array. It could be as much as 70% of the original array. So because we have two recursive calls and subproblems of different size, this does not fit into the situations that the master method covers. It's a very rare algorithm in that regard. Now, there are more general versions of the master method, of the master theorem, which can accommodate a wider class of recurrences, including this one here. Alternatively, we could push the recursion tree proof so that we could get a solution for this recurrence. Some of you might want to try that at home. But I want to highlight a different way you can solve recurrences just for variety, just to give you yet another tool. Now, the good news about this approach that I'm going to show you is that it's very flexible. It can be used to solve sort of arbitrarily crazy recurrences. It's certainly going to be powerful enough to evaluate this one. The bad news is that it's very ad hoc. It's not necessarily very easy to use. It's kind of a dark art figuring out how to apply it. So it's often just guess and check is what it's called. You guess what the answer to a recurrence is, and then you verify it by induction. Here, because we have such a specific target in mind, the whole point of this exercise is to prove a linear time bound, I'm going to call it just hope and check. So we're going to hope that it's linear time, and then we're going to try to produce a proof of that, just that verifies the linear time bound using induction. Specifically, what are we hoping for? We're crossing our fingers that there's a constant. I'm going to call it A. A could be big, but it's got to be constant. And again, remember, constant means it does not depend on n in any way, such that our recurrence at the top of this slide, t of n, is bounded above by a times n for all n at least 1. Why is this what we're hoping? Well, suppose this were true. By definition, t of n is an upper bound on the running time of our algorithm. So if it's bounded above by a times n, then it's obviously O of n. It's obviously a linear time algorithm, where a is the constant that gets suppressed in the big O notation. So that's the hope. Now let's check it. And again, check means just verify by induction on n. So the precise claim that I'm going to prove is the following.
I'm going to go ahead and choose the constant a. Remember, all we need is some constant a, no matter how big, as long as it's independent of n. That'll give us the big O of n time. So I'm actually going to tell you what a I'm going to use for convenience. I'm going to choose a to be 10c. Now what is c? C is just the constant that we inherit from the recurrence that we're given. Now remember what this recurrence means. This is what the running time is of the deselect algorithm, and the c times n represents the work done outside of the recursive calls. So this is just the constant multiple on the amount of linear work that deselect does for sorting the groups, for doing the partitioning, and for doing the copying. Okay, so there's going to be some small constant, reasonable constant, and for the proof I'm just going to multiply that by 10 and use that as my a. And the claim is, if I define a in that way, then indeed it is true that for all n at least 1, t of n is bounded above by a times n. Now I realized I pulled this constant a out of nowhere, right? Why 10 times c? Well, if you recall our discussion when we proved that things were big O of something else, there again there was some constant. So to formally prove that something is big O of something else, you have to say what the constant is. And in the proof, you always wonder, how do you know what constant to use? So in practice, when you're actually, if you have to actually do one of these proofs yourself, you reverse engineer what kind of constant would work. So you just go through the argument with a generic constant, and then you're like, oh, well, if I set the constant to be this, I can complete the proof. So we'll see that's exactly what's going to happen in the proof of this claim. It'll be obvious. The very last line, you'll see why I chose a equal 10c. So I just reverse engineered it for what I needed for the proof. But to keep the proof easy to follow line by line, I decided to just, full disclosure, tell you the constant right at the beginning. Now, no prizes for guessing that the way this proof proceeds is by induction on n. Induction is the obvious thing to use. We're trying to prove an assertion for every single positive number n, and moreover we're given this recurrence, which relates solutions of smaller subproblems to that of bigger problems. So that sets things up for use of the inductive hypothesis. If you want a longer review of what proofs by induction are, I suggest that you go back and rewatch the optional video where we prove the correctness of Quicksort. There's a fairly formal discussion of what the template is like for a proof by induction, and that's the one we're going to apply here. So there's two ingredients to any proof by induction. There's a usually trivial one in the form of a base case that's also going to be trivial here. So in the base case, you just directly establish the assertion when n equals 1. So we're trying to prove that t of n is at most a times n for every n. When n equals 1, if we just substitute, then what we're trying to prove is that t of 1 is at most a times 1, also known as a. And we're given that t of 1 is 1. Right? That's the base case of the recurrence that we're given. So that's what we're using here. What we want to be true is that this is at most a times 1, but it is. So the constant c, we're assuming, is at least 1. So certainly if you multiply c times 10 to get a, it's definitely at least 1. So the right-hand side here is unquestionably bigger than the left-hand side. A, in fact, is even bigger than 10, let alone bigger than 1. So the interesting ingredient is generally the inductive step. So remember, what you do here is you assume you've already proven the assertion that, in this case, the t of n is at most an, for all smaller integers, and now you just merely have to prove it again for the current integer. So we're now interested in the case where n is bigger than 1, and the assumption that we've already proven it for everything smaller is called the inductive hypothesis. So what does it mean that we already proved it for all smaller numbers? It means we can use, in the proof of our inductive step, the fact that t of k is at most a times k for all k strictly less than n. All we got to do is enlarge the range of n's to which this holds to one more, to the current value n. And all we have to do is follow our nose. So pretty much we have to start on the left-hand side with t of n. We have to wind up on the right-hand side with a times n. And pretty much at every step of the proof, there's just going to be one conceivable thing we could do. So we just follow our nose. We start with what we want to upper bound, t of n. Well, what do we got going for us? The only thing we can do at this point is invoke the recurrence that we were given up here. So we have an upper bound on t of n in terms of the t value of smaller integers. So we are given that t of n is at most c times n plus t of n over 5 plus t of 7/10 n. I'm of course ignoring fractions. You would round up or round down if you wanted to be precise, and the auxiliary lecture notes are more precise if you want to see what the gory details look like. But it's really just exactly the same argument. One just has to be a little bit more anal about it. So now that we've invoked the recurrence, what can we possibly do? Right? We can't really do any direct manipulation on any of these three terms, but fortunately, we have this inductive hypothesis. That applies to any value, any integer, which is less than n. So we have here n over 5, that's certainly less than n. We have 70% of n, that's certainly less than n. So we can apply the inductive hypothesis twice. We already know that these t-values are bounded above by a times their arguments. So t of n over 5 is at most a times n over 5. T of 7/10 n is at most a times 7/10 n. Now we can group terms together. Now we're comparing apples to apples. So we have n times quantity c plus a over 5 plus 7/10 a. Let me just go ahead and group the two a terms together, and that's going to be 9/10 a. Now don't forget where we're going, what the end goal is. We want to upper bound t of n by an, so we want to write that this is bounded above by a times n. And now you see exactly how I reverse engineered our choice of a as a function of the given constant c. Since a is 10 times as big as c, if I take 90% of a and add c, I just get a back. So by our choice of a, this equals an. And that pretty much wraps things up. So don't forget what all this stuff stands for. So what did we just prove? What did we just prove by induction? We proved t of n is at most a constant times n for every n. That is, t of n is big O of n. What was t of n? That was the running time of our algorithm. That's what we cared about. So because t of n is big O of n, indeed deselect runs in O of n time. This optional video will be more or less the last word that we have on sorting for the purposes of this course. And it'll answer the question, can we do better? Remember, that's the mantra of any good algorithm designer. I've shown you n log n algorithms for sorting, merge sort in the worst case, quicksort on average. Can we do better than n log n? Indeed, for the selection problem, we saw we could do better than n log n. We could do linear time. Maybe we can do linear time for sorting as well. The purpose of this video is to explain to you why we cannot do sorting in linear time. So this is a rare problem where we understand quite precisely how well it can be solved, at least for a particular class of algorithms called comparison-based sorts, which I'll explain in a moment. So here's the formal theorem I want to give you the gist of in this video. So in addition to restricting to comparison-based sorts, which is necessary, as we'll see in a second, I'm going to make a second assumption which is not necessary, but is convenient for the lecture, which is that I'm going to think only about deterministic algorithms for the moment. I encourage you to think about why the same style of argument gives an n log n lower bound on the expected running time of any randomized algorithm. Maybe I'll put that on the course side as an optional theory problem. So in particular, quicksort is optimal in the randomized sense. It has average n log n time, and again, the claim is that no comparison-based sort can be better than that, even on average. So I need to tell you what I mean by a comparison-based sorting algorithm. What it means, it's a sorting algorithm that accesses the elements of the input array only via comparisons. It does not do any kind of direct manipulation on a single array element. All it does is it picks pairs of elements and asks the question, is the left one bigger or is the right one bigger? I like to think of comparison-based sorts as general-purpose sorting routines. They make no assumptions about what the data is other than that it's from some totally ordered set. I like to think of it really as a function that takes as an argument a function pointer that allows it to do comparisons between abstract data types. There's no way to access the guts of the elements. All you can do is go through this API which allows you to make comparisons. And indeed, if you look at the sorting routine in, say, the Unix operating system, that's exactly how it's set up. You just pass it a function pointer to a comparison operator. I know this sounds super abstract, so I think it becomes clear once we talk about some examples. There's famous examples of comparison-based sorts, including everything we've discussed in the class so far. There's also famous examples of non-comparison-based sorts, which we're not going to cover, but perhaps some of you have heard of, or at the very least, they're easy to look up on Wikipedia or wherever. So examples include the two sorting algorithms we've discussed so far, merge sort. The only way that merge sort interacts with the elements in the input array is by comparing them and by copying them. Similarly, the only thing quicksort does with the input array elements is compare them and swap them in place. For those of you that know about the heap data structure, which we'll be reviewing later in the class, heap sort, where you just heapify a bunch of elements and then extract the minimum n times, that also uses only comparisons. So what are some famous non-examples? I think this will make it even more clear what we're talking about. So bucket sort is one very useful one.
So bucket sort is used most frequently when you have some kind of distributional assumption on the data that you're sorting. And remember, that's exactly what I'm focusing on avoiding in this class. I'm focusing on general purpose subroutines where you don't know anything about the data. If you do know stuff about the data, bucket sort can sometimes be a really useful method. For example, suppose you can model your data as IID samples from the uniform distribution on 0, 1. So they're all rational numbers, bigger than 0, less than 1, and you expect them to be evenly spread through that interval. Then what you can do in bucket sort is you can just pre-allocate n buckets where you're going to collect these elements. Each one is going to have the same width with 1 over n. The first bucket, you just do a linear pass through the input array. Everything that's between 0 and 1 over n, you stick in the first bucket. Everything between 1 over n and 2 over n, you stick in the second bucket. 2 over n and 3 over n, you stick in the third bucket, and so on. So with a single pass, you've classified the input elements according to which bucket they belong in. Now, because the data is assumed to be uniform at random, that means you expect each of the buckets to have a very small population, just a few elements in it. So remember, if elements are drawn uniform from the interval 0, 1, then it's equally likely to be in each of the n available buckets. And since there's n elements, that means you only expect 1 element per bucket. So each one is going to have a very small population. Having bucketed the data, you can now just use, say, insertion sort on each bucket independently. You're going to be doing insertion sort on a tiny number of elements, so that'll run in constant time, and then there's going to be a linear number of buckets, so it's linear time overall. So the upshot is, if you're willing to make really strong assumptions about your data, like it's drawn uniformly at random from the interval 0, 1, then there is not an n log n lower bound. In fact, you can elude the lower bound and sort in linear time. So just to be clear, in what sense is bucket sort not comparison-based? In what sense does it look at the guts of its elements and do something other than access them by pairs of comparisons? Well, it actually looks at an element in the input array and it says, what is its value? And it checks if its value is 0.17 versus 0.27 versus 0.77, and according to what value it sees inside this element, it makes the decision of which bucket to allocate it to. So it actually stares at the guts of an element to decide what to do next. Another non-example, which can be quite useful, is counting sort. So this sorting algorithm is good when your data, again, we're going to make an assumption on the data, when they're integers and they're small integers. So say they're between 0 and k, where k is, say, ideally at most linear in n. So then what you do is you do a single pass through the input array. Again, you just bucket the elements according to what their value is. It's somewhere between 0 and k, and it's an integer by assumption. So you need k buckets, and then you do a pass, and you sort of depopulate the buckets and copy them into an output array. And that gives you a sorting algorithm which runs in time O of n plus k, where k is the size of the biggest integer. So the upshot with counting sort is that if you're willing to assume the data are integers, bounded above by some factor linear in n, proportional to n, then you can sort them in linear time. Again, counting sort does not access the array elements merely through comparisons. It actually stares at an element, figures out what its value is, and uses that value to determine what bucket to put the element in. So in that sense, it's not a comparison-based sort, and it can, under various assumptions, beat the n log n lower bound. So a final example is the well-known algorithm called radix sort. I think of this as sort of an extension of counting sort, although you don't have to use counting sort as the inner loop. You can use other so-called stable sorts as well. This is stuff you can read about in many programming books or on the web. And the upshot of radix sort is you assume that the data are integers. You think of them in digit representation, say binary representation, and now you just sort one bit at a time, starting from the least significant bits and going all the way out to the most significant bits. And so the upshot of radix sort, it's an extension of counting sort in the sense that if your data is integers that are not too big, polynomially bounded in n, then it lets you sort in linear time. So summarizing, a comparison-based sort is one that can only access the input array through this API that lets you do comparisons between two elements. You cannot access the value of an element, so in particular, you cannot do any kind of bucketing technique. Bucket sort, counting sort, and radix sort all fundamentally are doing some kind of bucketing, and that's why when you're willing to make assumptions about what the data is and how you are permitted to access that data, that's why you can bypass, in all of those cases, this n log n lower bound. But if you're stuck with a comparison-based sort, if you want to have something general purpose, you're going to be doing n log n comparisons in the worst case. Let's see why. So we have to prove a lower bound for every single comparison-based sorting method, so fix one. And let's focus on a particular input length, call it n. Okay, so now let's simplify our lives.
Now that we're focused on a comparison-based sorting method, one that doesn't look at the values of the array elements just in the relative order, we may as well think of the array as just containing the elements 1, 2, 3, all the way up to n in some jumbled order. Now, some other algorithm could make use of the fact that everything is small integers, but a comparison-based sorting method cannot. So there's no loss in just thinking about an unsorted array containing the integers 1 to n inclusive. Now, despite seemingly restricting the space of inputs that we're thinking about, even here, there's kind of a lot of different inputs we got to worry about, right? So n elements can show up in n factorial different orderings, right? There's n choices for who the first element is, then n minus 1 choices for the second element, n minus 2 choices for the third element, and so on. So there's n factorial choices for how these elements are arranged in the input array. So I don't want to prove this super formally, but I want to give you the gist, I think the good intuition. Now we're interested in lower bounding the number of comparisons that this method makes in the worst case. So let's introduce a parameter k, which is its worst case number of comparisons. That is, for every input, each of these n factorial inputs, by assumption, this method makes no more than k comparisons. The idea behind the proof is that because we have n factorial fundamentally different inputs, the sorting method has to execute in a fundamentally different way on each of those inputs. But since the only thing that causes a branch in the execution of the sorting method is the resolution of a comparison, and we have only k comparisons, it can only have 2 to the k different execution paths. So that forces 2 to the k to be at least n factorial, and a calculation then shows that that forces k to be at least omega n log n. So let me just quickly fill in the details. So across all n factorial possible inputs, just as a thought experiment, we can imagine running this method n factorial times and just looking at the pattern of how do the comparisons resolve. Right? For each of these n factorial inputs, we run it through the sorting method. It makes comparison number 1, then comparison number 2, then comparison number 3, then comparison number 4, then comparison number 5. And it gets back a 0, then a 1, then a 1, then a 0. Maybe on some other input, it gets back a 1, then a 1, then a 0, then a 0, and so on. The point is, for each of these n factorial inputs, it makes at most k comparisons. We can associate that with a k-bit string. And because there's only k bits, we're only going to see 2 to the k different k-bit strings, 2 to the k different ways that a sequence of comparisons resolves. Now to finish the proof, we are going to apply something which I don't get to use as much as I'd like in an algorithms class, but it's always fun when it comes up, which is the pigeonhole principle. The pigeonhole principle, you'll recall, is the essentially obvious fact that if you try to stuff k plus 1 pigeons into just k cubbyholes, one of those cubbyholes has got to get 2 of the pigeons. Okay? At least one of the cubbyholes gets at least 2 pigeons. So for us, what are the pigeons and what are the holes? So our pigeons are these n factorial different inputs, the different ways you can scramble the integers 1 through n. What are our holes? Those are the 2 to the k different executions that the sorting method can possibly take on. Now, if the number of comparisons k used is so small that 2 to the k, the number of distinct executions, the number of distinct ways comparisons can resolve themselves, is less than the number of different inputs that have to get correctly sorted, then by the pigeonhole principle, one cubby gets 2 holes. That is, 2 different inputs get treated in exactly the same way by the sorting method. They are asked exactly the same k comparisons, and the comparisons resolve identically. Okay, so it's one jumbling of 1 through n, and you get a 0, 1, 1, 0, 1, and it's a totally different jumbling of n, and again, you get a 0, 1, 1, 0, 1. And if this happens, the algorithm is toast, in the sense that it's definitely not correct, right? Because we fed it 2 different inputs, and it is unable to resolve which of the 2 it is, right? So it may be one permutation of 1 through n, or this totally different permutation of 1 through n. The algorithm has tried to learn about what the input is through these k comparisons, but it has exactly the same data about the input in the 2 cases. So if it outputs the correct sorted version in one case, it's going to get the other one wrong. So you can't have a common execution of a sorting algorithm unscramble totally different permutations. It cannot be done. So what have we learned? We've learned that by correctness, 2 to the k is in fact at least n factorial. So how does that help us? Well, we want to lower bound k. K is the number of comparisons this arbitrary sorting method is using. We want to show that's at least n log n. So to lower bound k, we better lower bound n factorial. So, you could use Stirling's approximation or something fancy, but we don't need anything fancy here. We'll just do something super crude. We'll just say, well, look, this is the product of n things, right? N times n minus 1 times n minus 2, blah, 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 blah. And the largest of those, the n over 2 largest of those n terms are all at least n over 2. The rest we'll just ignore. Pretty sloppy, but it gives us a lower bound of n divided by 2 raised to the n divided by 2. Now we'll just take log base 2 of both sides, and we get that k is at least n over 2 log base 2 of n over 2, also known as omega of n log n. And that, my friends, is why a correct deterministic sorting algorithm that's comparison-based has got to use n log n comparisons in the worst case. So in this set of lectures, we'll be discussing the minimum cut problem in graphs, and we'll be discussing the randomized contraction algorithm. A randomized algorithm which is so simple and elegant, it's almost impossible to believe that it could possibly work, but that's exactly what we'll be proving. So one way you can think about this set of lectures is as a segue of sorts between our discussion of randomization and our discussion of graphs. So we just finished talking about randomization in the context of sorting and searching. We'll pick it up again toward the end of the class when we discuss hashing, but while we're in the middle of randomization and probability review, I want to give you another application of randomization in a totally different domain, in particular to the domain of graphs rather than to sorting and searching. So that's one high-level goal of these lectures. A second one is we'll get our feet wet talking about graphs, and a lot of the next couple weeks that's what we're going to be talking about, fundamental graph primitives. So this will give us an excuse to start warming up with the vocabulary, some of the basic concepts of the graph, and what a graph algorithm looks like. Another perk, although it's not one of the main goals, but I do want to point out this fact, is that at least compared to most of the stuff that we're discussing in this class, this is a relatively recent algorithm, the contraction algorithm. By relatively recent, I mean, okay, it's 20 years old. But at least that means most of us, I know not all of us, but most of us at least were born at the time that this algorithm was invented. And so just one quick digression, in an intro course like this, most of what we're going to cover are oldies but goodies, stuff from as much as 50 years ago. And while it's kind of amazing, given how much the world and how much technology has changed over the past 50 years, that ideas in computer science from that long ago are still useful, they are. Okay, so it's just sort of an amazing thing about the stuff that the first generation of computer scientists figured out. It's still relevant to this day. That said, algorithms is still a vibrant field with lots of open questions, and when I have an opportunity, I'll try and give you glimpses of that fact. So I do want to point out here that this is a somewhat more recent algorithm than most of the other ones we'll see, which dates back to the 90s. So let's talk about graphs. Fundamentally, what a graph does is represent pairwise relationships amongst a set of objects. So as such, a graph is going to have two ingredients. So first of all, there's the objects that you're talking about. And these have two very common names, and you're just going to have to know both of the names, even though they're completely synonymous. The first name is vertices. So vertex is the singular, vertices is the plural. Also known interchangeably as nodes. I'll be using the notation capital V for the set of vertices. So those are the objects. Now we want to represent pairwise relationships. So these pairs are going to be called edges. And will be denoted by capital E. And there's two flavors of graphs, and both are really important. Both come up all the time in applications, so you should be aware of both kinds. So there's undirected graphs and directed graphs, and that just depends on whether the edges themselves are undirected or directed. So edges can be undirected, by which I mean this pair is unordered. There are just two vertices of an edge, the two endpoints, say U and V, and you don't distinguish one as the first and one as the second. Or edges can be directed, in which case you have a directed graph. And here, a pair is ordered. So you do have a notion of a first vertex or a first endpoint and the second vertex or second endpoint of an edge. Those are often called the tail and the head, respectively. And once in a while, although I'll try to not use this terminology, you hear directed edges called arcs. Now, I think all of this is much clearer if I just draw some pictures. Indeed, one used to call graphs dots and lines. The dots would refer to the vertices. So here's 4 dots or 4 vertices. And the edges would be lines. So the way you denote one of these edges is you just draw a line between the two endpoints of that edge, the two vertices that it corresponds to. So this is an undirected graph with 4 vertices and 5 edges. We could equally well have a directed version of this graph. So let's still have 4 vertices and 5 edges. But to indicate that this is a directed graph and that each edge has a first vertex and a second vertex, we're going to add arrows to the lines. So the arrow points to the second vertex, or to the head of the edge. So the first vertex is often called the tail of the edge. So graphs are completely fundamental. They show up not just in computer science, but in all kinds of different disciplines, social sciences and biology being two prominent ones. So let me just mention a couple of reasons you might use them just off the top of my head, but literally there's hundreds or thousands of others. So a very literal example would be road networks. So imagine you type in asking for driving directions from point A to point B in some web application or software or whatever. It computes a route for you. What it's doing is it's manipulating some representation of a road network, which inevitably is going to be stored as a graph, where the vertices correspond to intersections and the edges correspond to individual roads. The web is often fruitfully thought of as a graph, a directed graph. So here the vertices are the individual web pages and edges correspond to hyperlinks. So the first vertex in an edge, the tail, is going to be the page that contains the hyperlink. The second vertex, or the head of the edge, is going to be what the hyperlink points to. So that's the web as a directed graph. Social networks are quite naturally represented as graphs. So here the vertices correspond to the individuals in the social network, and the edges correspond to relationships, say friendship links. I encourage you to think about amongst the popular social networks these days which ones are undirected graphs and which ones are directed graphs. We have some interesting examples of each of those. And often graphs are useful even when there isn't such an obvious network structure. So just to mention one example, let me just write down precedence constraints. So to say what I mean, you might think about, say you're a freshman in college and you're looking at your major, say the computer science major, and you want to know what courses to take in what order. And you could think about the following graph, where each of the courses in your major corresponds to a vertex, and you draw a directed edge from course A to course B if course A is a prerequisite for course B. That is, it has to be completed before you begin course B. Okay, so that's a way to represent dependencies, sort of a temporal ordering between pairs of objects using a directed graph. So that's the basic language of graphs. Let me now talk about cuts in graphs, because again, this set of lectures is going to be about the so-called minimum cut problem. So the definition of a cut of a graph is very simple. It's just a grouping, a partition of the vertices of the graph into two groups, A and B, and both of those two groups should be non-empty. So to describe this in pictures, let me give you a cartoon of a cut in both the undirected and directed cases. So for an undirected graph, you could imagine drawing your two sets A and B. And once you've defined the two sets A and B, the edges then fall into one of three categories. You've got edges with both of the endpoints in A. You've got edges with both of the endpoints in B. And then you've got edges with one endpoint in A and one endpoint in B. So that's generically what the picture of a graph looks like viewed through the lens of a particular cut AB. The picture for directed graphs is similar. You would again have an A and you'd again have a B. You have directed edges with both endpoints in A, directed edges with both endpoints in B. And now you actually have two further categories. So you have edges who cross the cut from left to right, that is, whose tail vertex is in A and whose head vertex is in B. And you can also have edges which cross the cut in the opposite direction, that is, their tail is in B and their head is in A. Usually when we talk about cuts, we're going to be concerned with how many edges cross a given cut, and by that I mean the following. The crossing edges of a cut AB are those that satisfy the following property. So in the undirected case, it's exactly what you'd think it would be. One of the endpoints is in A, the other endpoint is in B. That's what it means to cross the cut. Now in the directed case, there's a number of reasonable definitions you could propose about which edges cross the cut. Typically, and in this course, we're going to focus on the case where we only think about edges that cross the cut from the left to the right, and we ignore edges which cross from the right to the left. So that is, the edges that cross the cut are those with tail in A and head in B. So referring to our two pictures, our two cartoons of cuts, for the undirected one, all three of these blue edges would be the edges crossing the cut AB, because they're the ones that have one endpoint on the left side and one endpoint on the right side. Now for the directed one, we only have two crossing edges. So the two that cross from left to right, with tail in A and head in B. The one that's crossing backward does not contribute. We don't count it as a crossing edge of the cut.
So the next quiz is just a sanity check that you've absorbed the definition of a cut of a graph. All right, so the answer to this quiz is the third option. Recall, what is the definition of a cut? It's just a way to group the vertices into two sets, A and B. Both should also be non-empty. So we have n vertices, and essentially we have one binary degree of freedom for each. For each vertex, we can decide whether or not it goes in set A or it goes in set B. So two choices for each of the n vertices. That gives us 2 to the n possible choices, 2 to the n possible cuts overall. Now that's slightly incorrect, because recall that a cut can't have a non-empty set A or a non-empty set B, so those are 2 of the 2 to the n options which are disallowed. So strictly speaking, the number is 2 to the n minus 2, but 2 to the n is certainly the closest answer of the 4 provided. Now, the minimum cut problem is exactly what you'd think it would be. I give you as input a graph, and amongst these exponentially many cuts, I want you to identify one for me with the fewest number of crossing edges. So a few quick comments. So first of all, the name for this cut is a min cut. A min cut is one with the fewest number of crossing edges. Secondly, to clarify, I am going to allow in the input what's called parallel edges. There'll be lots of applications where parallel edges are sort of pointless, but for minimum cut, actually, it's natural to allow parallel edges. And that means you have 2 edges that correspond to exactly the same pair of vertices. Finally, the more seasoned programmers among you are probably wondering what I mean by you're given a graph as inputs. You might be wondering about how exactly that's represented. So the next video is going to discuss exactly that, the popular ways of representing graphs and how we're going to usually do it in this course, specifically via what's called an adjacency list. Okay, so I want to make sure that everybody understands exactly what the minimum cut problem is asking. So let me draw for you a particular graph with 8 vertices and quite a few edges. And what I want you to answer is, what is the min cut value in this graph? That is, how many edges cross the minimum cut, the cut with the fewest number of crossing edges? All right, so the correct answer is the second choice. The min cut value is 2, and the cut which shows that is just to break it basically in half, into the 2 halves. In this case, there are only 2 crossing edges, this one and this one, and I'll leave it for you to check that there's no other edge that has as few as 2 edges. Now, in this case, we got a very balanced split when we took the minimum cut. In general, that need not be true. Sometimes even a single vertex can define the minimum cut of a graph, and I encourage you to think about a concrete example that proves that. So why should you care about computing the minimum cut? Well, this is one problem amongst a genre called graph partitioning, where you're given a graph and you want to break it into 2 or more pieces. And these kinds of graph partitioning problems come up all the time in a surprisingly diverse array of applications. So let me just mention a couple at a high level. So one very obvious one, when your graph is representing a physical network, what identifying something like a min cut allows you to do is identify weaknesses in your network. Okay, perhaps it's your own network and you want to understand where you want to soup up the infrastructure because it's in some sense a hotspot of your network or a weak point. Or maybe there's someone else's network and you want to know where the weak spot is in their network. In fact, there were some declassified documents about 15 years ago or so, which showed that the United States and Soviet Union militaries back during the Cold War were actually quite interested in computing minimum cuts, because they were looking for things like, for example, what's the most efficient way to disrupt the other country's transportation network. Another application, which is a big deal in social network analysis these days, is the idea of community detection. So the question is, amongst a huge graph, like say the graph of everybody who's on Facebook or something like that, how can you identify small pockets of people that seem tightly knit, that seem closely related, from which you'd like to infer that they're a community of some sort? You know, maybe they all go to the same school, maybe they all have the same interest, maybe they're part of the same biological family, whatever. Now, it's to some degree still an open question how to best define communities and social networks, but as a quick and dirty sort of first order heuristic, you can imagine looking for small regions, which on the one hand are highly interconnected amongst themselves, but quite weakly connected to the rest of the graph. So subroutines like the minimum cut problem can be used for identifying these small, densely interconnected, but then weakly connected to everybody else
pockets of a graph. Finally, cut problems are also used a lot in vision. So for example, one way you can use them is in what's called image segmentation. So here what's going on is you're given as input a 2D array where each entry is a pixel from some image. And there's a graph which is very natural to define given a 2D array of pixels, namely you have an edge between two pixels if they're neighboring. So for two pixels that are immediately next to each other, left and right or top to bottom, you put an edge there. So that gives you what's called a grid graph. And now, unlike the basic minimum cut problem that we're talking about here, in image segmentation it's most natural to use edge weights, where the weight of an edge is basically how likely you expect those two pixels to be coming from a common object. Why might you expect two neighboring pixels to come from the same object? Well, perhaps their color maps are almost exactly the same, and you just expect that they're part of the same thing. So once you've defined this grid graph with suitable edge weights, now you run a graph partitioning or min-cut type subroutine, and the hope is that the cut that it identifies rips off one of the contiguous objects in the picture. And then you do that a few times, and you get the major objects in the given picture. So this list is by no means exhaustive of the applications of min-cut and graph partitioning subroutines, but I hope it serves as sufficient motivation to watch the rest of the lectures in this sequence. Okay, so this video is not about any particular graph problem, not about any particular graph algorithm, just sort of the preliminaries we need to discuss algorithms on graphs. How do we measure their size? How do we represent them? And so on. Remember what a graph is. It really has two ingredients. First of all, there's the set of objects we're talking about. Those might be called vertices. Synonymously, we might call them nodes. We represent pairwise relationships using edges. These can be either undirected, in which case they're ordered pairs, or an edge can be directed from one to another. In that case, they're ordered pairs, and we have a directed graph. Now, when we talk about, say, the size of a graph or the running time of an algorithm that operates on a graph, we need to think about what we mean by input size. In particular, for a graph, there's really two different parameters that control how big it is, unlike an array. For arrays, we just had a single number, the length. For graphs, we have the number of vertices and we have the number of edges. Usually we'll use the notation n for the number of vertices, m for the number of edges. So the next quiz asks you to think about how the number of edges m can depend on the number of vertices n. So in particular, I want you to think for this quiz about an undirected graph. It has n vertices. There's no parallel edges. Okay, so for a given pair of vertices, there's either 0 or 1 edge between them. Moreover, let's assume that the graph is unconnected. Okay, so I don't want you to think about graphs that have 0 edges. Now, I haven't defined what a graph is, what it means for a graph to be connected formally yet, but I hope you get the idea. It means it's in one piece. You can't break it into two parts that have no edges crossing between them. So for such a graph, no parallel edges in one piece, n vertices, think about what is the minimum number of edges it could possibly have, and what is the maximum number of edges as a function of n that it could possibly have. All right, so the correct option is the first one. The fewest number of edges that a connected undirected graph can have is n minus 1, and the maximum number of edges that an undirected graph with no parallel edges can have is n times n minus 1 over 2, better known as n choose 2. So why does it need at least n minus 1 edges if it's going to be in one piece? Well, think about adding the edges one at a time, okay, each of the edges of the graph. Now, initially, you just have a graph with 0 edges. The graph has n different pieces, n isolated vertices, and there's no edges at all. Now, each time you add one edge, what you do is you take two of the existing pieces, at best, and fuse them into one. So the maximum decrease you can have in the number of different pieces of a graph is it can decrease by 1 each time you add an edge. So from a starting point of n different pieces, you got to get down to one piece. So that requires the addition of n minus 1 edges. You can also convince yourself of this by drawing a few pictures and noticing that trees achieve this bound exactly. So for example, here is a 4-vertex tree that has 3 edges. So this is a case where m is indeed n minus 1. Now, for the upper bound, why can't you have more than n choose 2? Well, it's clear that the largest number of edges you can have is for the complete graph, where every single pair of edges has one between them. Again, there's no parallel arcs, and edges are unordered, so there's at most n choose 2 possibilities of where to put an edge. So again, if n equals 4, here would be an example with the maximum possible number, 6 edges.
So now that I've got you thinking about how the number of edges can vary with the number of vertices, let me talk about the distinction between sparse and dense graphs. It's important to distinguish between these two concepts because some data structures and algorithms are better suited for sparse graphs, other data structures and algorithms are better suited for dense graphs. So to make this precise, let me just put down this very common notation. N is the number of vertices of the graph under discussion. M is the number of edges. This is quite standard notation. Please get used to it and use it yourself. If you reverse these, you will confuse a lot of people who have familiarity with graph algorithms and data structures. Now, one thing we learned from the previous quiz is the following. So in most applications, not all applications, but most applications, M is at least linear in N. Remember in the quiz you saw it was at least N minus 1 if you wanted the graph to be connected. And it's also big O of N squared. This is under the assumption that there's no parallel arcs. Now, there are cases where we want to allow parallel arcs. In fact, we'll do that in the contraction algorithm for the min-cut problem. There are cases where we want to allow the number of edges to drop so low that the graph breaks into multiple pieces. For example, when we talk about connected components. But more often than not, we're thinking about a connected graph with no parallel edges, and then we can pin down the number of edges M to be somewhere between linear in the number of nodes, linear in N, and quadratic in N. Now, I'm not going to give you a super formal definition of what a sparse or a dense graph is, and people are a little loose with this terminology in practice. But basically, sparse means you're closer to the lower bound, closer to linear. Dense means you're closer to the upper bound, closer to quadratic. Now, I know this leaves ambiguity when the number of edges is something, like n to the 3/2. Usually in that case, you'd think of it as a dense graph. So usually anything which is more than n times some logarithmic terms, you'd think of that as a dense graph. But again, people are a little bit sloppy with this when they talk about graphs. Next, I want to discuss two representations of graphs, and we're mostly going to be using the second one in this course. But this first one, the adjacency matrix, I do want to mention just briefly, just on this slide. This is a supernatural idea where you represent the edges in a graph using a matrix. Let me describe it first for undirected graphs. So the matrix is going to be denoted by capital A, and it's a square n by n matrix where n is the number of vertices of the graph. And the semantics are the ijth entry of the matrix is 1 if and only if there's an edge between the vertices I and j in the graph. I'm assuming here that the vertices are named 1, 2, 3, 4, etc. all the way up to n. It's easy to add bells and whistles to the adjacency matrix to accommodate parallel edges, to accommodate edge weights, or to accommodate directed arcs, directed edges. If you wanted to have parallel arcs, you could just have aij denote the number of arcs that are between I and j. If edges have different weights, you can just have aij be the weight of the ij edge. And for the directed graph, you can use +1s and -1s. So if the arc is directed from I to j, you'd set aij to be +1. If the arc is directed from j to I, you'd set aij to -1. There are many metrics by which you can evaluate a data structure or a representation. Two important ones I want to discuss here are, first of all, the number of resources it requires, and in this context, that's the amount of space that the data structure needs. The second thing is, what are the operations that the data structure supports? So let's just begin with the space requirements. What are they for the adjacency matrix? All right, so the answer, at least with the sort of straightforward way of storing a matrix, is n squared. And this is independent of the number of edges. So you could try to beat this down for sparse graphs using sparse matrix tricks. But for the basic idea of just actually representing an n by n matrix, you got n squared entries. You got to store 1 bit in each, whether the edge is there or not. So that's going to give you n squared space. The constants are, of course, very small because you're just storing 1 bit per entry. But nonetheless, this is quadratic in the number of vertices. Now that's going to be fine if you have a dense graph. If the number of edges is as high as n squared, then you're not really wasting anything in this representation. But in a sparse graph, if m is much closer to linear, then this is a super wasteful representation. Let's talk about the adjacency list representation. This is the dominant one we'll be using in this class. This has several ingredients. So first, you keep track of both the vertices and the edges as independent entities. So you're going to have an array or a list of each. And then we want these two arrays to cross-reference each other in the obvious way. So given a vertex, you want to know which edges it's involved in. Given an edge, you want to know what its endpoints are. So let's say first, most simply,
each edge is going to have 2 pointers, one for each of the 2 endpoints. In a directed graph, of course, it would keep track of which one is the head and which one is the tail. Now, each vertex is going to point to all of the edges of which it's a member. Now, in an undirected graph, it's clear what I mean by that. In a directed graph, you could do it in a couple ways. Generally, you'd have a vertex keep track of all of the edges for which it is the tail. That is, all of the edges which you can follow one hop out from the edge. If you wanted to, you could also have a second array at a more expensive storage where the vertex also keeps track of the edges pointing to it, the edges for which it's the head. So let me ask you the same question I did with an adjacency matrix. What is the space required of an adjacency list as a function of the number of edges m and the number of vertices n of the graph? So the correct answer to this question is the third option, theta of m plus n, which we're going to think of as linear space in the size of the graph. So this quiz is a little tricky, so to explain the answer, let me return to the slide with the ingredients of adjacency lists, and let's compute the space for each of these 4 ingredients separately. Most of them are straightforward. For example, consider the first ingredient. This is just an array or a list of the n vertices, and we just need constant space per vertex to keep track of its existence. So this is going to be theta of n, linear in the number of vertices. Similarly, for the m edges, we just need linear space in the number of edges to remember their existence. So that's going to be theta of m. Now, each edge has to keep track of both of its endpoints. So that's 2 pointers, but 2 is a constant. For each of the m edges, we have a constant space to keep track of endpoints. So that's going to give us another theta of m, constant per edge. Now, this fourth case, you might be feeling kind of nervous because a vertex, in principle, could have edges involving all n-1 other vertices. So the number of pointers at a single vertex could be theta of n. Also, you could have, you do have n vertices, so that could be theta of n squared. And certainly in something like a complete graph, you really would have that much. But the point is, in sparse graphs, n squared is way overkill to the space needed by this fourth set of pointers. Actually, if you think about it, for each pointer in the fourth category, a vertex pointing to a given edge, there's a pointer in the third category pointing in the opposite direction from that edge back to that vertex. So there's actually a one-to-one correspondence between pointers in the third category and pointers in the fourth category. Since the third category has space theta of m, so does all of the pointers in the fourth category. So adding up over the 4 ingredients, we have 1 theta of n and 3 theta of m's, so that's going to give us overall a theta of m plus n. If you prefer, another way you could think about this would be theta of the max of m and n. These are the same up to a constant factor. Now, as we discussed in a previous slide, often m is going to be bigger than n, but I wanted to do a generic analysis here, which applies even if the graph is not connected, even if it is in multiple pieces. So the space of the adjacency list is within a constant factor, the same as the number of ingredients in the graph, the number of vertices plus the number of edges. So in that sense, that's exactly what you want. Now, being confronted with these 2 graph representations that I've shown you, I'm sure you're asking, well, which one should you remember? Which one should you use? And the answer, as it so often is it depends. It depends on 2 things. It depends on the density of your graph. It depends on how m compares to n, and it also depends on what kind of operations that you want to support. Now, given what we're covering in this class, and also the motivating applications I have in mind, I can give you basically a clean answer to this question for the purposes of these 5 weeks, which is we're going to be focusing on adjacency lists. The reason we're going to focus on adjacency lists in this class is for both of these reasons, both because of the operations we want and both because of the graph density and motivating applications. So first of all, most of the graph primitives, not all, but most will be dealing with graph search, and adjacency lists are perfect for doing graph search. You get to a node, you follow an outgoing arc, you go to another node, you follow an outgoing arc, and so on. And so adjacency lists are the perfect thing to do graph search. Adjacency matrices are definitely good for certain kinds of graph operations, but they're not things we're really going to be covering in this class. So that's reason 1. Reason 2 is a lot of the motivations for graph primitives these days comes from massive, massive networks. I mentioned earlier how the web can be fruitfully thought of as a directed graph, where the vertices are individual web pages and directed arcs correspond to hyperlinks, going from the page with the hyperlink pointing to the one that the hyperlink goes to. Now, it's hard to get an exact measurement of the web graph, but a conservative lower bound on the number of vertices is something like 10 billion. So that's 10 to the 10. Now, that's pushing the limits of what computers can do, but it's within the limits. So if you work hard, you can actually operate on graphs with 10 to the 10 nodes. Now, suppose we use an adjacency matrix representation. So if n is 10 to the 10, then n squared is going to be like 10 to the 20. And now we're getting close to the estimated number of atoms in the known universe. So that is clearly not feasible now, and is not going to be feasible ever. So the adjacency matrix representation is totally out for huge sparse graphs like the web graph. Adjacency lists, well, the degree on average in the web is thought to be something like 10. So the number of edges is only going to be something like 10 to the 11. And then the adjacency list representation will be proportional to that. And again, that's really pushing what we can do with current technology, but it is within the limits. So using that representation, we can do non-trivial computations on graphs, even at the scale of the web graph. So now I get to tell you about the very cool randomized contraction algorithm for computing the minimum cut of a graph. Let's just recall what the minimum cut problem is. We're given as input an undirected graph, and parallel edges are allowed. In fact, they will arise naturally throughout the course of the algorithm. That is, for a given pair of vertices, we allow multiple edges to have that pair as endpoints. Now, I do sort of assume you've watched the other video on how graphs are actually represented, although that's not going to play a major role in the description of this particular algorithm. And again, the goal is to compute the cut. So a cut is a partition of the graph vertices into two groups, A and B. The number of edges crossing the cut is simply those that have one endpoint on each side. And amongst all of the exponentially possible cuts, we want to identify one that has the fewest number of crossing edges, or a min-cut. So here's the random contraction algorithm. So this algorithm was devised by David Karger back when he was an early PhD student here at Stanford, and this was in the early 90s. So like I said, quote unquote, only about 20 years ago. And the basic idea is to use random sampling. Now, we've known forever, right, ever since Quicksort, that random sampling could be a good idea in certain contexts, in particular when you're doing sorting and searching. And one of the things that was such a breakthrough about Karger's contraction algorithm is it showed that random sampling could be extremely effective for fundamental graph problems. So here's how it works. We're just going to have one main loop. Each iteration of this while loop is going to decrease the number of vertices in the graph by 1, and we're going to terminate when we get down to just 2 vertices remaining. Now, in a given iteration, here's the random sampling. Amongst all of the edges that remain in the graph to this point, we're going to choose one of those edges uniformly at random. Each edge is equally likely. Once you've chosen an edge, that's when we do the contraction. So we take the two endpoints of the edge, call them the vertex u and the vertex v, and we fuse them into a single vertex that represents both of them. This may become more clear when I go through a couple examples on the next couple of slides. This merging may create parallel edges, even if you didn't have them before. That's okay, we're going to leave the parallel edges, and it may create a self-loop edge where now both of the endpoints is the same. And self-loops are stupid, so we're just going to delete them as they arise. Each iteration decreases the number of vertices that remain. We start with n vertices, we end up with 2. So after n minus 2 iterations, that's when we stop, and at that point we return the cut represented by those 2 final vertices. You might well be wondering what I mean by the cut represented by the final 2 vertices, but I think that will become clear in the examples, which I'll proceed to now. So suppose the input graph is the following 4-node, 5-edge graph. There's a square plus 1 diagonal. So how would the contraction algorithm work on this graph? Well, of course, it's a randomized algorithm, so it could work in different ways. And so we're going to look at 2 different trajectories. In the first iteration, each of these 5 edges is equally likely. Each is chosen for contraction with 20% probability. For concreteness, let's say that the algorithm happens to choose this edge to contract, to fuse the 2 endpoints. After the fusion, these 2 vertices on the left have become 1. Whereas the 2 vertices on the right are still hanging around like they always were. So the edge between the 2 original vertices is unchanged. The contracted edge between the 2 vertices on the left has gotten sucked up, so that's gone. And so what remains are these 2 edges here, the edge on top and the diagonal. And those are now parallel edges between the fused node and the upper right node. And then I also shouldn't forget the bottom edge, which is edge from the lower right node to the supernode.
So that's what we mean by taking a pair of vertices and contracting them. The edge that was previously connected to them vanishes, and then all the other edges just get pulled into the fusion. So that's the first iteration of Karger's algorithm, or one possible execution. So now we proceed to the second iteration of the contraction algorithm, and the same thing happens all over again. We pick an edge uniformly at random. Now there's only 4 edges that remain, each of which is equally likely to be chosen, so a 25% probability. For concreteness, let's say that in the second iteration we wind up choosing one of the 2 parallel edges, say this one here. So what happens? Well, now instead of 3 vertices, we go down to 2. We have the original bottom right vertex that hasn't participated in any contractions at all, so that's as it was. And then we have the second vertex, which actually represents the fusion of all of the other 3 vertices. So 2 of them were fused, the leftmost vertices were fused in iteration 1, and now the upper right vertex got fused in with them to create this supernode representing 3 original vertices. So what happens to the 4 edges? Well, the contracted one disappears. That just gets sucked into the supernode and we never see it again. And then the other 3 go where they're supposed to go. So there's the edge that used to be the rightmost edge that has no hash mark. There's the edge with 2 hash marks that goes between the same 2 nodes that it did before. Just the supernode is now an even bigger node representing 3 nodes. And then the edge which was parallel to the one that we contracted, the other one with a hash mark, becomes a self loop. And remember what the algorithm does is whenever self loops like this appear, they get deleted automatically. And now that we've done our n-2 iterations, we're down to just 2 nodes, we return the corresponding cut. By corresponding cut, what I mean is one group of the cut is the vertices that got fused into each other and wound up corresponding to the supernode. In this case, everything but the bottom right node. And then the other group is the original nodes corresponding to the other supernode in the contracted graphs, which in this case is just the bottom right node by itself. So the set A is going to be these 3 nodes here, which all got fused into each other, contracted into each other, and B is going to be this node over here, which never participated in any contractions at all. And what's cool is, you'll notice, this does in fact define a min cut. There are 2 edges crossing this cut. This one, the rightmost one, and the bottommost one. And I'll leave it for you to check that there is no cut in this graph with fewer than 2 crossing edges. So this is in fact a min cut. Of course, this is a randomized algorithm, and randomized algorithms can behave differently on different executions. So let's look at a second possible execution of the contraction algorithm on this exact same input. Let's even suppose the first iteration goes about in exactly the same way. So in particular, this leftmost edge is going to get chosen in the first iteration. But instead of choosing one of the 2 parallel edges, let's suppose that we choose the rightmost edge to contract in the second iteration. Totally possible, 25% chance that's going to happen. Now what happens after the contraction? Well, again, we're going to be left with 2 nodes, no surprise there. The contracted node gets sucked into oblivion and vanishes, but the other 3 edges, the ones with the hash marks, all stick around and become parallel edges between these 2 final nodes. This again corresponds to a cut, A and B, where A is the left 2 vertices and B is the right 2 vertices. Now this cut, you'll notice, has 3 crossing edges. And we've already seen that there is a cut with 2 crossing edges, therefore this is not a min cut. So what have we learned? We've learned that the contraction algorithm sometimes identifies a min cut and sometimes it does not. It depends on the random choices that it makes. It depends on which edges it chooses to randomly contract. So the obvious question is this a useful algorithm? So in particular, what is the probability that it gets the right answer? And we know it's bigger than 0 and we know it's less than 1. Is it close to 1 or is it close to 0? So we find ourselves in a familiar position. We have what seems like a quite sweet algorithm, this random contraction algorithm, and we don't really know if it's good or not. We don't really know how often it works, and we're going to need to do a little bit of math to answer that question. So in particular, we'll need some conditional probability. So for those of you who need a refresher, you either go to your favorite source or you can watch the Probability Review Part 2 to get a refresher on conditional probability and independence. Once you have that in your mathematical toolbox, we'll be able to totally nail this question, get a very precise answer to exactly how frequently the contraction algorithm successfully computes the minimum cut.